Hi everyone, welcome to PrepFusion. So now we are going to see the marathon 2 on basic semiconductor physics. So we are studying EDC. In EDC our first chapter is basic semiconductor physics. So first marathon we have already covered, right? Now we are going to see the marathon 2. There we are going to discuss about semiconductor under non-equilibrium and the continuity equation. Then we will see Fermi-Dirac distribution, and after that we will see the energy band diagram for different conditions, and then whatever the miscellaneous concepts are left, those concepts we will see, and some questions also we are going to solve. Okay, so this will be roughly around 10.5 hours of marathon, and the previous marathon was of 12 hours. So in 22.5 hours we are covering our whole EDC, and in these 22.5 hours you will get the maximum information in any course. Whatever the information you get, no matter whatever the number of hours are there, they may have more number of hours, but in these 22.5 hours you will be getting the maximum information that is helpful for your examination and for any kind of examination you appear for, whether it is gate or any kind of examination. Okay, and in the minimum time we are covering, because in EDC there is a lot of theory, so we are not wasting time in writing down the theory. We will understand the concept, theory is already written. Okay, so yeah, you will surely enjoy it. Already you would have already seen the first marathon, so in the similar manner you are going to enjoy second marathon, because in the second marathon there are more tougher topics like Fermi-Dirac distribution and energy band diagram, continuity equation. These are considered as a tougher topic. So you would see in one line only, without doing the derivations, we are writing down the formula and everything with just pure intuition, no mugging up, nothing. Okay, with zero mugging up with the formula, we are going to write down every single formula. So you would surely enjoy this session. Yeah, that's it. And if someone wants to enroll into the full course, then he can go to our website prepfusion.in, and there he can go to the subject wise course section, and he can enroll into the full course. Okay, so you can enroll into the full course of EDC. You can apply the code PREP, P-R-E-P. So the price of the full course is 899 now. Okay, so after applying the code you will get it in 899 rupees. So as of now this is the promo code till 10th of September. This promo code is there till 10th of September. So it might happen that you are watching this video in some other time, right? So this promo code might not be applicable. So if it is not applicable, then what you can do, you can come to the Telegram group and you can ask there what is the promo code, or you can go to the community post and see if there is any promo code available or not. As of now this is the promo code. You will get to the final course in 899 rupees till 10th of September. If you are watching it some other time, then you can ask in the Telegram group. And if you want to watch the launch video as well, so you should watch the launch video as well, because here I have given the complete schedule that how the videos will be coming. Okay, so just if you want to resonate with the schedule, then you can resonate with the schedule as well. So first see the schedule here, what all things we will be covering, everything I have told here, and then you can purchase the course. And if you want to study from YouTube, from some other resource, then you can study from there as well. But as of now on YouTube, from our side, semiconductor physics will be completely coming, and that will surely be completely coming. I cannot promise about PN junction, I cannot promise about BJTs. I am thinking to bring MOSFET, but I cannot promise about MOSFET as well. Okay, so yeah, these things, whatever that I promised, that I have already brought on YouTube. Okay then, yeah, thank you very much. Let's get started. Let's get started with our concepts now. Yeah, thank you. And don't forget to put a like, and if you found the content helpful, if you find it helpful, then you can comment down as well. Yeah, thank you. Hi everyone, welcome to PrepFusion. So in the last lecture we were studying about diffusion current density, right? And in the diffusion current density, in the last I told you that we will be studying about Fermi-Dirac distribution, that we will be commenting on the probability of finding an electron. But I changed my mind, I changed the slide, and now first we will be studying about your semiconductor under non-equilibrium. Okay, so we will be keeping our semiconductor under non-equilibrium. What was our equilibrium condition? That our equilibrium condition, mass action law was valid, right? Number of electrons multiplied with number of holes, that value will be constant. If it was intrinsic, number of electrons were equals to number of holes, so n into p is equals to ni square. If it became n type, the number of holes, the number of electrons got increased in n type, but the number of holes got decreased, so multiplication was constant. So this was our equilibrium condition. Now the equilibrium will be disturbed. Something we will do, what we will do is that we will throw light on the semiconductor. Because we are throwing the light, light is having some energy, and because of that energy some electron hole pair will be generated, so they will disturb the equilibrium condition. So that phenomena we need to study, but that phenomena will come, but that will take some time. For the first 30 minutes we will be discussing some discrete topics, like this question is there, then another question would come, then we will make some conclusion. So for the first 30 minutes you will feel like that, sir, we are understanding everything, but the topic is combined, not making any sense. That you are teaching one topic, two topic, three topic, but combined it is not making sense. It will make sense in the end of the video. So you need to have some patience here. Okay, so just keep on watching on the screen. If I tell you something to remember, then only you need to remember. Otherwise, just keep on watching, keep on working in your rough notebook, and have the patience. Everything will make sense in the end. All good for you? Okay. And this topic is considered as a typical topic. Okay. Usually, students find it very, very difficult in the whole EDC, in the whole subject I am talking about. Not only in basic semiconductor physics, in the whole EDC, people find it difficult. But we will understand in a very good manner. First, we will build up some base, and then we will move to the topic. Okay. So let's get started. You need to solve this question. Since you have already studied about drift current and diffusion current, you would be able to solve it. What is given? Electric field is 0. The total electric field is 0. And these are the carrier profile. This is the, let's call it number of electron. Let's call it p-type, let's call it n-type semiconductor. Okay. This is the n-type semiconductor, and this is the profile of electrons. And this is also the profile of electron with respect to distance x. You need to find the value of dj by dx. And what is j? J is total current density. J is total current density. That means in this total current, drift current will also come and diffusion current will also come. Drift and diffusion, both of the component would come. Okay. So for the first one, you let me know. Let's just say in both of the cases, drift current would be 0 only. Why is that so? Because what is the formula of drift current? So the formula of drift current is, let's call it case A and let's call it case B. The formula of drift current is NQ NX, since it is varying. So NQ mu n E. And sir, since this is 0, in both of the cases drift current is 0. I don't need to think about drift current. Only thing I need to think about is diffusion current. So in the first case, let's talk about the diffusion current. What is the diffusion current? In the first case, there is no concentration gradient. That means concentration is same. It is uniformly doped. Since it is uniformly doped, that means there is no concept of diffusion current. Because what is the formula of diffusion current? Q dn dnx by dx. What is the slope here? 0. So what will be the answer? 0. So for the first case, drift is 0, diffusion is 0. So total current is 0. So for the first case, total current is 0. And if you differentiate, what will be the differentiation of 0? That would be 0. Okay. Now for the second case, drift current is 0. What about the diffusion current? So here you can see that the slope is constant, right? What I mean to say is that dnx by dx is constant. So what will be the value? Q dn into some constant. This is constant, this is constant, this is constant. So whole value is constant. Whole value is some constant. And this is equals to the total current, because drift current is already 0. So what will happen? If I differentiate this total current, what I will get? Constant plus 0 will be constant. What will be the differentiation of constant? That would be 0. So under 0 electric field, if your profile is either constant, if your carrier concentration profile is either constant or linear, then the differentiation of current density with respect to x will be 0. Sir, why we are focusing on this quantity? We will understand that. Have some patience. But you understood that if there is no applied electric field and the profile, the concentration profile is either linear or constant, then the differentiation of current density with respect to x, that would be 0. All good? All fine? Solve the similar thing for this question. The profile is constant. What does that mean? Diffusion current is 0. Right? Diffusion current is 0. And what about the drift current? Drift current will be n q mu n into E. E is constant. E is some constant. E is some constant value. So the whole value will be constant. Right? If the whole value is constant, that means this complete Jx is constant. And if this complete Jx is constant, then the differentiation is also 0. So only in 3 conditions you are getting differentiation equals to 0. There are only 3 conditions where you are getting this differentiation equals to 0. What is the first condition? That electric field is 0, profile is constant. You don't need to mug it up. You will be able to think, okay, electric field is 0, profile is constant, drift, diffusion, both 0, differentiation will be 0. Second case, electric field is 0, drift is gone. nx is linearly varying. Okay, concentration is linearly varying. That means dnx by dx would be constant. So if you again differentiate it, then that would be 0 only. So here also dgx by dx will be 0. And third case, diffusion is gone, drift is constant, and differentiation of a constant value will be 0 only. So these three cases, you don't need to mug up these cases. But if these cases are coming in front of you, will you be able to tell the answer of this particular thing? Yes. But now why we are focusing on this djx by dx? What it is representing? What is J? J is current density, right? I by A. And here there is dx and this is di as well. So what will be A into dx? Volume, right? So let's understand that. What we mean to say is that, let's just say this was a semiconductor. Semiconductor will be a 3D, right? It will be a 3D material. Let's just say this is a semiconductor. In this semiconductor, I am taking a very small area. Although this looks like a very big volume, but I am taking a very small volume. In this semiconductor, I am taking a very small volume, which is having a length of dx and cross-section area of A. Cross-section area of A. Length of dx, very small length I have taken, but cross-section area will be A only, right? Cross-section area of A. So what your A dot dx will represent? It will represent the small volume, right? Now what I am saying, what does 1 by q dgx by dx represent? First let's talk about dgx by dx. What does this represent? What is J? I by E. Sir, you are saying that current is a function of x. Yes, it could be a function of x, right? Nq mu E, right? Current could be a function of x. Here you have already seen. This is very simple thing. Yeah, so current would be a function of x. So what I am saying is that this is I by A dot dx. So this I can call it as per unit volume. So this is nothing but current per unit volume. Say yes or no? dgx by dx shows current per unit volume. All fine, right? Now what is current? Current is q by t. Sorry, not q by t. I should say total charge divided by time. Current is total charge divided by time and dot dv. So what this quantity is representing? Total charge per unit volume per unit time. dgx by dx is representing a total charge per unit volume per unit time. Now what is total charge? Let's just say in this particular semiconductor I am having only one electron. So what will be my charge? Q. If I am having 2 electrons, charge will be 2q. If I am having 2 electrons and 2 holes, that means carrier concentration is 4. 2 electrons and 2 holes, that means total charge will be 4q. So if I am saying that my carrier concentration is N, capital N, if my carrier concentration is capital M, then what will be the total charge? N into Q. Total charge will be N into Q. And now if I divide this quantity by 1 by Q, if I divide this quantity by 1 by Q, if I divide this quantity by 1 by Q, so what will happen? Q and Q will get cancelled out. So what is 1 by Q dgx by dx is representing? It is representing the number of charge carrier per unit volume per unit time. So 1 by Q dgx by dx represent number of charge carriers in per unit small volume per unit time. Is that clear to you or not? How we started? Dgx by dx, what is your current density? I by A. If I see here, A dot dx becomes the volume, right? Area multiplied by the length. What it would become? It would become the volume. So it is like current per unit volume. Now what is current? Current is charge by time, total charge by time. So total charge would be the number of charge carrier into Q, right? Number of charge carrier into Q, because one charge carrier would be having a charge of Q, right? So total charge will be NQ. So now if I cancel out Q with Q, then what this 1 by Q dgx by dx is representing? That is representing number of charge carriers per unit volume per unit time. So number of charge carriers either can come into this, or it can come, or it can get out of this. Basically, either the number of charge carriers can increase here, or it can decrease. Are you able to understand this point? Let's just say some current is coming, some current density Jx is coming. Okay. So what will be the current density going out? I am calling this as Jx plus dx. So if the going out current is more, what does that mean? That means dgx by dx is positive. I hope you know this thing, right? If basically if you draw a graph of y versus x, simple mathematics, on this point your slope will be positive. On this point dy by dx is positive. and on this point dy by dx will be negative. What is the reason behind that? Because here y is increasing, right? So if I say if my current density is increasing, that means this current, this going out current is more. So if dgx by dx is positive, that means going out current is more. And if dgx by dx is negative, that means going out current is less. Basically, input current is more and going out current is less. If this is the scenario, then dgx by dx would be negative, right? And if output current is more and input current is less, then dgx by dx would be positive, right? All these will make sense. Just have some patience. Some more points we will see. Okay, all these will make sense for continuity equation. Usually continuity equation is studied with respect to a lot of mathematics, but we will just reduce it in a very short manner. So till this point, what we have understood? So this 1 by q dgx by dx represents the net outflow or inflow of the number of charge carriers per unit volume per unit time due to the current. Is that clear to you? So whatever the thing that I wrote down here, that you can write down in a rough manner. In rough manner, in your notes you can write down what 1 by q dgx by dx is representing. The total inflow or outflow, because either the charge can get into it or the charge can get out of it. So inflow or outflow of total number of charge carriers per unit volume per unit time due to the current. Is that clear to you? And if dgx by dx is positive, what does that mean? That means current leaving the small volume is more than the current entering into it. And if dgx by dx is negative, that means current leaving the small volume is less than the current entering into it. All good? That means current entering is more, leaving is less. That means dgx by dx would be negative. And if current going out is more and entering is lesser, then dgx by dx would be positive. All good? Now this is a very, very important point. People just mug it up. Every student will just remember it, but we will understand what I am saying. Number of electrons increased per unit volume per unit time. What that quantity would be equals to. So let's just see it. This is our small volume, right? Now I am saying that the current entering and this is the current flowing out. I am saying that current flowing out is more and this is less. Okay, current flowing out is more and current flowing in is less, right? The electron will always move opposite to the direction of current flow, right? Electron always moves opposite to the direction of current flow. Let's just say the current is flowing in this direction, then electron would surely be moving in this direction. So if the current is flowing in this direction, so where the electron would be moving? Electrons will be moving in this direction. Now you are saying that current flowing out is more. That means electrons getting in will be more. You are saying that this current is more and this current is less. That means the current flowing out is more. That means electrons getting into the small volume will be more and getting out of this small volume will be lesser. Say yes or no. You are already saying that dgx by dx is positive. If dgx by dx is positive, what does that mean? That current flowing out is more. If the current flowing out is more, that means electron entering into the volume will be more and electrons entering out will be lesser. So what do you understand? If dgx by dx is positive, that means the value of current, the value of electrons inside the volume will increase. Are you able to understand this point or not? A very, very typical point. No one is going to explain you with this intuition. Believe me, they will needlessly use any mathematics and you will just write down, okay, you will be happy. But use your intuition, use your brain here. Current entering out is more. That means the electrons getting into will be more. What I need to write? I need to write the number of electrons increased per unit volume. That means here what will be my answer? 1 by q dgx by dx. Because what is 1 by q dgx by dx represent? 1 by q dgx by dx represent the net outflow or inflow of a number of charge carriers per unit volume per unit time. So here what is happening? The charge carrier is getting increased and we are considering the charge carrier to be electron. The charge carrier could be electron, it could be hole as well. But for the electron what is happening? If your output current is more, that means if you are considering that dgx by dx is positive, then what is happening? The electrons are actually getting increased inside the volume. All good for you? All fine? Do the same for hole and let me know what will be the answer. Here I will write down djn. Why jn? because it is about the electrons. Do the same for the holes and let me know what will be the answer. If I say this current is more and this current is less, that means djx by dx for holes I am saying that it is positive. I am saying that it is positive. This value is positive. So current getting out is more. Holes will always flow in the direction of current, right? If this is the direction of current, so this will be the flow of holes. So lesser current is going in. That means lesser holes are going in and more current is getting out. That means more holes are getting out. So what will happen? The density of electrons inside this small volume will decrease. Not electrons, sorry. The density of holes inside this small volume will decrease because more holes are getting out. Is that clear to you? If dgx by dx is positive, that means this current is more and this current is less. That means more holes are getting out and less holes are getting in. That means density of holes inside this small volume is getting decreased. But what you need to write down? You need to write down number of holes increased. If you need to write down number of holes increased, what does that mean? That means you will have to put a negative sign here. Is that clear to you or not? That means the current entering would be more and the current getting out would be less. If current entering is more, that means number of holes entering are more. And if current getting out is number of holes entering would be more. And if current getting out is less, that means number of holes getting out is less. So here the hole concentration will increase. That means you need to take dgx by dx as negative. So this value is negative, negative would eventually become positive. So this is showing the number of holes increased. If you cannot understand it, which is I have given good enough explanation, I hope you will be understand. If you are not able to understand, then just by remember a trick. When you wrote down the diffusion current, so for electrons, how did you write it down? Sir, nq dnx by dx. Sorry, dnq dnx by dx. And for holes, what you did? Sir, dpq dpx by dx and another negative sign. So for holes you are using the negative sign, for electrons you are using the positive sign. So in the whole EDC you will do the same thing, that for electrons you will use the positive sign and for holes you will use the negative sign. But the content that I explained here, that you are not going to find in the textbook. Okay, it is very intuitive, and within one line we will be writing down the continuity equation. Otherwise you see in the notes the derivation of continuity equation will take 2 pages, but we will write down only in one line. In one line only you will see the continuity equation. Do you remember the pointing theorem? Pointing theorem you might have studied in your semester examination. That also takes 2-3 pages, but in one line we write down the pointing theorem. Only in one line. Similar thing we are going to do with the continuity equation as well. In one line we will write down the continuity equation if these particular basics are clear. I hope these basics are clear to you. So what we started with? First we started with when dgx by dx is 0. So that condition we have seen when it is 0. So if you can remember, you can remember. Otherwise this condition will be mentioned in the examination. Okay, this condition will be mentioned that E is equals to 0. This is the profile. If this condition is mentioned, then you will be able to derive that both are 0. Okay, or this condition might also be mentioned, then also you will be able to derive that this would be equals to 0. Now why we are focusing so much on dgx by dx? Because dgx by dx represent a particular quantity. So 1 by q dgx by dx is representing the number of electrons or the number of charge carriers flowing in or flowing out per unit volume per unit time. Okay, and if dgx by dx is positive or if it is negative, then you would know the meaning. And number of electrons increased per unit volume per unit time is given by 1 by q djn by dx, and number of holes increased per unit volume per unit time is given by minus 1 by q djp by dx. Within 30 seconds you will be able to revise these slides. Now this is a very simple thing. If a light is having a wavelength of lambda, then what will be its energy? So energy of light is given by E equals to h mu. Okay, and mu is equals to c by lambda. These formula we have studied in our elementary classes. Not in elementary classes, in class 11-12 we have studied these formula. The energy of a photon Light means photon only. Okay, light means photon. So the energy of a photon is given by E equals to hc by lambda. Okay. Now this has a typical value. Hc has a typical value. What is h? H is Planck constant. What is the value? 6.63. H is Planck constant, having a value of 6.63 10 to the power minus 34 joule into second. Right? That would be the value. And C you already know, 3 into 10 to the power 8 meter per second. So when you solve all these things, then you get a particular answer which you should remember. 1242 electron volt nanometer divided by lambda. Divided by lambda. So value of Hc is, if you multiply H with C, then what answer you will be getting? You will be getting the answer in joule. Joule into meter. The answer you will be getting in joule into meter. And then you convert it into electron volt. So the way you convert it into the electron volt, and then final answer will be this. 1242 electron volt nanometer. Okay. Now let's just say lambda is given as 10, not 10. Let's just say lambda is given as 36 angstrom. What is the value of angstrom? Angstrom is 10 to the power minus 10 meter. If you don't know, just write down 1 angstrom. This is known as angstrom. That is equals to 10 to the power minus 10 meter. So can you convert it into the nanometer? Yes. That would be 10 to the power 1 minus 1 nanometer. So here what I will write down? 10 to the power minus 1 nanometer. So nanometer to nanometer will get cancelled out. And what will be my final answer? My final answer will be 1242 into 0 electron volt. 12,420 electron volt. So your energy of the photon will be 12,420 electron volt. Try remembering these data as well. Okay, both of the data you should remember. 1242 electron volt nanometer, because a lot of time they will be asking the energy in electron volt only. So there you will not be converting. You will just remember 1242 electron volt nanometer divided by lambda. All good? All fine? So everything will make sense. Just have some patience. Now there are two things, generation and recombination. These things I have already discussed. Let's just say I was having a semiconductor, right, at 0 Kelvin. So at 0 Kelvin, in the valence band I am having all the electrons, and in the conduction band I am not having any electrons. So what really happened? Just as I increase the temperature, what will happen? Some covalent bond will be broken from here, and some electrons from the conduction band, some electrons from the valence band will go into the conduction band. So this electron from the valence band is going into the conduction band. This electron from the valence band is going into the conduction band because of the temperature. So this process is known as generation. Generation of electron hole pair. Generation of electron hole pair, right? So in a semiconductor, when energy, it could be heat, it could be light, when the energy is given, new electron hole pairs are generated. This process is known as generation. And what is recombination? So this generation process will keep on going, but you know that there will be some equilibrium condition, no? If it is intrinsic type of semiconductor, or if it is not intrinsic, then this condition would be there, no? N naught equals to P naught, N naught into P naught equals to Ni square. So what may happen is that some electrons may fall back as well. Like what will happen? These electrons will spend some time. These electrons will be spending some time in the conduction band, and they may fall back as well. So let's just say this fall back, then what will happen? This might generate electron and hole pair. So basically, if this electron is falling back into the hole, that means from electron from the conduction band is falling into the valence band, then whatever the electron hole pair was generated, that is destroyed. Because initially what was the scene? This was the electron, but what happened was this electron went here and hole was created. Now what really happened? The electron has fall back. So if the electron has fall back, so this vacancy is gone, and here there is no electron. So now eventually the same condition we have got. So this process is known as recombination. Like the electron hole pair being destroyed. Here electron hole pair are being generated, and here electron hole pair are being destroyed. So what is written? An electron and a hole can meet and cancel out each other. When this happens, they both disappear. Electron fills the hole and energy is radiated. Okay. So when the electron is going from here to here, when the electron is going from valence band to conduction band, then it was taking some energy. It was taking some energy because of the temperature, right? Or it could be because of the light, or it could be because of any heat. So it was taking some energy. Now when the electron is falling back, it will release some energy. Okay. So whenever electron gains some energy, So here it is gaining some energy. Now if this electron is falling back into this hole, then it will release some energy. So here energy was given, now here the energy will be released. So whatever the energy was given, the same energy will be released, right? If it is falling from the same level, what I mean to say is that, let's just say this gap was 1.1 electron volt, okay? So you have to give 1.1 electron volt energy, then it will reach here. Now if it is falling from here only, then it will release 1.1 electron volt only. Like whatever the band gap is there, it will release the energy equal to that only. But it might happen that it is falling from this level. So first what will happen, it will fall from here to here, and then it will fall from here to here. So here also it will release some energy, and here also it will release some energy, okay? Although these are not important for the conceptual purpose, I am just telling. So whenever electron gains some energy, and if it falls back, it will release some energy as heat or light. And we have already seen when it releases the heat and when it is releasing the light in the last lecture only, when we studied about direct and indirect band gap semiconductor, okay? So if there is a momentum change, then it will generate the heat, otherwise light, okay? So these are just two basic terms I wanted to tell. Now we will revise our RC circuit. Sir, suddenly why RC circuit? Everything will make sense. Have some patience. So this was your system, this was your RC circuit. If I apply 5 volt to it, on this RC circuit, if I am applying 5 volt, then what will happen? This capacitor will charge. This capacitor knows that I want to charge till 5 volt. This capacitor knows that I want to charge till 5 volt, but will it charge instantaneously? No, right? What will happen is that it will take some time to charge. It will take some finite time. The capacitor knows that I need to charge till 5 volt, but it will not charge instantaneously. Any system doesn't respond instantaneously. You turn on the fan. You want to turn on the fan at a speed of 5, but will it, just as you click on the button, will it be moving at a speed of 5? No. First it will get a speed of 1, 2, 3, 4, and then it will come to 5, right? So in the similar manner, this RC circuit, if you give 5 volt to it, the capacitor knows that I want to charge till 5 volt, but it will not instantaneously charge till 5 volt. It will take some time and then it will reach. Let's just say it was taking a time of t1 only. So till it took the time of t1 and it has reached till 5 volt, right? Now at 5 volt, what you have done is that you have changed the switch. Initially you were giving 5 volt supply. Now what you have done is that you have connected it to the ground. So what will happen? Whatever the initial voltage that it has developed a 5 volt. Now it knows that I need to deliver all the voltage to the ground. But that means I need to deliver all the energy to the resistor. That means this will be completely discharging. So capacitor will be discharging from 5 to 0 volt, because you have removed the source and you have connected this to ground. So capacitor will discharge. It will discharge from 5 to 0 volt. Now capacitor knows that I need to go to 0 volt, but but will it go instantaneously? When you turn off the fan, the fan gets turned off instantaneously, or it takes some time? It takes some time, right? From 5 to 4, 4 to 3, 3 to 1, and then to 0. So similarly, this will discharge, but it will take some finite time. And these time depend on some time constant that is known as tau, RC. Now there are two kinds of steady state. You can either call this as steady state, because when you gave the 5 volt, this was the steady state, that I have reached the 5 volt, and just as you removed the 5 volt, then this could be the steady state, because after removing the 5 volt, when you are getting the 0 volt, this could also be known as steady state. Steady state means your voltage is not changing with respect to time. Steady state means your voltage is not changing with respect to time. If you have turned on the fan, then let's just say now fan is moving at the speed of 5. So it will continue moving at the speed of 5 only, right? So now the speed is not changing. So that is known as steady state. With respect to time, nothing changes. So steady state, the word steady state is defined with respect to time, not with respect to distance. Okay. So what I will be writing down, the meaning of steady state is with respect to time, not distance, or I am just writing down x. And steady state and constant both are the same thing. Constant is defined with respect to t. That means your value is constant. It is not changing with respect to time. And if I say uniform means it is not changing with respect to x. When I was saying that this electron concentration is having uniform profile, we are having uniform doping. So what is the meaning of uniform? Uniform means it is not changing with respect to x. And if I say constant, that means I am talking about time. So this thing we use in EMFT as well. In EMFT as well, I say the same thing. There is a difference between uniform and constant. Constant means, just look at the last word, constant, t. T means time. So if I say something is constant, that means it is not changing with respect to time. And if I say something is uniform, that means it is not changing with respect to distance. Okay. So with respect to time, not distance. Here, instead of writing x, better let me write down distance. And constant and steady state both are the same thing. Okay. Constant is nothing but a steady state only. Well and good. Now slowly we are moving towards our topic. Why we studied so, sir? All these things I already know. I have studied my network analysis. I already know all these things. Sir, why we studied it? You will understand. Have some patience. Okay. Now our semiconductor under equilibrium we have seen. In intrinsic semiconductor, just 1 second guys. Yeah. Sorry for the interruption actually, like in between if I feel too much of cough, then I need to stop, right? I hope you guys are not getting irritated of it. Please don't get irritated and focus more on studying, not on these things. My health is never improving. The number of charge carriers with respect to distance x I am drawing. Okay. So I know that if uniform doping is there, so let's just say this is my semiconductor. So I know that number of electrons will be equal to number of holes, and that will be equal to number of intrinsic carrier concentration in intrinsic semiconductor at thermal equilibrium. That means temperature is constant. Now I am not increasing the temperature, I am not decreasing the temperature. If I am at 300 Kelvin, then yes, now the number of electrons and number of holes are 10 to the power 10 centimeter cube inverse. Roughly this value for silicon. So this value is constant now, right? And this is not changing with respect to x. Why so? Because this is uniform doping, right? So under uniform doping we are considering. So I know that number of charge carriers, that would be number of electrons will be equal to number of holes will be equal to Ni, right? This 0 I am putting, it is showing that under equilibrium. Okay. What about the n-type semiconductor? In n-type semiconductor, you would know that number of electrons would be more, and here you know that number of holes would be more, right? And here number of holes will be less, and here number of electrons will be less. So what I will write down here? What I will write down? Number of electrons in n-type semiconductor at thermal equilibrium. Number of holes in n-type semiconductor at thermal equilibrium. Number of holes in p-type semiconductor at thermal equilibrium. And number of electrons in p-type semiconductor at thermal equilibrium. Okay, so just the notation I am telling. Number of electrons in n-type semiconductor at thermal equilibrium. Number of holes in n-type semiconductor at thermal equilibrium. Number of holes in p-type semiconductor at thermal equilibrium, and number of electrons in p-type semiconductor at thermal equilibrium. This value will be more than this because it is for p-type. Here electrons will be more, and here both will be equal. All good, all fine. And in all of the scenarios, the mass action law will be valid, right? What will be the mass action law? Will say n naught into p naught will be equals to Ni square n naught number of electrons in n-type semiconductor at thermal equilibrium, number of holes in n-type semiconductor at thermal equilibrium, and number of holes in p-type semiconductor at thermal equilibrium and number of electrons in p-type semiconductor at thermal equilibrium will be equals to Ni square. So these mass action law will also be valid. But now what I am doing, my semiconductor was happy. Here it was lying very happily. But now what I will do is that I will expose it to some external source, and that external source I am telling as light. So what was the condition? I am assuming that my n-type semiconductor is under equilibrium. So it is having a certain number of holes, it is having a certain number of electrons. So number of electrons per unit volume in n-type semiconductor under equilibrium, number of electrons in n-type semiconductor under equilibrium. Let's just say I am giving 10 to the power 16. And I am saying that my intrinsic carrier concentration is 10 to the power 10. Okay, this is my intrinsic carrier concentration. When it was intrinsic, this much number of electrons and hole was there, right? So what will be the number of what will be the number of holes in n-type semiconductor at thermal equilibrium? That would be 10 to the power 4. If you are not able to understand this, that sir, from where this 10 to the power 4 came, that means you are not studying. Mass action law, right? 10 to the power 16 into 10 to the power 4 will be equal to 10 to the power 10 whole square. So this you should be able to understand. So this was the condition of thermal equilibrium. Everything was fine. But now what I am doing is that I am throwing a light. What I am doing? I am throwing a light which is having an energy of h mu. And this energy h mu is greater than this band gap. On this semiconductor, I am throwing a light having an energy of h mu which is greater than this band gap. Now what will happen? Already number of electrons were there, already some holes were there. But because of this light, these electrons will get enough energy that these electrons will be moving from the conduction band to valence band. Sorry, valence band to conduction band. I am saying opposite. The electrons will get enough energy to move from valence band to conduction band. So what will happen is that they will make a electron and hole pair. Electron and hole pair. Electron and hole pair. So this was the equilibrium concentration. This was the equilibrium concentration. But you disturbed the equilibrium. How you disturbed it? By throwing some light of having energy which is larger than the band gap. And because of that, some electrons got the enough energy to get excited from the valence band to conduction band. And they generated electron hole pair. The number of electrons generated and the number of holes generated are same, right? Electron and hole will be generated in pair. Here there was no electron hole pair initially. Like electron hole pairs were not there. These electrons are coming because of the donor atom, right? And some holes are coming because of thermal energy. Now because of this external energy as well, some electron hole pairs are generated. Now let's just say I know that initially I am having 10 to the power 16 and here I am having 10 to the power 4. Let's just say because of this energy I know that extra 10 to the power 4 centimeter cube inverse electron hole pair will be generated. What I mean to say is that 10 to the power 16 were initially there, 10 to the power 4 were initially there. Now because of this light, here you can see that 3 electron and 3 hole pair are generated. So because of this light, I am saying that extra 10 to the power 4 centimeter cube inverse electron hole pair will be generated. Now this semiconductor knows that I am exposed to the light. This semiconductor knows that here I am exposed to the light. And since I am exposed to the light, I need to generate these 10 to the power 4 centimeter cube inverse electron hole pair. But the semiconductor will say that, sir, I am not going to generate it instantaneously. I will take some time, because you know that every system takes some time. This capacitor knows that it is exposed to 5 volt. But capacitor knows that I need to generate 5 volt. But capacitor will say that I need some time to generate 5 volt. Similarly, your fan will say that to run on 5 speed, I need some time. So similarly, this semiconductor also knows that I need to generate extra hole pair, right? Extra electron hole pair. So these are known as excess carrier. So I need to generate these excess carrier. So, but I will not do it instantaneously. I will take some time. So this excess carrier that I am calling as delta P, or you can call it as delta N as well, right? These were the thermal equilibrium carrier concentration. Now excess carriers are generated. So this you can call as delta P and this you can call as delta N, right? So this will be surely a function of time t. This will also be surely a function of time t, and both will be equal as well, because I know that electron hole pair will be generated. So both will be a function of time t. Now what may happen is that this intensity of light may decrease with respect to the length L. Basically, let's just say if I turn on this light, here, so the intensity of the light is maximum here, but as it is covering the distance, the intensity will keep on decreasing. So you are throwing the light here, but it might happen that the intensity of light keeps on decreasing. That means here there is maximum light, here there is lesser light, even lesser light. So intensity of light may decrease. It can decrease in any manner, or it might happen that it may not decrease, right? It might happen that you are throwing the light from all the side. From everywhere you are throwing the same intensity of light. So it might happen that it may not decrease. But we will take the worst case. We will take the case that the intensity of light may decrease with the distance. So these excess carrier concentration could be a function of x as well. So till this point, what did you understand? at equilibrium we were having certain number of electrons and certain number of holes. Since it was n type, then the number of holes were number of electrons were more than the number of holes. Then at x equals to 0, I throw some light. Since the light is having energy more than the band gap, then some electron hole pairs will be generated. Some electrons from the valence band will be getting enough energy to get excited into the conduction band. An electron hole pair will be generated. Both electrons, the number of electrons extra generated and the number of holes extra generated, both will be equal in amount, right? So number of electrons, excess number of electrons and excess number of holes, both will be equal in amount, right? Now these excess carrier concentration could be a function of time as well and could be a function of space as well. Why it could be a function of time? Because the semiconductor will not respond immediately. It may take some time to reach to the steady state. That means the steady state value is this much, that I need to generate 10 to the power 4 centimeter cube inverse in the electron hole pair. But how it will say that, sir, first I will generate one electron hole pair, then 2, then 3, then 5, then 7, then 10, then 10 to the power 2, then 10 to the power 3, and then 10 to the power 4. So it will take some time to reach. So it can be a function of time t. It can be a function of space x as well, because you are throwing the light at x equals to 0, so the intensity of light may decrease with respect to the length L. So it could be a function of space as well, and both will be equal in amount. So till this point everything is clear to you or not? Everything is absolutely clear. And here you cannot apply the mass action law, because equilibrium is disturbed, right? Extra electron hole pairs are generated. In n-type semiconductor, you are expecting that these many electrons and holes will be there. But because of the light, extra electron hole pairs are generated. So the semiconductor is under non-equilibrium now. And that's why you cannot apply the mass action law here. Basically, previously what was the condition? N naught multiply with P n naught was equals to Ni square. But now what happened is that N naught has become, there are these many electrons, along with that these are the x's. So function of x and function of t, right? Multiply with, this is the sign of multiplication. P n naught was already there and x's these are generated. X t is equals to Ni square, which is not true, because N naught dot P n naught is equals to Ni square. So these are the x's guys, and these x's guys will not be that small. Okay, don't think that, sir, if this is 10 to the power 4, so this will be, sir, some 10 value or 10 to the power 1 value, then we can ignore it. You cannot ignore it. These will be pretty high value, because this light will be having more than enough energy to make a high number of electron hole pairs. Okay, so mass action law is not valid. Every theory is written. Okay, everything is written. My target was to explain you the concept, and that I have explained. Let's read out the theory, whatever that has been written. Okay, so in n-type semiconductor under thermal equilibrium, the electron concentration and hole concentration are np naught and pn naught. अरे भाई ये क्या लिख दिया, n naught, right? n naught electron concentration in n-type semiconductor at thermal equilibrium. So it will be n naught at x equals to 0 and t equals to 0. At time t equals to 0, what I am doing, the semiconductor is illuminated with the light of photon energy is equals to h mu. The incident light generates additional electron hole pair within the semiconductor. Due to this optical excitation, the carrier concentration deviates from the equilibrium values. The intensity of light may decrease with respect to the distance. Therefore, the number of excess carrier also decreases as a function of distance, right? Hence, the excess carrier concentration becomes a function of position x. In addition, the generation of excess carriers does not occur instantaneously. When the light is switched on, the carrier concentration increases gradually. It needs to reach to 10 to the power 4, but it will reach gradually 10 to the power 1, 10 to the power 2, and then 10 to the power 4, passing through a transient state before reaching the steady state. This state is known as transient state. Okay, those who haven't studied network analysis, they would not know. This is known as transient state. Like when the fan is trying to go to the speed of 5, first it will go to speed 1, 2, 3, 4. So these 1, 2, 3, 4, this is known as transient state. And once it has reached to the steady state, that is the speed of 5. Okay, so this is your transient. Thus, the excess carrier concentration depends both on position and time, and it is expressed as delta n xt, excess electrons and excess hole, that is represented as delta pxt. Since each photon, yeah, this line is very important. Since each photon generates one electron along with one hole. What does that mean? That means this is the light. You are having a light of, let's just say, you are having a light which is having a power of 1 watt. You are having a light which is having a power of 1 watt. In this light, there could be a lot of power of 1 watt and energy of 1 joule. Okay, so this is the energy of one photon. Are you able to understand this point? So one photon will generate one electron hole pair. We will solve a numerical, it will be more clear to you. So basically in one light source there could be a lot of photon. In one light source only there could be a lot of photon. So those photons, let us say there are 10 photons, then 10 electron hole pair will be generated. If there are 20 photons, then 20 electron hole pair will be generated. If there are 30 photons, then 30 electron hole pair will be generated. Okay. So in one light source there could be a lot of photons. So one photon will generate one electron hole pair. And since they are generating electron hole pair, that means number of electrons and number of holes are equal. So delta nxt will be equal to delta pxt. All good? All fine? So now the total carrier concentration will be given by n naught. Here what you need to write down, n naught. Basically only need to change is n naught. Number of electrons in n-type semiconductor at thermal equilibrium plus delta nxt, and total, like, did you understand what is this nxt? Nxt is that total carrier concentration, total hole, total electrons. This is your total free electrons, or I will directly write down total electrons, and this is your total holes. So equilibrium holes you are having, equilibrium electrons you are having, along with that excess electrons and excess holes. Okay. Now let's just say I have reached at the steady state. I have passed out the transient state. I have reached at the steady state. That means now these excess carriers, these excess electron and these excess holes will not be a function of time t. What I mean to say is that if this fan is running at a speed of 5, if the capacitor has got the 5 voltage, now the 5 voltage is fixed with respect to any time. If I turn on the fan at 1 p.m. and at 1.1 p.m. at 1 p.m. 1 minute, this is running at a speed of 5, then always it will run at a speed of 5 only until I make some changes. Until I again click on the button, until I make any changes, it will always run at 5 only. Are you able to understand this point? So if I am saying that I have reached to the steady state, that means these excess carriers will not be a function of time now. Now they have generated 10 to the power 4 electron hole pair. They have already generated 10 to the power 4 electron hole pair. So now they will not be a function of time. So at the steady state, what I can write down as delta nxt would be equals to delta nx, right? What I can write down, delta nxt would be equals to delta nx, and your delta pxt would be equals to delta px. Where? At the steady state. Because steady state has reached, that means you have reached out the maximum number of electron hole pair. Now these number of electron hole pair will not change. All clear? So all these scenario we will again understand with respect to different diagrams. So don't worry about that. So now at the steady state, the excess carrier concentration becomes constant with respect to time. So total carrier concentration are given by n naught plus delta nx and p naught plus delta px. All good? All fine? You are not getting confused with the notation? Don't get confused with the notation. Now there is another point. Let the steady state excess electron hole pairs are 10 to the power 4 centimeter cube inverse. 10 to the power 4 centimeter cube inverse. So these many electron hole pairs you are generating at a steady state. So just let me know one thing. What will be the total carrier concentration at the steady state? What will be the total number of electrons at the steady state? So previously how many electrons you were having? 10 to the power 16. Plus 10 to the power 4. Nearly equals to 10 to the power 16 only, right? But what about the holes? I should have given the space, no? Where I would write down now. Not having any space, so I will have to adjust, but let's understand it. What about the holes? Holes initially was 10 to the power 4. Now extra 10 to the power holes are generated. What you can see? 2 into 10 to the power 4. So there is no significant change in the number of electrons, but there is very high change in the number of holes. What kind of semiconductor we are studying? N-type semiconductor. In N-type semiconductor, who are the majority? Electrons. So in N-type semiconductor, electrons are majority, and because of the lights, they are not getting changed much significantly. But the minority carrier concentration, which are holes, they are getting changed significantly. So what will be our matter of concern? Like, who will change our current? If number of electrons, previously it was 10 to the power 16, now also it is 10 to the power 16 only. So will they generate any current? No, they will not generate any extra current. So who will be our matter of concern now? Matter of concern will be minority excess carriers. Say yes or no. Why minority excess carrier? Minority, what I am saying? Minority excess carrier. Excess carrier means delta pxt. And what do you mean by minority? Minority means holes in case of N-type semiconductor. And in case of P-type semiconductor, who will be the minority? Electrons. So our matter of concern will be shifted towards the minority excess carrier concentration. Minority holes. Excess means because of the light. So minority excess carrier concentration. Because minority excess carrier concentration are changing in a significant manner. Okay, all points are clear to you. Everything is very smooth, right? So this thing I have written here. In N-type semiconductor, let's shift it like this. Okay, all fine. Yeah, fine. In N-type semiconductor, the equilibrium electron hole concentration is already very high compared to the hole concentration. Equilibrium electron concentration is already very high compared to the hole concentration. Under non-equilibrium condition, the change in electron is relatively very small, whereas the change in number of holes is much more significant. Therefore, in this analysis, in the analysis of non-equilibrium behavior, greater emphasis will be placed on minority carriers, minority excess carrier, or you can say minority carriers. So our matter of concern will be more towards minority carriers. When the excess electron hole pairs are generated by illumination, the number is, so there is something called low level injection. What do you mean by low level injection? Let's just say initially I was having 10 to the power 16 number of electrons and number of holes were 10 to the power 4. Now I need to generate, now because of the light, these excess carriers are generated. Now these excess carriers should be less than 10 to the power 16. That means these excess carriers should not be too high that it will cross this value only. Are you able to understand this point? Let's just say I say that the excess carriers are generated are 10 to the power 20. Excess carriers that are generated are 10 to the power 20. So what will be the number of electrons? 10 to the power 16 plus 10 to the power 20. What that would be? 10 to the power 20. And what will be the number of holes? 10 to the power 4 plus 10 to the power 20. That would also be approximately 10 to the power 20 only. So this is known as high level injection. That you have thrown the light of so much high energy. The light is having so much of high energy that a lot of electron hole pairs are generated. And at very high energy, at very high temperature, or you can say at very high energy, what will happen is that I told you the semiconductor will start behaving like an intrinsic semiconductor. Where we studied that? In the second last lecture, right? So it will start behaving like an intrinsic semiconductor. You can see that 10 to the power 20, 10 to the power 20. So this analysis will never be asked. In your syllabus, low level injection is there. Okay. So only they will make sure that these excess carriers are lesser than the majority carrier concentration. So this is what is written. When excess electron hole pairs are generated by illumination, their number is smaller, not much smaller. It could be near to this as well. Okay. So their number is still smaller than the equilibrium concentration of majority carrier. This condition is known as low level injection. Okay. So always low level injection will be asked. That means the number of charge carriers, the number of excess charge carriers that are generated, the number of them will be lesser than the majority charge carriers. So this was your majority charge carrier, number was lesser than that. Here you can see that 10 to the power 4, 10 to the power 10 to the power 4 and 10 to the power 4. And the excess charge carriers were 10 to the power 16, which were much lesser. So this is known as low level injection. So now based on whatever that we have studied, we will try to solve this question. This is not a problem, okay? This question will not be asked in the examination, but it will help you to clear your concept. Okay? So whatever that we have studied, based on that only this particular question is there. What they are saying? You should be able to understand whatever that is written. What they are saying? N-type semiconductor is given. Thermal equilibrium electron hole concentration is 10 to the power 16, 10 to the power 4. When everything was fine, this was the condition. Then what really happened? At t equals to 0 and at x equals to 0. So this was your semiconductor at x equals to 0. Semiconductor could be having a length of L. So at x equals to 0 and at t equals to 0, you are throwing the light. And since you are throwing the light, you know that electron hole pair will be generated. Now these electron hole pairs will not be generated instantaneously, it will take some time. How much time it is taking? 5 microseconds. So steady state will be reached at 5 microseconds. And the excess electron hole pair that are generated, those are 10 to the power 4 at the steady state. Okay, at the steady state. Do you understand the meaning of at the steady state? That means excess carrier concentration, initially they started from 0, then 10 to the power 1, 10 to the power 2, 10 to the power 3, and then eventually they reach to 10 to the power 4. Okay, the excess hole concentration inside the semiconductor decreases exponentially with the distance x. Okay, what I am saying is that let's just say here you are having excess carrier concentration as 10 to the power 4. So with the distance, it will decrease exponentially. Is that clear to you? Are you able to understand what I am saying here? This they have given that this response will be exponential. It could be linear as well, or it might happen that it is constant as well. It could be exponential, it could be linear, it could be constant, it could be anything. But it is given that it is decreasing exponentially with the distance x. Are you able to understand what I am saying? So whatever that has been said in the question, is that clear to you? There was the semiconductor, n-type semiconductor was there, electron hole concentration was there, illuminated the light, because of that electron hole pairs are generated, steady state is reached at 5 microsecond. Okay. And in the semiconductor, the intensity of light would be decreasing. Here there is more intensity, but as you go ahead, the intensity of light would decrease, right? Because of that, the electron basically here there will be more electron hole pair generated, but here there will be less electron hole pair will be generated. So if the intensity of light is decreasing inside the semiconductor, that means the electron hole pair will also be decreasing, and that decrease is exponential. They have mentioned that in question. It could not be mentioned, it might be mentioned. So whatever that is mentioned, that you need to take. Okay. So you need to draw that total hole concentration versus x with respect to different time instants. That means at t equals to 1 second, at t equals to 3 second, at t equals to 5 microsecond, you need to draw the hole concentration with respect to x. And then what they are saying is that you are switching off the light at 7 microsecond. You are switching off the light at 7 microsecond. And the thermal equilibrium is restored at 12 microsecond. What is the meaning of that? First, what you did, you generated the light. You gave the light. Because of that, electron hole pairs were generated. So initially you were having some, this is again n naught. Okay. So n naught you were having. Because of that, some extra carrier came into action. Previously you were having p n naught, and some extra carrier came into action. Now just as the light is gone, now what semiconductor will say? That I am not having any light. I am again under the thermal equilibrium condition. So these guys need to go now. Basically you turned off the fan. You have turned off the fan. So fan will say that I was at 0, so I will move at the speed of 0 only. That means I will be at rest. In this question, when I remove the source, capacitor will say that what was my initial voltage? 0 volt. So I will go back to my 0 voltage. So now capacitor is trying to go to 0 voltage only. So similarly, what the semiconductor will say? That initially my electron hole concentration were this. Because of the light, these were generated. But now the light is gone, so you also will go. So we guys will also go. But they will not go instantaneously. If you turn off the fan will not turn off instantaneously. 5, 4, 3, 2, 1, 0. Similarly, capacitor discharging from 5 volt to 0 volt exponentially. Similarly, here as well, these 10 to the power 4 will not go instantaneously. They will also go exponentially. Is that clear to you or not? All good? All fine? So let's see what the question is saying, and let's try to draw the waveforms. So you do it on your own in rough notebook. I need to take some break. I need to drink some water, and then I will draw the waveform in this manner. The diagram has been made, and better I should have written NP naught, PN naught. Sorry, N naught, number of electrons in n-type semiconductor, number of holes in n-type semiconductor, 0. And this is the steady state 10 to the power 4 centimeter cube inverse. We will draw at different time at 0 second, 0 second, 1 second, 3 second, 5 seconds. So at 0 second also I will draw at 1 second. And what I need to draw? I need to draw the minority carrier concentration. Okay, minority carrier, whole concentration means minority carrier concentration. So total holes I need to draw. What will be your total hole? What will be the total number of holes? Pxt, total number of holes will be equals to the equilibrium number of holes plus the excess holes that are generated, right? But these will be a function of time, these will be a function of space as well. But this guy is constant. So at t equals to 0, there was nothing. At t equals to 0, there was nothing. At t equals to 0 only, they turned on the light. So at that time, everything was fine. Everything was fine. So at that time, number of holes in n-type semiconductor at thermal equilibrium was 10 to the power 4. Just as the light turned on, these 10 to the power 4 got changed. Something will come into action here. In 1 microsecond, I don't know how much will be generated. I have no idea how much more holes will be generated, but I know that steady state will be reached at 5 microsecond. That means I know that these many excess holes will be generated at 5 microsecond. So at 1 microsecond, 10 to the power 4 will not be generated. Lesser than that will be generated. I am assuming that at 1 microsecond, 10 to the power 4 plus 100 more are generated. What I am saying, at 1 microsecond, 10 to the power 4 plus 100 more are generated. But where the intensity of the light is high? At x equals to 0. So these 10 to the power 2 are generated here. Basically, at 1 microsecond, initially you were already having 10 to the power 4. Now extra 10 to the power 2 are also generated. But these are generated at x equals to 0. Now what they are saying is that the intensity of light is decreasing inside the semiconductor. So whole concentration inside the semiconductor is decreasing exponentially. So this whole concentration will decrease exponentially. Are you able to understand this point or not? So this whole concentration will decrease exponentially and it will reach the thermal equilibrium value only. This thermal equilibrium value was 10 to the power 4. What I mean to say is that here there were more lights, so more electron hole pair were generated. So this I am saying that at 1 microsecond, this is the maximum number that is generated. What I am saying, at 1 microsecond, this is the maximum number that is generated. With respect to the distance x, it will decrease. Why so? Because here there is lesser light, here there is even lesser light, here there is even lesser light, or let's just say here there is no light at all. And if there is no light at all, then equilibrium will be maintained. So this concentration will decrease exponentially. Why exponentially? Because it is given. If it was given linearly, then it could have been linear as well. If it was saying that it is constant, that means whatever the number of holes are generated here, the same number of holes are generated here, same here, everywhere the same number of holes are generated. So it could be constant as well, or it could be linear as well, or it could be exponential as well. Depends on the given question. Okay. Well and good. Yeah. So next, let's see at 3 microsecond. So at 3 microsecond, what will be the behavior? So at 3 microsecond, what I am saying is that already I was having 10 to the power 4. This much I was already having. Because of the light, 10 to the power 4 plus 10 to the power 3 is generated. 10 to the power 4 plus 10 to the power 3 generated, but the maximum will be generated at x equals to 0. Why is that so? Because with respect to the distance, the intensity of light is decreasing, so the carrier concentration will also decrease. The whole concentration will also decrease in this manner. And it might happen that at some point the light is not even reaching, so concentration will be nearly 0. The excess carrier concentration will be nearly 0, but whatever that you are having previously, basically this guy is not changing. This guy is saying that I will not change. Now only change will be done in this particular value, right? Now I know that steady state is reached at 5 microseconds. So I am pretty sure that at 5 microsecond, 10 to the power 4 plus 10 to the power 4 will be generated, because this is the steady state. This is the steady state condition. So 2 into 10 to the power 4 centimeter cube inverse. So this is the steady state condition, and after that it will decrease exponentially with respect to the distance. So this is the diagram we are drawing with respect to the distance. Is that clear to you? Okay. Now at 7 microsecond, what you were doing? At 7 microsecond, the light was turned off. At 7 microsecond, the light was turned off. So at 7 microsecond as well, the same condition was there, right? At 7 microsecond as well, just before 7 microsecond, I am talking about 6.9999 microsecond. At 6.99 microsecond as well, the number of holes cannot be generated more. Previously, the number of holes were 10 to the power 4. Because of the light, more 10 to the power 4 were generated. So now more cannot be generated. 2 into 10 to the power 4 is constant now. That will not increase. So at 7 microsecond as well, the same diagram you will get, because the effect of light will come into action after 7 microsecond. Are you able to understand this point? Right? So this is how the same graph will go. Basically at x equals to 0, you would be having 2 into 10 to the power 4 only. Make sure that you notice this, we are drawing with respect to x. That means this is our semiconductor. We are drawing with respect to the semiconductor, with respect to the distance x. We are not drawing with respect to the time. With respect to the time as well, we will draw the graph, but that graph will be different. This we are drawing with respect to x. Where the effect of time is coming into action? Here. Initially, at time t equals to 0, there was nothing. At time t equals to 1 microsecond, 10 to the power 2 came into action. At t equals to 3 microsecond, 10 to the power 3 is coming into action. At t equals to 5 microsecond, 10 to the power 4 is coming into action. At t equals to 7 microsecond, 10 to the power 4 remains constant, right? And at t equals to 9 microsecond, what will happen? Now the light is gone. Since the light is gone, so what will happen? The semiconductor will say that whatever the extra that you have generated, I don't want that extra, because the light source is gone, no? And since the light source is gone, the semiconductor will say that whatever that you have extra generated, reduce that to 0. So already I was having 10 to the power 4. This was the already value that I was having. Let's just say your capacitor is already, this I cannot explain with the example of capacitor, because capacitor will completely discharge, but just understand with respect to your semiconductor only, because semiconductor is having that this much number of charge carriers I am already having. Now the extra that you have generated, that should be erased. So extra 10 to the power 4 we have generated, and light was turned off at 7 microsecond. So between 7 microsecond to 9 microsecond, there has been a gap of 2 microsecond. And since there is a gap of 2 microsecond, so in 2 microsecond, the charge carriers would have decreased. So from 10 to the power 4, let's just say I am saying that we have went to 10 to the power 2. What will be the value? That I don't know. It will be a rough value. It is just a rough value that we are putting. Then at 11 microsecond, next at 11 or 13, next at 12, and 12 is the steady state, right? 12 is the steady state, 7, 9, and next directly at 12. So at 12 as well, you are getting the steady state, no? What they are saying, the thermal equilibrium is restored at t equals to 12 microsecond. What does that mean? That means whatever the extra was generated, those are gone. Whatever the extra was generated, those were gone. So this is your thermal equilibrium that has been generated at t equals to 12 microsecond. Is that clear to you or not? I hope this whole process is clear to you. A very, very typical process, but with respect to diagram, if you are understanding, the important part to understand here is that this whole concentration is a function of x as well, it is a function of t as well. That we have already understood. Then I got to know that at t equals to 0, I am turning on the light. So initially there was 10 to the power 4, those are there. Now since there is a transient, so it will take some time to reach to 10 to the power 4 centimeter cube inverse carrier concentration. So in 1 microsecond it would have reached 10 to the power 2. In 2 microsecond it would have reached 10 to the power 3. In 5 microsecond it would have reached the steady state, that is 10 to the power 4, right? So this would be the total carrier concentration. Here excess carrier concentration is also there, and your minority thermal equilibrium concentration is also there. So what this was known as, this much value was known as delta Px. Why I am not writing down the function of here? What I will write down? Here I will write down delta Px3. Why delta Px3? Because these are the excess holes generated till 3 seconds. These are the excess holes generated till 5 seconds. But I know that more than this will not be there. So here also I can write down the same thing, no? Excess holes generated till 7 seconds or 5 seconds. So that would be equals to delta Px only. And already you are having 10 to the power 4. Is that clear to you? Already you are having 10 to the power 4. So excess carriers that are generated at the steady state, those are delta Px, and that is equals to 10 to the power 4. And now what really happened? These guys started decreasing because light is gone. Here at 7 microsecond, light is gone. So semiconductor will say that I want to reach to my thermal equilibrium. That means I want to reach to this value. So you are having 2 into 10 to the power 4. Semiconductor will say that reduce it to 10 to the power 4 again. So reducing and then finally completely reduced. Is that flow clear to you? Now you need to draw the diagram of Pxt with respect to x and with respect to t in 3D. Okay. So we are going to draw this diagram in 3D. Keep your full concentration, then only you will be able to understand. On x-axis, what is there? Hole concentration. On y-axis, there is hole concentration. On this is the distance. That means this is your semiconductor. This is x equals to 0, x equals to L. You are throwing the light at t equals to 0. You are throwing the light at t equals to t1. Okay. The light has been thrown at t equals to t1. Okay. And steady state is reached. Steady state reached at t equals to 0. Steady state is reached at t equals to 0. You are drawing the whole concentration with respect to time and with respect to the distance. So forget about the distance. First, only focus on the time. Okay. So whole concentration. So initially, what was the whole concentration you are already having? That was equals to number of holes in n-type semiconductor at thermal equilibrium. So that was your Pn naught. Okay. Now the light turned on at t equals to t1. So let's just say this is the time where the light was turned on. This is the 3D diagram. You are focusing on these two guys. All these are 90 degree. Okay. These angles are 90 degree. I hope you know what is 3D. So all these are 90 degree. They are basically, this is the graph we are doing. Whole versus time. Okay. So now what is happening? Till t equals to t1. Till t equals to t1 there was nothing. Till t equals to t1 there was nothing. Just as at t equals to t1 the light is falling. If the light is falling, then what will happen? The number of hole concentration, the number of holes, the number of excess carriers, they will start increasing. They will start increasing, right? They will start increasing. They need to reach to 10 to the power 4 value, but they will take some time. They will take some time and then they will reach here to this value at t equals to 0. Is that clear to you? Now what this will be known as? This was your Pn naught and this will be known as your delta Px. So total number of holes at thermal equilibrium, sorry, not thermal equilibrium, very sorry, the word is wrong. Total number of holes at steady state. What is Px? Total number of holes at steady state. Total number of holes at steady state. That will be called as delta, not delta Px, only Px. And that would be equals to initially Pn naught that you are having plus the excess carrier that you have generated. And now this will not change with respect to the time. Right? So can I draw at the steady state? What this will be known as? This condition will be known as steady state. So what I am doing? I am drawing the whole concentration with respect to x at steady state. If I am in this plane, if I am in this particular plane, whole concentration versus distance. If I am there in this particular plane, whole concentration versus distance. If I am in this particular plane, that means I have reached to t equals to 0. Let us say if I am here, that means I am there at some t equals to t2. This is not my steady state. Where is my steady state? My steady state is at t equals to 0. So if I am on this particular plane, if I am moving on this particular plane, that means I have reached to my steady state. And yes, I have reached to the steady state. T equals to 0 is a steady state. Now what I am doing is that I am drawing whole concentration with respect to the distance x. That means when you go inside the semiconductor, the intensity of light may decrease. The intensity of light may be decreasing, right? So the whole concentration with respect to the distance may be decreasing. So what kind of graph you will be getting? This kind of graph you will be getting. But make sure that only the excess carrier will be gone. these carriers, only the excess carrier will be gone. These are the thermal equilibrium carriers, they will remain there for sure. They will remain there for sure. Because these were the initial hole concentration that you were having in n-type semiconductor. So did you understand this graph or not? In 3D, a very good graph, just it is giving you the complete concept of whatever that we have discussed in last 1 hour. Hole concentration versus time versus distance. Okay, this time is increasing from here, t1 to 0. T1 time is some negative time. Let's just say t1 is minus 5 microsecond. At minus 5 microsecond, you just turned on the light. The light if you just turn on the light, then the hole concentration will not increase instantaneously. It will take some time. Already you are having this much concentration, which was your equilibrium hole concentration, right? Now the hole concentration started increasing. The hole concentration started increasing. This value, the value started increasing. You know that in hole concentration we are moving upward. So value started increasing. But at the t equals to 0, we have reached to the maximum value. That is known as delta px. So after that, if I don't remove the light, this concentration will remain the same. What I am saying is that if I don't remove the light, then this concentration will remain the same. It will remain the same if I don't remove the light. And this graph will keep on going. This red graph that I have drawn, this graph will keep on going like this. This graph will keep on going like this. In 3D we are drawing the graph. I hope you are able to catch up. So this graph will keep on going like this at all the temperatures. Sorry, at all the time, not temperature, sorry, at all the time, because after that steady state is maintained, right? And now when I am drawing the graph, how I am drawing this particular graph? How I am drawing this particular graph? Because I am assuming that the concentration is decreasing exponentially. The intensity of the light is decreasing in the semiconductor, so the concentration is decreasing exponentially. So this is what I am assuming, and this is how I have drawn the graph. And this graph is drawn at steady state. So this is the point of steady state. This is the point of steady state. Can I draw this graph without the steady state as well? What I mean to say is that the same kind of graph I can draw here as well. The same kind of graph, like starting from here, just a rough diagram I am making, starting from here, and this is how it will go. Starting from here, and this is how it will go, and this value is equals to delta Pn not only. What I mean to say is that from this plane, what I am picking, this is the bottom of the plane. This is the bottom of the plane, and from here you know that hole concentration is Pn naught, that is constant. This is the constant value, and I am drawing the graph at t equals to t2. At t equals to t2, I know that delta px is not achieved. That means 10 to the power 4 centimeter cube inverse is not achieved. Some 10 to the power 3 centimeter cube would have achieved. So total concentration is this value, which is this, plus some other value, which is this. So your graph will be starting from here, but eventually with this factor distance, it will decrease. Is that clear to you? Mostly in textbook what you would find, or in the lectures what you would find, is that always people will draw only this steady state graph. So people don't even understand that it could be a function of time as well. Are you able to understand this point? So everything is clear to you? That the excess hole concentration is a function of time and a function of space as well. But this function of space is not fixed. What I mean to say is that it could be constant or it could be linear as well. So you are not sure what kind of profile will be given. So it could be exponential, linear or constant. What I am saying, constant, linear or exponential. So by default it could be anything, sorry, it could be anything, but this is your by default. So most probably it will be mentioned in the examination that how the concentration of excess charge carriers are decreasing. But this will be surely exponential. What I am saying, another new point I am telling, the excess carrier concentration that is increasing with respect to the time, this will be surely exponential. exponential. Is that clear to you? Okay, so this particular diagram will be surely exponential. Now if I say that at t equals to 0 I have turned off the light, what I am saying, steady state is reached at t equals to 0 and at t equals to 0 I have turned off the light now, then what will happen? The semiconductor will say that I will lose everything. What semiconductor will say that whatever that you have given me, whatever this concentration that you have given me, I will lose it completely. I will lose it completely. अरे भाई क्या दिक्कत है? Just I am showing this is how it will lose it completely and it will again reach at Pn naught. So let me try to draw the diagram in a better manner. It will be very much let me copy it. Okay, let me copy it and then what I would do is that I would remove all these and I will try to draw it again. Yeah, so this was our diagram. Now what I am saying is that light source is removed at t equals to 0. So whatever the light source was there, that is removed at t equals to 0. So semiconductor will say that whatever the excess carrier that I have generated, those excess carriers should be gone. I don't want these excess carrier, whatever the excess carrier you are having at steady state, whatever this 10 to the power 4 value that you are having, those value I don't want. So these values will be gone. So these values will be gone, and eventually at some time at the steady state, what it will do is that it will reach to its equilibrium value, that is Pn naught. Okay, so this is the diagram with respect to the time. This is the diagram with respect to the time. With respect to the time. Okay, and if I want to include the distance as well, at steady state only I am drawing the graph. This was your steady state. So at steady state, this kind of a graph you got. What kind of graph you got? You know that at steady state the concentration may start decreasing with respect to the distance. So here this is the steady state, here you are having the maximum concentration, but the excess carrier concentration may be start decreasing with respect to the distance x. And why it is decreasing? Because the intensity of light may decrease with respect to the distance x. So I said that this will be surely exponential. So I am saying that this will also be surely exponential. Are you able to understand what I am saying? This graph, whatever the graph that you are getting with respect to the time, that will be surely exponential. But whatever the graph that you are getting with respect to the distance, that could be exponential or linear or constant as well, whatever the nature is given. Is that clear to you? But the graph with respect to time will be surely exponential. Is that clear to you? Now if I need to write down the value of hole concentration with respect to the time, if I need to write down Pt, not Pt, I am just writing down delta Pt. What does that mean? That how your excess carrier concentration is changing with respect to the time. Are you able to understand this point? What I am saying? How your excess carrier concentration is changing with respect to the time. If you need to write down the capacitor charging equation, how do you write down? Sir, 5 into 1 minus e to the power minus t by 2. Sir, eventually it will try to reach to 5 volt. So eventually, sir, it will try to reach to delta px going through a tangent. So 1 minus e to the power minus t by 2. Here I will write down tau p. This tau p is known as carrier lifetime. And what is this carrier lifetime? We will discuss. So this tau p is known as carrier lifetime. But this will be the true equation if a switch is turned on at t equals to 0. If switch is turned on at t equals to t1, then what will be the equation? This will be the equation, right? So here I will write down the equation in this manner because I know that the switch is turned on at t equals to t1 divided by tau p. Okay, don't try to mug up the equation, just try to understand it, and when we solve the problem it will be all clear to you. Don't worry about that. Okay, sir, how this equation came, you don't need to worry. You don't need to worry about the derivation. And what if the light source is removed at t equals to 0? The light source is removed at t equals to 0. So whatever the delta px that you are having, that will decay down. So what I am writing, the excess carrier concentration with respect to the time. So what that would be? Sir, whatever the delta px that I was having, sir, whatever the 5 volt that I was having, that will be exponentially decaying. So whatever the delta px that I am having, whatever the delta px that I am having, that will also exponentially decay. But what if the light source is turned off at some t equals to t2? Here the light source is turned off at t equals to 0. But what if it is turned off at some t equals to t2? So what you will write down? T minus some other value divided by tau p. Considering that light source is turned off, light turned off at t equals to t2. Very simple thing. When you solve the problem, everything will be clear to you. Okay, don't worry about that. When you solve the questions, every single thing will be absolutely clear to you. Okay, all clear? So at t equals to t1, the light was turned on. The target was to reach to this delta px value. The target was to reach to this 10 to the power 4 value. Okay, so I need to generate excess carrier concentration of 10 to the power 4. So 10 to the power 4 is my final value. So 10 to the power 4, 1 minus e to the power minus t by tau p. What is this tau p? That I will tell you. Okay, so whatever the time it takes, in that manner you can tell. Okay, and let's just say the switch was turned on at t equals to t1. So this is what I will be writing. These equations are coming from the transient part. You know how to write down the equation of transient. So from there you can write down these equations. And if the switch is turned off, that means if the light is turned off, what does that mean? That means whatever the excess carrier concentration that you are having, that will decrease exponentially. So if that is decreasing exponentially, so whatever this 10 to the power 4 that I am having, that will decay down. So 10 to the power 4 e to the power minus t by 2. But let's just say this switch was turned off at t2. So t minus t2 by 2. All clear? Okay. So these response will be surely exponential. But here I am not writing down any equation. Here I am not writing down any equation. That I am not writing down any equation like this. So delta px e to the power minus x by diffusion length. This LP is known as diffusion length. What is this diffusion length? That also I will tell you. But this equation I am not writing down for this one because it is not certain. It could be some different as well. It could be linear as well. So what it would be? Delta px into 1 minus x by LP. This kind of equation could also be there. Or simply delta px. That means whatever the excess carrier concentration that you have made, that will remain the same. Or it could be linear, or it could be exponential. So this will be the equation for exponential, this will be the equation for linear, and this will be the expression for uniform, right? So that's why we are not writing down any particular equation for the excess carrier concentration with respect to x, but we can write down the equation for excess carrier concentration with respect to the time. Excess carrier concentration with respect to time we can write down, but excess carrier concentration with respect to x, we are not writing down any equation. Okay, it could be anything. So here I am writing down, it could be anything. So with respect to x, how I should write down? Oh, let's not write down. Okay, let's not write down the equation. All good. Concept is clear to you. Forget about the equation, forget about anything. Concept should be clear. That is clear to you, right? Now we need to see the definition of a minority carrier lifetime. Then I said that there is something called diffusion length as well. So let's see the definition of these two things. So I told you that from the conduction band, electron will go to the, from the valence band, electron will go to the conduction band, right? Making a hole. Now it will stay there for some time and then it will recombine with the hole. This is known as, whatever the time it was staying here, that time is known as minority carrier lifetime. The electron was generated, electron hole pair was generated, then it remained there for some time. Whatever the time it was left, the average time is known as carrier lifetime. Are you able to understand this point? So before recombining, whatever the time the electron in the conduction band is spending, that time is known as minority carrier lifetime. Why it is written as minority carrier lifetime? What does that mean? That means we are relating with respect to this example. How I am relating? That here light was turned off. Now if light is turned off, that means whatever the excess carrier that was generated, whatever the excess electron hole pairs that were generated, just as the light is turned off, what will happen is that they will say that now your time is up, you need to go, right? What semiconductor will say, just as the light is turned off, semiconductor will say that there is no light source, I need the thermal equilibrium condition. So they were generated because of the light. Now they know that they have to die, right? This have to destroyed, this have to be destroyed, this electron and hole needs to recombine. So whatever the time they are spending before recombining, this particular time, whatever the time they are spending before recombining, that is known as minority carrier lifetime. Is that clear to you or not? So minority carrier lifetime is defined with respect to this condition. First I gave the general condition, that what do you mean by lifetime? So there was an electron, there was a hole. So electron hole pair was generated. Now electron needs to recombine with the hole. So whatever the time that electron is spending there, that is known as lifetime. Now talking about the minority carrier lifetime. So just as the light is turned off, what will happen is that the electron and hole needs to recombine now. Whatever the excess carrier that was generated, that needs to be destroyed. And for that if you need these electron hole pair to be destroyed, then electron and hole pairs should be recombining. Electron and hole should be recombining. So after the light is turned off, how much average time they are spending, that average time is known as minority carrier lifetime. Okay, some electron will be spending more time, some electron will be spending less time, some electrons will be spending some time in between. So whatever the average time they are spending, that time is known as minority carrier lifetime. Okay, so the minority carrier lifetime is the average time and excess minority carrier exists before it recombines. Electron in p type, hole in n type. Minority carrier you understood, right? Because we focus more on minority carrier only. So electrons will be minority in p type and holes will be minority in n type, right? The physical meaning is it measures how long excess minority carriers survive under non-equilibrium condition. So whenever there was non-equilibrium condition, this was the equilibrium condition, this was your equilibrium condition, this was also your equilibrium condition, here also you have reached to the equilibrium condition. But in this non-equilibrium condition, when there was light, light was removed, so electron hole pair were generated. So for how much time they actually survived there? So the average time is known as minority carrier lifetime. And what is this diffusion length? The diffusion length is associated with the distance. So now what will happen is that here the concentration is more, here the minority carrier concentration is more, and here the minority carrier concentration is less. So minority carrier concentration are actually diffusing. So the average length that they are covering. So the definition is written that diffusion length is the average distance an excess minority carrier travels by diffusion before it recombines. Okay. So here what do you see is that here the excess carriers are more, but here the excess carrier are less. That means here the excess carrier has been recombined. So this is what it means, whatever the average distance it is covering. Going from here to here, whatever the average distance your electron hole pair are covering. Basically what is the scenario is that just as you throw the light, there will be more electrons here because the light has been thrown here, and there will be lesser electrons here. So whatever the average distance that they are covering, electron hole, electron hole, electron hole. So whatever the average distance that they cover, that is known as diffusion length. The formula is important. The definition, everything is not important. So there is a relation between minority carrier lifetime, diffusion length and diffusivity. That is known as L equals to under root d tau. How do I remember it? La, do, tofi. Okay. These are the words in Hindi. La, do, tofi. How do I remember? La, do, sorry, la means L. La, do, tofi. Like give me toffee. This is what I am saying. Toffee means candy. So la do toffee. If you are someone who can understand Hindi, then you can make this trick. La do toffee. Otherwise you will be forgetting it. Do you remember that formula? D equals to mu into Vt. How did I tell you to remember? A, B, C, D, U, V. Right? So if you don't make any trick, then you will be forgetting it. You will be doing sir that sir D I will be putting here, VT I will be putting here, those error you will do. And here also if you don't remember the formula, you will be making the error like sir D equals to under root L2. So these kind of things you will be doing. So how will you remember? Sir, la do to phi. Give me to phi. This is to D L. Lifetime is shown by to. Diffusion length is shown by L. So la do to phi. L equals to under root D2. Okay. So this formula, along with that there is another formula. What is that? D equals to, this formula also you should not be forgetting. D equals to UV. So mu into VT. D is the diffusivity, tau is the minority carrier lifetime, and L is the diffusion length. Okay, everything is clear. Even if the definition is not clear, don't worry about that. Formula are important. For solving the problem, formula are important. But you understood the minority carrier lifetime. What is the minority carrier lifetime? The average time it is spending before recombining. And what is the diffusion length? The average time it is spending before recombining. Sorry, the average length it is covering before recombining. So diffusion length is associated with the length and diffusion time is associated with the time. Okay. So what is your diffusion length? Diffusion length, here there are more minority carrier, here there are lesser minority carrier. So whatever the length they are covering before recombining, that length is known as diffusion length. Okay. So this is the formula that they have written. D is the diffusion coefficient, or you can call it diffusivity of minority carrier. Tau is the minority carrier lifetime. And what is the physical meaning? It tells how far excess minority carrier can move in the semiconductor under non-equilibrium condition before they disappear. So here the minority carrier concentration has been, excess minority carrier concentration has disappeared. Here there is minority carrier concentration. That means here there are holes, but whatever the excess that was generated, that is gone. Okay, all fine. If you feel like that sir it is too much, then it is not actually too much. I am just explaining too much, I guess. Don't feel like that sir there are a lot of things, how will I remember? Very simple analogy I have given just by the capacitor example. So you will be able to solve the problem in the easiest manner, that is my guarantee. Okay, so just cover whatever that I am telling, and that would be more than enough to go. So this formula and this formula, that these two formula till this point we have understood. Now I need to take some break, and then we will be studying about generation rate and recombination rate. Very simple thing. Electron hole pair are generating. So with what rate they are generating, that is known as generation rate, and with what rate they are recombining, that is known as recombination rate. So the rate of electron hole pair being generated per unit volume per unit time, that is known as generation rate. What will be the unit? Per unit volume per unit time. So let's just say 10 to the power 14 electron hole pair were generated per unit volume per unit time. Okay, generation rate and recombination rate with the rate that they are recombining. So that is known as recombination rate. Now what is the formula of recombination rate? Very, very important. The most important thing of this whole chapter. So that we will see after a break. Let me take some break. Let me drink some water, and then I will come back. Okay. Yeah, welcome back guys. So we were studying about generation rate and recombination rate. So number of excess charge carriers generated per unit volume per unit time was generation rate, and number of charge carriers recombining per unit volume per unit time was recombination rate. Okay, so we were majorly focused on excess charge carriers, because when you are illuminating the light, excess charge carriers are being generated, right? So your recombination rate, this is a very, very important formula. So your recombination rate will be proportional to excess charge carriers. Say yes or no? Excess charge carriers. Say yes or no, right? And it could be a function of both space and time. Why is that so? Because excess charge carriers can be a function of space and time. Excess charge carriers are both the function of space and time. That's why recombination rate can also be a function of space and time, right? So when you remove this proportionality sign, what you will get? Now let us say there is n-type semiconductor. So in n-type semiconductors, charge carriers will be both electrons and hole, because excess charge carriers will be generated in electron hole pairs, right? Whatever the excess charge carriers that are holes generated, same number of electrons will also be generated. But what we focus on? We majorly focus on the minority, right? In n-type semiconductor, I will be focused on delta P. Although the same delta N is also generated, but my focus will be on delta P, right? So when I am writing down the formula, at that time I will be writing down delta P x T for n-type semiconductor. Are you able to understand this point? if I am saying that in n-type semiconductor, excess charge carriers generated are holes, which are delta p xt. So can you tell me how much excess charge carriers generated, which are electrons? What is the amount of that? That amount will be similar to the holes only, because excess charge carriers are generated in electron hole pair. So if I know how much holes are generated, then I know that how much electrons are also generated. But whenever you write down the formula of recombination rate, you focus on minority excess charge carriers. What I am saying? Minority excess charge carriers. Excess means which are generated because of the light. Minority means holes. So this I am saying for n type. But don't confuse yourself saying that, sir, delta P and delta N will be different. No, they will be same only. But when we write down the formula, we focus on the minority excess charge carriers. Is that okay for you? So this is the formula for recombination rate for n type. And when you remove the proportionality sign, what you get? When I remove the proportionality sign, I will get 1 by tau p. So when I remove the proportionality sign, I get 1 by tau p. And it is pretty obvious as well. Why is that so? Because if tau p is high, if your lifetime is high, that means you are recombining slowly. If lifetime is high, then electron hole pairs are recombining slowly. So this particular formula that I have derived, or you can say just I have simply put down with the condition that tau p is a constant. It is not a function of space and time. Because you are saying that recombination rate, here I should have written Rxt, right? Because you are saying that recombination rate is a function of, let's write down the formula again, Rxt. Recombination rate is a function of x and t, and that is proportional to excess charge carriers, which is a function of x and t, right? So you are removing the proportionality sign, so you are getting something called 1 by tau p. So this tau p has to be a constant and uniform. That means it should not be depending on time, or it should not be depending on space. Is that clear to you or not? So here I am what I am writing down. Tau p is constant and uniform. It should not be depending on x, it should not be depending on time t. Is that okay for you or not? So this I have written for n type. Similarly for p type, what will be my formula? Similarly for p type. In p type, I will be focused on the minority charge carriers. Minority excess charge carriers. Who will be minority excess charge carriers? Those will be holes, right? So formula for recombination rate in p type, recombination rate in n type, recombination rate in p type. So minority excess charge carriers, there will be electrons. Although the number of electrons will be equal to number of holes only, but those will be electrons. And divided by tau n. What is tau n? Lifetime of lifetime of electrons, and tau p is lifetime of holes. So this formula is very, very important. But along with that, there is this condition important as well, that your tau should be constant and uniform. So this particular formula, which every student remembers, that sir, Rx is equals to delta P by tau P, and sir, Rx is equals to, or Rx you can call Rn Rp, whatever you want to call, basically excess minority carrier concentration divided by the lifetime. So this formula you will be able to remember, but this is applicable only when your tau P is constant and uniform. And at the steady state, what will happen? The recombination rate will be only a function of x, right? The recombination rate will only be a function of x. Why is that so? Because time term will be gone, because you are at the steady state now. Now your carrier concentration is not changing with respect to x. So your carrier concentration, your excess carrier concentration has been fixed. Or you can write down the formula as this as well. So people usually remember this formula. They don't even consider that delta P could be a function of t as well. So actual formula is this, but this formula is applicable at the steady state. Again, it is applicable for the condition that your tau is constant and uniform. In all the questions till this date in GATE examination, tau has been always constant and uniform, but there was one question in GATE 2022 examination, they did not mention about the lifetime. So there everything is changing. So I will solve that particular question. Till this date, everywhere the solution is wrong for that GATE 2022 examination problem. Excellent problem it was. Okay. So although they get the answer, but luckily they are getting the answer. So we are going to discuss that particular question in great detail. So very important condition that tau should be constant and uniform. Tau will be constant for sure. Constant means it should not be depending on time. So tau itself is a time. Lifetime itself is a time only. So how it will be depending on time, right? But it cannot be uniform all the time. It can be depending on x. Basically, as you go into the semiconductor, as you move into the semiconductor, your lifetime may be changing. Your lifetime will surely be constant, no? Why it is constant? Because time itself is a time only. Lifetime itself is a time. So it will never depend on the time, but it can depend on the distance. As you walk, as you move into the semiconductor, your carrier lifetime may change. So this is very important condition that you will apply this formula only when your carrier lifetime is uniform. It will be surely constant, so it is pretty obvious. You don't even need to write down that it should be constant. It will be surely constant, but it should be uniform as well. So again I am repeating very important formula, like your 90% of the gate question will be solved by this particular formula only. That's it. Only using this formula your 90% of the gate problems will be solved from this particular topic. What is that formula? The recombination rate is equals to excess minority carrier concentration divided by their lifetime. Excess minority carrier concentration or excess charge concentration I should write down. Excess charge carrier concentration, excess charge carrier concentration. So excess charge carrier concentration divided by their lifetime. All good? All fine? Okay. Let's move to our next topic, that is continuity equation. So everything that we were studying, only we were studying for this particular thing, continuity equation. So usually this topic is started from this particular slide, but last 1 hour and 30 minutes we were discussing just to write down the equation in a good manner. So what does the continuity equation tells? So continuity equation, even mechanical engineering will be studying, civil engineer student will also be studying. Continuity means whatever that is coming, that will flow out. That's it. That means things will be conserved. Let's just say, or forget about any analogy, here only you will be able to understand. So let's just say this was my semiconductor. I am calling this as p-type semiconductor. Okay, this is my p-type semiconductor. In this p-type semiconductor I am throwing some light. Because of this light, what will happen? The minority carrier concentration will be increased. Like majority will also be increased. What I mean to say is that holes will also be increased, but electrons will be also increased, right? And we will be focusing on the minority carrier concentration. So there will be change in the concentration of electron. So change in the concentration of electron with respect to time. So this is change in the concentration of electron per unit volume per unit time, because concentration is always given in centimeter cube inverse. So concentration of electron per unit volume per unit time. So change in the concentration of electron per unit volume per unit time would be equals to generation rate minus recombination rate. Why is that so? Because generation rate means excess carriers are generated. Recombination rate means they are being recombined. So generation minus recombination will be equals to whatever that is effectively left. Along with that, one more term will come. 1 by q j nx 1 by q dj nx by dx. Why that so? Because of the current as well, no? If the current outflowing is more, if the current flowing out is more and current flowing in is lesser, then the number of electrons will be getting increased inside the small volume. So this we have already seen. So for the electrons, what we use? We use the positive sign. This is your continuity equation, and you go and check out the step for getting this final answer. For getting this final answer, you will have to go through a very high level of mathematics. Not very high level of mathematics, that means basically a lot of mathematical calculation you need to do. Then only you get to this final expression. But without even doing any mathematics, we are writing down this final expression. Generation rate, number of charge carriers being generated, and recombination rate, number of charge carriers being destroyed. So total charge carriers that are being generated, will be given by generation rate minus recombination rate. But one more phenomena is there, that is the current.
if current flowing out is more and current flowing in is less, that means the electrons getting in is more and electrons getting out is less. That means the concentration of electron is getting increased inside this small volume. So plus 1 by q j plus 1 by q djx by dx. So this is the continuity equation for electrons in p-type semiconductor, because we will be focusing on minority carrier concentration. Why we are focusing on minority carrier concentration? Because minority carrier concentration is getting changed significantly, but majority carrier concentration is not changing that much. Is that clear to you or not? Is this equation clear to you or not? So this is written for the p-type. Similarly, you can write down for the n-type as well. So complete theory I have already written down here. So for electrons, the continuity equation for the electrons will be delta n by delta t plus 1 by q delta jn by del x plus generation rate minus recombination rate. Here I have given the complete formula that it will be depending on x and t, it will be depending on x and t, and it will be depending on space only, right? Now delta n by delta t is rate of change of electron concentration with respect to time, and here the definition is also given. What is the definition? Definition says that it is based on the principle of conservation of charge. Okay, so whatever that is going in, that should go out, right? So the rate of increase of carrier concentration per unit volume, that would be equals to net inflow of charge carriers per unit volume plus generation rate minus recombination rate. Net inflow, generation rate minus recombination rate. And for the case of holes, there will be a negative sign here, right? You can see there has been a negative sign. It has been written minus 1 by q djpx by dx plus generation rate minus recombination rate. And why this negative sign, you already know, right? In detail we have done the explanation. Now you are able to understand that why we focus so much on 1 by q dj by dx. So the reason was this continuity equation. Now you are able to understand continuity equation in a very easy manner, right? What is 1 by q djx by dx? That we already know. Generation rate, recombination we already know, and generation rate minus recombination rate is showing the net generation of the electron. That means whatever the electrons that are being generated minus those are recombined, so that would be the net electrons that are generated. All good, all fine. So for both of the cases you are able to write down the continuity equation. Let's see some special cases. So under steady state, what is the meaning of steady state? The meaning of steady state is that now your excess charge carriers are not changing. So what does that mean? Here I wrote down that what will be the number of electrons? That will be the number of electrons in p-type semiconductor at thermal equilibrium plus excess electrons plus excess electron. So these are your number of electrons. This is this n that I have put here. This n is this one. So this value is already constant. NP naught is already constant. Now if I say steady state, what is the meaning of steady state? That means this value also has reached to its maximum. That means if excess charge carriers generated should be 10 to the power 4. So now we have reached to the 10 to the power 4. Now your delta n will not change with respect to the time. Your delta n is also constant. So at the steady state, if I do dn by dt, what that would be? That would be equal to 0, right? Steady state means electron concentration is, or minority carrier concentration is not changing with respect to the time. So minority carrier concentration is not changing with respect to the time. So delta n by dt I am directly putting. That means the concentration with respect to time is not changing. Electric field is 0 and your carrier profile is constant. The other name of this carrier profile is, if I say carrier profile is constant, what does it means? That means there is uniform illumination. What is the meaning of uniform illumination? That means from all the side light is coming. Here, 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 from here, here, here as well light is coming. Here as well light is coming. Here as well light is coming. So what I said, the intensity of light may decrease exponentially inside the semiconductor, but if the light is coming from all the side, then what will happen? The carrier profile will be constant only. That means whatever the excess carrier concentration you generated here, the same excess carrier you will be getting here as well. So this is known as uniform illumination. So in the examination they will not write down Nx is constant. What they will write down? There is uniform illumination. So if the word uniform illumination is written, then you will understand that the excess carriers are not changing with respect to the distance. That means in whole semiconductor, in the complete semiconductor, the excess carriers are constant. Not constant, the excess carriers are uniform. Not constant. Constant and uniform both are different words. So excess carrier is having uniform profile. And already you know that NP naught is constant only. NP naught is already constant, right? So what you will understand from here, Et is 0 and Nx is constant. What does that mean? What does this particularly mean? What is the meaning of this whole thing? We have seen it in the first slide. In the very first page we have seen this. Et is 0 and Nx is constant, or you can say Nx is constant, wrong word. Nx is uniform, really sorry. Nx is uniform. Constant is the wrong word here. Nx is uniform, that means it is not changing with respect to the distance. So what do you think, what will be the answer of this particular thing? That means your djx by dx would be equal to 0. Why is that so? Because E is 0, that means drift current is 0. If Nx is constant, what does that mean? The diffusion current is 0. So total current would be 0. Then differentiation will surely be 0. So what did you see here? This term is gone. This term is also gone. This term is gone. This term is also gone. Basically, 0 would be equals to 0 plus generation rate minus recombination rate. So from here, what you will get to know is that generation rate would be equals to the recombination rate. So at a lot of places you would see that under steady state generation rate is equals to recombination rate. Is that statement true? That under steady state generation rate is equals to recombination rate? Absolutely wrong. Under steady state, for the case of uniform illumination such that there is no electric field is applied, then your generation rate is equals to recombination rate. So never ever tell that, sir, under steady state generation rate will be equals to recombination rate. I will show you a question of GATE 122 examination. There steady state will be mentioned, but generation rate will not be equals to recombination rate, because these conditions will not be satisfied there. They will give this condition, they will also give this condition as well, but they will not talk about this particular condition. So there you cannot say that, sir, generation rate will be equals to recombination rate. Is that okay for you or not? So generation rate will be equals to recombination rate when your dgx by dx is 0. And when dgx by dx will be 0, if electric field is 0 and Nx is uniform. That means there is a case of uniform illumination. That means at all the, as you move into the semiconductor, at all the values of x, there is same carrier concentration. Okay. Now again, under steady state, you already know that dNt by dt would be 0. Et is 0. What does that mean? Drift current is 0. And Nx is linearly varying. What I am saying? Nx is linearly varying. If Nx is linearly varying, what does that mean? If Nx is having linear variation, that means your drift current is constant. And if you do the, sorry, your drift current is not constant. Your drift current would be uniform. I should not say constant. Even in the first slide as well, I have written constant. Okay, here I should have written uniform. Uniform. Uniform means it should not be changing with respect to the distance. Uniform, not constant. Uniform. Okay, uniform, uniform. Here also uniform. This is also uniform. So now which case we are discussing? This case we are discussing, right? So if your Nx is, yeah, here you can write down constant, right? Here you can write down a constant value. Why I can write down the constant? Because it will be a particular value, no? So uniform, constant, both will have the same meaning. So here the slope will be constant. Slope will give a particular value. And if you do the differentiation of a diffusion current, then what you will get? 0 only. So whatever the two conditions that we discussed in first two pages, those only our special case are. So these are our special case. So here as well you would know that this will be equals to 0. What does that mean? That means here also generation rate will be equals to recombination rate. So generation rate will be equals to recombination rate if you are under the steady state, applied electric field is 0, and your profile is either uniform or linearly varying. What I am saying, generation rate is equals to recombination rate under steady state, applied electric field is 0, and your profile is either uniform or linearly varying. Is that okay for you? Okay. There was one more condition, by the way. The total electric field was constant and your profile was uniform. In this condition as well, what was happening? In this condition as well, dgx by dx was 0, right? Because if this profile is uniform, that means your diffusion current is 0. And if your total electric field is constant, then your if total electric field is constant, then oh, this is an error we have done, I guess. No, sorry. Here n is also constant, no? N is uniform, nx is uniform. So this is uniform. That means nothing is depending on x. Electric field is not depending on x, mu is not depending on x, q is not depending on x, and n is also not depending on x, right? This is also uniform only. So everything is uniform. Then you do the differentiation with respect to x, what you will get 0 only. So this was also a condition, but it is not very famous. What you would see in the examination is that they will give electric field, external electric field 0 only. Basically, in the examination, till this date, whatever the question have been asked, always this condition and this condition was given, always. So that's why people usually don't discuss that it is equals to constant. Like if total electric field is constant and your profile is uniform, that means if there is a case of uniform illumination with the constant electric field, then also your dgx by dx would be equals to 0. Along with that, under steady state as well. So under steady state, if steady state is there, what does that mean? Under steady state, and if steady state is there, that means dn by dt is equals to 0. So this is 0, dgx by dx is 0. What does that mean? Generation rate is equals to recombination rate. Okay. So three conditions are there, but you remember only one thing: steady state you need to see, okay, and then profile you need to see. ET0 will be given. Steady state, ET0, profile. Profile is uniform or linear. Then your generation rate will be equals to recombination rate. Don't feel like that, sir, there is too much. There is nothing too much, right? Very, very simple thing. Now a very easy question, try solving it. The correct form of a continuity equation for a semiconductor under non-equilibrium is, sir, this formula you have told, this formula also you have told. Sir, from where these formula came into action? Try doing it on your own. You should be able to do it. These formulas are also there, no? Just write down the expression of j and x. What will be the expression of j and x? That could be n, q, mu. This could also be a function of x. Electric field, okay, plus q dn dnx by dx. And when you do the differentiation, what you will be getting? Differentiation divided by q. So q and q will get cancelled out. Now what you will see here, this is also a function of x, this is also a function of x. So u into v formula I will apply. What does that say? One as it is, first one as it is. So first one as it is, differentiation of the second, plus second one as it is. That means mu into, why sir, why you are not applying q? Because q is gone, no? Because I have divided by q. So this q I have taken this side. Now what I am doing? I am doing the differentiation. So differentiation of, first I am doing the differentiation of nx, ex as it is. Then I will do the differentiation of ex keeping nx as it is. Here also I need to do the differentiation again. So that will be double differentiation. Okay. So 1 by q, here gnx by dx. So what you can see, mu ex, yeah. So mu e, this term is here, right? This term is here, this term is here, and generation rate minus recombination rate is already given, right? Similarly, all these terms are coming in, all these terms are coming for holes as well, just there will be an extra negative sign. Where there will be extra negative sign? Why there will be extra negative sign? Because you know that whenever we write down for the holes, extra negative sign we add up. So here negative sign is there, here negative sign is there, and why there is no negative sign here? There should be negative sign here as well, no? Right. There is some error. If I put here negative sign, I will put basically negative sign I will put, so negative. Yeah, negative sign will not come here. It will be positive only. Why is that so? Because for holes, what you will write down? This will be your JPX, no? This will be your JPX. What will be your JPX? N, Q, mu, E. And when I write down the diffusion current, for holes, then again negative sign will come, no? So Q into dp dpx by dx. So here in place of n, I need to put p. Now this q I will take this side and then I will differentiate. Mu ex as it is, then dpx by dx plus then mu px as it is, dex by dx minus dp d square px by dx. Okay, but extra negative sign I need to add. So this will be negative, this will be negative, and this will be positive. Now you can check what you can see: negative, negative, positive, generation rate minus recombination. So all options are correct. Okay, so only in the options this kind of question can be asked. These formula you don't need to remember. That's why I will remember this answer. Practically impossible to remember, no? Actually, people will find this one to remember as well. Like this also will be difficult to remember. But we have developed the intuition that total increased concentration with respect to time would be equals to generation rate minus recombination rate. Now, carrier concentration because of the current will also increase. So what term will come? 1 by q dgx by dx. So this will be easy to remember without any mathematics, right? After that, if it is required, you can derive it, but in the examination, this will never be used. These will never be used in the examination. Only in MCQ they can ask, or MSQ they can ask that what is the correct form of continuity equation for semiconductor under non-equilibrium. So this is how you can tell the answer. All good? All fine? So now our task would be just to solve the problems. So for 2 hours, we have understood the complete theory. Now we will be just doing the problem solutions. So questions will be there and we need to solve it. That's it. So how we would approach the problems? Although you don't need to mug it up, but what you will be first looking at it? You will be looking at the special cases. That means you will be looking for which condition? Steady state. First thing is steady state, electric field 0. I am writing down. Steady state, electric field 0, and carrier profile is either completely uniform or linearly varying. If this thing is there, then you will directly do generation rate is equals to recombination rate. And what is the formula of recombination rate? That is equals to delta p divided by tau p, delta px divided by tau p, and since we are looking at a steady state, so let's write down in a better manner. Since we are looking at the steady state, so now nothing will be a function of time t. All the things will be function of x only. So all the things will be function of x only. Why is that so? Because we are at the steady state. So at the steady state, recombination rate and generation rate both will be equal and both will be function of x. And what is the formula of recombination rate? That is equals to delta px divided by tau p or delta nx divided by tau n. So this I will apply in n type and this I will apply in p type. Okay. So this will be our best case. And secondly, constant and uniform lifetime. Constant and uniform lifetime. This is also very, very, very important. Why it is very important? Because whatever the formula that you have written down, this formula is applicable only for this case, that your lifetime should be uniform. It will be surely constant, there is no doubt about that, but it should be uniform as well. It should not be a function of x. Okay. As you go into the semiconductor, as you move into the semiconductor, your lifetime should not be changing. If it is changing or if it is not mentioned, that they did not even discuss about lifetime, then you cannot take it uniform. Then you cannot apply this formula. Is that okay for you? And if worst case otherwise, then you have to go for continuity equation. And there is only one question till this date in the GATE history that you need to go to continuity equation. Although luckily in that question, even if you solve it without continuity equation, you are getting the correct answer. But that was lucky. So I will solve that question without continuity equation, and then we will see that we are getting the correct answer. Then we will see what wrong thing we are doing and how to make it correct. What will be the correct answer of that particular thing. So great discussion we are going to do on that particular question. But as of now, The summary is clear to you. This is the only summary for solving the problems. That's it. Questions will be solved from here. Whatever that we have studied, that we have built up the base. But from the continuity question, this is how the questions will be solved. So let's get started. Everything that we have studied, that will be surely helpful. Okay. So let's get started. This is the first question. All these questions are from our Niemann's book. Okay. Donald Niemann book. Semiconductor Physics by Donald A. Niemann. So from there only these questions are picked. And most of the gate questions are framed from that particular book only. Like 90% of the gate questions are coming from that particular book directly, just by changing some data. So let's get started. Although this is written by ChatGPT, because what I do is that I give them prompt, like I change some of the values of the questions and then I put it here. So that's why just I try to make it more exam oriented, right? Whenever like any writer is writing down the book, then he is not writing down for any examination purpose. He is writing down that PhD guys might be studying it, MTech guy might be studying it, even beta guys might be studying it. So everyone should be able to understand what they are doing. It doesn't mean that he is writing down the textbook to make you pass for a competitive examination, right? NPTEL lectures and these textbooks are never made for competitive examination. They are made for the understanding purpose. So that's why as an educator, it is our duty that we read it, we make a good conclusion out of it and then represent in front of you so that it would be helpful for cracking the competitive examination. So yeah, let's get started with this question. N-type gallium arsenide semiconductor is there. N-type it is, and this was the donor concentration. It is illuminated at T equals to 0, generating 10 to the power 14 electron hole pairs per centimeter cube. What does that mean? This is your generation rate. So N-type semiconductor was there. It was at equilibrium. Donor concentration was 10 to the power 16. Okay. And Ni value is also given. Ni value is also given. So you can see that donor concentration is much higher than Ni. So what does that mean? Approximate number of holes will be equals to 10 to the power 16 only, right? And so the approximate number of electrons will be equals to 10 to the power 16 only. And what will be the number of holes? That will be Ni square by Nd, Ni square by N, 10 to the power 20 divided by 10 to the power 16, that would be 10 to the power 4 centimeter cube inverse. So this was the equilibrium. Then what really happened? At T equals to 0, they illuminated the light and generating 10 to the power 14 electron hole pair per centimeter cube at steady state only, like this is the steady state concentration they would have given. That means at steady state 10 to the power 14 extra electron hole pairs are generated. What does that mean? That means the value of delta Px is equals to delta Nx is 10 to the power 14 centimeter cube inverse. Did you understand this point or not? Do you agree to this point? Say yes or no. Surely you agree to this point, no? Right? Because these many electron hole pairs are generated. The illumination is turned off at 50 nanosecond. Given that the minority whole lifetime is 10 nanoseconds. So whole lifetime is given, that is 10 nanosecond. Determine the whole concentration at 15 nanosecond and 60 nanosecond. So very simple question. What was the scenario? What was the scenario? The scenario was like this. Initially, you are having, we will be talking about the minority carrier concentration, right? So initially you are having 10 to the power 4 here. Then at T equals to 0, they turned on the light. At T equals to 0, they turned on the light. They turned on the light at T equals to 0. So now what will happen? The concentration will try to increase. The concentration will try to increase. Basically, the number of holes will try to increase. Already they are having 10 to the power 4. So they want to reach to 10 to the power 14 plus 10 to the power 4. Basically, they need to generate more 10 to the power 14. So what will be the equation? The equation will be, if I write down delta P T, that means they want to reach to 10 to the power 14, starting from 0, e to the power minus T by tau P minus 1. Oh, sorry. 1 minus e to the power minus T by tau P. Capacitor equation. Capacitor wants to charge to 5 volt, starting from 0. Now no one will say that, sir, we are starting from 10 to the power 4. 10 to the power 4 is the constant thing that it will always have, right? Are you able to understand this point? 10 to the power 4 it will always have. There is no one who can change it. We are just focusing on the excess carrier that are generated. So 10 to the power 14 are the excess carrier that are generated. Right? So this equation we have already discussed in great detail. Now you are able to understand what is happening. Now what they are asking at 15 nanosecond. At 15 nanosecond, what will be the concentration? At 15 nanosecond. And TOP value is also given, that is 10 nanosecond. So you can write down. It wanted to reach to 10 to the power 14. But in 15 nanosecond, how much it would have reached? In 15 nanosecond, it would have reached. I have spent more than enough time. I have made the diagrams as well. So I hope you would be able to understand. Otherwise, it would become very difficult that what is happening, you wouldn't even know. Right? Instantaneously, they cannot generate 10 to the power 14. They will take some time. So they want to reach to 10 to the power 14 at the steady state. So this is how I will write down the equation. The switch is turned on at t equals to 0 nanosecond and at 15 nanosecond it is turned off. So what will happen at 15 nanosecond, we will see that. But first our target is to find out at 15 nanosecond. So 15 divided by 10. So what will be the answer? A to the power 1.5. A to the power so 0.77 into 10 to the power 14 centimeter cube inverse. So your excess carrier concentration at 15 nanosecond is this much. So this is the excess carrier concentration. So what will be the total? So total whole concentration at t equals to 15 nanosecond. That would be equals to what? These are the excess plus something that I already have. So I already have 10 to the power 4 plus excess, which is 0.77 into 10 to the power 14. So what you will get? 10 to the power 4 is approximately nothing in front of 10 to the power 14. 0.77 into 10 to the power 14 centimeter cube inverse. So this is the answer of the first one. Very simple, very straightforward. Now what is happening at 15 nanosecond, at 50 nanosecond, you are turning off the switch. So what will be the concentration at 15 nanosecond? First I need to find out that thing, because I know that since light is gone at 15 nanosecond, the light is gone. So now after that what will happen is that it will decrease. But I am not pretty sure that at 15 nanosecond have we reached to this value or not. Are you able to understand what I am saying? At 15 nanosecond, it might happen that you wanted to reach to 10 to the power 14, but it might happen that you were not able to reach here at 15 nanosecond. Like what I mean to say is that what if he turned off the switch at 15 nanosecond only? At this time only he turned off the switch. Then what would have happened? Then your excess carrier concentration would be decreasing from this value, not from this value. So first I need to see at 15 nanosecond what is the scenario. Although I directly know that my time constant or carrier lifetime is 10 nanosecond and this is 50 nanosecond. So at 5 topi time, approximately I will reach here. If you know network analysis in a good manner, then in thrice of the time constant, this is like a time constant only, no? So in thrice of the time constant, you reach to the 95% of the value, and in 5 times of the time constant, you reach to the 99% of the value. So forget about all these things, just apply the formula. What I am saying is that first we need to find out that what is our concentration at 50 nanosecond. Have we reached to our steady state or not? So excess carrier concentration I am finding at 50 nanosecond. Divided by 10, right? Divided by 10. So e to the power minus 5 will be a very, very low value. Minus 1. So you can see that 99.3. So answer is coming 0.9932 into 10 to the power 14 centimeter cube inverse. So this much you have reached. So this is the concentration at 50 nanosecond. Okay. Now the switch is turned off. Switch is turned off at 50 nanosecond only. Switch is turned off at 50 nanosecond. Now what will happen to the excess carrier concentration? The excess carrier concentration will decrease from this particular value. What is this value? 0.9932 into 10 to the power 14. From this particular value, it will exponentially decrease, starting from 15 nanosecond, right? Divided by tau p. What is tau p here? Tau p is 10 nanosecond. Is that clear to you or not? Let's put tau p only. So after that, it will decrease. Basically, in 10 seconds of the window, when you turn off the switch, in 10 seconds of the window, you are checking at 60 nanosecond. What does that mean? After turning off the switch, after that, after 10 nanosecond, what is your condition? When you turned off the switch, after that, after 10 nanosecond, what is the condition? Or they have simply written at 60 nanosecond, what is the condition? Did you understand this point? That's why we put t minus 50. Do you understand? Because here I'm gonna put 60 here. So window of 10 nanosecond was there. So what I'm gonna do is that here I'm gonna put 60 nanosecond. So 60 minus 50, that means window of 10 nanosecond. So what I will be getting? 0.9932 into 10 to the power 14 e to the power minus 60 minus 50, that would be 10 nano divided by tau p. So 0.9932 divided by E. So 0.36 into 10 to the power 14 centimeter cube inverse. This is the excess concentration at 60 nanosecond. So what will be the total concentration? Total whole concentration at 60 nanosecond. So this is the excess one. Plus we know that this will always be there. 10 to the power 4 will always be there. So what you are getting? Approximately 0.36 into 10 to the power 14 centimeter cube inverse. So although in the examination this question will not take that much of time, what I will think directly, I will see, okay, at 10 t equals to 0, illumination has started. That means excess carrier will start generating, but it will not generate instantaneously. It will take some time. Exponentially it will rise. Exponentially it will rise. It needs to reach to 10 to the power 14. So equation would be 10 to the power 14 1 minus e to the power minus t by tau. So at 15 nanosecond I can find out the answer. Now what I can see that at 15 nanosecond, at 50 nanosecond, the switch is turned off. That means the illumination is turned off. So what will happen is that whatever the excess carrier has been generated, they will exponentially decay to our equilibrium concentration, right? So then I would see that 50 nanosecond, that means my time constant is 10 nanoseconds. So 10 to 50, 5 tau time is there. That means surely I have completely reached to the excess carrier concentration. Steady state excess carrier concentration I have already reached. So 50 nanosecond is actually the steady state only. So this much concentration I am already having. Now what will happen is that it will decrease exponentially. So from 10 to the power 14, nearly about 10 to the power 14, it will exponentially decrease. So from 10 to the power 14, it is exponentially decreasing. So e to the power minus t by tau. T minus 50 nanosecond I can write down, but I would see that from 50 to 60 nanosecond they are asking. That means I am having a window of 10 nanosecond. So here 10 nanosecond will come. So 10 nano divided by 10 nano. So answer would be this one. Very easily you would be able to solve, right? Let's go to the next one. N-type semiconductor with donor concentration is this much, illuminated uniformly. What does that mean? That means since this is N-type semiconductor, so I would be focusing on minority carrier concentration. So this is uniform, right? This much is calculate the under steady state. You read the question and you see under steady state. Did they discuss about electric field anywhere? That means electric field is also 0. They did not discuss about electric field anywhere, no? So total electric field is also 0. What does that mean? That means generation rate is equals to recombination rate. Generation rate is equals to recombination rate, and that is given as 10 to the power 20 centimeter cube second inverse. Can I apply the formula? You can apply the formula if your lifetime is constant. Lifetime is constant. So the recombination rate is given as 10 to the power 20. Can I apply the formula? Yes. What they are asking? Excess majority carrier concentration they are asking. But you know that, sir, here I will put the formula of minority carrier concentration. Why is that so? Why minority carrier concentration? Sir, because sir, if I put the minority carrier concentration here, then I will be able to use this lifetime, because my minority carrier concentration is holes. So excess minority carrier concentration I am putting here, divided by the lifetime. So excess minority carrier, since it is uniformly illuminated, so there is no meaning of writing down X here. I will directly write down delta P. Why I am directly writing delta P? Because uniform illumination is there, no? So whatever the excess carrier that has been generated, let us say any value that I get, that will be uniformly distributed. That means that will not change with respect to X. And since you are already at steady state, so it will not change with respect to time as well. So there is no variation with respect to space and with respect to time. That's why you can see that generation rate and recombination rate are constant and uniform. They are neither depending on the X, nor they are depending on T. Everything is crystal clear to you. Every single thing that is written in this question, that is clear to you, and this is the way of solving any problem. That whatever that is written in the statement, everything should be clear, right? So delta P by tau P value is 10 microseconds. So from here you can see your answer would be coming, delta P would be 10 microseconds. So 10 to the power 20 centimeter cube divided by second into 10 microsecond. 10 microsecond. Okay, second to second will get cancelled out. 10 to the power 50 centimeter cube units. This is your delta P. But what they are asking? They are asking the value of delta N. Excess majority carrier concentration. And who are the majority? N. That means they are talking about excess majority carrier concentration, which will be excess holes. How many excess holes are generated? You know that electron and hole pairs, electron and holes are generated because of the light illumination. Electron and holes will be generated in pairs. So that would be only equals to delta. Everything is crystal clear, very simple question. Okay, generation rate was given, that would be equals to recombination rate, but condition you need to see, because usually I have seen that people will just remember generation rate equals to recombination rate, forget about the continuity equation. They don't even care about the continuity equation. Generation rate equals to recombination rate, this is the formula. But there are a lot of things. How generation rate became equals to recombination rate? When you can apply this formula. So this was also very, very important, that it is not a function of space, it is not a function of time, then only I can apply this formula. Okay, so a lot of things are there, then only you can apply generation rate equals to recombination rate. So before 2022, in all the question, this thing was working. In gate examination, in all the problems, this thing was working. But in 2022, there was one question that changed everything. Okay, so you need to take care of all these things, right? Consider one dimensional hole flux as shown in figure they have not given. If the generation rate of holes in the differential volume, generation rate they have given 10 to the power 20 centimeter cube second inverse. Recombination rate they have given. So here generation rate and recombination rate are not same. What must be the gradient of in the particle carrier density to maintain the steady state hole concentration? Steady state. Now what do you mean by gradient? Gradient means variation with respect to space. What I am saying? Gradient means variation with respect to space. But in EDC we only take the variation with respect to x-axis only, or y-axis or z-axis. Basically we focus on 1D variation. But when we go to EMFT we focus on 3D variation. So that's why we use the sign of gradient there. But here what we will use? D by dx. So what they are asking? They are actually asking dp by dx. Sorry, what I am doing? djp by dx. This is what they are asking. Will it be depending on x? No. Why is that so? Because generation rate and recombination rate are not depending on x. Although we will consider that it is depending on x, but when the final answer would come, we will know that it is not depending on x. Oh, sorry. Like this whole value will not depend on x, but this carrier density is depending on x. What I am saying is that this carrier density is surely depending on x. This whole answer is not depending on x. Because if carrier density is not depending on x, let's just say this carrier density is a constant value, then what will be the value of this one? 0, no? So carrier density is not a constant value here. Are you able to understand this point? Okay. So this is what we need to find. What we need to find? What we will do is that we will apply our continuity equation. So what will our continuity equation will say? 0 would be equals to minus 1 by q d jpx by dx. what is written? Gradient in the particle current density. Gradient in the particle current density. This is the meaning of a gradient. D by dx, current density. So this is what I need to find. Gradient in the particle current density plus generation rate minus recombination rate. Usually we write down generation rate minus recombination rate. Right? So from here what do you see? Usually we write down as capital G. So here what do we see? Q into generation rate minus recombination rate. What is the value of Q? 1.6 into 10 to the power minus 19. Where is Q? Q is not given. Generation rate minus recombination rate. 10 to the power 20 minus 2 into 10 to the power 19. 10 to the power 20 minus 2 into 10 to the power 19. So 10 into 10 to the power 19 minus 2 into 10 to the power 19. So what you will see? 10 minus 2 will be 8. So 8 into 10 to the power 19 you will be getting. I hope you know how to do this calculation. Right? 10 minus 2, 8 into 10 to the power 19. So this and this is getting cancelled out. 1.6 into 8. 1.6 into 8. So 12.8. Now what will be the unit? Centimeter to the power minus 4. Why is that so? Because current, sorry. What is the unit of current density? That is ampere per centimeter square divided by another centimeter. So unit will be ampere into centimeter cube inverse. Gradient in the particle current density. So current density is ampere per centimeter square divided by another centimeter. So answer would be ampere into centimeter cube inverse. Ampere into centimeter cube inverse. This will be the answer. Very simple. And why centimeter? Because sir, everything is going into centimeter. Right? All good. And you can see here is that this is centimeter cube, and this is per second, and charge unit is coulomb. So from there ampere would come and centimeter cube will remain there as it is. Okay. So very easily you can write down the unit as well. Answer would be 12.8. Although the answer of this particular question, I saw the answer in some on internet somewhere, but that was given wrong. Okay. They forgot to multiply with 1.6. So if you find the answer on internet and anywhere, they gave the answer like this, but that is wrong. Okay. You need to multiply with 1.6 as well. So don't forget this Q as well. Okay. This question also asked in gate examination only. Consider a long rectangular bar of a direct band gap p-type semiconductor. The equilibrium hole density is 10 to the power 17 and intrinsic carrier concentration is 10 to the power 10. So what does that mean? Holes are 10 to the power 17 cube inverse and equilibrium carrier concentration is intrinsic carrier concentration is 10 to the power 10 centimeter cube inverse. What does that mean? The number of electrons would be 10 to the power 3 centimeter cube inverse. Okay. Electron and hole diffusion length are given. That means diffusion length of electron and diffusion length are given. So diffusion length of hole is 1 micrometer and diffusion length of electron is 2 micrometer. Okay. This is given. The left side of the bar at x equals to 0 is uniformly illuminated with laser having photon energy greater than the band gap. That means this energy is greater than the band gap. This is what they are saying. And if this energy is greater than the band gap, what does that mean? Electron hole pair will be generated. Okay, excess electron hole pairs are generated only at x equals to 0 because of the laser. The steady state electron density at x equals to 0 is 10 to the power 14. So at steady state, that means it will vary with the time, but at the steady state you have reached to 10 to the power 14. So excess electron hole pairs, that means delta P is equals to delta N, that is equals to 10 to the power 14. Okay, at x equals to 0. Okay, due to laser illumination. Under these conditions and ignoring electric field, the closest approximation of the steady state electron density at x equals to 2 micrometer is. That means they are asking with respect to the distance. They are asking with respect to the distance. So how it will be decreasing, that you need to tell. So I told you by default we need to take exponential decrease. So whatever the length could be there, I don't know what is the length of the semiconductor, but what they are asking at 2 micrometer. So at 2 micrometer, what will be the excess carrier concentration? They are talking about only excess carrier concentration. No? The closest approximation steady state electron density they are asking. They are asking about the complete electron density at x equals to 2 micrometer. So these many electrons I already have, 10 to the power 3, and excess electrons are also generated. Excess electrons are also generated, which will be a function of x. Why is that so? Because there is no uniform illumination. They are saying that I am doing the illumination only at x equals to 0. So first I am doing the illumination at x equals to 0, and at steady state 10 to the power 14 has reached. But if you go into the semiconductor, as we move into the semiconductor, the intensity will decrease exponentially. So exponentially these electron concentration will decrease, right? So e to the power minus x by Lp, where Lp is the diffusion length. Okay, so this formula specifically I cannot write down, because it may happen that it may decrease exponential, or it may happen linear, or it may happen it could be constant as well, right? But by default here nothing is mentioned, we have to take exponential. And from the options as well you can see that it would be exponential only, 0.37, 0.63. So this is the value of 1 by e. So you can use your brain, right? And here why I am writing down Lp, this would be ln, right? Did you understand how did I write down the formula? Because I know that exponential decrease would be there, no? So 10 to the power 14 e to the power minus x by, now here what I should write down? I should write down something related to length only, that is the diffusion length, 2 micrometer. So from now onwards you can remember the formula if you are not able to understand. 10 to the power 14, that is the concentration at x equals to 0 with respect to the distance, it will reduce exponentially. So 10 to the power 14 e to the power minus x by ln. Okay, because this will be micrometer and this will also be micrometer. So in the e to the power you will get some constant value. This is our target. So length micrometer, and this is also micrometer. Now it is not just related to this particular subject. In the whole electronics question paper, electrical question paper, in instrumentation question paper, whenever you don't know what kind of profile you will get, what I am saying, in any of the question paper, whether it is about EM wave or whatever it is, when you don't know what kind of profile you will get, by default take it exponential. Let's say some wave is coming having an amplitude of P naught. They are asking the amplitude of the wave at 2 micrometer. What you will do? Sir, P naught e to the power minus, at 2 micrometer they are asking. Now in the question I will find something having a unit of meter inverse. Okay, so if I get something having a unit of meter inverse, then I will simply multiply. And if I get something having a unit of a meter, then what I will do? I will divide. Because in e to the power something constant I need to have, no? Like I cannot find the value of e to the power 2 centimeter square. Doesn't make any sense. I can find the value of e to the power 2. I cannot find the value of e to the power 2 centimeter square. So this is known as like absorption coefficient. In most of the examination, what will be written? Absorption coefficient. Absorption coefficient. That will be alpha, and that will have a unit of meter inverse. Here we are using diffusion length. So 1 by ln I am writing. If you see closely, e to the power minus x multiply with 1 by ln. So e to the power x will have a unit of micrometer, 2 micrometer. I need to find at 2 micrometer. What will be the unit of 1 by ln? That would be micrometer inverse. So micrometer will be cancelled out with micrometer inverse, right? Very simple thing. So this I am telling for every single thing. I remember during my instrumentation question paper, there was question from optoelectronics. So I never studied optoelectronics, right, in instrumentation, because it is not in our GATE syllabus. But 2 questions of optoelectronics I was able to solve just by using my intuition. One I solved using aptitude only. That question was based on Doppler effect. So Doppler effect you can understand by simple aptitude. So that I solved using simple amplitude, and one was like what will be the intensity at a particular distance. So there also I know that blindly I should go with exponential. So there also I applied the same thing, exponential, and it went correct. But in EM wave, in power something different happens. I hope you remember. In optical fiber as well, when it comes to power, the different formula come into action. So you can revise your EMFT notes. There I told you to specially focus on optical fiber. In optical fiber, the formula of power is different, right? So there you can revise your notes. You will be able to see that. Yeah. So 10 to the power 14 e to the power minus x by ln. So at what point I need to find? At 2 micrometer I need to find. So electron concentration, excess electron concentration at 2 micrometer, that would be 10 to the power 14 e to the power minus 2 micrometer divided by ln. What is the value of ln? 2 micrometer. So that would be 10 to the power 14 e to the power 2 will get cancelled out, micrometer will get cancelled out, 10 to the power 14 e to the power minus 1, and 10 to the power 14, this 10 to the power 14 was having a unit of centimeter cube inverse. So what will be the answer of delta n you are getting at 2 micrometer? That is 1 by E. 1 by E is 0.37, right? Let's check it again just for our confirmation. Yeah, 0.37. And equilibrium electron concentration is equilibrium electron concentration in p-type semiconductor. In p-type semiconductor, equilibrium electron concentration is 10 to the power 3 centimeter cube inverse. So total electron concentration at 2 micrometer, that would be given as 0.37 into 10 to the power 14 plus 10 to the power 3. So approximately it will be equals to 0.37 into 10 to the power 14 centimeter cube inverse. So this will be the answer. Very simple question, very straightforward. You should be able to solve it. The only thing was this thing, that if the profile is not given, I will take it exponential. So from 10 to the power 14, it will reduce exponentially. Let's go to the next one. A semiconductor has a cross section area of 1 centimeter square, thickness of 0.1 centimeter. That means you can find out the volume. Something will be happening with respect to the volume as well. Determine the number of electron hole pairs that are generated per unit volume per unit time by uniform absorption of 1 watt of light at a wavelength of 6300 angstrom. A very good question. Assume each photon creates 1 electron hole pair. So from 1 photon you get 1 electron hole pair. Second, if excess minority carrier lifetime is 10 microsecond, then what is the steady state excess carrier concentration? All good? All fine? So let's get started. So this was your semiconductor having thickness whatever it is. Let's talk about the dimension later on. But what is happening? Electron hole pair are generated because of the light that we are putting, right? Because of the light. So light is having a power of 1 watt and it is having an energy of hc by lambda, right? It is having an energy of hc by lambda. So what will be its energy? So value of h 6.63 I am putting. Like if I put I can put this value as well because I remember this value. I told you I will remember this value. 1242 electron volt nanometer. 1242 electron volt nanometer divided by lambda. Lambda is 6300 angstrom. Angstrom means 10 to the power minus 10 meter. But I need to convert it into the nanometer. So 10 to the power minus 1 I will take here. So 630 nanometer. So here I will put 630 nanometer. Now what I will be getting? 1242 divided by 630. 1242 divided by 630. So nanometer to nanometer is getting cancelled and I am getting 1.97 electron volt. This is the energy. But what is this power? 1 watt. What is watt? Do you remember this formula? E is equals to PT and power is equals to energy per time. That means in 1 second you are having 1 joule of energy. What they are saying, in 1 second you are having 1 joule of energy. If power is 2 watt, that means in 1 second you are having 2 joule of energy. Per second, how much energy? So the wave that is coming or the light that is coming, that is having in per second it is giving you energy of 1 joule. What I am saying is that light energy per second, that is 1 joule. This is the total energy of light per second. Now what is the energy that we have found out? 1.97 electron volt. So we need to convert it into the joule because calculation we are going to do in the joule. what you can do, either you convert this into electron volt or you convert this electron volt into joule. So we will convert this electron volt into the joule. Okay. So 1 electron volt is equals to how much joule? Did I tell you to remember? No. I told you simple, go by the formula Q into V. So if 1.6 into 10 to the power minus 19 coulomb gets a voltage of 1 volt, then it is equals to 1 electron volt. And coulomb into volt is equals to joule. So 1 electron volt is equals to 1.6 into 10 to the power minus 19. 1 electron volt is equals to 1.6 into 10 to the power minus 19. So you don't need to mug it up. Okay. Just go by the simple formula. So 1.6 into 10 to the power minus 19 joule. So into 1.6. So 3.15. 3.15 joule. Now what is this? 3.15 into 10 to the power minus 19 joule. This is the energy of one photon. This is the energy of one photon. Are you able to understand what I am saying? If they are saying that this is the energy of light, that means this is the energy of a light is having a wavelength of this much. That means it will have this much of energy. So this energy will be of photon. So in EDC, whenever you write down the answer of energy, you will always write down per photon. So one photon is having this much of energy. Now you are having how much energy? 1 joule energy you are having. What I mean to say is that this was my power. This power was giving me, sorry, this was my light. This light was giving me 1 joule of energy per second. In 1 second, it was giving me 1 joule of energy because power was 1 watt. It was having a wavelength of this much. What does that mean? That means per photon in this light, there will be a lot of photon. In this light, there will be this is the whole light. In this whole light, there will be a lot of photon. And the complete light is giving me 1 joule of energy per second. And I know the energy of 1 photon. This is the energy of 1 photon. What I mean to say is that this E is equals to hc by lambda. This is what? This is not the energy of light. This is the energy of photon. Energy of photon. Energy of photon. So this is not the energy of light. This is the energy of photon. Energy of light per second is 1 joule actually. This is energy of 1 photon. What does that mean? That 1 photon is having energy of this much. 1 photon is equals to this much energy. That means in 1 joule, how many photons you will have? That means this much energy is equals to 1 photon. That means 1 joule will be equals to what? 1 joule will be equals to what? So this will go downward. 3.15 into 10 to the power minus 19 photon. Because you know that your light is giving you 1 joule of energy per second. Why I am focusing on 1 joule? Because the light was having a power of 1 watt. That means in 1 second it is giving you 1 joule of energy. Now energy of 1 photon is coming out to be 3.15 into 10 to the power minus 19 joule per photon. That means 1 photon is having this much of energy. So in 1 joule, how many photons would be there? So 1 by 3.15. That means 31.7 into 10 to the power 17. So in 1 joule, let's go to the next page. So what does that mean? That means that this is a good question. You just need to understand it. I will again explain it. Don't worry. So in 1 joule, you are having 31.7 into 10 to the power 17 photon. So what does that mean? That means that your light is throwing this much photon per second. Let's understand it again. Your light was throwing 1 watt power. What does that mean? It was throwing in 1 second, it was throwing 1 joule energy. Till this point, everything is clear. Now I know that the wavelength of the photon is 6300. So what will be the energy of 1 photon? The energy of 1 photon is 3.15 into 10 to the power minus 19 joule. So 1 photon is having this much energy. That means this much energy means 1 photon. But how much total energy you are having? You are having 1 joule of energy. So 1 joule of energy means how much photon? 1 joule of energy means this much of photon. That means your light is having this much of photon per second. That means on this semiconductor, on this semiconductor, this much of photon are coming per second. Everything, every calculation is going per second. So on the semiconductor, 3.17 into 10 to the power 17 photon per second is being incident. On semiconductor, 3.17 into 10 to the power 17 photon are being incident per second, and each photon will make one electron hole pair, one excess electron hole pair, one excess electron hole pair. That means this much photon per second, how much excess electron hole pair they will create. So what they are asking, determine the number of electron hole pair that are generated per unit volume per unit time, right? So because of 3.17 into 10 to the power 17 photon per second, 3.17 into 10 to the power 17 electron hole pair will be generated. So in 1 second we are getting 3.17 into 10 to the power 17 electron hole pair. But what we need to find? We need to find electron hole pair generated per unit volume per unit time. Electron hole pair generated per unit volume per unit time. Per unit time means this is your per unit time only, no? Per second this much electron hole pair are being generated. So that would be equals to per second this much electron hole pair are being generated, but per unit volume you need to find. So what is the volume? Here if I find out the volume, so area is 1 centimeter square and thickness is 0.1 centimeter. So 1 centimeter square into 0.1 centimeter. So what is the answer you will be getting? The answer will be 3.17 into 10 to the power 18 centimeter cube inverse second inverse, and this also will have a unit of second inverse only. Why this is having a unit of second inverse? Because per second these many electrons are being generated. Per second these many electron hole pairs are being generated. Is that understandable to you or not? How this final answer came, is that understandable to you or not? This is the final answer. Again let me explain. What they were asking, how many electron hole pairs are generated per second per unit volume. We were having a particular power of a light, that power was 1 watt. That means in 1 second it was giving you 1 joule of power. What was the energy of one photon? Energy of one photon was 3.15 into 10 to the power minus 19 joule, right? Total energy you were having was 1 joule, and one photon was having this much of energy. That means how much total photon you are having? This much total photons you are having. So on your semiconductor material, these many photons are incident per second. That means each photon will give you one excess electron hole pair. What does that mean? These many photons will give you these many excess electron hole pair per second. So in 1 second, 3.17 into 10 to the power 17 photon per second was generated. This much photons were generated per second. But in the whole semiconductor, in this whole semiconductor, what they are asking? They are asking per unit volume. So I have to divide by volume as well, because they are asking per unit volume. So I have to divide by volume as well. Right? So 3.17 into 10 to the power 18 centimeter cube second inverse. Next, if excess minority carrier lifetime is this much, then steady state excess carrier concentration you need to find. Steady state excess carrier concentration you need to find. Now what is this? Steady state they are talking about, they did not talk about the profile at all, right? So uniform illumination we need to consider, right? Did they talk about the profile? Uniform absorption is there, one light of water. So what I will assume is that I have to make the assumption, because this question is not completely not completely available. So what they are saying is that steady state is there. Okay, steady state is there. What is this actually? This is the generation rate only, no? Are you able to understand this point? This is the generation rate. these many electron hole pairs are being generated per unit volume per unit time. That is known as generation rate only. So this what we have find out. We have find out the generation rate. Now steady state is given, right? Steady state is given. Along with that, doping profile is not given, and electric field also they did not mention. So electric field is 0, and now doping profile also I will consider uniform or linearly varying, because they are throwing the light. Now they did not say that I am throwing the light at x equals to 0. So I will assume that they are throwing the light in the whole semiconductor only. Uniform illumination I will assume. Okay, so I will assume this is uniform only. So from here I can say that my generation rate is equals to recombination rate, and that means this will be equals to excess carrier concentration. What they are asking? Excess minority carrier concentration. Minority majority what is there I don't know, because they don't even tell which kind of semiconductor is there. So anything you can assume. So basically I will write down here minority excess carrier concentration, minority excess concentration divided by the lifetime. Okay, so this is your generation rate, multiply with lifetime, that is 10 microsecond lifetime. What that will be? Minority excess carrier concentration. That would be equals to minority excess concentration. So this will be the answer. You can solve it. Okay, this will be the answer of second one. So basically they just, in the first question they were just asking the generation rate, that how many electron hole pairs are generated per unit volume per unit time. So that we have find out by all this calculation. So this question was also very good. This kind of question till this date in the GATE examination has never been asked. So surely it is coming very soon, that they will give the power, they will give the energy of one photon. So energy of one photon you are having, power you are having, per second power you are having, that means you are having joule, you are having the energy per second. From there you will understand that okay, this is actually the energy per second. So from here I can find out the number of photon, and one photon will create one electron hole pair. So these many electron hole pairs are being generated per second, and if they are asking per unit volume, then I will have to divide by the volume. So per unit volume per second I have find out the electron hole pairs generated. That means I have find out the generation rate. That would be equal to recombination rate. If these conditions are satisfied, then I can find out the minority excess carrier concentration if lifetime is mentioned, and lifetime is also constant here, constant and uniform. Lifetime is constant and uniform. So you will get this particular answer. All good, all fine. Very simple question, very straightforward. Let's go to the next one. This is also GATE PYQ. This was from Niemann. So those who are having black background, they are from Niemann, and those who are having black background, they are from GATE PYQs. So this is also GATE PYQs. You solve it on your own. You try this question, then you try this one, then try this one, then try this. No, okay, this is just then try this one. So 4 questions you try, and then we will solve this particular question. So 4 questions we will solve in this lecture. Okay, very simple question these are. So you can try all these questions on your own, and then we will solve this particular question, which is the best question of whole EDC till this date. In the examination they only asked this statement. They did not ask these questions. But if they had asked these questions, then a lot of forget about the students, because I also gave GATE 2022 examination. No one actually solved it. I have talked to GATE 2021, rank 1, rank 3, rank 4. I have talked to all the people. Then did not even read this question. So forget about the students. Students were never able to solve this question. But even the teachers were not able to solve. Now a lot of teachers would say that I was able to solve, but I was a student at that time. No, I know that. Until the answer key came. Answer key came on 21st of Feb. I exactly remember the date. Until the answer key came, there was no one who gave the solution of this question. And whatever the solution that they have given till this date, this is 2025, this is September 2025, I am recording this video. Till this date, they are giving the solution wrong. And I will prove it, that what is wrong in their solution. That's why I added these 4 options as well. I made this question as MSQ. As per them, this will be the answer. But actual answer will be this one. So we will discuss that. This question will be the best thing you would ever see in EDC. Okay, so we will discuss that. Okay, don't worry. But you try to solve this question 1, 2, this question as well. Here a little concept will be used. I told you one thing, in the examination if you don't know about anything, with the distance always exponential decrease would be there. So if intensity or power here is P naught, then with the distance it will decrease exponentially. This concept will be used and you will be able to solve this question. So 1 question, 2, 3 and 4. You try solving it. I will take break, I will have my dinner and then I will come back. Okay then, yeah, thank you.
Yeah, welcome back guys. So did you try this question? So let's get started. Silicon is uniformly doped. Length is 0.1 micrometer. Donor concentration is given, that is 10 to the power 16 centimeter cube inverse. This is the donor concentration that is given. Okay, and they did not mention about intrinsic carrier concentration. Then what we need to do is that we need to consider this as a number of electron, right? So number of electron will be 10 to the power 16 centimeter cube inverse, and number of holes at thermal equilibrium. This is the number of electrons at thermal equilibrium. Number of holes at thermal equilibrium, nearly we have to take 0, because they did not mention the intrinsic carrier concentration. So we need to assume that Ni is very lesser than Nd, and then I cannot even apply the mass section law. So Ni value I don't know, Nd value is very large, so I would say that number of holes are approximately 0 at thermal equilibrium. But now what we are doing is that we are illuminating some light, and since we have illuminated the light, electron hole pair are generated at this rate. So how the electron hole pairs are being generated? That are being generated as 10 to the power 17, because GL naught value is given as 10 to the power 17, 1 minus x by L. L value will also be mentioned. No, it is not mentioned. Yeah, L value is 0.1 micrometer, that is mentioned. So this is how electron hole pair are being generated per centimeter cube, per unit volume, per unit time. Diffusion coefficient is given for holes, that is 100 centimeter square per second. Low level injection you need to consider. Linearly decaying steady state excess hole concentration. Linearly decaying steady state excess hole concentration. What does that mean? That means delta Px is linear, right? Whole lifetime is also given. Whole lifetime that is given, that is constant. Whole lifetime is given and it is uniform and constant. So what you understand now? Now I can apply the formula of recombination, right? So this condition is given, right? Steady state is also given. Somewhere it would have been mentioned that they are talking about steady state. Yeah, steady state is also given. Delta Px is also linear. Steady state is also there. What does that mean? That means that your generation rate would be equals to recombination rate, and that would be equals to delta Px by tau p. So whatever that we wanted, everything is given. What all thing we wanted? Tau p should be uniform and constant. Steady state should be there, and delta Px should be linear. All these 3 things we want. If these things are there, that means your question is very straightforward. And in 99% of the cases are there that these things would be surely there. Okay. So generation rate is equal to recombination rate. Generation rate is given. What is my target? My target is to find, let's see what we need to find. We need to find the magnitude of a diffusion current density at x equals to L by 2. So I need to find diffusion current density. So diffusion current density could be there because of the electrons as well, because of the holes as well. Because what I know is that in the semiconductor, if I am emitting the light, in the semiconductor, if I am emitting the light, then excess carrier which are generated, let's just say excess holes are generated, then excess electron will also be generated, no? Right? So if I make the graph with respect to x, what I am doing, I am making the graph with respect to x. So if I talk about electrons, so at the thermal equilibrium, number of electrons in n-type semiconductor at thermal equilibrium was equals to 10 to the power 16 centimeter cube inverse, and number of holes in n-type semiconductor, at thermal equilibrium was 0, right? Now excess electron will also be generated and excess holes will also be generated. How much they will be generated? Let's find out. So GL is given, not GL, sorry, generation rate is given, that would be equals to recombination rate, and that would be equals to delta Px by tau p, right? So what do you find out from here? This value is equals to 10 to the power 17, 1 minus x by L. 10 to the power 17,
1 minus x by L. Everything is going in centimeter cube, that we will remember. Tau p value is 10 to the power minus 4. Tau p value is 10 to the power minus 4. So what we will get, delta px as 10 to the power minus 4, so that would be 10 to the power 13. 10 to the power 13 into 1 minus x by L. This is the expression of delta px. Now you know that whatever delta px is there, the same delta nx would also be there. At x equals to 0, how much you are having? 10 to the power 13. So at x equals to 0, 10 to the power 13 holes are generated, then 10 to the power 13 electron will also be generated. And with respect to the distance, what I mean to say is that here 10 to the power 13 electrons are generated, and here 10 to the power 13 holes are also generated, and with respect to the distance, it is linearly decaying. With respect to the distance, this will also linearly decay, and this will also linearly decay. That means here there is more concentration, here there is more concentration, and here there is lesser concentration. So electrons will diffuse here. That means because of the electrons, this will be the diffusion current, and holes will also diffuse here. Because of the holes, this will be the diffusion current, right? Because of the illumination, the illumination is not uniform, it is linearly decaying. So here the concentration of electrons has increased, here the concentration of electron and holes has increased, while here the concentration of electron and holes are less. Because of that, electron and holes will diffuse and current would come into action. So diffusion current will be there because of the holes as well, and diffusion current will be there because of the electrons as well. So if you want to find out the diffusion current, what all thing you would need? Q you would need, dn you would need, and dnx by dx you would need, right? This is the current because of the electrons, and because of the holes the current is in the negative direction. So here I will put the negative sign. So if I have the delta px value, then I can differentiate it. I have the delta px value, I have the delta nx value as well. So this value I can get, this value also I can get, q value I already know, and dp value is given. In this question, they did not even give the dn value. So here actually they are asking that diffusion current because of the holes only. What I am saying, they are asking the diffusion current because of the holes, and they forgot to mention it. And this is the same language that came in the GATE examination. I don't remember the year, but this was the same language written. Whenever people solve the question, they will just take the minority carrier concentration and find out the answer. But the doubt may be arising to a student that, sir, the number of electrons that are generated, the same number of holes that are generated, the same number of electrons are also generated. No, so they will also diffuse. That means the current will be flowing in the opposite direction, so the current will be less. Like this is the hole current, and this is the electron current. They are flowing in the opposite direction, so current will be subtracted. So ideally, I should take into the action this diffusion current as well. But in the examination, they forgot to mention it, that they are talking about only the minority carrier diffusion current. That means they are talking about the current because of the holes. So there it should have been written the magnitude of the diffusion current because of the holes. So this was the error in this question that I am telling. In the examination, if they had mentioned the value of dn, then the question would become very interesting. Because what is our habit? Whenever we solve the problem related to continuity equation or related to semiconductor under non-equilibrium, what we do is that blindly we only focus on minority carrier concentration. But just think about it. If the current is coming, then it will come because of the electrons as well and because of the holes as well. And both will be in the opposite direction. So one will try to cancel out each other. Basically, they will be subtracted from each other. Are you able to understand what I am saying? Right? So there is an error in this question. They did not mention the value of dn. That's why we will only take that diffusion current because of the holes. If I was there in the examination hall, I would have only calculated the diffusion current because of the holes. Why so? Because I know that there is some error. Because if they wanted to talk about the current because of the electrons as well, they would have given the value of dn. So this is the thing that I wanted to tell. That's why I made this diagram. So what I will write down here, dn value not given. So what I am saying, ignore jn
ignore. So what I will take care into action now, I will only care about GPX, and that would be equals to Q dp dy dx delta nx, not delta nx, sorry, not delta nx, here I should have written delta px. Q dp by x, dp by dx. What is p? P is equals to, here I should write down px. What is p? Px is equals to number of holes in n-type semiconductor at thermal equilibrium plus number of excess holes with respect to distance x. So this delta px plus at thermal equilibrium, how many holes were there? At thermal equilibrium, how many holes were there? 0 holes were there. And let's just say this value was non-zero. Let's just say this value was non-zero. But will this value contribute in diffusion current? What I am asking, is there any importance of this value for the diffusion current? If I find out dpx by dx, then I know that this value will be constant. This will not be a function of x, because this is there in the whole semiconductor. So this will be always there. Only this will be varying with respect to the distance. So what I will get? At all the places I have seen that directly this formula will be written and question is solved. But there is something wrong in this question that we understood, right? Although finding the answer was not difficult, but there was something wrong that we have understood. Now everything we can do. Although here there will be negative sign as well, but you don't need to care about negative sign. Why so? Because they are only asking about magnitude. They are not talking about the direction. Okay, so when you solve it, what you will get? Q value I already know, 1.6 into 10 to the power minus 19. dp value they have given, that is 100. Everything is going in centimeter. 100. When you differentiate this with respect to x, what you will get? 10 to the power 13 divided by 1 by L. So minus sign is there, minus sign will be there. So 10 to the power 13 divided by L. What is the value of L? 0.1 micrometer. 0.1 micrometer. What is the value of L? 0.1 micrometer. Now just tell me what I should write down here. Think about it, what I should write down. 0.1 micrometer directly I should write down and calculate this final answer. Is that my final answer? Basically I am differentiating it. After differentiating, what I am getting is that 10 to the power 13 divided by L and then negative sign. Value of L is 0.1 micrometers, so that I am putting here 0.1 micrometer. Or let's put L only. So here I am putting the value of L. This negative sign and this negative sign has cancelled out each other, so positive sign is coming. Now in place of this L, what I should put? 0.1 into 10 to the power minus 4 centimeter. Say yes or no, because all the calculation is going in the centimeter, no? Are you able to understand this point or not? So this is a very, very important point. People would mess up here. 0.1 into 10 to the power minus 6 they will write down. But everything is going into centimeter. So whenever the distance is coming, I need to make sure that everything should be in centimeter. So 0.1 into 10 to the power minus 4. So what I am getting? This is 10 to the power 15. 15, this is 10 to the power minus 5. 15, 5, 20. This is 10. So 16. 16 ampere per centimeter square. Because what is the unit of current density? That is ampere per area, and area is going in centimeter. So ampere per centimeter square. There you go. This is the final answer. But this was also an important discussion that we did not consider anything about the electrons. This was the reason. The dn value was not given. So I kind of ignored it. But the same slope that you are getting here, this value would have been same. This value would have been same. But they are saying that dn value, forget about it. Okay, well and good. So they actually mean to ask because of the holes only. Okay, so this question is solved. Let's go to the next one. Yeah, sorry for the interruption guys. So let's solve this question. Silicon is there at 300 Kelvin, uniformly doped with the acceptor atom. Okay, so this is the equilibrium condition that silicon is there at 300 Kelvin, acceptor atom is uniformly doped, and they are not mentioning intrinsic carrier concentration. That means number of holes will be approximately equals to number of acceptor atom that are equals to 10 to the power 16 centimeter cube inverse. This is the number of holes in n-type semiconductor at thermal equilibrium, and number of electrons, sorry, this is your p-type semiconductor only, no? And number of electrons in p-type semiconductor at thermal equilibrium will be nearly 0. Why so? Because Ni is not mentioned. This is the scenario, right?
Now at t equals to 0, you are throwing the light, and you are throwing the light uniformly. You are throwing the light uniformly. So first thing that we required, that your delta px or delta nx, whatever it is, both will be equal only. Why both will be equal? Because electron and holes will be generated in pairs, and that will be uniform. So first thing I require, that is good, uniform they are. So from here I know that dgx by dx would be equal to 0. Secondly, I can see that carrier lifetime is given, that is 5 into 10 to the power minus 7 second, and generation rate is also given, but they are not saying that it is done at the steady state. So generation rate is equal to recombination rate, nothing can we can do, right? What do you need to find? You need to find conductivity. Conductivity as a function of time. So what is your conductivity? What is the general formula that we have studied? General formula n q mu n plus p q mu p. Now this cannot be a function of time, this cannot be a function of time, this cannot be a function of time, and this cannot be a function of time, because these values are already mentioned, mu n, mu p already mentioned. Who can be a function of time? This can be a function of time, and this can be a function of time. And why they are the function of time? Because light is being injected. Because of the light, they are the function of time, right? So what will be your sigma t now? Sigma t would be equals to n plus delta nt, because you know that since the light is illuminated at the semiconductor, we will generate electron hole pairs. So whatever the holes are generated, the same number of electrons will be generated. What most of the student would do in this question is that they will forget this one. They will again focus on the minority carrier concentration. They will only take into action delta p. Who is the minority here? Okay, it is p type semiconductor. So they will only take into action delta n. They will forget about delta p, because it is our habit that whenever we see semiconductor under non-equilibrium, we forget about the majority carrier concentration. So here majority is p. So they will forget about delta p. What people would do, those who have already solved, they would have forgot about this delta p here. I am pretty sure. So this would be your final answer. Now you know that this n is equals to 0. Number of electrons. What is the total number of electrons? Total number of electrons are number of electrons at thermal equilibrium plus the excess electrons, which is a function of time. You know that it will be a function of time. Why it will be a function of time? Because the number of electron or hole pair that we need to generate, they will not be generated instantaneously. They will take some time to reach to its steady state value. So they will be a function of time, and this will also be a function of time. But I know that this is equals to 0, and this value I already know. So now what will be my answer? Delta nt q mu n plus delta pt q mu p plus pp naught, which I already know, q mu p. This is your delta t. Now just let me know one thing. At t equals to 0, what will be the scenario? Will this be there? This would be equals to 0 at t equals to 0. At t equals to 0, delta nt and delta pt would be equals to 0 only. Why so? Because light is illuminated at t equals to 0. So that means there are no excess carriers at t equals to 0. After t equals to 0, the things will start happening. But at t equals to 0, there are no carriers. So if I need to find the conductivity at t equals to 0, at t equals to 0, there are no excess carriers. So delta n at 0 and delta p at 0 would be equals to 0 only. And one thing also I am pretty sure, one thing you know that excess carrier, whichever the excess carriers that are generated as holes, the same number of electron will also be there. So you can say that so delta nt would be equals to delta pt as well, because electron and holes will be generated in pairs only, right? So conductivity at t equals to 0 will be just this pp naught q mu p, or you can directly say pp naught is equals to na. So na into q into mu p. What is the value of na? Value of na is 10 to the power 16 into 1.6 into 10 to the power minus 19. And what is the value of mu p? That is 380. So you will put it and you will get the value of this thing. Conductivity, Siemens per centimeter. Everything is going in centimeter only. So this answer you will get conductivity at t equals to 0. Now you need to find the conductivity as a function of time t. I will find out as a function of time t, then I will put t equals to infinity.
For that, what I need to use the formula of generation rate. This is given, which is 8 into 10 to the power 20 centimeter cube second inverse. From here I know that my this term is gone, and although this here I will apply it in minority carriers, so minority carriers are electron here, so this term is gone. But what about dn by dt? What I mean to say is that if I apply, is there anywhere steady state mentioned? What I am saying, steady state is mentioned or not? Steady state is not mentioned. So what you will say, sir, I will have to apply this particular thing, that would be equals to generation rate minus recombination rate. Now in your answer, what you require? Delta NT you require, delta PT you require. What you require? Delta NT. What delta NT would be equals to? You know that rise will be exponential. So delta NT would be equals to whatever the excess carriers that you are going to generate at a steady state. What is delta N? Delta N is excess electrons at steady state. You know that this is where I will be reaching. This is where I will be reaching using the exponential form. So actually what you require? You require excess electron concentration at steady state. Are you able to understand what I am saying? Sir, I thought of applying continuity equation. Then I saw that I have the generation rate, but I don't have the recombination rate. I am stuck here. Then I thought, what I require, sir? I require conductivity, sir. Now in the conductivity, sir, number of electrons and number of holes I will be requiring. In number of electrons and in number of holes, there will be excess carrier generated. So that is my matter of concern, sir. I need to find excess carrier generated as a function of time t. I know that they will be rising as a function of time t. But if I know the steady state value, that means these many electron hole pair will be generated, sir. If I know that particular value, then sir, my job will be done. So yes or no? Are you able to understand what I am saying? And that means you will apply this equation, but you are applying the equation at steady state only. I am applying the continuity equation, although dn by dt is not always equals to 0, but at the steady state it will be equals to 0, no? So what I will say is that at steady state generation rate is equals to recombination rate. So generation rate is equals to recombination rate, that would be equals to the excess carrier concentration, which is delta n divided by tau n. It would be a function of x, but it is not a function of x. Why is that so? Because it is constant, uniformly distributed. So it is not a function of x, it is constant. So from here I can find the value of delta n. What will be the value of delta n? That would be simply generation rate into tau n. So 8 into 10 to the power 20 into 5 into 10 to the power minus 7. So 8 into 10 to the power 20 into 5 into 10 to the power minus 7. 40 into 10 to the power 13 centimeter cube inverse. So this is the value of delta n you are having. So now you can find out the value of delta nt as well. So your delta nt would be equals to 4 into 10 to the power 14 1 minus e to the power minus t by tau. What is the value of tau? Tau is 0.5 micro, right? 0.5 micro. 0.5 micro. So this is the value of delta nt, which would be equals to value of delta pt as well, right? So if I add a page, now I have find out the value of delta nt and delta pt. So your sigma t is equals to, sir, one value will be this value I already know, 0.608 plus delta nt q mu n plus delta pt q mu p. Now I know that 0.608 plus, sir, I know delta nt will be equals to delta pt. So the value will be 4 into 10 to the power 14, and everything is going in centimeter cube, right? Everything is going in centimeter. So 4 into 10 to the power 14, 4 into 10 to the power 14, 4 into 10 to the power 14 into 1 minus e to the power minus t by 0.5 micro. Sir, this I have taken common. Q also I can take common. Q also I can take common, which will be 1.6 into 10 power minus 19. And sir, in the bracket, mu n plus mu p will come. So, what is the value of mu n plus mu p? Mu n plus mu p. That is 1280. Are you able to understand what I am doing here? Say yes or no. So, what you will see, 0.608 plus 4 into 10 to the power 14, 1280. So, that would be 1.28, 10 to the power 3, 10 to the power 17, 10 to the power minus 2. So, what I will do is that 4 into 1.6, 4 into 1.6 into 1.28, 4 into 1.6 into 1.28, 4 into 1.6 into 1.28, 10 to the power 3, 10 to the power 17, 10 to the power minus 2. 0.081. Yeah, okay. So what we are getting, 0.081. This much we are getting, right? Okay. So if you solve these things, this is what you are getting, 0.081 into 1 minus e to the power minus t by 0.5 micro. This is your delta NT. Now they could have asked at any value. When you solved it, what error did you do? You forgot to take, sir, this thing into action. Sorry, this was the minority, so you forgot to take this thing into action. You know that, sir, because of the thermal equilibrium, something would come. Then you forgot about the excess majority charge carriers as well. Excess majority charge carriers. That means you forgot about the excess holes as well. These many holes were already there, but excess holes will also come into action. So those you forgot about, and then you messed up the question, right? And secondly, what is the second thing? Here also you thought that, sir, I cannot apply generation rate equals to recombination rate, which is correct. But what I require the concentration at steady state only. That's why I can apply the generation rate equals to recombination rate formula. Everything is correct. Everything is absolutely fine, right? So if I need to find at infinity, what I will do, I will put t equals to infinity. That means it is simply the steady state. At steady state means electron hole pair are being generated. So because of the excess carriers, this much things is coming into action. Because of the excess carriers, this much conductivity is increasing. So 0.608 plus 0.081. So 0.689, which was pretty simple. I should not have solved it. 0.689 Siemens per centimeter. So this is the answer that we are getting. All good? All fine? So this question is also solved. Only the good question I am picking up. You would go to the gate PYQs, you will see that, sir, they are nothing. We are able to solve the gate PYQs, sir, in one go. These are not there in the gate PYQs, okay? These are pretty good questions. I am picking only the selected ones. Those are pretty good. Now this is a gate PYQ, you will be very easily able to solve. The band gap for gallium arsenide is 1.42 electron volt. And intrinsic carrier concentration is also given. In order to generate electron hole pair, what kind of wavelength should be there? You know that the applied energy should be greater than the band gap energy. That means Hc by lambda should be greater than the band gap energy, which is equal to 1.42 electron volt. What is the value of Hc? 1242 electron volt nanometer divided by lambda. That should be greater than 1.42 electron volt. So electron volt to electron volt is getting cancelled out. So lambda should be less than 1242 nanometer. This is coming here 1.42. So from here, what do you see? Lambda should be lesser than 1242 divided by 1.42. Answer is coming in nanometer. So this is the answer we are getting, 874.64 nanometer. But I need to convert it into the micrometer. So answer will be 0.87 micrometer. So lambda should be less than 0.87 micrometer. So as per you, this should be the answer, 0.87 micrometer. Now sir, this lower limit is also given. Sir, this lower limit is also given, no? Lower limit of lambda means
higher limit of energy, what I am saying, lower limit, what is the energy? This is the energy that we are giving. Lower limit of lambda means higher limit of energy. That means they have given the higher limit of the energy. What is the lower limit of the energy? That at least you need to give 1.42 electron volt, then only electron hole pair will be generated. But you cannot give very high energy. What will happen? The electrons will gain very high energy. Since they are having very high energy, they will move very fastly and they will collide with the atoms, and because they will be colliding with the atoms, the heat will be generated, and that heat will be burning out your device. Okay. Or what may happen is that you have given so much of high energy that you are able to cross the work function. What is work function? You might have studied in your class 12th. If you haven't studied, don't worry about that. Work function will come into action in EDC as well. So you have given so much of high energy that electron will try to escape from the material. So this can also happen, but that is very impractical. What will happen is this, that I have written. If the wavelength is very small, that means photons are having very high energy, then electron will get excited with extra energy higher than the band gap. This extra energy will not help in creating more carriers. What it will do? Electrons will quickly lose it as a heat to the lattice. This process is called thermalization, where carriers will give up the excess energy to the vibrations of the crystal. Okay, and hence photons below a certain wavelength should be photons below a certain wavelength are not practically useful, which defines the lower limit of the range. So this limit is practically defined, you cannot calculate it. Are you able to understand this point? That means wavelength should be lesser than this and wavelength should be greater than some other thing as well. That wavelength should be greater than some other thing as well. What is, how much it should be greater, that is practically defined. But you can see that they have framed the option smartly, that all the options are different here. Okay, so lower limit you cannot define, but a higher limit you can define. Similarly, for the energy you can define the lower limit, but you cannot define the higher limit. That means you cannot give very high energy to any electron, and if you give very high energy, then your device may be burning out. Well and good. Let's solve this question. This is also a good question. A germanium sample of dimension 1 cross 1 centimeter square is illuminated with 20 milliwatt and 600 nanometer laser light as shown in the figure. What do you understand? 20 milliwatt is the power. That means you are giving 20 millijoule energy per second, and 60 nanometer is the wavelength of a photon. That means you can find out the energy of one photon, right? The illuminated sample surface has a 100 nanometer lossless silicon dioxide layer that reflects 1/4 of the incident light. What do you mean by that? That means if I intensity of light is coming, then 1/4 will be reflected back. That means I by 4 will be reflected back and 3I by 4 will be getting in. 3I by 4 will be getting in. So this is your silicon dioxide, SiO2, and this is my germanium. So let me make it a bit more bigger. This is the scenario here. So I intensity of light was coming, I by 4 was reflected. This much we have studied. Okay. From the remaining light, 1/3 of the power is reflected from the silicon dioxide and germanium interface. So this is your SiO2 and this is your germanium, and this is your SiO2 germanium interface. This is your SiO2 germanium interface. So I by 4 was reflected. So 3I by 4 came into here. Now out of this 3I by 4, 1/3 of this is from the remaining light, 1/3 of this power. Okay, they are talking about power, so they are not talking in intensity. Intensity and power both are the same thing actually. Okay, intensity and power both are the same thing. From the remaining light, 1/3 of the power reflected from the silicon dioxide interface. That means from here, 1/3 of this. What will be the 1/3 of this thing? That would be half. Sorry, P by 4. 1/3 of this will be P by 4. So from 3P by 4, P by 4 is reflected from here. Then how much is going here? P by 2. So inside the germanium, how much is going? P by 2. 1/3 and okay, 1/3 of the power is reflected from the silicon oxide germanium interface, 1/3 is absorbed in the silicon layer and 1/3 is transmitted through the other side. So now here P by 2 is coming. Okay, here P by 2 is coming. Now this total power was 3P by 4. 1/3 of this, what will be the 1/3 part? P by 4, P by 4 and P by 4. So these are the 1/3 parts. So 1/3 part is reflected back, this P by 4 is gone, and 1/3 part here will be eaten up. 1/3 part of 3P by 4, that would be P by 4. So this will be eaten up by the germanium, or you can say that what they have said, 1/3 is absorbed in the germanium and 1/3 is transmitted, and here P by 4 is transmitted. Is the diagram clear to you or not? P came, P by 4 gone, then 3P by 4 was there. Now 3P by 4 is having 3 parts, P by 4, P by 4, P by 4. So P by 4 was gone from here, P by 4 was eaten up, and the remaining P by 4 is getting out. Okay, absorption coefficient, what they are saying, 1/3 is transmitted through the other side. If the absorption coefficient of germanium at 600 nanometer is 3 into 10 power 4 centimeter inverse and band gap is 0.66, then the thickness of germanium layer up to 3 decimal places. Okay, so here how much light came into action? P by 2. In the germanium layer, what we are talking about, we need to find out the thickness of germanium layer. So P by 2 light came into action. When it covered the distance of T, the intensity became P by 4. Started with P by 2, by covering the distance of T, P by 4 was the final output. That means what I am saying is that if in the germanium, if there is power P, not P, I will say P dash, and if I cover the distance of T, then eventually I will be getting out with P dash by 2. This is the scenario. Or you can see here is that you started with P by 2, when you got out, you had P by 4. So I started with P by 2, it will exponentially decrease. Now some coefficient is given. What is that coefficient? Absorption coefficient is given. So that absorption coefficient is having a unit of centimeter inverse. What it is having? It is having a unit of centimeter inverse. So what I will write down here? E to the power minus alpha x. So this is your, I would say, power with respect to distance x. So if I have covered a distance of t, my power has become P by 4. So this was actually P by 2 and this was actually P by 4. So if I cover the distance of t, my power has become P by 4. So initially it was P by 2, I covered a distance of t, it has become P by 4. So what you will see here is that P and P will get cancelled out, it will become ln2 divided by alpha. That would be equals to t, because alpha is having a unit of centimeter inverse. When it goes upward, it will become centimeter. So this is the answer, ln2 divided by, what is the value of alpha? 3 into 10 to the power 4. 3 into 10 to the power 4. Centimeter inverse, right? Centimeter inverse. So if I solve it, what do I get? 0.231, but in micrometer you need to tell. So 23.10. Yeah, this is the answer. ln2 divided by 3 into 10 to the power 4 was there. So answer was coming. This was the answer in centimeter. So ln2 divided by 3 I did. So what answer I was getting? 0.231. So 0.231 into 10 to the power minus 4. I need to make 10 to the power minus 3. So if I am multiplying with 10 to the power minus 2, so here I need to multiply with 10 to the power 2 as well. So what you are getting? 23.1 micrometer. Okay, 23.10 micrometer. So this is the answer. Well and good. Although in the examination what they are saying, rounded off to 3 decimal places. What does that mean? I should write down 23.104. In the examination, the answer should have been written as, this is how you should write down the answer, 23.104 micrometer. This answer should be written. There you go, that's it. Okay. Now this is the question that is left. So that we will solve in a separate video. Okay, I will make a separate video for this particular question. So this lecture is completed. I hope you enjoyed it. it might seem tough at a, like I don't think when you have completed the lecture it will feel like tough topic. It will be very easy topic for you. Although it is not completed, the beauty lies in this particular question as well. So I will make a separate video for this particular question because I will be uploading on YouTube as well. So this solution will go on YouTube as well because need to give the solution, right? We need to give the solution so to some people. Those people should know that what is known as quality actually. Okay. So we will do that. I hope the concept is clear. You can try this question on your own. You can try this one on your own. Let's see if you are able to solve. Will be very tough to solve. Will be very tough to solve. Like GATE AIR1 in 2022 examination, he was not able to solve it. So you try solving it, and let's meet in the next lecture. Okay. So in the next lecture, I will solve this particular question only. Okay then. And after that, we will start our Fermi-Dirac distribution. Yeah. Thank you very much. Hi everyone. Welcome to PrepFusion. So this question was asked in your GATE 2022 examination, which is based on basic semiconductor physics in the topic of semiconductor under non-equilibrium, or you can call it continuity equation. Okay. In the examination, they asked only this question: the magnitude of current density because of the excess electrons at x equals to plus minus 2 ln. So answer was 0.59 milliampere per centimeter square, but I made it a MSQ. Okay. I made MSQ. So here there is a very high chance of doing the error. So wherever I have seen the solution is absolutely wrong, and I will prove it here. That's why I made this question as MSQ. The solution is wrong, but answer is correct. Somehow the answer got matched because they got lucky. That's the bottom line. So let's see. First, we will see the wrong solution. Then we will see what is wrong in that, and then we will make the correct solution. Okay. So let's get started. So what is given? P-type semiconductor is there, and this is the photo generation rate is given. That means this is your generation rate. This is the generation rate they have given, and this is the recombination rate that they have given. So generation rate and recombination rate are given. And what all other things are given? Excess minority carrier concentration is 0 at x equals to plus minus 2 ln. What does that mean? What will be minority carrier concentration? That will be electrons. So excess minority carrier concentration at x equals to plus minus 2 ln is equals to 0. Okay. Conditions are mentioned. Steady state is mentioned in this question. Somewhere steady state was mentioned for sure. Right. Low level. Steady state is mentioned. Okay. Steady state is mentioned. So all the analysis we are doing at the steady state. That means the number of excess carriers are not changing with respect to the time. They have reached to their maximum value. Diffusion length is given, that is 10 to the power minus 4 centimeter. And charge is given, that we already know. And the profile of a photo generation rate and recombination rate is also given. Okay. So now what people did, like we can do the analysis between 0 to ln and ln to 2 ln, because between 0 to ln the recombination rate is same and generation rate is same. Then between ln to 2 ln, ln to 2 ln, this is different recombination, this is different recombination rate, and this is different generation rate. So we will do the analysis between two regions. So let's get started. First, I will write down what we need to find. They are asking the magnitude of current density. Here electric field is also 0, right? Under 0 electric field. So there will be, if electric field is 0, what does that mean? That means there will be no drift current. So drift current is 0, what does that mean? Only diffusion current will be there in the action. So only diffusion current I need to find. So what will be my diffusion current? Diffusion current, because of the minority carrier concentration, which will be holes. That would be equals to Q dn dnx by dx. And because of excess carrier concentration I need to find. So here what I will write down? Delta nx. Because my excess carrier concentration I am assuming as delta nx. Okay. My excess carrier concentration, excess electrons which are generated because of the light, which are generated because of the illumination. So my excess electrons are delta nx, which I am assuming. Now between 0 to 2 ln, what do you see? What people did? So here I am doing, this is what I need to find. I need to find it at plus minus 2 ln. So Q into dn at x equals to 2 ln. Okay, the profile is symmetric. So whatever you get at 2 ln, that same thing you will get at minus 2 ln as well. Profile is symmetric, no? Like whatever the generation and recombination is there from 0 to 2 ln, the same is there between 0 to minus 2 ln. So I will just find at 2 ln, and then my job will be done. So what people did, like if I just take the region between 0 to ln. So if I take the value of x between 0 to ln, so what I can see, the recombination rate is given as 10 to the power 20 e to the power minus x by ln, because I am taking the positive value of x. So 10 to the power 20 e to the power x by ln. So this I am doing the wrong solution. Okay, wrong solution. Just keep your eye here. So for recombination rate, we have studied a formula: minority excess carrier concentration divided by the lifetime. So minority excess carrier concentration is delta nx divided by the lifetime, that is 2n. So from here, delta nx you find out, that is 10 to the power 20 2n e to the power minus x by ln. So what I need to find, let's see this option. What they are asking, excess minority carrier concentration at x equals to 0. That means delta nx I have find out, that is 10 to the power 20 e to the power 2n e to the power x by ln. So if I need to find it out at 0, what I will do, I will put 0 here. So e to the power 0 will be 1. So 10 to the power 20 2n. What is tau? We know that there is a relation, diffusion length is dn 2n. So your ln square will be equals to dn 2n. So your 2n would be ln square by dn. So here you can put that. So you would say that, sir, delta n 0 at x equals to 0, basically this value delta n naught is coming out to be 10 to the power 20 ln square by dn. 10 to the power 20 ln square by dn. You will click on this, and that is absolutely wrong. Wrong. Where we went wrong? Why it is wrong? Here you went wrong. R equals to delta nx by 2n. What did I tell you? When this formula is applicable. In the lecture I told you when this formula is applicable. This formula is applicable only when 2n is uniform. It should not be a function of space. Did they mention anywhere about 2n? Did they mention anywhere about the lifetime? Did they say that lifetime is uniform? That means it is not a function of x. Lifetime could be a function of x, no? Nowhere it is mentioned that lifetime is not a function of x. It could be a function of x. So how can you apply this formula? This formula is applicable only when 2n value is not a function of x. It is uniform and constant. Till this date in the GATE examination, apart from this question, in every single question 2n value is mentioned. Some 10 to the power 4, 10 to the power minus 4 microsecond, 10 to the power 3 microsecond, whatever it is mentioned, some uniform value was mentioned. Some value in the second without the function of x was mentioned. Then r was given, 2n was given, so you would multiply and then you would find out delta nx. But here they did not even discuss about 2n. So you cannot say that lifetime is uniform. You don't even know. So can you apply this equation? No, you cannot apply this equation. And there you go, here they went wrong. And that's why this answer is also coming wrong. What I usually have seen is that people would do 0 to ln, then they will do this analysis, and between ln to 2ln they will apply continuity equation. What I will ask between ln to 2ln, what I am saying, between ln to 2ln, why don't you apply this formula? Between ln to 2ln, if I apply this formula, what will happen? Between ln to 2ln, if my x is between ln to 2ln, what I am saying, I will apply this particular formula. Recombination rate is equals to excess minority carrier concentration divided by 2n. What is the recombination rate between ln to 2ln? That is 0. Recombination rate between ln to 2ln is 0. What does that mean? That means delta nx should be 0. What does that mean? That first, sir, you are getting the exponential profile. First you are getting, from here if I find out this delta nx, which is absolutely wrong, but if I assume that this is correct, so first, sir, you are getting exponential profile. That means first, sir, your nx is reducing like this, just as you reach at ln, after that delta nx is becoming 0. So between ln to 2ln, delta nx should be equals to 0. Now what is the slope here? What is the slope of excess carrier concentration at 2ln? What is the slope? Slope is 0. So here you will put 0. So your answer should be equal to 0. Right? But what they have done, just to match the answer, that between 0 to 2ln, you are applying this formula, recombination rate. But between ln to 2ln, they are applying continuity equation. Luckily, what happened there was, this 2n will be cancelled out. In the final expression, this 2n will be cancelled out. The whole error is because of this 2n. So it will be luckily cancelled out and you got the answer. But the reality is neither here nor here you can apply this formula. You have to go by continuity equation. So this I told you every time, that every time you need to notice the lifetime. If your lifetime is not constant, if your lifetime is not uniform, that means if it is not a function, of x, then only you can apply this formula. But if it is a function of x, or you don't know, or you cannot comment, then you have to go to continuity equation. So now we need to solve the continuity equation, and then we will get to know that actually our carrier concentration at n equals to 0 is coming out to be whatever the answer you got previously divided by 2. So if you had solved by this particular analysis, then luckily you would have got the correct answer, but there would be a lot of doubt that sir, why you did not apply this here, why I cannot apply r equals to 0 and this formula here, because here as well, in this region as well, I don't know what is my tau n, what is my lifetime. So from ln to 2ln as well, I cannot comment about the lifetime. So again, I cannot apply this formula, right? So if you are applying this formula, that means you are doing it wrong. Luckily you got the correct answer. Let's do the correct solution, and the mathematics of the correct solution is very interesting. Okay, very interesting. The mathematics will be interesting between 0 to ln. After that it will become very easy. Okay, if I had solved using this formula, no, the way they have solved, so I would use 0 mathematics. Using 0 mathematics also I can find out this answer, but that would be wrong. Between ln to 2ln, do you really think that I need to apply any continuity equation? Between ln to 2ln, what is happening? Recombination rate is 0, generation rate is 0, and already this thing is 0. Why so? Because steady state is given. If steady state is given, then this thing is already 0, no? So what is left? Only this thing is left, right? So what that would be equals to? That would also be equals to 0, because what is your continuity equation? Your continuity equation is dn by dt 1 by q dj by dx plus generation rate minus recombination rate. So this is gone, this is gone, this is gone. So dj by dx is equals to 0. When it is possible? When nx is linear. If your nx is linear, then differentiation of it would be constant, and differentiation of constant would be 0. What I mean to say is that if your d by dx jx is equals to 0, what does that mean? That your jx is constant? Say yes or no. If jx is constant, what does that mean? That means your diffusion current is constant. And when diffusion current could be constant? What is the formula of diffusion current? Q into dn d by dx delta nx. This you need constant, this is already constant, you need this to be constant. And when d by dx delta nx could be constant? When nx is linear. So nx has to be linear. So what I could have done is that, sir, this graph is there which is exponential, and after that, sir, decay would be linear. So if I just find out the value of carrier concentration at ln, then my job will be done, because I know that at 2ln the concentration is actually becoming 0. If I find out the value of concentration at ln, then after that my job will be done. No, because at 2ln the concentration is becoming 0. That means I would know the slope. If I know this particular value, let's just say this value is alpha. So can I tell the slope of this line? Yes. What that would be? Alpha divided by, what is this length? Ln, and this length is 2ln. So alpha divided by ln, and minus sign, because this is the negative slope. So I have already known the slope. So if I know the slope, I will put it here, then I can simply calculate the answer. And from here I can find out the value of delta nx at ln. So simply I will put ln here. So what I will get? 10 to the power 20 tau n e to the power minus 1. So this is the value at ln. Now I need the slope. So this is the value, this alpha value that I put, that is the value at ln. Then if I need the slope, what I will do? I will just simply divide by ln. Although what I am telling is that is wrong, but I am saying that in second region as well, if you are applying a continuity equation, that means you are just making the problem complex. Just by using your brain, you could have reduced the calculation. Although this is absolutely wrong. Whatever that we are doing here, that is absolutely wrong. Okay, and now we will start the correct solution. So first 13 to 15 minutes I just spent just to tell you that whatever that you have studied, if you have previously studied this solution, then make the corrections now. Okay, and the mathematics between 0 to ln, that will be brilliant. Like, you will have to use some very good knowledge here. So let's get started and let's analyze it with the correct solution. So now only thing that I am left with, I have to apply continuity equation. Okay, so I have to apply continuity equation. So even if I am taking 0 to ln, I have to apply continuity equation. So what is your continuity equation? We are talking about minority carrier concentration, which are our electrons. So dn by dt would be equals to 1 by q djnx by dx plus generation rate minus recombination rate. Here generation rate is a function of x, so I will write down generation rate minus recombination rate. And since you are working at steady state, so this is gone. Okay, so what do you get? 1 by q. What is the value of jnx? Jnx will simply be equals to jnx. Here drift current is 0. Drift current is 0. So your total current would be equals to diffusion current only, right? And that would be equals to q into dn. That would be equals to q into dn into d by dx of excess carrier concentration. D by dx of excess carrier concentration. What that would be? Excess carrier concentration would be delta nx. Okay, so 1 by q into dn. What I am putting? I am putting this value because q into dn is constant, so that is coming outside. Now basically I hope you are able to understand what we are doing. 1 by q d by dx, I am putting the value of jnx. What is the value of jnx? That is q into dn d by dx of delta nx plus generation rate minus recombination rate. I hope you have understood what I have done. Okay, so now q into dn is a constant part that will come outward. So d square by dx square delta nx generation rate minus recombination rate. What is generation rate? 10 to the power 20. And what is recombination rate? 10 to the power 20 e to the power minus x by ln, and that is equals to 0. So what I can see here, q and q will get cancelled out. Dn I can throw on the other side. Delta nx is given as 10 to the power 20 generation rate minus recombination rate. Sorry guys, 10 to the power 20 e to the power minus x by ln minus 1 divided by dn. Look, q to q got cancelled out. Dn, what I have done is that I have taken this part this side. So 10 to the power 20 e to the power minus x by ln, that would be plus and this will be minus. So this is what I will be getting, and dn I have just put downward. All good. Now what I need to do? I need to do the integration on both of the side. So if I do the integration on both of the side, what I am getting? This is what I am getting. 10 to the power 20. What will be the integration of this one? That would be e to the power minus x by ln multiply with ln minus x plus constant. So this is the value of dnx divided by dx you are getting. Differentiation of excess carrier concentration with respect to x, this is what you are getting. Now you can see that generation and recombination profile are symmetric. What I am saying, generation rate and recombination rate profile are symmetric. What does that mean? That means nx will also be symmetric, no? Delta nx, that will also be symmetric only. Why so? Like whatever the carriers are being generated at the same rate, carriers are at the, basically whatever that is happening between 0 to 2 ln, the same thing is happening between 0 to minus 2 ln as well. At the same rate generation is done, and at a different rate recombination is done, and the similar thing is happening between 0 to minus 2 ln as well. So delta nx profile will also be this delta nx profile will also be symmetric, or you can call it will be even. For any even function which is differentiable, for any even function which is differentiable, you let me know what will be the value for this particular thing. You let me know what this will be equivalent to. Let's just say there is a function f, there is a function fx which is even. There is a function fx which is even. Okay, and I calculate the differentiation with respect to x at x equals to 0. What will be the answer I will get? Cosinusoid. What will be the differentiation at x equals to 0? 0. Take more example, any example you want to take. Let's make the, someone will say that sir I will make the waveform like this. Now sir, what is the differentiation at x equals to 0? Sir, it is not even differentiable. It is not even differentiable at x equals to 0, because when you go at 0 plus, the slope is positive, and when you go at 0 minus, the slope is negative. So it is not even differentiable. But I am getting some answer, that means my delta nx is differentiable. So I need to consider only differentiable function. So any function you take, what will be the differentiation? 0. Any even function you take, differentiation at x equals to 0 will be equals to 0 only. Are you able to understand this point? And why is that so? Because differentiation of even function will be odd. Differentiation of a even function will be odd. What is the what is the differentiation of cosinusoid? Sinusoid, right? Differentiation of cosinusoid is sinusoid, and sinusoid is odd function. So differentiation of even function will be odd, and every odd function at 0, every odd function at x equals to 0 will be 0 only. So enough points I have given. You just need to understand that if your function is even, then the differentiation with respect to x would be equals to 0. Do you understand this point? So first boundary condition I have got. What boundary condition I have got? That value of this particular function at x equals to 0 is 0. So this is equation 2. So from equation 1 and 2, what I will do, I will put x equals to 0. From equation 1 and 2, I will put x equals to 0 here. So if I put x equals to 0 here, what I am getting? 10 to the power 20 divided by dn minus ln plus c, minus ln plus c should be equals to 0. So value of c is coming out to be ln. Value of c is coming out to be ln. So now what do you see? This thing I have got 10 to the power 20 by dn minus ln e to the power minus x by ln minus x plus ln. So this is the value that I am getting. Now let's try to plot the profile of delta nx. This is the differentiation of delta nx you have got between 0 to ln. Between 0 to ln, this is the differentiation that you have got. Okay. Now you are trying to plot delta nx, not the slope. I know that it will be symmetric, so a very rough diagram I am making. I am not sure how the waveform will go. I am just thinking that it is going like this, because delta nx expression I haven't got. I have just got the d by dx delta nx expression till ln, right? Now after ln, what do I know? After ln, what do I know? That when you reach at 2 ln, the whole carrier concentration is going to be 0. And one thing also I know is that between ln to 2 ln, between ln to 2 ln, your recombination rate is equals to generation rate, and since it is steady state, so this is equals to 0. What does that mean? That means, sir, this thing is equals to 0. And what does that mean? What is jnx, not jpx, sorry, jnx? How this came? Because of the continuity equation. Now differentiation of jnx is equals to 0. What does that mean? That means nx profile will be linear. This I have already proved. Again let me prove. What is jnx? That is q into dn into this thing, delta nx. Here I should put delta nx. Delta nx profile will be linear. right? So if this differentiation is equals to 0, that means this has to be constant, Jnx has to be constant. This is already constant, this is already constant. Now if you want this to be constant, what does that mean? That means delta nx has to be linear, right? Because let's just say there is a linear function 3x plus 2. What is the differentiation of this? 3, a constant value. But if it was 3x square, then what will be the differentiation? 6x, which is not possible. So by using your intuition without using any mathematics, I have said that it will be linear only. Say yes or no? Okay, it will be linear only. Now just let me know one thing, just let me know very simple thing. Whatever the slope that you are getting at 2 ln, whatever the slope that you are getting at 2 ln, the same slope you will get at ln as well. Say yes or no? If I need to find the value of d by dx delta nx at 2 ln, that would be equals to d by dx delta nx at ln as well, because the linear graph is there, no? Can I find the value of d by dx delta nx at ln? Yes, because this is going between 0 to ln, no? So in this equation, if I put x equals to in this equation, if I put x equals to ln, then I will be able to get this value, and that will be equals to this value. Basically, this graph is continuous, no? This graph is continuous. So whatever the slope that you are getting at ln, it's not that it is breaking at ln. If the graph was breaking at ln, then you would have said that, sir, if the graph is breaking at ln, then I cannot comment that whatever the slope you get at 2 ln, the same slope you will get at ln. Then I cannot comment. But it will not break because delta nx value cannot go to infinity. This is continuous. So whatever the slope you get at ln, that same slope you will get at 2 ln, right? And the value of slope at ln you can get from this particular expression. So what I mean to say is that what I would do, sir, d by dx delta nx at x equals to ln, that would be equals to what? 10 to the power 20 divided by dn minus ln e to the power minus 1 minus ln will get cancel out, minus ln plus ln. So what you are getting? 10 to the power 20 ln by dn e to the power minus 1. So this is the value of slope you are getting at x equals to ln. The same value you will be getting at x equals to 2 ln as well. So what you are having? You are having the slope of excess carrier concentration with respect to x at 2 ln. What you actually needed? This is what I need to find. This is my target. This was my target. So what I actually needed to find? I needed to find the value of current at plus minus 2 ln. What that would be equals to? Sir, q into dn d by dx delta nx at x equals to plus minus 2 ln. 1.6 into 10 to the power minus 19. Value of dn is not mentioned. Yeah. And this is the slope that we are getting, 10 to the power 20 . So dn to dn is getting cancelled. 1.6 by e 10 to the power minus 19, 10 to the power 20. What is the value of ln? Ln value is 10 to the power minus 4 centimeter. Everything is going in centimeter. So you solve this and you will get the answer. So 1.6 divided by e, then 10 to the power minus 3 you are having. So 1.6 divided by e, that will be the answer. E is 2.7. So if I just needed to solve the gate question, no, then I would have done in this manner, 0.588 milliampere per centimeter square. So if I just needed to find out this answer, no, then it should have been done in this particular manner that I have solved. This was absolutely wrong. Luckily you got the answer. Just to prove that this is wrong, I had to make these two options as well, because according to them this would be the answer, right? According to these guys who are solving like this would be the answer, because what they would do, tau n will be replaced with, or that I have already done, I guess. Right? So now what is our target? I have to find out the value of delta nx, right? This I have already got, this expression I have got, but from this expression I need to find out the value of delta nx, no? Then only I will be able to comment that what will be the value of excess carrier concentration at x equals to 0. So I need to find out the expression of excess carrier concentration. So let's find out the expression of excess carrier concentration. So what I need to do, I am doing the second part now. So I will just copy whatever that I have already find out. That is minus ln minus 10 to the power 20 ln by dn minus 10 to the power 20 ln by dn e to the power minus x by ln, e to the power minus x by ln, minus 10 to the power 20 x by dn, minus 10 to the power 20 x by dn, plus 10 to the power 20 ln by dn. Now again I will have to differentiate. So if I differentiate, what I will get? So ln square it would be, and this negative sign would become positive, right? E to the power minus x by ln is being integrated, so ln would go upside, ln square it would become, and this will become a positive sign. 20 x square by 2 dn plus 10 to the power 20 ln dn x plus another constant, that is t. Your constant will also come. Now I need to find the value of this constant. How would I find? Pause the video and think about it. How would you find it? Did you think about it? Very tough to think. To be very honest, it took me a lot of time to think that how will I find out the value of this d. Best thing of this particular question is finding out the value of d. How will you find it out? What do you know? Can you let me know what will be the concentration at ln? Can you let me know the value of delta nx at x equals to ln? Yes sir, I can surely let you know. Why? Because I know the slope. I know this slope. What is this slope? This slope is equivalent to, this slope is 10 to the power 20 ln by dn e to the power minus 1. So let's do it here. This is your ln, this is your 2 ln, and this slope I already know. This slope I have find out 10 to the power 20 ln by dn e to the power minus 1. 10 to the power 20 ln by dn e to the power minus 1. So can you let me know what will be this value? This value is already 0, so what will be this value? This slope is actually negative, and this value is 0, so what will be this value? Very simple thing, no? Very simple thing, right? You can find it out. y2 minus y1 upon x2 minus x1 is equals to this value, right? So let's just say this value is delta nx at x equals to ln. Although this value will be this value only, which is pretty simple, but still let's find out. Delta nx at x equals to ln minus delta nx at x equals to 2 ln would be divided by ln minus 2 ln would be equals to this slope. This value is 0. this value will be equals to minus ln, and here this minus sign is already there. So what answer you will get? Delta nx value at x equals to ln. The answer that you will be getting is 10 to the power 20 ln square by dn e to the power minus 1. Not very tough to think, like very basic mathematics. That's why I'm not explaining it much. I hope this much mathematics you already know. At x equals to ln, what I am doing is that if this slope I know, that means if I cover a distance of ln, then this much I am reducing. So where I would have started from? 10 to the power 20 ln square by dn e to the power minus 1 divided by ln would give me this slope. Yes, it is giving me this slope. So this value is not very tough to find. Delta nx value at x equals to ln. This value we have find out. Right? And now using this value, I will put in this equation. So very smartly, just think about the professor who has framed this question. We are solving and we are finding so much of difficulties, but just think about the professor who has thought this problem. Like huge respect to that professor. I surely want to learn EDC from him just by looking at this question. I'm not sure who framed it, but just think about it, like how he would have thought. Although we disrespected that thought if we solve by this method, which is absolutely wrong, doesn't make any sense. A lot of counter questions are there. Actual beauty, he would have solved it in this manner, but he could have framed it a better problem if he had made MSQ like this, right? Then it would have been a better problem. But in MSQ, there is very high chance that you can blindly guess any answer. Like what if some guy would have put AD without a zero effort, he would have got +2 marks. But in integer type, you cannot put the blind answer, right? So that might be the reason he only asked the photogenerated current. He would not have thought that people will be applying this formula and they will get the answer. Like from this formula only, you apply the same thing after that, you will get the answer. Okay, what I am saying, you apply this formula and you will get the same answer, luckily. But actual beauty is this. Okay, so a delta nx value at x equals to ln we have find out. Now just I will put here and I will get the value of d. So what I can see, let's call it equation 3 and let's call it equation 4. So from equation 3 and 4, what I can see, delta nx value at x equals to ln is equivalent to 10 to the power 20 ln square by dn e to the power minus 1 I have put in this manner. If I put ln, what do I get? 10 to the power 20 ln square by dn e, because here if I put ln, the same thing I will be getting, minus 10 to the power 20 x square by 2 dn in place of x I am putting ln, and here also you put ln 20 ln square by dn plus d is equals to 0. Oh, sorry, not 0, sorry guys, that would be equals to 10 to the power 20 ln square dn by e. This constant I should not have put as d because d is already dn now. So let's put it somewhat else. Let's put it as alpha. So this constant is alpha. Okay, so this and this is getting cancelled out, and value of alpha is coming out to be minus 10 to the power 20 ln square by 2 dn. This is the value of alpha you are getting. Okay, and since this is the value of alpha, now you can find out the expression of delta nx. So delta nx expression you are getting is 10 to the power 20 ln square by dn e to the power minus x by ln. So according to a lot of people or every single people, whoever have given the solution, this was the answer, right? In place of ln square by dn, they have simply put 2n. So according to them, this was the expression of delta nx between 0 to ln, which is absolutely wrong. This is not the complete expression. This is the complete expression. This is the complete beauty of this equation. 10 to the power 20 divided by 2 dn x square plus 10 to the power 20 ln by dn
into x minus 10 to the power 20 ln square by 2dn. And please don't like take the offense that sir why you are talking about like this about the other professors, other teachers. I never ever talk about like this for other teachers, but there are some teachers who will act as if they are the god, and they will just think that other people are just needless, they just copy their content, this that, they will just keep on talking about them. Okay. And regarding me, they talk a lot, like they talk what kind of words they use I will not say. So they should get some reality check that you need to learn a lot now. Okay, that's why I am saying that you act as if you are a god, you know this subject, that subject, we are teaching for 10 years, for 12 years. Where is your experience in solving these problems? Hardly one or two good question would come, no, in the examination, hardly one or two, and you mess up like this. And it's been 4 years since that question have come. Until this point, they haven't realized that if I am applying that formula between 0 to ln, then if I apply the same formula between ln to ln, the things are getting wrong. Till this point, they are not realizing it. And they talk about experience, this thing, that thing. Okay, you go to my channel. Till this point in gate 121, this question has come in op-amp. That was based on differentiator. People say dy dx, sorry, dy dt minus 1 by rc, somewhat like this relation they write down. Absolutely wrong. This is not the analysis of differentiator. You type down gate 121 differentiator question, PrepFusion Himanshu Agarwal, you will see the real analysis there. In 2024 also some good question came from op-amp only. You see the real analysis of that. In gate 2018 there was a good question in a combination in a sequential circuit that that was having an answer of like you need to design, that was based on FSM, but that was actually based on sequence generation. So you need to generate the sequence. Okay, so how many flops will be required? So that was the question. 5 flops will be required. Traffic light problem. Okay, very famous. So you see the analysis of those problems, then you will realize that what is the level of content here, what is the reason why I left my job and came here. Okay, although I should not be much hampered about these people, because I know they will always talk about needless thing. They will never ever focus on improving. There was one more question like in gate 200 2000, I don't know, 2010 I guess. So this question itself was wrong. Okay, itself was wrong, and I made the solution. Like whenever I made the solution, I just said that the right solution I am giving, and just I am doing my job. But needlessly you try to pull your leg, then I will have to reply no. I will never start anything. Like I will never start talking about other one. Whatever that you are doing, you are absolutely great, and if it is required, I share your content as well. Okay, I recommend your content to other people as well if it is required. But you need to build up. You need to build up a decent mentality at least. So this was the question. There I said that this question is wrong. I proved it. I simulated it as well. I gave the simulation result as well. And then he gave the solution things like in their live classes talking about that this guy, these guy don't know anything, this or that. And now I see their notes, they have changed the question because they have realized that they have done something wrong. So surely you have realized here, then you should realize here as well. Okay, this integrator problem. There are questions in EMFT as well. There are questions in digital electronics as well. Till this date, all the questions are solved wrong. And every single question I will pick up and give the correct solution with the correct explanation. That's my sure guarantee for this particular field. If I stay in this field for more than 5 years, every single question that has been asked in the gate examination will be solved correctly. Even if the IITs have messed up, that thing also I will point out. And I will do it not for one subject, two subject, for all 10 subject, every single topic of electronics for gate examination. And I will do it, and I will do it in the best perfect manner that no one has ever done. You call it arrogance, you call it overconfidence, you call it whatever you can call, but this is my confidence, and if I am saying something, I will do it. Okay, so you keep on talking. You will always keep on talking in your live classes. I only once or twice I reply, and I reply with the concept, and this is the concept, and this is the thing, that this is the expression of delta nx. Did you ever think of it? Did you ever think in this direction? Okay, so yeah, I wasted your time, but all fine.
Now I need to find out the value of delta nx at x equals to 0. The main point is I should not be much bothered about their comments, but I don't know कैसे मतलब false hope में जी रहे हैं. hope तो नहीं कहना चाहिए, false sense में जी रहे हैं कि मतलब हम तो पता नहीं क्या ही कर दिया. थोड़ा सा सवाल इधर उधर होता है मतलब गेट एग्जाम में, और बस सिग्नल का एक सवाल आया था बढ़िया इधर उधर होके, सैम्पलिंग वाला, जिसमें सैम्पलिंग वेवफॉर्म को शिफ्ट किया था और सिग्नल वैसा ही था, दे दिया उनका आंसर. ना किसी ने सोल्यूशन दिया. इतने लोगों की टीम होती है, इतने सारे लोग होते हैं, 10-12 लोग मिलके 2-3 सवाल आते हैं जो ठीक आते हैं एग्जाम में, उनमें भी गड़बड़ हो जाती है सोल्यूशन में. इधर वो देते ही नहीं है, इधर दे डोंट इवन डिस्कस इट, एंड इफ दे डिस्कस, I don't know what kind of legendary legends gods goat don't know how what kind of words they use for themselves. I don't know if they don't have the reality check or not. I have my reality check. I need to learn a lot of new things, and I have that reality check. If I am teaching EDC, let's just say this subject I am teaching, so I am watching the content of 5 gate educators. I am studying Niemann, and I am referring to 2 NPTEL lectures. So these 5 gate educators, Niemann and 2 NPTEL lectures. After that I am framing my content, and then I am coming here. Sir, why these gate educators? Sir, they are your competitor, you are copying from them. No, I am learning. Who knows, one educator would have taught one good thing. I can learn from him, and it is a good thing. I will appreciate it, and I will also see that what they are actually teaching. Major source of learning will be this, but I need to check here as well, no, that what they are teaching, I need to teach better than them. So these are my competitor. Always you will look at your competitor, and this should be the way. I don't know why people will take it on ego. You should always watch the content of your competitor. Surely you should watch it, because your target would be that at least I need to teach better than him. And this I follow in all the subjects. This is just about the EDC. Same goes for communication. Same goes for EMFT. EMFT complete playlist is available on YouTube. You watch the content once. Like what kind of visualization I given. The subject that is considered as mathematics. With zero mathematics we are doing that subject. With zero mathematics. EMFT. Analog, network analysis. Next year I will be taking control and mathematics as well. You see the signal system. Like signal system, they consider it as a mathematics. I gave it the flow of electronics. That signal system is electronics. Without signal system there is no electronics. In signal system we have discussed the concept of control system, network analysis, analog electronics, digital electronics as well. Like everything we have discussed in signal system. Every single thing we have discussed. Fourier transform, Fourier series, that how they came into action. So that kind of content if we are providing, that means if I say my content is unique, if I say my content is something that has never been delivered in this gate field, then I mean it. Okay, and I will keep on making it. Although it's not reaching much of the people, although it is reaching decent enough people, more than decent enough people, and when it reaches the larger audience, people will realize what kind of depth is there on this particular platform. Okay, yeah, again got distracted. So at 0 you need to find out, since this is on YouTube and I am not wasting time in between the question. In the last I am doing, I am wasting the time, because just you need to put the value of 0 here. If you put x equals to 0 here, what you will get? 10 to the power 20 ln square by dn. This term will be gone, this term will be gone. So what you are left with? 10 to the power 20 ln square by dn minus 10 to the power 20 ln square by 2 dn. So what will be the answer? 10 to the power 20 ln square by 2 dn. Okay, so that will be the answer. So if we go back to the question, then this will be the answer. Okay, this is also wrong. So A and D are correct. Well and good. So this was a very good question. I wanted to discuss it. I hope you enjoyed it. Right from the 0 you see there was huge mathematics. Although if I had solved by using this one, then I could have solved it in 3 lines only. Right, delta nx. I would put ln here, then I would get the value of slope, and if I have the value of slope, then I will just put it here. My answer is done. Okay, and sir, you wrote the gate 122 examination. Did you get it correct in the examination hall? Absolutely not. It is practically impossible to get this question correct in the examination hall. No one can get this question correct in the examination hall. Okay, no one. So practically impossible to get it correct. Like even if you solve by this, then also you will have to think of it, right? Here also thoughts are required. Because when this question came, actually no one gave the solution. Now people will be claiming that I was the first one to give the solution, this thing, that thing. But I remember I was the aspirant, no? I was the aspirant. So till the date of answer key, no one gave the solution. I exactly remember the date. On 21st Feb answer key was released, and on 21st Feb only the solution came, and that solution came in this manner, which was absolutely wrong. At that time I was just a student, I did not have this much of knowledge, but now I am an educator, right? When you are learning a subject as a student, when you are learning a subject as an educator, both are complete different thing. When you learn as an educator, you refer to a lot of resources, you do every possible thing, and then you think on your own. And the resources that I mentioned, like those professors, IIT professor NPTEL, along with that there is one more resource, which is, who has written this? What do you think? ChatGPT, AI. So DeepSeek and ChatGPT, these two AI tools. I made a video as well that how you can use it as a teacher and as a student. Both can make efficient use of AI. So how efficiently you can use AI, that video also I have made on YouTube only. You can check out that video. Okay then, yeah, that's it. This is the end of this solution. Thank you very much. Happy learning. And if you want to enroll in full course of EDC, then you can go to our website, which is prepfusion.in. Their full course of EDC is just available in 899 rupees. Okay, you need to apply the promo code PREP. You apply this promo code PREP and you will get it in 899 rupees. Okay then, yeah, thank you very much. Happy. Hi everyone, welcome to PrepFusion. So in this video we are going to study about Fermi-Dirac Distribution. So what is this Fermi-Dirac Distribution that we are going to see, and this is going to be our final video for basic semiconductor physics. So what is this Fermi-Dirac Distribution? So let's just say this is your semiconductor. In this semiconductor you will be having some energy states. Energy state could be there in conduction band, it could be there in valence band. Okay, so let's just say this is my energy state E. Now on this energy state, either electron will be there or it will not be there. Either there will be electron or it will not be there, right? So Fermi-Dirac distribution comments on finding the probability of electron on a particular energy state. So probability of finding an electron on a particular energy state, that is given by Fermi-Dirac distribution. Since it was given by Fermi, so I will write down F. Probability of finding the electron at a particular energy state E, that is given by 1 upon 1 plus e to the power E minus EF by KT. K, you know what is K? What is one constant? T is the temperature in Kelvin. 1 upon 1 plus everything you know. E is the energy level. E is the energy state, not energy level. E is the energy state. The energy state where you are finding the probability of a electron. And EF is the Fermi energy level. Now sir, what is this Fermi energy level? So it is just like a reference energy level. It is practically not existing. What I mean to say is that in your semiconductor, there will be conduction band, there will be valence band. That's it. But we will define some reference energy level that is known as Fermi energy level. So this is your Fermi energy level. It could be somewhere between conduction band to valence band. Is that okay for you? Even this can go into the conduction band as well. It can go into the valence band as well. We will discuss all these things. But as of now, what you need to consider that EF is nothing but a reference energy level which is practically not existing. We are just defining it. Why we are defining it, you will understand. So have some patience. So as of now, what we have studied, Fermi-Dirac distribution comments on the probability of finding an electron on a particular energy state, not energy level. Okay, comments on the probability of finding an electron on a particular energy state, and that probability is given by 1 upon 1 plus e to the power E minus EF by KT. E is that particular energy state, EF is Fermi energy level, KT you already know, right? So this is what has been written. It tells us about the probability of finding an electron in a particular energy state. So just notice this word, energy state, not level. A very important point, very important point, that it comments on the probability of finding an electron at energy state, not energy level. Okay, and at a certain temperature as well, because temperature can the temperature can also vary, right? What is E? E is equals to that energy of the state. EF is the Fermi energy level. What is Fermi energy level? We will discuss about that. K is the Boltzmann constant and T is the temperature. Now what I am saying, the temperature is 0. Temperature is 0 Kelvin. And E is greater than EF. What I am saying is that you need to find the probability of finding the electron at energy state E, which is above EF. What I mean to say is that if this is your EF, then energy state E is here. So E is above EF and temperature is 0 Kelvin. So what will happen? 1 upon 1 plus some positive value e to the power E minus EF will be positive because E is greater than EF. So some positive value divided by 0 Kelvin. What that will be equivalent to? 1 upon 1 plus something divided by 0, or that would be infinity. And what is the value of e to the power infinity? Infinity only. So what is the answer you are getting? 0. So probability probability of finding an electron at an energy state which is above the Fermi energy level at 0 Kelvin will be equal to 0. What I am saying, let me repeat it. Probability of finding an electron at the energy state E which is above Fermi energy level at 0 Kelvin will be equal to 0. That means if you are at 0 Kelvin and your energy state is above EF, then you will not find any electron here. Is that clear to you or not? Okay. Now let's see the second thing. Now my energy state is below EF. Now my energy state is below EF. This is my energy state. Okay. Now I need to find the probability of finding an electron at this particular energy state. That would be given by you should write down this formula at least 5 times in your rough notebook. Just now write it down, this formula, at least 5 times, because it is very important. This whole lecture will be going towards this particular formula, and surely the question is coming from this particular formula. 100% I am saying question is coming. So at least write down 5 times. 5 times you write down this formula. 1 upon 1 plus e to the power E minus EF by kT. Okay, yeah, so let's do it. 1 upon 1 plus e to the power E minus EF is negative now, right? E is less than EF, that means E minus EF would be negative, divided by 0. So what you will be getting? 1 upon 1 plus negative divided by 0 e to the power minus infinity, right? Negative divided by 0. Let's just say minus 1 divided by 0. So that would be minus infinity. Minus 2 divided by 0. That would be equal to minus infinity, right? And what is the value of e to the power minus infinity? That is 0. E to the power minus infinity is 0. So what is the answer you are getting? 1. So here you are getting answer 0 and here you are getting answer 1. So what you will say? At 0 Kelvin temperature, probability of finding an electron below Fermi energy level is 1 and probability of finding an electron above Fermi level is 0. That means at 0 Kelvin, all the electrons will be lying under the Fermi energy level. Again, let me repeat the statement. At 0 Kelvin, all the electrons will be lying under the Fermi energy level. Do you understand by this? Do you understand this line or not? E is less than EF means energy level is under Fermi energy level, and E is greater than EF. That means your energy state is above Fermi energy level. If I am saying energy here, I should use the word energy state. But in the language, when I am speaking, sometimes if I call level, then also you should understand that I am calling state only. E is the energy state, but for EF we use the word Fermi energy level. Okay, but E is the energy state. So in language, sometimes if I mess up and I say E is the energy level, then you should say that E is meaning for energy state only. Are you able to understand what I am saying? Because in the language, because we will keep on saying Fermi energy level. So here I can say E is the energy level, but it is actually energy state. Okay, so E is the energy state. Do you understand the meaning between energy level and the energy state? Yes, you already understand, because in the basics we have seen. What is energy level? Energy level is like a floor and energy state is like a room. So on one floor there could be multiple rooms. So on one energy level there could be multiple energy state, right? So that you have already understood. So probability of finding an electron below the Fermi energy level is 0, and probability of finding an electron below the Fermi energy level is 1 at 0 Kelvin, and probability of finding an electron above the Fermi energy level at 0 Kelvin will be 0. All good? All fine? So let's draw the Fermi energy level for intrinsic, N type and P type. So this is what is written: at 0 Kelvin all states below EF are full and above EF are empty. So what do you think? At 0 Kelvin, what is the scenario in intrinsic semiconductor? all the electrons will be lying in the conduction, all the electrons will be lying in the valence band, and there will be no electron in the conduction band. So where I can draw the Fermi energy level? Sir, even if you draw here or here or here or here, sir, everything would be fine. Right? Because what is the condition? That, sir, below Fermi energy level, everything should be filled, and above Fermi energy level, everything should be empty. So, sir, if I draw here, then you would say that below it, fine, above it, there is nothing. Yeah, it is also fine. But actually, we draw it right in between. Okay, right in between. Because there should be a symmetry, no? Like below this, everything is filled. Above this, everything is empty. So, this is your Fermi energy level of a intrinsic semiconductor, EFI. What about n-type semiconductor? Where I should draw it? In n-type semiconductor, what will happen? You will dope some donor atom. And since you have doped the donor atom, each donor atom will be giving you one electron. This electron is nearly free. This is not completely free. Since this is nearly free, so it will make an energy level just below the conduction band, because it requires very less energy to get into the conduction band. But at 0 Kelvin, it is not getting energy. That means at 0 Kelvin, it will be there in the donor energy level only. It is not getting into the conduction band. So at 0 Kelvin, this will be the scenario. There are some electrons in the valence band. There are, these are the bound electrons. These are nearly free electrons, not completely free, nearly free electrons, which are ready to go into the conduction band just as they get some energy. But they are not getting the energy. That's why they are here. So what do you think where I should make my Fermi energy level? So this is where I will make my Fermi energy level. So this is your Fermi energy level for n-type semiconductor. And what do you think here? This will be interesting. Where I should make my Fermi energy level? Here? No. It is about the electrons, no? It comments on finding the electron. It comments on the probability of finding the electron. Do you really think that acceptor atom is having any electron? No, acceptor atoms are having the holes, right? Because if you dope acceptor atom, they will give you a hole which is ready to take electron. So this is the vacancy for the electrons. So where I will make it? Here I will make it. Someone will say that, sir, even if you make it here, then also definition is satisfied. Definition says that below Fermi energy level, everything should be filled, and above Fermi energy level, everything should be empty. So still this condition is satisfied. But if you are making this above the donor energy level, so this you will make below the acceptor level, right? So now also the condition is satisfied, no? That above everything is empty. These are empty only, and this is also empty only, and below this everything is filled. Yes, below this everything is filled. So this is your Fermi energy level of p-type. So in n-type, Fermi energy level is near to the conduction band. In p-type, Fermi energy level is near to the valence band, right? Say yes or no. And in intrinsic, it is right in between. In the intrinsic semiconductor, the Fermi energy level is right in between. Is that clear to you or not? Okay. So I am asking you this question. Find the probability of finding electron at energy state which is 0.1 electron volt above the Fermi energy level. Consider room's temperature. So what will be your answer? Sir, they are asking above the Fermi energy level. Above the Fermi energy level. So probability of finding an electron above the Fermi energy level, we know that everything will be filled below the Fermi energy level. Above the Fermi energy level, everything will be empty. So sir, this is the answer, which is wrong. Because everything that we discussed till now, that was for 0 Kelvin. What is the temperature given here? 300 Kelvin. So what you need to find? You need to find the probability you need to find the probability of finding an electron at an energy state which is 0.1 electron volt above the Fermi energy level. So if this is your so if this is your Fermi energy level, then this will be your energy state. What they are saying? The difference between E and EF is 0.1 electron volt. So E minus EF is given as 0.1 electron volt. And what will be the value of KT at room's temperature? 0.0259 electron volt at T equals to 300 Kelvin. This thing also we know. So what we need to find? Probability of finding an electron at this energy level E, that would be equals to 1 upon 1 plus e to the power E minus EF by KT. So 1 upon 1 plus e to the power 0.1 divided by 0.0259. So when you solve it, you will get the answer 0.02. So this is the answer. Okay, so not 0. Blindly you are not going to put 0. Whatever that we discussed, that below the Fermi energy level everything will be filled, above the Fermi energy level everything will be empty. That was at 0 Kelvin only, not at any random temperature. Is that clear to you? Okay. Now at any random temperature, what I am saying, probability of finding an electron at energy level EF. What you need to find? You need to find the probability of finding an electron at energy level EF. Now you will say that, sir, this formula is applicable for the energy state, not for energy level. But here you need to find the probability of finding an electron at energy level EF. This is what you need to find at any random temperature, which is not equal to 0 Kelvin. So, sir, how you can apply the formula? I can apply the formula if on energy level, on this energy level EF, there is only one state. Then energy level and energy state would be the same thing only, no? Are you able to understand what I am saying? On Fermi level, if there is only one state, that means whatever the electron is found, that will be there on this state only, no? If there are more than one state, let's just say there are two states, and I am saying that probability of finding an electron on this Fermi energy level is 1 by 2. That means probability of finding the electron on this particular energy state will be 1 by 2 into 1 by 3. And here also 1 by 2 into 1 by 3. Why so? Because on this Fermi energy level, on this floor, if some person can be found, that probability is 1 by 2. Now on this floor there are 3 rooms. On this floor there are 3 rooms. So what is the probability of finding the electron, or what is the probability of finding that particular guy in one room? That would be 1 by 2 into 1 by 3, 1 by 2 into 1 by 3, 1 by 2 into 1 by 3. But if I say on this floor there is only one room, and probability of finding a guy on this floor is 1 by 2. So what is the probability of finding the guy on this particular room? That will also be 1 by 2 only, because if he is there on this floor, then surely he will be in this room only. That means if your energy level is only having one state, then your formula will be working for the energy level as well. Are you able to understand this point? So your Fermi energy level is just an imaginary energy level. It is not a practical energy level. So you will, by default, you will consider that it is having only one state. In the examination as well, let's just say they are calling E as an energy level. Okay. And they are asking you what is the probability of finding an electron at this particular energy level. Or let's just say this question was there in the examination, but in place of state they have mentioned level. So by default you will consider that on this energy level there is only one state. If there are more than one state, then they will specifically mention it. If they are not mentioning it, that means by default you will say level equals to state. But if there are more than one state, they will specifically mention it, and that is known as degeneracy factor. We will discuss that. Okay, so they will specifically discuss it. Okay, they will specifically mention in the question. So here also this formula will be applicable. Why so? Because on one Fermi energy level we will consider that there is only one energy state. Okay. So what will be the formula? 1 upon 1 plus EF minus E minus EF by KT, right? E minus EF by KT, that was the formula, but in place of E we are putting EF. So EF minus EF by KT. Temperature could be anything, but it is not 0 Kelvin. So what you will be getting? 1 upon 1 plus e to the power 0 divided by something. 0 divided by something, what that would be? 0 only. 0 divided by something will be 0 only. So e to the power 0 is 1. So what is that? Answer is getting half. So probability of finding an electron at Fermi energy level at any random temperature is half. So that's why we define this Fermi energy level. Are you able to understand this point? So this can work as a reference for us. At 0 Kelvin, above it everything is empty, below it everything is filled. And at any random temperature, at EF, the probability will be half. Right? So this is how we define our Fermi energy level. The Fermi energy level is an imaginary energy level. It is not practical energy level that electrons can occupy. At 0 Kelvin, all the states below EF are completely filled with electrons, and all the states above EF are empty. At any temperature, the probability of finding an electron at EF is 1 by 2. Now, what I am asking, probability of finding the electron at some energy level which is above EF. Probability of finding an electron at an energy level which is above EF at any random temperature. At any random temperature will be less than 1 by 2. Do you agree to this point or not? What I am saying, energy level which is above EF at any random temperature, what I am saying, E is greater than EF. E is greater than EF and temperature is anything random. So what you will write down? F of E 1 upon 1 plus e to the power E minus EF by kT. This value will be positive, right? And this is some value, kT will be some value. E to the power something positive, it will be surely greater than 1, for sure. E to the power something positive will be surely greater than 1. You can take any value or you can just simply draw the graph of e to the power x. No, what will be the graph of e to the power x? At 0 it will throw the value 1, e to the power 0 value is 1. So if in the e to the power, if you are getting anything positive, even if you are getting 0.00001, then also answer will be more than 1. So this value will be more than 1. E minus EF, right, which is positive. Positive divided by something, that means the whole value will be positive. In e to the power, if there is anything positive, then the value will be greater than 1. So this value is greater than 1. This particular value is greater than 1. Let's just say this value is 1.1. So what will be the answer? 1 upon 1 plus 1.1, that would be 2.1. Is it greater than 1 by 2 or less than 1 by 2? It is less than 1 by 2. So at 0 Kelvin, what was the scenario? At 0 Kelvin, the scenario was above EF, probability is 0. Above EF, probability is 0. In the worst case, the probability could be 1 by 2. Basically, the probability will be between 0 to 1 by 2 only. Worst case means, what will be the worst case? The worst case would be that this value becomes how much? This value becomes 1. And when it can become 1? When E is equals to EF. When E is equals to EF, when E is equals to EF at any random temperature, when E is equals to EF, this will become 1 by 2. So above EF, probability of finding the electron will be 0 at 0 Kelvin. At any random temperature, it will be lesser than 1 by 2. Are you able to understand this point or not? Just the simple mathematics. And we will understand it with respect to Venn diagram as well. Don't worry about that. But are you able to understand the mathematics? If E is greater than EF, this value is positive. KT is also positive. E to the power anything positive would be greater than 1. That means this value is greater than 1. So 1 plus something greater than 1 will be greater than 2. So 1 divided by something greater than 2 would be less than 1 by 2. So probability of probability of finding electron for E greater than EF at any random temperature will be less than 1 by 2. Okay, and for E less than EF, probability of finding an electron will be surely greater than 1 by 2, and it can never be greater than 1, so it has to be less than 1. So are you able to understand this? I will just simply write down in statement what I am writing down. Just here I will write down probability of finding an electron at energy level or at energy state E which is greater than EF will always be less than 1 by 2. And probability of finding an electron at energy level or at energy state which is less than EF will always be greater than 1 by 2, and surely the probability cannot be greater than 1. And this is true for any random temperature. T is any temperature where T is any temperature which is not equals to 0. All good? All fine? Now we need to draw the graph. Which graph I need to draw? I need to draw the graph of F of E versus E, where this is my EF. So let's draw it at 0 Kelvin. At 0 Kelvin, how I will draw this graph? So at 0 Kelvin, before EF, probability of finding an electron will be 1. But after EF, the probability of finding the electron will be 0. Let it go like this. So this is the diagram at T equals to 0 Kelvin. Now let's draw it at T equals to 300 Kelvin. Okay. So at at T equals to 300 Kelvin, what will happen? For E less than EF, for E less than EF, what will happen? The probability will be greater than 1 by 2. So this point I am calling, this is the probability 1 and this is the probability 1 by 2. Okay. So what will happen? When E is equals to 0, when E is equals to 0, at energy level, what I mean to say is that, let's write down the formula. F of E is equals to 1 upon 1 plus e to the power E minus EF by kT. So what I mean to say is that E is much lesser than EF. E is much lesser than EF. That means this value is very large in negative. E minus EF is very large in negative, because if E is much lesser than EF, then E minus EF will be very large in negative. That means it will be somewhat e to the power minus infinity only. So here the probability will be 1 only. What I mean to say is that if energy is 0 energy, it is not practically possible. But what I am saying is that if your energy level is much below EF, that means EF minus E is very large, because energy, this is your EF and my energy level is much below EF. That means this gap is very large. If this gap is very large, that means E minus EF is very large negative value, because this is at higher level and this is at lower energy level. So E minus EF will be very large negative value. So negative divided by something, that would be negative only, and very negative means e to the power minus infinity. That means e to the power minus infinity will be 0 only. So 1 by 1, that would be 1, and slowly it will start reducing. But you know one thing, that for E less than EF, the probability will always be greater than 1 by 2. That means the graph will reduce, but it will not go lesser than 1 by 2. Are you able to understand this point? So the graph will be reducing like this, and after that it will go somewhat like this. This is how the graph will go. Is that okay for you? Let me draw it again. Okay, is that fine for you? For E less than EF, what I can see, for E less than EF, the probability of finding the electron is always greater than 1 by 2. This is what I have written for E less than EF. If your energy level is below EF, then surely the probability will be greater than 1 by 2. And if your energy level is, or energy state is, above EF, then probability will be less than 1 by 2, which is less than 1 by 2. This point is 1 by 2 only. Okay. And it is pretty obvious as well. What do you mean by that? So let's just say this was your 0 Kelvin, this was your valence band, and this was your conduction band. As you increase the temperature, what will happen? Sir, some electrons from here will go here, and some vacancies will be created here, and some electrons will be here. Sir, initially you said that, sir, this was my EF. Now let's just say, sir, this is only your EF, but what you can see, that what you can see is that above EF as well, now there are some electrons. Previously above EF there was 0 electron. So you said that at 0 Kelvin this is the scenario. At 0 Kelvin this is the scenario, that there is nothing. But now, sir, just as you increase the temperature, some electrons from the conduction band is going into the valence band. That means above EF as well you are getting some electrons now. So that means there is some finite probability of finding the electron above EF as well. But it will never be more than the electrons in the valence band. Right? So that's why this is the graph, that here the probability will be 1 by 2 and here the probability will be less than 1 by 2. This I am drawing for T equals to 300 Kelvin. Now you need to draw the graph for T equals to 400 Kelvin. Draw it by your own. What I am saying, draw the graph for T equals to 400 Kelvin. How the graph will go? Use the mathematics and use this band diagram as well. Use both of the things. How the graph will go? This is how the graph will go. This will be the graph at T equals to 400 Kelvin. So first understand by band diagram. So this was the scenario at T equals to 300 Kelvin. Now if you increase the temperature more, what will happen? More electrons will go here, more electrons will go here, more electrons will go here. And this was your EF. So probability of finding the electron above the Fermi energy level has increased. Previously there were only 2 electrons, now the electrons are 3. So probability of finding the electron above the Fermi energy level has been increased. But now, what is the scenario? Now the scenario is here the electrons are gone. That means probability of finding the electrons below the Fermi energy level. Previously there were 4, and now just as you increase the temperature at 400 Kelvin, there are 2 only. So probability of finding the electrons below the Fermi energy level has decreased. This is for T equals to 400 Kelvin. Now if I draw for T equals to 500 Kelvin, then what will be the scenario? Then here the probability will keep on decreasing. But after that the probability will keep on increasing. So this will be the graph for T equals to 500 Kelvin. Are you able to understand this point or not? As the temperature increases, the probability of finding the electron above Fermi energy level increases and below Fermi energy level it decreases. And let's go by the mathematics now. What I will do? I will use the mathematics now. So what is happening? Temperature is increasing. This term is increasing. That means this whole term is going down. E to the power whole term is going down. That means this complete e to the power is going down. 1 upon something is going down. That means this value is increasing. What I am saying is that I am saying E is greater than EF. E is greater than EF. That means this value is positive. E is greater than EF means e to the power something positive divided by kT. Now temperature goes up. So this value goes down. E to the power some value goes down. That means this whole value goes down. That means the whole denominator is going down. And if whole denominator is going down, that means this whole value is going up. So for E greater than EF, the value is going up. The probability is going up. So you can see that with respect to the temperature, it is going up. But for E less than EF, what will happen? For E less than EF, what will happen? For E less than EF, e to the power E less than EF, that means something negative divided by kT. If T increases, for E less than EF, if T increases, what will happen? If T increases, then this value will increase. Then total value e to the power negative total value is decreasing. E to the power negative total value is decreasing. That means what I can say, 1 upon e to the power positive is decreasing. E to the power negative means e to the power minus x means 1 upon e to the power x. So if this value is decreasing, then what will happen? The whole value will go up, no? Because there is a negative sign. So the whole value is going up. So this whole value is going up. That means 1 upon something is going up. What does that mean? The whole value should go down. So you can see that as the temperature increases, the probability of finding the electron is going down. So this was there for T equals to 0 Kelvin, and after that the graph came into action for T equals to 300 Kelvin. Then the graph came into action for T equals to 400 Kelvin. And then the graph came into action for T equals to 500 Kelvin. T equals to 500 Kelvin. So is this graph understandable to you or not? By the Venn diagram, by your simple concept, from whatever you want to understand, it is surely clear to you. Say yes or no. So this has been written in very short line. At higher temperature, occupation probability at higher energy will increase, and while occupation probability at lower energies will decrease. Is that clear to you or not? So all the mathematics I am not going to write down in the notes. That you can write down in rough manner anywhere, like here, if you want to write down, you can write down. But now you are able to understand what is happening. Shall I repeat whatever that we have understood till this point? Okay, Fermi energy level, sometimes it becomes typical for the student if you don't understand it, but you are able to understand it. Fermi-Dirac distribution, which we started from, probability of finding an electron at a particular energy state E is given by 1 upon 1 plus e to the power E minus EF by kT. If E is greater than EF at 0 Kelvin, there will be no electrons, and if E is less than EF at 0 Kelvin, there will be all the electrons. Probability 0, probability 1. Okay, then we draw the diagram for intrinsic, n-type, p-type. For n-type, the Fermi energy level is near to the conduction band, and for p-type, the Fermi energy level is near to the valence band, and for intrinsic, it is somewhere in between. Then we got to know that the formula that we derived, the conclusion that we made, that was applicable only at T equals to 0 Kelvin, that above EF everything will be filled and below EF everything will be empty. That is true only for 0 Kelvin. If there is some other temperature, then I have to apply the mathematics. But another thing I get to know is that if your energy level is above EF, then at any temperature the probability cannot be greater than 1 by 2. It has to be less than 1 by 2. Why so? Why so? Because if E minus EF is positive, then positive divided by any temperature will be the value greater than 1. So 1 divided by anything greater than 2 would be less than 1 by 2. And similarly, opposite would happen that if your energy level is below EF, if your energy level is below EF, then at any temperature the probability will be greater than 1 by 2 only. All good, all fine. So this has been written, and this is also one of the conclusion. And then we draw this graph. This graph also we understood that as you keep on increasing the temperature, the probability of finding the electron at higher energy level will increase, and probability of finding the electron at lower energy level will decrease. Okay, so it is decreasing with the increasing temperature, and this is increasing with the increasing temperature. So this is what we have understood. Every single thing is crystal clear to you. Say yes or no. Let's go to the next one. So this you need to let me know, and from here we will make another conclusion. So let's see what is that conclusion. So you find out this particular thing. Probability of finding an electron at energy state E, which is delta E above the Fermi energy level. What does that mean? That means E minus EF is delta E. Energy state E, which is delta E above the Fermi energy level. So this is your Fermi energy level, and this is your energy state E, right? So this is delta E. So what will be my answer? 1 upon 1 plus e to the power delta E by kt. This is the answer, right? What is the formula? 1 upon 1 plus e to the power E minus EF by kt. E minus EF is delta E. So this is what I have written. Usually what will happen is that delta E will be given greater than or equals to 3 kt. Okay. In your examination, 100% this condition will be there. 100%. Surely I am saying that delta E will be greater than or equals to 3 kt. Answer is done. Okay, answer is done. I am just telling one separate thing. This answer is done. I am just telling one more thing. So this will be delta E would be greater than or equals to 3 kt. Let's take the worst case that delta E is equals to 3 kt. So what will be your answer? 1 upon 1 plus e to the power 3 kt by kt. So kt will get cancelled out. Your answer will be 1 upon 1 plus e to the power 3. Now go to your calculator and check the value of e to the power 3. So this e to the power 3 is much larger than 1. What I am saying, e to the power 3 will be much larger than much larger than 1. So if it is much larger than 1, then this one I can ignore, because e to the power 3 is very much larger. Now this e to the power 3 can go upward, so this will become e to the power minus 3. So what is happening here? So your final answer is coming out to be e to the power minus 3. So what is happening here? This gap, basically this particular thing will be greater than or equals to 3. That means this value will be very much larger. E to the power del E by kt will be very much larger than 1. In your examination, this condition will be 100% satisfied. What I am saying, e to the power del E by kt. Since del E is greater than or equals to 3 kt, I am taking the worst case. Then also I get to know that e to the power del E by kt is much larger than 1. That means this 1 can be ignored. So final answer is e to the power minus del E by kt. And what was your del E? Del E was, what I mean to say is that, although this point will again come into action, but still I am saying, what I am saying, it will be nearly equals to e to the power minus del E by kt. Will that be okay for you if I write down in this manner? Because this condition will be satisfied for sure. And what was your del E if you remember? Your del E was e to the power minus, del E was E minus EF. E minus EF by kt. So probability of finding an electron at a particular energy state E is given by e to the power minus E minus EF by kt. Probability of finding an electron at energy state E. Probability of finding an electron at an energy state E is approximately given by e to the power minus E minus EF by kt. Although all these points will come again, but just here I thought of explaining it, so I explained it. Because e to the power delta E by kt, this value will be very much larger, so 1 can be ignored. So e to the power minus delta E by kt, right? E to the power minus delta E by kt. So what is delta E? Delta E is E minus EF. So probability of finding an electron at energy state E will be approximately given by e to the power minus E minus EF by kt. It is known as Boltzmann approximation. Okay, you know name, you don't need to remember that it is Boltzmann approximation or whatever it is, but you just need to say that this answer is also possible. Well and good. Okay, so this is just I have written, but our answer was this much only. Now what you need to find? Probability of not finding an electron at energy state E, which is delta E below the Fermi energy level. Not finding an electron. Then what I can do? I can find the probability of finding the electron, then I can, what I mean to say is that if I find the probability of finding an electron at energy state E, which is 0.4, so what will be the probability of not finding an electron? That would be 1 minus FOV, right? So there you. So what I need to find? I need to find the probability of finding an electron, the probability of not finding an electron at energy state E, not finding an electron. So that would be equals to 1 minus probability of finding an electron at energy state E, right? So that would be equals to 1 minus 1 upon 1 plus. Now you let me know what is the scenario here. This is your E and this is your EF, right? Probability of not finding an electron at energy state E, which is delta E below the Fermi energy level, right? So what will be the value of E minus EF? Oh, sorry. Below the Fermi energy level. No, so this is the Fermi energy level and this is the energy state. So what will be the value of E minus EF? That will be minus delta E. Because EF is at higher level, no? Your energy state E is below EF, delta E below. So that means EF minus E is equals to delta E. I should write down EF minus E is equals to delta E. So E minus EF would be equals to minus delta E. So 1 upon 1 minus 1 upon 1 plus e to the power E minus EF by kt. What is the value of E minus EF? Minus delta E by kt. 1 upon 1 plus e to the power E minus EF by kt. E minus EF is minus delta E by kt. All good, all fine. Let's try to solve it. What you will get? 1 plus, or what I can do is that let's solve it. 1 plus e to the power minus delta E by kt. This I am multiplying here. Basically I am taking the LCM. I am taking the LCM, then this goes here and this goes here. Minus 1 divided by 1 plus e to the power minus delta E by kt. Okay, so what will happen? 1 to 1 will get cancelled out. So what you will be left with? This e to the power delta E by kt, in numerator and denominator, what I am doing? I am dividing by e to the power minus delta E by kt. So what I will get? 1 upon 1 plus e to the power delta E by kt. So this is the probability of not finding an electron, which is below energy state E, which is delta E below the Fermi energy level, not finding an electron. What that is coming out to be? 1 upon 1 plus e to the power delta E by kt, 1 upon 1 plus e to the power delta E by kt. So what do you understand by that? Probability of finding an electron at energy state E, which is delta E above the Fermi energy level, is equals to probability of not finding an electron at energy state E, which is delta E below the Fermi energy level. What do you understand by that? Let's just say this was your Fermi energy level, and there was an energy state E1 here, and there was an energy state E2 here. What was the gap? Let's call this as E1, this as E2. Okay, otherwise you will be getting confused. E1, okay, and this as E2, E2, E2. Yeah. So the gap between E1 and EF is delta E, and gap between EF and E2 is also delta E. So if you are saying that I am finding an electron here, that means that electron would have come from this state only, no? That means if you are saying that I am finding the electron here, that means you will not find the electron here, because EF is right in between. That means above EF if you are finding the electron, that means below EF you are not finding the electron. Are you able to understand what I am saying? EF is the imaginary Fermi energy level, which is your reference point. So above this particular point, if I am finding the electron, that means it would have surely come from here only, no? So if it is already there, that means here there is a vacancy. Vacancy means holes. Holes means not finding the electron. So above EF if you are finding, that means below EF you will not find. So probability of finding the electron above EF will be equal to probability of not finding the electron below EF. But the condition is both should be at the same level. That means it should be delta E above, it should be delta E below. It's not that, sir, this is the energy level E1, this is the energy level E2, and this is your EF. So this gap is, sir, some 1 electron volt, and sir, this gap is some 5 electron volt. So probability of finding the electron will be, if you are finding the electron here, that means you will not find the electron here. No, that is not the condition. Both should be symmetric. Above EF, everything is symmetric. So above EF if I am finding, then below EF I am not finding. This is that I have proved using the mathematics. That's it. And I hope you have understood the mathematics. What I did here was I just divided by e to the power minus delta E by kt. So this became 1, this also became 1, and 1 upon e to the power minus delta E by kt would become e to the power plus delta E by kt. All good? So above EF there is an electron, below EF there is not an electron at the same energy level. So these kind of questions are asked in the gate examination sometimes. Okay, so let's keep it here. Let's keep this diagram here, this diagram also, this diagram also. So if they are asking this question, probability of finding an electron at an energy state which is 0.05 electron volt above the Fermi energy level is given by 0.4. So what you will do, you will make the Fermi energy level above the Fermi energy level which is 0.05 electron volt above the Fermi energy level. This is your Fermi energy level, this is your energy state, let's call it E1. So here the probability is 0.4. Using this information, determine the probability of not finding an electron at energy state 0.05 electron volt below the Fermi energy level. So PE2 they are asking, not finding an electron. So what that would be? That would be 0.4 only. They could have asked they could have asked the value of finding the electron. Probability of finding the electron, that would be 0.6, because this gap is same only. So how will you solve it? How will you solve this particular question? If you don't know, if you don't remember anything, sir, this is the straightforward question is coming in front of me in the examination hall. How will I solve it, sir? So probability of finding an electron at energy level E1, that would be 1 upon 1 plus, it is E minus EF, E minus EF. Since it is 0.05 above, so here I will use the positive sign, divided by kt. So this is the value of f of E1, which is given as 0.4. Sir, what I need to find? I need to find the value of, this is my final answer. This is what I need to find. What I need to find, sir? Probability of not finding an electron at energy state E2. Sir, that would be equals to this thing, sir, and that would be equals to one plus e to the power sir, E2 is below EF. So E2 minus EF would be minus 0.05 divided by kt. So if you take this downward, or you can say I am dividing by e to the power minus 0.05 divided by kt in the numerator and denominator. So what I will be getting? I will be getting 1 upon 1 plus e to the power 0.05 divided by kt. This value is similar to 0.4 only. So sir, this answer and this answer will be the same. So this will be my answer. Probability of not finding the electron. Okay, so this is the final answer. Probability of not finding the electron at energy level or at energy state E2, which is 0.05 electron volt below the Fermi energy level. Okay, so this concept is also useful in solving the problems, but even if you don't remember this concept, then also you will be able to solve the problem by simple concept, right? Now I can draw the graph. What I am drawing? I am drawing the f of E versus, not f of E, I should not say f of E. This axis I am not telling what it is, I am just telling that this is your energy. So this graph I am saying that at a particular temperature, this is the graph of probability of finding the electron at a particular energy state E, at a particular energy state E.
So this is the graph of f of e. Then what this will be? This will be the graph of 1 minus f of e. Because if this value is 1, then this value is 0. And if this value is 0, then this value is 1. And what will be this value? This value will be simply equals to half. So this is the graph of probability of finding the electron at an energy state E, which is below EF, or it could be above EF as well. What I mean to say is that probability of finding an electron at energy state E, which is above EF by delta E amount. What I mean to say is that this is the value of E. So this is your delta E amount. Okay. Now I need to find out the probability of finding an electron which is here at energy state, which is here. This is also delta E. This is your energy state E1. This is your energy state E2. Here what we saw, here we saw that our energy state E1 was above EF and E2 was below EF. But this formula is applicable for opposite case as well. What I mean to say is that this is my EF and this is my E1 and this is my E2. Now if I know that I am having an electron here, that means this electron will not be here. What I mean to say is that both gaps are same, delta E and delta E. What I mean to say is that if I know the probability of finding an electron at energy state E1, which is delta E below the energy state EF, then I can tell you that what will be the probability of not finding an electron at energy state E2, which is delta E above the EF. Symmetricity is there, no? This is what I am saying. This graph and the other graph, it will be this graph, which is the probability of not finding an electron. So for this particular graph, for the white graph, if you are standing here, then this will be your answer. And for this, for this red graph, this will be your answer. And for this white graph, if you are standing here, then this will be your answer. So both red and white graph are giving you the same answer. Both red and white graph are giving you the same answer. One is telling about the probability of not finding the electron, and one is telling about the probability of finding the electron. One is talking about energy level E1 and one is talking about energy level E2. So E2 is below EF by delta E, E1 is above EF by delta E. So probability of finding the electron at energy level or at energy state E1, which is delta E above the EF, is equals to probability of not finding an electron at energy level E2 or at energy state E2, which is delta E below the EF. Shall I again repeat the statement? Or opposite is also true. What is the opposite? The probability of, let's talk about this particular energy level. What I am saying, let's talk about this particular energy level. This is the energy level E2, not E2, let's call it E3, and this is the energy level E4. Okay, and both are giving you the same results. Both graphs are giving you the same results. So repeat the statement. What I am saying, this is your delta E1 or delta E2. Let's call this as delta E1, and this is also your, this will be your E4. So gap between E4 and EF is also delta E2 only, and let's call this as delta E1, delta E1. So probability of not finding an electron at energy state E3, which is delta E above EF, will be equals to probability of finding the electron at energy state EF, which is delta E2 below EF. The same scenario that I explained here. That if I know above EF at a particular state there is an electron, that means below there will not be any, that there will not be any electron. And if I know that below that there is an electron, that means above that there will not be any electron. Is that clear to you or not? Very simple thing. Just I can say that the graph is like symmetry. Above a particular energy level, finding an electron, probability of finding an electron will be equals to below a particular energy level, not finding an electron. So in the statement, these lines could be written and they can ask you whether the statement is correct or not. So forget about all these concepts. You don't remember the graph. What you can do is that you can simply derive it there using this thing, using this thing.
if you don't remember the statement. I also recommend not remembering any statement. Just you should know that I have studied this kind of concept, that above EF at a particular energy level, below EF at a particular energy level, something is there, some relation is there, and that I can derive in the examination based on the given statement. So in the examination, if this statement is written, the probability of finding an electron at energy level delta E above the Fermi level is equals to probability of not finding an electron at the same energy level delta E below the Fermi level. And opposite is also true. What does that mean? The probability of not finding an electron at energy level delta E above the Fermi level is equals to the probability of finding an electron at the same energy level delta E below the Fermi energy level. So here if I apply not finding an electron, and here if I ignore this note, then also the statement will be true. So two statements could be written in the like which of the following statement is true? Statement 1, statement 2, statement 3, statement 4. So it could be MSQ, you need to mark the correct statement. Is that clear to you or not? So you will just draw the diagram. There what you will do, you will draw these two diagrams. So this diagram I will draw, this diagram I will draw, so this diagram I will draw, and in between, sir, I will make EF and EF. Then I will say that, sir, that here if electron is there, that means here electron will not be there, and if here electron is there, here electron will not be there. That's it. So probability of finding an electron which is delta E1 above the Fermi energy level, that would be, if that is something that I know, then the probability of finding an electron at energy state E2 which is delta E1 below the Fermi energy level, that would be the same. Probability of not finding the electron, finding the electron. Okay, here also finding the electron, not finding the electron. So statement and everything is clear to you, right? I don't need to explain it more. All good, all fine. Let's go to next topic, which is very, very important. Probability of finding an electron in the conduction band. Now in the conduction band, if I am saying that I am having an electron, what does that mean? I am talking about free electron. That means I am talking about the charge carrier. So what I am saying, probability of finding a charge carrier in the conduction band. Probability of finding a charge carrier in the conduction band, because when I am saying that there is an electron in the conduction band, that means that is free to move, and if that is free to move, that is known as charge carrier. So this is nothing but our charge carrier. Charge carrier. Okay. So what that would be equals to? Probability of finding an electron in the conduction band. Now you will say that, sir, this is the energy of the lowest state of the conduction band. EC is the energy of the lowest state of the conduction band. Then, sir, this energy EC1 will be slightly greater than EC, and sir, this energy will be EC2, which will be slightly greater than EC1 and slightly greater than EC, and sir, this will be EC3. So, sir, all these energies are different. There will be slight gap. Let's just say if EC is at 1 electron volt, then EC1 will be at 1.01 electron volt. This would be 1.02 electron volt, and this would be 1.03 electron volt. Because this is how the diagram is made, no? As you go upward, the energy will be increasing. But in our calculation, we will assume that all are having the same energy. Nearly they are having the same energy. So what I am writing down, for our calculation, for ease of calculation, this is something that is considered. So probability of finding an electron at energy state EC, that would be equals to probability of finding an electron in the conduction band. Is that okay for you or not? Because in the conduction band there are a lot of states, and all states are having different energy. In the conduction band there are a lot of states, all states are having different energy, but we are saying that all are having the same energy, that is EC only. That means what you will consider is that in conduction band only there is one state, that is EC. So probability of finding the electron at energy state EC will be given by 1 upon one plus e to the power EC minus EF by KT. Now what did I tell you? That, sir, this EC minus EF by KT would be greater than 3 KT. What I mean to say is that in our case that is known as non-degenerate semiconductor. So in the end of this video, I will again explain what do you mean by non-degenerate semiconductor, but I hope you already remember non-degenerate and degenerate. What do you mean by non-degenerate? That means their doping is moderate, and degenerate means doping is very high. High doping. You remember in first or second video I explained this, and here there is moderate doping. So basically what I mean to say is that this value will be very high in our case. That means EC minus EF will be sufficiently large enough. So e to the power 3 is coming, that I told here in this analysis. Here e to the power 3 would come. So if e to the power 3 is coming, that means this value will be sufficiently large. If this is sufficiently large, then you can ignore the 1. If I can ignore the 1, then this can go upward. So the similar thing I am going to write down here. Okay. So it can be approximately equals to, in our case, this is your approximation. It can be approximately equals to e to the power EC minus EF by KT. There you go. This is known as Boltzmann approximation or Boltzmann statistics. Okay. So this formula we will be using. This formula will be using, not this formula. This also I can use, but this will take more time in the calculation. So this formula we will be using. Probability of finding an electron at energy state EC, or you can say probability of finding an electron in the conduction band. That would be equals to e to the power minus EC minus EF by KT. All good, all fine. Now what we are asking? Probability of finding an hole in the valence band. So holes are made only in the valence band, right? Holes are made only in the valence band. In the valence band, if there are holes, what does that mean? That means electrons are not there. Because how the holes are made? Holes are made because electron went to the conduction band. That's why holes are made, no? Are you able to understand this point? So generation of holes is there because electrons are gone. That means what I can write down? Probability of finding a hole in the valence band is equals to probability of not finding an electron. Probability of not finding an electron in valence band. Say yes or no? And that would be equals to 1 minus probability of finding the electron in the valence band. This is the probability of finding the electron in the valence band. Probability of finding the electron in the valence band, that would be equals to 1 minus f of EV. What is f of EV? F of EV is probability of finding the electron in the valence band. Say yes or no? All good? So 1 upon 1 plus 1 minus 1 upon 1 plus e to the power EV minus EF by KT. If I solve it, what I will be getting? This will go here, this will be minus 1. Basically, I will take the LCM now, right? I will take the LCM. So e to the 1 plus, what I will be getting? 1 plus e to the power EV minus EF by KT minus 1 divided by 1 plus EF minus EF by KT. So this and this will get cancelled out. What you are left with? So basically 1 and 1 is getting cancelled out, so I am just removing it from here. I am just removing it from here. Okay. So what I can do now? I can divide by the same in the upward side and in the downward side. So if I divide by this particular thing, e to the power EV minus EF by KT, so what I will be getting? 1 here divided by e to the power EV minus EF by KT divided by e to the power EV minus EF by KT, that would also be 1 plus e to the power, what will happen to this particular thing? 1 is divided by e to the power EV minus EF by KT. So what you will be getting? Minus EV minus EF by KT. Okay. All good. Now you know that where will be your Fermi energy level? Fermi energy level will be above the valence band. If you go to the second page, I told you for the semiconductor, for the p-type semiconductor or n-type semiconductor or intrinsic semiconductor, whatever you take, basically the Fermi energy level is between the conduction band and valence band. For any semiconductor, the Fermi energy level will be between the conduction band and valence band. Right? In our calculation, it will always be between conduction band and valence band. So it will always be between somewhere between conduction band and valence band. That means it will be somewhere here, because if this is your valence band, then this will be your conduction band. So Fermi energy level will be somewhere here. So EV minus EF will be negative. EV minus EF will be negative. Say yes or no? EV minus EF will be negative because EV is at lower energy level, EF is at higher energy level. So E minus negative. So what it has become? E positive divided by kT. And I told you this positive value will be greater than 3 kT. What I mean to say is that simply EF minus EV will be greater than or equals to 3 kT. Here also I will write down the same thing. What I will write down? That I know that EC minus EF will be greater than or equals to 3 kT in our calculation for sure. And similarly here as well, who will be at the higher level? Who will be at the higher level? EF will be at the higher level. So here also I can write down that EF minus EV, not here, I should write down here. Here I am putting it out that EF will be at higher energy level. So EF minus EV will be greater than or equals to 3 kT. That means this gap will be greater than or equals to 3 kT. Okay, fine. So this value will be negative. Basically minus EV minus EF by kT is written. So can I write it down in this manner? EF minus EV by kT. EF minus EV by kT. Because already there was a negative sign. When I took it downward, there was already a negative sign. So that negative sign I have taken inside. So EV minus EF minus EV by kT I can write down. Do you agree to this point? Right? How it came? You will agree to this point. Now EF minus EV is greater than 3 kT. Then what I can do? One I can ignore. Then what will happen is that probability of not finding an electron in the valence band is coming out to be what I am saying. Probability of not finding an electron in the valence band or probability of finding an hole in the valence band is coming out to be, this part will go upward. So e to the power minus EF minus EV by kT. Don't worry, I will tell you a trick to remember the formula. Don't worry about that. You don't need to worry about anything. I will surely tell you the trick to remember. So probability of finding a hole, probability of finding a hole in the valence band is given by e to the power, approximately it is given by e to the power EF minus e to the power minus EF minus EV by kT. So two formula we have got, this formula and this formula. One was probability of finding the electron in conduction band. Probability of finding the electron in the conduction band. So roughly I am writing down e to the power something was there, and probability of finding the holes. This was for the electron and this was for the hole in valence band. That was e to the power something. So always you need to remember e to the power minus will come. Now here divided by kT would come and here divided by kT would come. The confusion will be here, sir. EC minus EF or EF minus EC. Just think about it. This is your EC. Where will be your EF? And this is your EV. EF will be somewhere between EF and EV. So EC will be greater than EF, no? EC will be greater than EF. And let's just say if I write down a negative value here. If I write down a negative value here. So what it will become? E to the power positive divided by kT. E to the power positive. That would be e to the power positive divided by kT. That would be greater than 1. That means probability of finding the hole is greater than 1. Probability is greater than 1. Is it possible? No. That means what you will do, e to the power minus, then something inside will be positive only, sir. Something inside will be positive only. Now what will be positive? EC is at the higher level than EF. So EC minus EF. EF is the higher level than EV. So EF minus EV. So you can see the formula. E to the power minus EF minus EV by kT. So what you will do, sir, e to the power minus, then which is at the higher level? EF is at the higher level. So EF minus EV by kT. Sir, e to the power minus, which is at the higher level? Sir, EC is at the higher level. So EC minus EF by kT. Will you be able to write it down? Probability of finding an electron in the conduction band is given by this. Probability of finding electron in the conduction band is given by this, and probability of finding a hole in the valence band is given by this. Probability of finding a hole in the valence band is given by this. E to the power minus EF minus EV by kT. All good, all fine. Everything is crystal clear to you. Okay. Now there is something called effective density of states. So you can see here
What did I tell you in the first lecture? As you go higher in the conduction band, the density of the state increases. That means here the states will be very near and here the states will be very far away. So basically in the conduction band these many states are there, right? But here the density is more. Basically if I cover the distance of, if I cover a volume of 1 centimeter cube, then here I am getting 4 state, but if I cover the volume of 1 centimeter cube, here I am getting only 3 state. So here the density of state is more, here the density of state is less. But total I know that total 7 states are there. So what they did, they made something called effective density of states. Effective density of states. That means effectively I am telling that in the conduction band these many states are there. What I mean to say is that as you go higher in the conduction band, the density of the state will increase. That means at the higher level more states will be there, at lower level there will be lesser state. Similar thing happen in the valence band as well. As you go lower in the valence band, the density of state increases. As you go lower in the valence band, the density of the state increases. That means here in 1 centimeter cube you are getting more states, and here in 1 centimeter cube you are getting lesser state. So I need to define some effective number that effectively these many states are there per unit volume. So what you can say, sir, 7 states are there in 2 centimeter cube. So you can say that, sir, effectively I am having 3.5 states in per centimeter cube. 3 was there in 1 centimeter cube, 4 was there in 1 centimeter cube. So effectively you find out some average value. This is not how it is calculated. I am just telling the way to understand that what is the meaning of effective density of state. So in the conduction band, as you move upward, the density of the state will increase, and in the valence band, as you move downward, the density of states will increase. So there is something called effective density of states. So that will be a fixed number that they will be giving 2 into 10 to the power 20 centimeter cube inverse. That is the value of effective density of states in the conduction band, and that is shown by NC. So effective density of states in the conduction band is given by NC, that is equal to 2 into 10 to the power 20 centimeter cube inverse. That means you will say that in the conduction band these many states are there. Okay, and similar thing can happen for valence band as well. Okay, all good, all fine. So this is what is written, effective density of states. No need to worry about that too much. Just you need to understand that it is like the number of floors available. So number of rooms available or floor you can say, because these are the states only, no? These are all the states. So number of rooms available. That is your effective density of states. That's it. So as you move higher in the conduction band, the density of the states increases. As you move lower in the valence band, the density of state also increases. To simplify the calculation, we define effective density of states, which represents the total number of energy state per unit volume in the conduction band or valence band that are effectively available for the electrons and holes to occupy. It essentially tells us how many electrons can occupy the conduction band and how many holes can occupy the valence band at a given temperature. That means for the electrons to occupy, these many floors are available, and for the holes to occupy, these many floors are available. So you understood the complete theory that has been written. Okay, so effective density of states for the conduction band, in the conduction band is shown by NC, and effective density of states in the valence band is shown by NB. Conduction band is always related to electrons and valence band is always related to holes. Electron means free electrons, and this is related to holes, right? So this NC is proportional to effective mass of electrons to the power 3 by 2 and temperature to the power 3 by 2. So collectively what I can write down? Collectively I can write down that NC is proportional to effective mass of electron multiply with temperature to the power 3 by 2. You need to remember it, not very tough to remember. Okay, the density of states in the conduction band is proportional to effective mass of electron to the power 3 by 2 and temperature to the power 3 by 2. And what about the holes? Sorry, what about the density of states in the valence band? So NV will be proportional to, when I say valence band, it is related with holes. Here I am writing down N, so here I will write down P to the power 3 by 2, temperature to the power 3 by 2. So NV is collectively proportional to mp to the mp star into T to the power 3 by 2. So mass, effective mass and temperature, power 3 by 2. I don't think it is very tough to remember. I hope it will be easy for you to remember. So collectively what I can write down, Nc is equals to, if I remove the proportionality sign, what I will get, Nc naught Mn star T to the power 3 by 2. And Nv will be equals to Nv naught, if I remove the proportionality sign, then Mp star T to the power 3 by 2. So this you will be able to remember, say yes or no. Nc is equals to Nc naught Mn star T to the power 3 by 2. Nv equals to Mv naught Mp star T to the power 3 by 2. Okay, very simple. The density of state in the conduction band is proportional to Mn star to the power 3 by 2 and temperature to the power 3 by 2. Density of state in the valence band is proportional to effective mass of holes to the power 3 by 2 and temperature to the power 3 by 2. All good? All fine? Let's solve a mathematics question. This question is of mathematics. Okay. In an apartment there are 100 rooms. In an apartment there are 100 rooms. Finding the probability of finding a person in a given room is 0.3. How many total people are expected to be in the apartment? Total number of people. Total number of people. What they are saying, 100 rooms are there. Let's take 10 rooms only. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Probability of finding a guy in a room is 0.3. So a room will be occupied with the person. What is that probability? That probability is 0.3. So there are total 100 rooms. In one room, it is probability that 0.3 guy could be existing. So in 100 rooms, how many guys could be existing? 30 guys. Very simple thing, no? 100 into 0.3. Why you took mathematics, sir? Because of this. What we need to find? We need to find the total number of electrons or holes per unit volume in a semiconductor. Any random semiconductor, it could be intrinsic, it could be extrinsic, it could be n-type, p-type, whatever it is. So whenever I say electrons, that means I mean free electrons, and whenever I say holes, that means it is holes only. And electrons are found in the conduction band and holes are found in the valence band. The effective density of states in the conduction band is given by Nc. The effective density of states in the valence band is given by Nv. Probability of finding the electron in the conduction band is given by f of Ec. Probability of finding an electron in the conduction band is given by f of Ec. And probability of not finding an electron, or you can say probability of finding a hole in the valence band, is given by 1 minus f of Ev. Okay, so this is what is written. Given that effective density of states of conduction band is Nc, effective and valence band is Nv, the probability of finding an electron in the conduction band is f of Ec, and probability of finding a hole in the valence band is 1 minus f of Ev. So there are total Nc rooms available. There are total Nc rooms available. The probability of finding an electron on one room that is having an energy of Ec, that probability is f of Ec. That probability is f of Ec. So what will be the probability of, what will be the total number of electrons? Again, just try to relate this particular thing with this example. There are Nc rooms available. On one room, finding the electron probability is f of Ec. That means how many total number of electrons would be there? So that number of electrons would be Nc into f of Ec. Say yes or no? Are you able to understand this point or not? There are total Nc rooms available. In these Nc rooms, there are different energy levels. There are different energy states. If this is having an energy of Ec, what I am saying is that if this is having an energy of Ec, then this will have energy of Ec1, Ec2, Ec3. But what we are assuming is that all are having the same energy. So probability of finding an electron in Nc, probability of finding an electron in Ec room is something that is known as f of Ec, and total
like this only total how many rooms are available? NC rooms are available. So how many total number of electrons would be there? NC into F of EC. Are you able to relate with this particular example? Surely you are able to relate, right? So total number of electrons per unit volume will be, this will also be mentioned in per unit volume, okay? This will also be mentioned in per unit volume. So they will also have the unit of centimeter cube inverse, centimeter cube inverse. So per unit volume, these many rooms are available. In one room, finding an electron probability is F of EC. So what will be the total number of electrons? That will be NC into F of EC. So that would be equals to NC. Now F of EC you need to write down. How will you write down? Sir, I know that e to the power minus. Now who will be at the higher level? Sir, EC will be at the higher level. Now you go to any course, anywhere you go, read any textbook. The derivation of this particular formula is very, very complex. You would see they would do some integration, this thing they will introduce, that thing they will introduce, they will spend 2 hours, and there they will have to write down that using higher order mathematics you will get the final expression. But everything we ignored. Just we build our intuition. Just we understood that how we can write down this formula. Just by pure intuition we are doing it. How I started? I started with F of EC. You did not even know, sir, what we are doing here. Why you are finding the probability of finding an electron in the conduction band. Then you find out the probability of finding a hole in the valence band. Sir, I don't know why you are doing so. Then sir, suddenly you told about effective density of state, and suddenly sir you took a mathematical problem. Now all these 4 slides combined, everything is making sense here. I could have directly written down this formula, or I could have used higher order mathematics, and there I would have said that you need to understand this mathematics on your own and then get the final answer. But now you have understood the flow, right? Effective density of states in the conduction band and in the valence band. Probability of finding a electron in the conduction band is F of EC. Probability of finding a hole in the valence band will be 1 minus F of EV. So here what I will write down, total number of states available are N of V. In one state, probability of finding a hole is 1 minus F of EV. So total number of holes per unit volume will be NV into this value we already know. Probability of finding holes. Sir, what I will write down, sir, e to the power minus. Sir, what I need to write down, positive value. So EF is at the higher level than EV. So EF minus EV by KT. There you go. Okay, you understood this slide in a very good manner. So let's write down the summary of the formula that we have understood till now. So you don't need to remember anything from the previous analysis that we have done. Just these 5 formula you need to remember and your job will be done. Just only these 5 formula. Okay. So probability of finding an electron at energy state E is given by 1 upon one plus e to the power E minus EF by KT. And I know that in our case it will be approximately equals to this thing, right? Now what is this? Probability of finding an electron in the conduction band. Probability of finding electron in conduction band, that is given by e to the power, yeah, so how will you write down? E to the power minus, now sir, EC is at the higher level or EF? EC is at the higher level, so EC minus EF by KT. And here I will write down probability of finding hole in valence band. So that would be equals to e to the power minus, sir, who is at the high level? EF is at the high level. So EF minus EV by KT. Total number of electrons, total number of holes. So NC into this probability, e to the power, sir, EC at the higher level, EC minus EF by KT. And here NV e to the power, sir, EF is at the higher level, EF minus EV by KT. Okay. Sir, NC is equals to NC naught Mn star T to the power
3 by 2. Sir, NV is equals to NV naught MP star T to the power 3 by 2. That's it. This is the only formula you need to remember, and you will be able to solve all the problems. 99.95% of the problems you will be able to solve from these formula only. That's it. And people feel that, sir, in this topic there are a lot of formula. Do you really think that any formula you need to mug up? No. Anything you need to mug up? No. Every single thing in EDC I am explaining with pure intuition. Along with that, there are formulas as well. With the formula as well, you can understand. So do you really think that I need to mug up any single thing? And you watch other series, and you watch other notes, you watch other lectures, and how people apply the formula. This formula came, this question came, this formula you apply. No. We will understand the meaning, and this is the meaning, right? Okay. Here NC note. Now what we will find out? We will find out the position of Fermi level for intrinsic semiconductor, for N-type semiconductor, and for P-type semiconductor. So for intrinsic semiconductor, there is a specific name of the Fermi level that is known as intrinsic Fermi level. Okay, there is a specific name of the Fermi level that is known as intrinsic Fermi level. So for the intrinsic semiconductor, whatever the Fermi level that you are getting, this is the conduction band, this is the valence band, and somewhere here you will get the Fermi level that is known as intrinsic Fermi level. Okay, so we will find out its position. So for intrinsic semiconductor, what do you know? N is equals to P is equals to Ni. Number of electrons is equals to number of holes is equals to intrinsic carrier concentration. So Ni, let's ignore it as of now. N equals to P I need to put. What I need to put? N equals to P. So what is N? Nc multiply with e to the power, sir, here positive number should come. That is equals to Nv e to the power, sir, here also. Sir, here also positive number should come. Right? Now what I am doing is that this Nv I am taking here, and this part I am taking here. So Nc by Nv I am getting here. Here what you are getting? Ev minus Ef. This is your Ev minus Ef by kT divided by e to the power Ef minus Ec by kT. Right? Now what can happen is that this part can go upward. So e to the power Ev minus, this part is going upward. So this is positive, so this became negative. So Ev minus 2Ef minus plus Ec divided by kT. Did you understand this part? Right? E to the power Ev minus 2Vf plus Ec divided by kT. This part is going here. Simple mathematics, nothing else. You should be doing it on your own. Okay. So now e to the power, this e to the power something, this e goes here. So what it will become? It will become ln. So ln Nc by Nv is equals to Ec plus Ev, and this kT, if ln goes here, then what it will become? Ec plus Ev minus 2Ef divided by kT. So I am directly multiplying this kT here. Okay, I am directly multiplying this kT here. So now 2Ef goes here, 2Ef goes here, and in place of Ef what I can put? Intrinsic Fermi level, because we are finding it for intrinsic carrier concentration, right? Sorry, intrinsic semiconductor. So here I can put EFI. So 2EFI is equals to EC plus EV minus KT ln NC by NV. So what you are getting? EFI is equals to, let's write it down on the next page. EFI is equals to EC plus EV by 2 minus KT by 2 ln NC by NV. This formula we have got. Again, the only formula I am asking you to remember, which is this. Okay, what I am asking you to remember? EFI is equal to EC plus EV by 2 minus KT by 2 ln NC by NV. What do you understand? Let us say, sir, this is EC, and sir, this is EV. This is EC, and sir, this is EV. Let us say this is at a 3 electron volt. and this is at 4 electron volt, and this is at 1 electron volt. So what will be the mid value of this? What will be the right mid, like right in between? What will be the mid value? Sir, 4 plus 1 divided by 2. That would be, sir, 2.5. So this will be the mid value. That means, sir, EC plus EV divided by 2, because 2.5 above 1, this gap is 1.5 and this gap is also 1.5, because 4 minus 2.5 is also 1.5. So this is the midpoint. So what is the midpoint? Sir, midpoint is EC plus EV by 2. So this is the midpoint. So this is known as E mid gap energy. This is known as E mid gap minus KT by 2 ln NC by NV. So sometimes what they can ask in the questions that in your intrinsic semiconductor, how much your Fermi energy level is far away from mid gap. Like basically, what is the gap between the mid gap and intrinsic Fermi level? That would be equals to KT by 2 ln NC by NV. So this formula you need to remember: EC plus EV by 2 minus KT by 2 ln NC by NV. Now special cases we can take, or by default cases also we can take, like case 1, which is known as by default as well. By default means if NC and NV are not mentioned. Okay, so case 1 is NC equals to NV, or what you can say, or I can say that Mn star is equals to Mp star, because if NC is equals to NV, what does that mean? That means that sir, Mn star no, this will have different constant, no, NC node, and this will have different constant. What I was about to say is that, sir, this thing would be there, no, Mp star. So I would say temperature and temperature will get cancelled out, and but this constant could be different, Mn star, Mp star. So if NC and NV are equal, then Mn star would be equal to Mp star, but not necessary, because this constant could be different. So either this condition is given or this condition is given. If this condition is given or this condition is given or this condition is given, then what you will do? Look, if this condition is also given, no, then also you will consider that, sir, these constants are equal only. Basically, either they will not mention NC and V. If they will mention, they will not, those will not be equal. What I mean to say is that in the questions, what will happen is that NC and V, either it will not even be mentioned, NC and V will not even be mentioned. If it is not mentioned, you will take NC equals to NV. That's it. And if it is mentioned, they will not be equal. Then you will have to find out the value. But if both are equal or not even mentioned, or not mentioned, then what you will do? Sir, my Fermi energy level will be right in between. So your intrinsic Fermi level most probably will be in between only. Is that okay for you? Okay. Well and good. And now what if Mn star and Mp star are mentioned? What I am saying, case 2, Mn star and Mp star are given. So sir, your EFI would be equals to EC plus EV by 2 minus KT by 2 ln. Sir, this NC would be equals to, sir, NC naught Mn star T to the power 3 by 2. And sir, this NV will be equals to NV naught Mp star T to the power 3 by 2. So temperature would be same. This also I will have to consider same only, because constant value they are not mentioning, same only. Okay, this is also gone. What I am left with? Mn star and Np star to the power 3 by 2. So Mn star divided by Mp star to the power 3 by 2, right? So what you are getting from here? From here, what you are getting? EFI is equals to EC plus EV by 2 minus KT by minus 3 KT by 4 ln Mn star divided by Mp star. EC plus EV by 2 minus 3 KT by 4 ln MP star divided by MP star. So do you really think that you need to mug up this formula? No, you are not mugging up the formula. Only formula that you are remembering is EC plus EV by 2. That means most probably it should be in the mid gap. But if NC and V are not mentioned, then the formula will be mid gap minus KT by 2 ln NC by NV. There is only this formula which is having KT by 2. Otherwise, all the formula will have simply KT. Only one formula is having KT by 2. Okay, so EC plus EV by 2 minus KT by 2 ln NC by NV. Not very tough to remember. Say yes or no, right? So how I can show it? So this will be your conduction band, and this will be your valence band, and somewhere in between you will get your Fermi energy level. अरे यार क्या कर रहा हूँ मैं? Conduction band, valence band. So by default I will consider that it is right in between, right in the middle. It is right in the middle. By default I will consider this. This is your EFI. And one thing you know, what do you know? That MP star is usually more than the Mn star. Right? What I am saying? MP star, effective mass of holes, is more than the effective mass of electron. Usually, not always, usually this is the scenario, no? That effective mass of holes will be more than the effective mass of electrons. So this value will be more. Usually, again in the question anything could be given. So if this value will be more, so ln, let's just say 1 by 2, ln 1 by 2 will be negative. So this value will be negative. So eventually this sign will become positive. Are you able to understand what I am saying? We will solve with respect to question. With respect to question you will be able to solve. But if you are just able to visualize it, then MP star would be more. If it is more, let's just say it is 1 by 2, then ln 1 by 2 will be a negative value. So this will become positive. That means in the mid gap, something is being added. In the mid gap, there is something that is being added. That means Fermi level will go above the mid gap. So Fermi level in the intrinsic semiconductor as well will be more nearer to the conduction band than the valence band. Usually, it is the usual case. But ideally what we will take, it is right in between, because we will take that NC equals to NV. Say yes or no? Okay. So ideally we will take NC equals to NV, but usually what happens is that effective mass of holes are more than the effective mass of electrons. Then this scenario can come into action. But from this slide, what is the conclusion that you have made? N is equals to P is equals to Ni. Then from there we derive this very simple derivation. The intrinsic Fermi level is coming out to be EC plus EV divided by 2 minus KT by 2 ln NC by NV. So you expected it to be right in between. It is coming in between only, but some offset is there. You can call it offset. That means it will be either above the middle gap or it will be either below the mid gap. So that offset is KT by 2 ln NC by NV. There is a negative sign. Don't forget this negative sign. Then you can put down this formula and you can get this value. Okay. So this was about our intrinsic semiconductor. In the intrinsic semiconductor, the Fermi level is in between the conduction band and valence band. Let's go to our N-type semiconductor. So Fermi level of N-type semiconductor is known as EFN. Okay, Fermi level of N-type semiconductor will be known as EFN. So in N-type semiconductor, what is the number of electrons you are having? E to the power EC minus EF by KT. But since we are talking about N-type semiconductor, so I am putting EFN by KT. Okay. So what you will be getting? This NC I can take here, and then I can take ln. So what I can see here is that ln NC by N is equals to EC minus EFN. Did you understand what I did here? No. N by NC, right? And this e to the power goes here, so this become L. Then this KT, then here what will be the scenario? Minus of EC minus EFN by KT. Then this KT can come here, this KT can come here. So this KT is coming here. Then this negative sign I can take this side, this negative sign I can take this side. Is that okay for you? This is like minus 1. So it can go as ln to the power minus 1. Basically, ln A is equals to minus ln 1 by E. Do you agree to this point? So if I need to erase this negative sign, whatever the negative sign is there, if I need to erase this negative sign, what I need to do? NC by N, right? So EC minus EFN will be equals to KT ln
Nc by n. So when I am doping, I will make sure that the number of electrons, when I am doping, I will make sure that number of electrons never go above the effective density of states. Why is that so? Because if this value goes above, let's just say this value was 4 and below value was 8. So what you are getting? ln 4 by 8, that would be ln 1 by 2. That is equals to minus ln 2. So this value will come out to be negative. If this value is coming out to be negative, what does that mean? That means EFN is at the higher level and EC is at the lower level. So always we will make sure while doping that NC will be greater than N. If NC is greater than N, then what will happen? This value will be positive. That means this gap will always be positive. So what do you understand? What do you understand? This was my conduction band. This was my valence band. Conduction band and valence band. So where will be your Fermi level? That would be near to the conduction band. Why so? Why is that so? Because if you increase the doping, if I increase the doping, then what will happen? Number of electrons will increase. This value will increase. If this value increases, if n increases, then this whole value decreases. If n increases, this whole value decreases. If this whole value decreases, then ln value also decreases. This whole value decreases. And if this whole value decreases, then this whole value decreases. That means EC minus EFN decreases. So more doping means lesser gap between conduction band and Fermi energy level. What I am saying? More doping means this value increases, so this value decreases. If this decreases, then this decreases, and then whole value decreases. So more doping, more donor atoms means this value is lesser. That means this gap is lesser. So more doping means you are moving more towards the conduction band. That means the gap between the conduction band and the Fermi energy level is lesser. So what do you understand here? Let's just say if this is my doping of ND1, this is my doping of ND1, then this is my Fermi energy level. And if my Fermi energy level is here for the doping of ND2, then which doping will be higher? ND1 or ND2? ND2 will be higher, because higher doping means your Fermi energy level is near to the conduction band in case of n-type semiconductor. So in case of n-type semiconductor, you get the Fermi energy level near to the conduction band. It is not in the middle. It is near to the conduction band and it is far away from the valence band. All good? All fine? So this is the formula of EC minus EFN. The same formula you can get from the value of P as well, value of holes as well. Because in the n-type semiconductor, it's not that only electrons will be there. Holes will also be there, no? Holes will also be there. So P is equals to NV e to the power minus EV minus, not EV, EFN minus EV by KT. Say yes or no? Do you agree to this formula? P is equals to NV e to the power, here positive value I need to write down. But here the Fermi energy level we are putting as EFN. So if you solve it, what you are getting? EFN minus EV, that would be equals to KT ln NV by KT ln NV by P. So let's just say in the examination, they are talking about n-type semiconductor, okay? What they are talking about? They are talking about n-type semiconductor, and in the question they have mentioned the effective density of valence band. Then this formula you will apply. If effective density of conduction band is available, then this formula you will apply. This value you can find out on your own by using the mass action law. So what did you understand? That sir, this value is coming out to be KT ln NC by N, and sir, this value is coming out to be KT ln NC by P. Do you need to remember any of the formula? No. Not a single formula you need to remember. Okay? No formula you need to remember. It will not be used to find out anything. So don't worry about that. Are you able to understand this point? This is just these formula are given in the textbook. That's why I wrote it down. Let's just say in the worst case in the examination they are saying that which of the formula is correct. Then can you derive it in one step only? You know that what will be the number of electrons? What will be the number of holes? In n-type, the number of electrons are more than the number of holes. That's why we focus on number of electrons. So in the examination, 99% chances are there that they will give the conduction band effective density of states. They will give the effective density of states for the conduction band. 99% chances are there. Okay. But in the worst case, for the n-type semiconductor, if they are giving the effective density of the states for the valence band, then you can apply this formula. Do you need to remember any of the formula? No. Okay, because we can derive it within the seconds. Let us say NC value is given and number of electrons you already know. Then can you find out this value? Yes. So rather than applying this formula, I will apply this formula there. NC value I will put, N value I will put, then I can do the calculation. So no formula you need to remember. All good? Okay, fine. So in n-type semiconductor, the electron concentration N is much greater than the hole concentration P. So N is greater than NP. Because of this, energy gap between the conduction band and the Fermi level is much smaller than the gap between the valence band and the Fermi level. Consequently, the Fermi level in n-type semiconductor lies closer to the conduction band than the valence band. So what they are saying, the energy gap between conduction band and the Fermi level is much smaller than the gap between valence band and the Fermi level. So this gap will be more and this gap will be lesser. And why this gap will be more? Because P value will be less, no? If I am saying that NC and V are same, if P value is less in n-type semiconductor, P value is less, that means this overall value is more, that means this overall value is more, that means this overall value is more. So the gap between EFN and EV will be more and the gap between EC and EFN will be lesser because this value is more. If this value is more, then this total value is less, then this value is less, then this whole value is less. So gap between EC and EFN will be lesser. So the conduction band the Fermi level will be near to the conduction band and far away from the valence band. The thing that we did on the second page here, this thing I am proving for any random temperature now. Any random temperature, for any random temperature you can see the condition. Okay, I don't need to draw the diagram here because previously I have already done. So formula, do you need to mug it up? No, don't mug up the formula. You can derive it any day. But yeah, just remember this particular thing. Let's go to the p-type semiconductor. No, first I need to see the position of Fermi level in n-type semiconductor relative to the intrinsic Fermi level. What does that mean? That means that previously you were having a semiconductor. It was intrinsic. When it was intrinsic, at that time this was your Fermi energy level, right in between, right in the middle. Now when it became n-type, that means you started doping it, then it became n-type, then your Fermi level reached here. So how much this Fermi level has moved to EFN. Previously it was EFI, then it has moved to EFN. So how much it moved? This is what we are calculating. So in the examination, sometimes what they can ask, find out the energy gap between the Fermi energy level of n-type semiconductor to the intrinsic Fermi level. So basically this gap we need to find out. When it was intrinsic, this was your Fermi energy level. When it became extrinsic, when it became n-type, then this is the scenario. So what is the gap between EFN and EFI? So that we need to find out, but we will find it out after a break because I have been recording for a very long time. I need to take a break now. Okay, so we will find it out after a break. You can try doing it on your own. Which formula you need to apply? Think about it. 4 formula we are having. These 4 formulas we are having. Mostly more important are these 2 only. But yeah, think about it. Which formula will you apply and get the answer? Okay. Let me take a break and then I will come back. Yeah, so did you try finding out the expression? So what we will do for n-type semiconductor, what is the number of electrons for n-type semiconductor? What could be my number of electrons? That would be equals to Nc e to the power minus Ec minus, here what I will write down? EFN, because I am talking about n-type semiconductor. So EFN by kT. Basically in my answer I need to introduce EFN and EFI. My target is to find out the difference between EFN minus EFI. This is my target. How can I introduce EFI? By talking about intrinsic semiconductor, right? For intrinsic semiconductor, what will be the scenario? In intrinsic semiconductor, number of electrons is equal to number of holes, that is equal to Ni. But I will be talking about number of electrons only. So here I will not put N because people will be getting confused. This N is this N is equal to Ni. But this N is of n-type semiconductor and this N is of intrinsic semiconductor. So when it was intrinsic semiconductor,
when my semiconductor was intrinsic, at that time where was my Fermi level? At that time what was the number of electrons? This is a different case. And when it became n type, then what was the number of electrons? This is a different case, right? So Ni is equals to Nc e to the power minus Ec. Here what I will write down? EFI by Kt. Okay. So if I divide equation 1 with 2, what I will be getting? So you can do the division, or shall I do it? I guess you can do everything on your own now. You are getting n by Ni. That would be equals to e to the power minus Ec will be getting out. So basically you will see EFN minus EFI by Kt. This is what you will be getting. Okay, n by Ni is equals to whatever it is, you don't need to remember it. Then what the final answer we are getting? EFN minus EFI is equals to Kt ln n by Ni. So this answer you will remember. Okay. So again, one more thing I am asking you to remember, EFN minus EFI. If I am asking you to remember something, then I will surely tell you a trick. So what will be the trick? This gap I need to tell, right? This gap I need to tell. With respect to the conduction band, which quantity is associated? Effective density of states. Effective density of states for the conduction band. Effective density of states for the valence band, right? Here EFN. EFN means I am talking about n-type semiconductor. In n-type semiconductor, who is the majority? Number of electrons. And when I talk about intrinsic semiconductor, so there who is the majority? Majority, minority, both are the same, and that is equals to Ni. So with EC, Nc is associated, with EV, Nv is associated, with EFN, N is associated, and with EFI, Ni is associated. Okay, so these are the associations. What formula I need to write down? I need to write down the formula between EFN and EFI. Difference between EFN minus EFI. That would be equals to, sir, Kt would come, Ln would come. Now the problem would be that, sir, on upward side should I write N or Ni? Because with EFN who is associated? N. With EFI who is associated? Ni. So N by Ni would come, or Ni by N would come. Now you know that value of N will be greater than Ni. What I know, N will be greater than Ni. And I know that this difference will be positive because EFN will be at higher level. So what will be the answer? N by Ni. There you go. Did you understand what I did here? EFN minus EFI. I need to remember Kt Ln would come. Because how do I remember? Formula of, what was the formula of EFI? EC plus mid gap minus Kt by 2 Ln. So Kt Ln I can remember. Minus Kt by 2 Ln Nc by Nv. So Kt Ln I can remember. So sir, Kt Ln would come. Now with EFN, N is associated. With EFI, Ni is associated. So Kt Ln N by Ni. Right? This is how I can find it out. So this formula only I am asking you to remember. These formula that we derived here, these you don't need to remember. You will simply solve by this equation. This equation you are already remembering. But what may happen is that sometimes they can ask the difference between EFN and EFI. So either you derive in this manner or you just remember it. I have told you the way to remember as well. So only whichever that are necessary, those only I will ask you to remember. So here you can write down remember. Remember. But this you don't need to remember. These all things you don't need to remember. Okay. So Kt Ln N by Ni. So similarly, all kind of formula will be there for the p-type semiconductor as well. In p-type semiconductor, where will be your where will be your Fermi energy level? Your Fermi energy level will be near to the valence band, right? So for p-type semiconductor, number of holes are given as total density of the effective density of the states for valence band. Effective density of the states for valence band multiply with probability of finding a hole in the valence band. Probability of finding a hole in the valence band, that is equals to e to the power, sir, minus here some positive value will come. So EFP is at the higher level than EV. So EFP minus EV by Kt. So what will be the answer you will be getting? EFP minus EV. This you can do on your own. Kt Ln Nv by P. This is the answer you will be getting. Similarly, the same formula you can derive with respect to EC as well. What I mean to say is that N will be equals to Nc e to the power, some positive value would come. So sir, EC is at the higher level than EFP. I am talking about p-type semiconductor. That's why I am putting down EFP. So from here, what will be the value of EC minus EFP? That would come out to be KT ln NC by N. But rarely these formulas will be used, so you don't need to remember these formulas. Which formula you need to remember? You need to remember the formula of difference between these two guys. Difference between the intrinsic Fermi level and the p-type semiconductor and the p-type Fermi level. Intrinsic Fermi level and p-type Fermi level. What will be the formula? What do you think? Which is the quantity associated with EFI? That is Ni. And which is the quantity that is associated with EFP? That means p-type semiconductor. In p-type semiconductor, who are the majority? Holes are the majority. And one thing I know that P will be greater than Ni. So what do you think? What should be the formula? KT ln. I am writing down the formula of EFI minus EFP. Now who is at the higher level? EFI is at the higher level. That means EFI minus EFP will be positive. So KT ln higher value divided by the lower value. So KT ln, which value will be higher? Number of holes will be higher. So EFI minus EFP. You can derive it with this derivation as well, but directly I have written the formula. How did I write it down formula? How did I write it down this formula? That also is clear to you. Okay. How did I derive it? What I will do? This P expression I will write down NV e to the power minus EFN minus EV divided by KT, and then NI expression I will write down NV e to the power minus EFI minus EV by KT. Right? So from there I will divide and both of them, then I will get this formula. Only thing you need to remember this formula, and how will you remember that also I have told. That also I have told. How will you remember? Sir, KT ln, I know that the gap will be positive because EFI will be at the higher level. So higher concentration divided by the lower concentration, because P value will be greater than Ni. All good? So this is the formula that we need to see. So as of now, which all formula you need to revise? These formula you need to remember. Not too much formula. Okay, this formula you need to remember. Then nothing here you need to remember. Then this formula you need to remember. Okay. Then nothing here you need to remember. Then this formula you need to remember. Okay. And this formula you need to remember. Not much stress, right? Not stress at all. Sir, if I don't need to remember these formula, then why did you derive it? That means in the examination or in some notes or in some textbook, if you find out these formula written, then at least you should know that what is happening. Like, have we ever studied this formula? Yes, we have studied those formulas. If any day in the further lecture I use this formula to explain some other concept, because I will be explaining the concept of quasi-Fermi level. So there I will use this formula again. Okay. So there I will tell you that we derived those formula just for the understanding purpose. So in the examination, for solving the problems, it will not be used. For understanding a particular concept, it will be used. That's why we are deriving it here. Okay. Now we have studied Ni square equals to A naught T to the power 3 e to the power minus Eg by Kt. And I told you I will give you the derivation of it. So let's see the derivation. Okay. So what is the value of N for intrinsic semiconductor? This is the concentration of a intrinsic semiconductor. So this is your intrinsic carrier concentration. So for intrinsic semiconductor, you know that N will be equals to, forget about intrinsic semiconductor, for any semiconductor, for any kind of a semiconductor, what do you know? For any kind of semiconductor, mass action law will be valid under thermal equilibrium. Mass action law will be valid under thermal equilibrium. So number of electrons will be equals to number of electrons multiplied with number of holes will be equals to Ni square. So N into P is equals to Ni square, that I know, right? So what I am putting, again I am putting N into P equals to Ni square. What is the number of electrons? What is the formula of number of electrons? Number of electrons will be density of states multiplied with e to the power, sir, something positive would come here. So EC minus EF by KT, right? EC minus EF. EF will be in between. So EC minus EF divided by KT. And what about P? So P will be NV e to the power, positive value would come. So who will be at the higher level? EF or EV? EF will be at the higher level. So EF minus EV by KT is equals to Ni square. What is NC? You know NC is equals to NC naught Mn star T to the power 3 by 2, and NV is equals to NV naught MP star T to the power 3 by 2. So here we need to see the variation with respect to temperature and band gap. We need to see the variation with respect to temperature and band gap. So I don't need this value. I don't need Mn star. So Mn star and MP star I will take as a constant, because they will be constant value only, no? Effective mass, that will be constant. I just need to see the variation of Ni square with respect to temperature and band gap. So that I am seeing. So I will put the value here. Nc naught Mn star to the power 3 by 2 and T to the power 3 by 2, and this value also I am putting now. Nv naught MP star to the power 3 by 2 T to the power 3 by 2 e to the power minus EC plus EF minus EC plus EF minus EF plus EV divided by ET. So this and this is getting cancelled out. EV minus EC, or you can write down minus of EC minus EV. So what will be your EC minus EV? This is your EC and this is your EV. So what will be your EC minus EV? Band gap. So here what you are getting, e to the power minus EC plus EF minus EF. So EF is getting cancelled. EV minus EC you are getting. So EV minus EC will be equals to EV minus EC will be equals to minus EG. So here you are getting e to the power minus EG by KT. Minus EG by KT. That is coming out to be equals to Ni square. So now you see constant, constant, constant. Why constant? Because we are seeing the variation with respect to temperature, and this is also constant. So all constant multiply A naught. So first I am writing down this Ni square. So Ni square. One more thing I would like to tell here is that let's not put these values. What I would do is that let's take it downward, and before that I want to include one more step. Nc multiply with Nc multiply with Nv. So Ni square is equals to Nc multiply with Nv, and then you know that e to the power minus EC plus EF, whatever it would come, then you would know that it will be replaced with minus Eg by KT. So this formula you don't need to mug up. If you can remember, then you can remember. Okay, if you can remember, then you can remember. Otherwise you can derive it any day, because what may happen is that in the examination what they can give you the Nc value, they can give you the Nv value, and they can give you the Ni square value, they can ask you the band gap, or they can give you Nc, Nv band gap value, they can ask you the Ni square value. Are you able to understand this point? So this formula is also used in one of the question. Not in the examination till this date, not in the examination this question have been asked, but in Niemann this formula is given and it has been used in one of the numerical as well. So it can be asked in your examination. So Ni square equals to Nc Nv e to the power minus Eg by KT. If you are able to remember, then remember. Otherwise you can derive it any day. N into P is equals to Ni square Nc e to the power minus Ec minus Ef by KT into Nv e to the power minus Ef minus Ev by KT. So very simple derivation, Nc into Nv e to the power minus Eg by KT. From there we got the same thing, and from here we understood that Ni square is equals to some constant T to the power 3 by 2 T to the power 3 by 2, that will become T to the power 3 e to the power minus Eg by KT. So this formula that we have understood, that we have written here. So Ni square equals to A naught T to the power 3 e to the power minus Eg by 2 minus Eg by KT. Just the derivation, no one will ask you. If you remember it, then it is good. Otherwise try remembering this one. So I am just putting a word R here, RE. Try remembering this one if you can remember. So shall we just write down that what all things we need to remember? After that we need to solve the questions only. So let's write down as a summary, formula summary, that what all things you need to remember. Formula to remember. If you just remember this slide, then your job will be done. Probability of finding the electron at a particular energy level E, that is given by 1 upon 1 plus e to the power E minus Ef by KT, and that would be given as e to the power minus E minus Ef by KT. Then directly number of electrons. Number of electrons will be Nc e to the power something positive would come, sir. So Ec minus Ef by KT. Then number of holes, sir, Nv e to the power something positive would come, that means EF minus EV by kT. This formula. Then what will be the value of Fermi level in intrinsic semiconductor? That would be equals to mid gap EC plus EV by 2 minus KT by 2 ln NC by NV. Okay. Secondly, NC is equals to NC naught Mn star T to the power 3 by 2 and NV is equals to NV naught MP star T to the power 3 by 2. Done? Okay. Then who will be at the higher level? EFN will be at the higher level. EFN minus EFI. What that would be? EFN minus EFI. So you will draw the diagram. Then sir KT ln N will be greater than Ni. So N divided by Ni. Second, sir EFP not EFP, EFI minus EFP. Why so? Because EFI will be at the higher level. So KT ln P by Ni. And lastly, sir, Ni square is equals to Nc into Nv e to the power minus Eg by Kt. Nc into Nv e to the power Eg minus Kt. There you go. These are the formula. That's it. Just if you remember these formulas, your job will be done. So 1, 2, 3, 4, 5, 6, 7 and 8. All with respect to all these formula, like a lot of questions you will be able to solve. Let's get started with this particular question. Silicon at a temperature of 300 Kelvin has its Fermi level positioned 0.25 below the conduction band. Okay. 0.25 electron volt below the conduction band. The effective density of states in the conduction band is given. NC value is given 2.8 into 10 to the power 19 centimeter cube. And it is below the conduction band, that means EC minus EF is given. The Fermi energy level, Fermi level is positioned 0.25 electron volt below the conduction band. So this is the conduction band and this is my Fermi level. Conduction band and this is my Fermi level. So that is 0.25 electron volt. Calculate the probability that a state in the conduction band is occupied by an electron. So what you need to find out? Probability of finding an electron in the conduction band. That would be equals to 1 upon 1 plus e to the power EC minus EF by KT. And I know that sir it will be approximately equals to e to the power minus EC minus EF by KT. Every calculation is going at 300 Kelvin. 0.25, 0.0259. So very simple thing. Everything you already know. So let me do this calculation. Yeah, so answer you are getting is 6.43 into 10 to the power 5. Okay. Next, calculate the thermal equilibrium electron concentration in silicon at 300 Kelvin. So this was A, this was B. Thermal equilibrium electron concentration at silicon at 300 Kelvin. So what will be the number of electrons? So number of electrons will be Nc e to the power minus EC minus EF by KT. Number of electrons will be Nc multiplied with the probability of finding an electron in the conduction band. So Nc into e to the power minus EC minus EF by KT. So Nc value is 2.8 into 10 to the power minus 19. Not minus 19, sorry, plus 19. And this probability is 6.43 into 10 to the power minus 5. So 6.43 into 2.8. So 1.8. So 1.8 into 10 to the power 15. 1.8 into 10 to the power minus 4. Minus 4 with minus 19. Yeah, 10 to the power 15. Yeah. So this is the answer you will be getting. Centimeter cube inverse. Very simple calculation. Very straightforward. Like there is nearly nothing in these kind of problems. Okay. So rather than mugging up the formula, we remember the concept and we will remember our tricks as well. Silicon at 400 Kelvin. Always notice the temperature. Whenever you solve a question of EDC, always notice the temperature.
silicon at 400 Kelvin has its Fermi level positioned 0.27 electron volt above the valence band. So what is given? Fermi level minus valence band is 0.27 electron volt. Everything is running at 400 Kelvin. The effective density of the states of for the silicon at 300 Kelvin is given as 1.04 into 10 to the power 19. So NV value at 300 Kelvin is given as 1.04 into 10 to the power 19. What I need to find, calculate the thermal equilibrium of whole concentration. So what I will do, sir, this is what I need to find at 400 Kelvin. You need to find everything you need to find at 400 Kelvin. So sir, it would be EV e to the power something positive should come. So sir, for the positive, EF minus EV by KT. Now all these calculation you need to do at 400 Kelvin. So what all things will change with respect to the temperature? NV value will change and this KT value will also change, no? Thermal energy will also change. NV is NV is proportional to temperature to the power 3 by 2. So NV value at 400 Kelvin will be divided by NV value at 300 Kelvin will be equals to 400 divided by 300 to the power 3 by 2. So what will be the NV value at 400 Kelvin? That would be 4 by 3 to the power 3 by 2 multiply with 1.04, right? 4 by 3 to the power 1.5 multiply with point so 1.6 into 10 to the power 19 centimeter cube inverse. Did you understand this point? NV is proportional to T to the power 3 by 2. Then you did the same thing. 4 by 3 to the power 3 by 2. So 4 by 3 to the power 3 by 2. What that would be? 4 by 3 to the power 3 by 2. So whatever the value it is, multiply with NV value at 300 Kelvin. So that is 1.04. So this is the answer I am getting. What about the VT value? Or you can say thermal energy value. So this is also proportional to temperature. What I mean to say is that thermal energy, here I can simply do the calculation. So your thermal energy is also proportional to temperature. So your thermal energy at 400 Kelvin yeah, so your thermal energy at 400 Kelvin divided by your thermal energy at 300 Kelvin is equals to temperature. Temperature is 400 divided by 300. So what will be the answer of thermal energy at 400 Kelvin? That would be 4 by 3 into 0.0259, right? 4 by 3 times of 0.0259 into 4 by 3, 0.034. So this is the scenario, electron volt. Okay. What is the value of NV? NV is 1.6 into 10 to the power 19 e to the power minus EF minus EV. EF minus EV is 0.27. So this value is already given at 400 Kelvin only, right? Divided by KT, that is 0.034. So from here I will get the answer. 0.034 reciprocal 0.27 plus minus e to the power into 1.6. So yeah, 6.43 into 10 to the power 15. So question was very simple only, just like the previous problem only. Whatever that we did in the previous problem, the same thing we are doing here. Just the thing is, with respect to temperature, things are changing. So with respect to temperature, NV value is also changing and ET value is also changing. Well and good. A germanium arsenide at 300 Kelvin has effective density of states in the conduction band as Nc and valence band this much. I'm really sorry for this particular thing, right? I hope you guys are not getting irritated. I know it might be sometimes it might be problem that your educator is not speaking fluently or clearly. I'm speaking fluently, I'm speaking clearly as well, but there is some break because of this thing, right? Because of my throat. And I was eating some ilaichi and all these things. Don't think that I am a fan of Ajay Devgan. Okay, I am not eating gutka. Gutka वगैरह नहीं खाता हूँ मैं.
इलायची वगैरह खा के मैं रिकॉर्ड करता हूँ ताकि कम खांसी आए, ठीक है। तो ये थोड़ी सी दिक्कत हो रही है, बट मैं इसको डिले नहीं कर सकता क्योंकि फिर सिलेबस बहुत लेट हो जाएगा। तो आई नीड टू कवर द सिलेबस एज वेल, सो I hope it is not being that much of a problem for you guys. Okay, so you guys need to cooperate, and you can put a like if you are watching it on YouTube. You can put a like. Yeah. Band gap is given, NC&V value is given, and band gap is not changing with respect to the temperature. You need to find the intrinsic carrier concentration of gallium arsenide at 450 Kelvin. So try doing it on your own. What is the formula that we saw? NC/NV e to the power minus Eg by kT. Now they are saying that this Eg is constant. This is not changing with respect to temperature. Rest all the things will change with respect to the temperature. This will change, and this will also change. So what will be your NC value at 450 Kelvin? So sir, that would be equals to 450 divided by 300, the value at 300. What is the value? 4.7 into 10 to the power 17. But it is proportional as power 3 by 2. Is that clear to you? NC value at 450, 450 divided by 300 to the power 3 by 2 into 4.7 into 10 to the power 17. So what we are getting? 4.5 divided by 3 to the power 1.5 into 4.7. So 8.63. And what about NV at 450? So that will also go through the same thing. So 1.5 to the power 1.5 into 7. So 12.85 into 10 to the power 18 centimeter cube inverse. Now what about the ET value? ET value at 450 Kelvin. So that would be 450 divided by 300 into 0.0259. So 450 divided by 300 into 0.0259. 0.3885 electron. There you go. Now you can solve it. So Ni square is equals to 8.63 into 10 to the power 17, 8.63 into 10 to the power 17 into 12.85 into 10 to the power 18 e to the power minus Eg is not changing with respect to the temperature, they are saying, but actually it changes, but they are saying that band gap is not changing with respect to the temperature. So 1.42 divided by kT, that is 0.03885. So this is the scenario, this will be the answer. So there we go, 1.42, 1.42 divided by 0.03885 plus minus e to the power. So 1.33 e to the power minus 16 I am getting. So 8.63 I will write down here, 12.85 I will write down here, 10 to the power 17, 10 to the power 18 into 1.34 10 to the power minus 16 I am getting. So effectively 10 to the power 19 I have. So 10 to the power 19 I have, and rest all the values I will multiply. Multiply with 8.63, multiply with 12.85. So the whole result they are giving me in 10 to the power minus 14. So whole result I am getting 1.48 into 10 to the power minus 14 into 10 to the power 17 into 10 to the power 18. This is what I am getting. So what I can see here, 10 to the power 3, so 10 to the power 21. So 1.48 into 10 to the power 21 Ni square. Now how will you do the calculation? Here try making something that is even 10 to the power 20, because you know that I will be able to take the under root. What I would do is that I will write this down as 14.8 into 10 to the power 20.
right? I took the 10 outside it, 14.8 into 10 to the power 20. Now Ni value will be under root 14.8, right, into 10 to the power 10. Say yes or no? Because under root of 10 to the power 20 will be 10 to the power 10. So now I just need to calculate 14.8 under root, that is coming out to be 3.84. Yes. So Ni value is coming out to be 3.84 into 10 to the power 10 centimeter cube inverse. So this is how you do the calculation when it comes to EDC. So that's why I am showing you every step. Are you able to understand this point? Because in EDC calculation takes a very important role. These are, none of them are PYQ, okay? None of them are PYQ. You will be able to solve the PYQ very easily. In PYQ, you will not find that this much temperature is changing. Very straightforward question would be there. These questions I am taking from Neiman only. Although written by ChatGPT, but taken from Neiman. Here, what did I tell you? That effective mass of electrons should be greater than the effective mass of holes. But here, things are different. So if things are different, there you will not be say, sir, it will be MTA. No. Whatever the value is given, I need to solve it. That's it. What they are asking? In silicon, effective masses are given as this much, this much. Calculate the position of intrinsic Fermi level with respect to the center of the band gap. Center of the band gap. So Fermi energy level is equals to EC plus EV by 2 minus KT by 2 ln NC by NV. And I know that NC is proportional to Mn star to the power 3 by 2 and NV is proportional to MP star to the power 3 by 2. So what I can see? EFI minus E mid gap is equals to minus KT ln Mn star to the power 3 by 2 and MP star to the power 3 by 2, already to the power 3 by 2. So this 3 by 2 can go in front. So what will become 3 by 4? So minus 3 KT by 4. Now you can put the value at 300 Kelvin. Yes. So minus 3 into 0.0259 divided by 4 ln Mn star is 1.08 divided by 0.56. One 1.08 divided by 0.56 ln into 3 by 4 into 0.0259. So 0.0127. 0.0127 electron volt, and minus sign is already there. So EFI minus E mid gap. This is what you are getting, or you can write down EFI minus E mid gap is actually coming out to be minus 12.7 milli electron volt. What does that mean? That means your intrinsic Fermi level is 12.7 milli electron volt below the, what they are asking, position they are asking. So it is below the intrinsic Fermi, below the center of the band gap. Your Fermi energy level, your intrinsic Fermi level is 12.7 milli electron volt below the center of band gap in silicon. Okay. So EFI is 12.8. I will write down 12.7 below center of mid gap. Is below from the center of mid gap. Okay, from center of mid gap it is 12.7 milli electron volt below. This is the answer. Let's go to the next one. Consider silicon at this much temperature. Effective density of states in the conduction band is given. Effective density of states in the valence band is given. The Fermi level is located 0.25 electron volt
below the conduction band H. The band gap in the silicon is 1.12 electron volt. Okay. So let's make the diagram. EC, EV, and Fermi energy level is 0.25 electron volt below. So this gap is 0.25 electron volt. And what is this total gap? What is this total gap? This total gap is 1.12 electron volt. So what do you think? What is this gap? 1.12 minus 0.25. 0.87, right? Now what you need to find? Thermal equilibrium, electron and hole concentration, right? So electron concentration will be equals to Nc e to the power minus Ec minus Ef by kT at 300 Kelvin only. No, temperature is not even mentioned. Yeah. So that would be equals to, what is the value of Nc? 2.8 into 10 to the power 19 e to the power 0.25, 0.0259. So 0.25 divided by 0.0259 into 2.8. So 1.8 into 10 to the power 15. Yeah, 1.8 into 10 to the power 15 centimeter cube inverse. What will be the number of holes? E to the power minus Ef minus Ev by kT, right? That is 1.04 into 10 to the power 19 e to the power minus Ef minus Ev. Ef minus Ev is 0.87 divided by 0.0259. So 0.87 divided by 0.0259 plus minus e to the power into 1.04. So 2.68 into 10 to the power 4. Yeah, so 2.7 into 10 to the power 4 centimeter cube inverse. Very simple question. Okay. And you ask these questions to your friends who are studying from somewhere else. They will not be able to solve very easily. They will see, okay, sir, this formula was there, that formula was there. Sir, how will I relate with NC? Okay, this thing I will apply. So forget about the formula. N equals to NC this formula, P equals to NB this formula. That's it. Okay. So we are not mugging up any formula. Whatever the formula that we need to remember, we have written in one slide only. Okay. Silicon at 300 Kelvin contains a, yeah, this is a good question. You should try it on your own. I think this is the last one. Yeah. So silicon at 300 Kelvin is having impurity concentration of 10 to the power 16. And somewhere intrinsic carrier concentration is also mentioned, so that I have also put. Determine the concentration of donor impurity atoms that must be added. So you are adding Nd to make it n-type, such that it becomes n-type, and the Fermi level is located 0.2 electron volt below the conduction edge. So that means this is the conduction band, this is the valence band. So as per you, your Fermi levels should be here. 0.20 electron volt. So you need to add up Nd, right? The effective density of states are given. Only for Nc the effective density of state is given. So for conduction band this is given. Now which formula do I know? The intrinsic carrier concentration is this. So how much Nd I need to dope? So which formula I know? I know the number of electrons. Number of electrons would be would be equals to Nc e to the power minus Ec minus Ef by kT. So this thing I know. I know the value of Nc. Yes. Ec minus Ef also I know. KT also I know.
Basically, I will see what all things are given. Nc is given, Ec minus Ef is given. So I can find out the number of electrons. So total number of electrons will be this much. So what is the value of Nc? E to the power minus, what is Ec minus Ef? 0.20 divided by 0.0259. So 0.2 divided by 0.0259 plus minus e to the power into 2.8. So 1.24 into 10 to the power minus 3. So what we are getting? 1.24 into 10 to the power minus 3. 1.24 into 10 to the power minus 3. Or better write down 12.40. I will write down 12.40 into 10 to the power minus 4. So it would be 12.40 10 to the power 15 centimeter cube inverse. These are the number of electrons that you are getting. This is what? This is the number of electrons. Now what do you know? What kind of semiconductor it is? N-type or compensated N-type? This is your compensated N-type. So for compensated N-type semiconductor, number of electron is equals to Na minus Nd by 2 plus under root Na minus Nd by 2 whole square plus Ni square. Now you know that Ni will be much lesser than Na minus Nd, because you know that already Na is very higher, Nd will be higher than that. So you are nowhere considering Ni. So this will go to 0. So you know that N value will be approximately equals to Na minus Nd. So from here, array yaar, compensated N type it is. So Nd minus Na. Sorry guys, Nd minus Na. Nd minus Na. Nd minus Na. So N will be Nd minus Na. So what will be the value of Nd? Nd will be N plus Na. So you can see 12.40 into 10. So 1.24 10 to the power 16 was a better option. 1.24 into 10 to the power 16. So 1.24 plus 1.24 10 to the power 16 plus 10 to the power 16. What that would be? 2.24 10 to the power 16 centimeter cube inverse. So this will be the value of Nd. That's the answer. Or better, I should keep this in the answer. All good? All fine? Very simple thing. Okay. Now the next topic is also very simple. Variation of Fermi level with respect to the temperature and doping concentration. So first we will see with respect to the doping concentration. So both in N-type and P-type we are going to see. So on y-axis I am making energy, on x-axis I am making doping concentration. That means if you are walking on x-axis, if you are moving on x-axis, then your doping concentration increases. So for N-type, and this is your conduction band, this is your valence band, and in between I am making intrinsic Fermi level. So initially you are having intrinsic semiconductor only, then you are doping it to make it N-type. So for N-type, what will be the scenario? For N-type, I know that first we will see with respect to formula, then we will see with respect to concept as well. Ec minus Efn. I don't remember the formula, but I remember this thing. What do I need? What do I remember? Number of electrons is equals to Nc e to the power minus Ec minus Efn by Kt. So from here what I will get? Kt ln n by Nc. So what I will get? Kt ln Nc by n. This is what I will be getting. From this only I have written down this formula. Although I don't remember it, but how will I write down? From here I can write down Ec minus Efn Kt ln Nc by n. Right? Now you know that if doping increases, then value of n will increase. The value of n will increase, and if the value of n will increase, then this value will decrease, then this value will decrease. So the gap between Ec and Efn will decrease. Ec and Efn will decrease. That means if you are doping more, then you are going towards a conduction band. So let's just say at a particular doping, you are here, and if you are moving in the x-axis, if you are moving in the x-axis, that means you are increasing the doping concentration. So as you increase the doping concentration, what happens? You move near to the conduction band. So this is your EFN. As you increase the doping concentration. Basically, previously what was the scenario? It was intrinsic. Just as I started doping it more, just as I started that donor concentration, just I started putting the donor concentration, what really happened? This started moving upward. So if I put more and more donor concentration, this will move more and more upward. So this is what I am doing. I am drawing it with respect to energy versus doping concentration. Energy versus doping concentration. So if doping concentration is more, if your doping concentration is more, that means you are more near to EC. Are you able to understand this point? Now let's just think about a semiconductor. Now this analysis is only important, otherwise you will be getting confused. Forget about it. Forget about it. Whatever that I told you till this point, you understand in this manner only. More doping, more near to EC. Lesser doping, further away from EC. But if it is n-type, then surely you know that it will be greater than EFI. That you already know. If it is n-type, then surely you know that it is greater than EFI. So more doping means more near to EC. That means here I am putting more doping. Okay. And similarly for p-type, what you will do? For p-type, what will be the formula? EFP minus EC, right? EFP minus EC. That would be equals to KT ln NV by P. KT ln NV by P. So more doping means these will increase, because more, if you are putting more trivalent atom, then more number of holes will be there. So this will increase. And if this is increasing, then this is decreasing, then this is increasing. That means more doping means EFP minus EC will decrease. That means EC will come near to EFP. So lesser doping means it was here, and more doping means it is coming near to valence band. So initially it was intrinsic. Then what you did? You started doping the acceptor atom. So acceptor atom you started doping. So Fermi level started moving downward, 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 downward. And when the doping was maximum, it has moved here. So this is about your EFP. So this is here as well, more doping. Very simple thing, very, very straightforward. Just remember that this is energy versus doping concentration. This is not energy versus X. Here we were drawing this diagram. All these diagrams are energy versus distance. Energy versus distance. So with respect to the distance, they are flat only. What I mean to say is that, do you remember the first lecture? In the first lecture, what we did? Let's come here. In the first lecture, what we did? 3s, 3p, 3s, 3p. Then this kind of diagram we got, right? Arey yaar. This kind of diagram we got. This I called as conduction band and this I called as valence band. So here what we were doing, we were going with respect to distance only. No, this was energy, this was distance. So as I was reducing the distance, this is what I got. So here I made the conduction band, here I made the valence band, and here I made the conduction band. So those I made with respect to the distance. So these conduction band and valence band that we draw, these we draw with respect to the distance. Are you able to understand this point? Now what I am doing, energy versus doping concentration. So based on the doping concentration, EC and EV will not change. EFI will also not change. Who will change? Based on the doping concentration, these EFN and EFP will change. So always look at the x-axis. What x-axis is given? Energy versus X would be different. Energy versus doping concentration would be different. Are you able to understand this point? As the doping concentration increases, the gap between the conduction band and the Fermi energy level of n-type will decrease. As the doping concentration increases, the gap between the valence band and the Fermi level of p-type will also decrease. That's it. Okay, more doping means more near to your conduction band or valence band. All good. So this is what has been written. In n-type, higher donor doping brings Fermi level closer to the conduction band and farther from the intrinsic level. In p-type, higher acceptor doping brings the Fermi level closer to the valence band and farther from the intrinsic level. Very simple thing. Next, this is the question. So this is like part A and this is part B. Two questions are there. Which semiconductor has more doping and what is the nature of doping? So in both of the semiconductor, donor atoms are doped, right? Donor doping. Why so? Because near to the conduction band, farther from the valence band, and here near to the valence band and farther from the conduction band. So here also, here accepted doping. Very simple question, free marks if these kind of questions are coming. Now which semiconductor is having more doping? Between semiconductor 1 and semiconductor 2, which is having more doping? Semiconductor 2. Why so? Because in the semiconductor 2, the conduction band and the gap between the conduction band and the Fermi level is very low. More doping means you are moving more towards the conduction band. So here more doping is there. That means Nd2 is greater than Nd1. And what about this one? Na2 is greater than Na1. Why so? Because you are more near to the valence band. So if you are more near to the valence band, what does that mean? That means acceptor atoms are more here. So if acceptor atoms are more, that means your Fermi level will be near to the valence band. Very simple thing. Okay, very straightforward. Let's draw with respect to the temperature. So now I will have to vary that temperature. So again for n type I will write down the formula. Which formula I will write down? Sir, EC minus EFN. Although sir you don't remember the formula, so no need to remember the formula. KT ln, you can any day you can derive it. KT ln NC by N, right? Yes. Now if temperature increases, then the gap between EC and EFN will increase. If the temperature increases, if I go on this axis, if I move towards a temperature axis, then the gap between EC and EFN will increase. This is your EC, this is your EV. Let's just say I started my EFN from here, so gap will keep on increasing. The gap will keep on increasing. So this is your EFN. Similarly for P type, EFP minus EV, that would be KT ln NV by P, right? So as you increase the temperature, the gap between Fermi energy level and the valence band will increase. So as I increase the temperature, the gap will keep on increasing. So this will be your EFP. So here there is more temperature. Here there is more temperature. Very simple thing. And do you remember the graph of number of electrons with respect to the temperature? Increases, and then at a very high temperature it is becoming intrinsic. That means if you are increasing the temperature, that means you are going towards making your semiconductor as intrinsic semiconductor. So if I am increasing the temperature, my Fermi energy level for both N type and for P type, for both of them it is moving towards intrinsic Fermi level. So as I increase the temperature, that means I am moving towards making my semiconductor into intrinsic semiconductor. That means my Fermi level will try to move towards intrinsic Fermi level. Or you can simply see from the formula, if temperature increases, the gap between EC and EFN increases, the gap between EC and EFN is increasing. Very simple thing, right? So this is what has been written. As temperature increases in N type, the gap between the conduction band and the Fermi level increases, while the gap between the Fermi level and intrinsic level decreases. But basically, this gap is decreasing and this gap is increasing. This is what it is saying, right? Initially, this gap was here. Initially, this gap was this much. Okay, well and good. So these are the diagram. This is the theory that has been written. And similarly for P-type semiconductor also, it has been written. Again, a very simple question. The same kind of simple question. You need to find out the relation between T1, T2. That means this is the relation. This is question A. This is question B. Energy versus the array. Yeah, energy versus X. This graph was energy versus X, right? Energy versus X. And this graph was energy versus temperature. And this graph is also energy versus X. Are you able to understand this point? This is now with respect to the distance. Now only thing you need to know is that the gap between EC and EFN is reducing here, and here it is more. What does that mean? If the gap is more, that means more temperature. So T1 is greater than T2. And here if the gap is more, that means T3 is greater than T4. Because if the temperature is more, if temperature increases, this gap increases, because formula says KT-ln. Or you can say that if temperature increases, that means I am moving towards making my semiconductor into intrinsic semiconductor. So if temperature increases, I am actually moving towards intrinsic semiconductor or intrinsic Fermi level. So this temperature T3 will be greater than T4, T1 will be greater than T2. So always you need to look at the examination that what they are asking. They are asking the graph with respect to temperature or with respect to the distance. So with respect to the distance, we have seen the graph is EC, EV, EFI in that manner, and EF. Only thing that can change is the gap. The gap. Rest all the things will be flat. This is what we are studying as till this point. Energy versus X. Till this point, we have seen the graphs are flat with respect to the distance. All whatever that can change is the gap, this gap, this gap, and this gap. Okay, well and good. Now this question will be interesting. Read the question and tell the answer. It is MSQ. Okay, it is MSQ. Read the question and tell the answer. For different doping concentration in both N-type and P-type semiconductor, the gap between the Fermi level and intrinsic Fermi level is shown. What is shown? EFP minus EI is shown, and EFN minus EI is shown. Basically, if I make the diagram, this is my conduction band, this is my valence band, and this will be my EFI. I know that this will be my EFN and this will be my EFP. So conduction, valence, EFI, EFN and EFP. So EF minus EFI versus the temperature is shown. What does that mean? As you increase the temperature, what you see? As you increase the temperature, the gap between EF and EFI is becoming lesser. Here this was the gap and then it is becoming lesser. So increasing the temperature means the gap between EF and EFI is becoming lesser. Here what is the gap between EF and EFI? Almost around 0.2, and then here the gap has become 0. Here what is the gap? Almost around 0.2, then it has become 0. Why it is for P-type and why it is for N-type? Because in P-type EF minus EFI will be negative, because EFI will be at a higher level. And why it is for N-type? Because in N-type EF minus EFI will be positive. Is that clear to you? Although it is not answering our question, our answering question will be answered based on the fact that which one will be larger, ND2 is greater than ND1 or NA1 is greater than NA2, whatever the relation is there, that we need to tell. Now I know that at a particular temperature, if there is more doping, what I am saying, at a particular temperature, I am fixing the temperature. I am fixing this temperature. This temperature is T. If there is more doping, what does that mean? That means this gap will be lower. More doping means EFN will be moving towards EC. That means this gap will be larger. So what I am saying, more doping shows that EFN minus EFI will be larger, and EFP, or you can say EFI minus EFP will also be larger. Because if there is more doping, that means your EFP is moving towards valence band. That means this gap will increase. So at a particular temperature, I am only varying the doping, not temperature. So at a particular temperature, who is having more gap? This guy is having more gap or this guy is having more gap? ND2 is having more gap than ND1. So what will be the answer? And here who is having more gap? Na2 is having more than the Na1. More doping means there will be more gap between EFI and EFP, because EFP will be moving towards EV and EFN will be moving towards EC. That means there will be more gap between EFI and EFN as well. More doping. So who is having more gap? Here the gap is roughly around 0.2, but here the gap is roughly around 0.3. And in this case, here the gap is roughly around 0.2, but here the gap is roughly around 0.3. You can see this is a different axis. This is not 0 here. This is not 0 here. This is 0 here. So 0 and downward everything is negative. 0 upward everything is positive. So EF minus EFI versus temperature graph is given. In the examination, what may happen is that they can simply ask this graph, or based on the graph they can ask the question. And surely in 2026 or in 2027 the question is coming like this. Surely in your examination you will see very soon this kind of question is coming. This kind of graph they can directly ask, that EF minus EFI versus temperature graph, how it will go for N-type and P-type. So that you should be able to make. You are able to understand this graph, right? as the temperature increases, you are moving more towards a intrinsic semiconductor, or you can say you are increasing more towards intrinsic Fermi level. That means this gap will keep on reducing. So yes, this gap is reducing. Why it is for n type, why it is for p type? Because in n type this gap will be positive, in p type this will be negative. So this is how the graph will go. And this graph is given in Niemann. From that particular graph I made this question. Okay. So surely it is coming very soon in your examination. So that's it about this topic. Is there anything else? No. Yeah, we can see this thing. Degenerate and non-degenerate semiconductor. So some points we need to see, some discrete point we need to see. That is degenerate and non-degenerate semiconductor. Do you remember what was degenerate and what was non-degenerate? In degenerate I said that there will be more doping, and here there will be moderate doping. Moderate doping. Here what was the ratio? You don't need to remember it. 1 ratio 1 to the power 3, and here 1 ratio 1 to the power 7. Right? So if I am increasing the doping, then what is happening? If you increase the doping, then let's talk about n-type semiconductor. If you increase the doping, what will happen? This EFN will move upward. So what if I do so much of doping that EFN is moving into EC? What I am saying, I have done so much of doping that my Fermi level has moved into conduction band. So if that scenario is happening, that means it is degenerate semiconductor, otherwise it is non-degenerate semiconductor. So we are studying all the cases about non-degenerate semiconductor, that we will not do so much of doping that our EFN will get into EC. Our Fermi energy level will not get into EC. We will not do so much of doping. We will make sure that we do that much of doping only, such that EC is always greater than EFN. That means our Fermi energy level is never getting into the conduction band. So this is something that has been written. Okay. Non-degenerate semiconductor doping is moderate. The Fermi energy level lies within the band gap. That means it will be closer to the conduction band, and closer to the conduction band for n type and closer to the valence band for p type. The level will be lying between the band gap. That means this will be conduction band, this is the valence band, and this is known as band gap. So here you can find out, here you can find out, wherever you can find out. So the Fermi energy level will be lying inside the band gap. Okay. Carrier concentration is low enough to follow Boltzmann stats. Okay. What do you mean by Boltzmann statistics? That means f of E is approximately equals to e to the power minus E minus EF by kT. So this approximation is valid in our case. Okay, in our case this approximation will be valid, and in your examination as well this approximation will always be valid. Degenerate semiconductor, doping is very high. Fermi level enters into the conduction band and over the valence band. Carrier concentration is so high that material will behave like almost like a metal, and Fermi-Dirac statistics we need to use. What is Fermi-Dirac statistics? F of A is equals to 1 upon 1 plus e to the power E minus EF by kT. That complete formula we need to use. All good. So in short, non-degenerate semiconductor means Fermi level inside the band gap, and degenerate semiconductor means Fermi level inside the band. Band could be conduction band or valence band. So if your Fermi level is entering into the conduction band or valence band, that means surely it is degenerate type of semiconductor. Otherwise it is non-degenerate type of semiconductor. Okay. Now in GATE 2024, there was a question. There was a term mentioned, degeneracy factor. What do you mean by degeneracy factor? So if I am saying that an energy level E1 is having degeneracy factor of 2. Energy level E1 is having degeneracy factor of 2. That means E1 is having two states. E1 is having two energy states. So degeneracy factor of energy level E1 is 2. That means energy level E1 has two energy states. If degeneration factor, if degeneracy factor is 5, that means it will have 5 energy states. If degeneracy factor is 10, then it will have 10 energy state. So on one level, on one floor, there are 2 rooms available. If I am saying that degeneracy factor is 2, okay. So use your whole brain and solve this question. Don't apply any formula that you have studied. Let's just say you might have studied this EDC chapter from somewhere else.
So they will solve this question with respect to some formula. They will write down some formula and they will solve it. I can also write down the formula. But if I write down the formula, then you will not be learning anything, right? You will just mug up the formula, and it is not possible to remember so much of formula in the examination hall. So minimum formula we are trying to remember. Minimum, least formula we are trying to remember, right? So you are not going to mug up any formula. Use your brain here. What this question is saying, make the diagram and try to get the answer. I am pretty sure you will be able to get the answer. I have also told the meaning of a degeneracy vector. That means on one energy level, there will be two states. So try thinking about it and try to get the answer. And if you are able to get this answer, then go for this particular question and tell me the answer for this particular question as well. Okay. So try solving this one and this one. And with that, this topic will end. Then we need to start this particular topic, energy band diagram for different kind of semiconductors. So this is also a very interesting topic, but first we need to solve this question and this question. So you try solving it on your own. I will have to drink some water and then I will come back and let's see. We will try solving these problems. Okay. Yeah, welcome back. So did you attempt this question? A non-degenerate n-type semiconductor is having 5% neutral dopant atoms. Fermi level is located 0.25 electron volt below the conduction band. So basically, we know one thing now, that this will be our conduction band. This is our Fermi level. So EC minus EF is given. That is given by 0.25. This distance is given 0.25 electron volt. And donor level ED is having a degeneracy of 2. What does that mean? That means if this is my donor level, ED, on this donor level there are two rooms. That means there are two states. Okay, this is the meaning of degeneracy of 2. Degeneracy factor is 2. So there are basically two states. On one donor level there are two donor states. This is the meaning of degeneration of factor of 2. Thermal voltage you need to take 20 millivolt. Thermal voltage you need to take 20 millivolt. Although it is 26 millivolt, but 20 millivolt you need to take. You need to find out the difference between EC and ED. So basically you need to find out EC minus ED. This is our target. Okay. What is the meaning of a semiconductor having 5% neutral dopant? What does that mean? That means let's just say this was my intrinsic semiconductor. Here I did the doping of 100 donor atoms. So 100 donor atoms are supposed to give me 100 electrons. These 100 donor atoms at 0 Kelvin all will be there at the donor energy level. So all the 100 electrons will be coming here. And as we get the temperature, what will happen is that they will move here. But we are not getting enough temperature that all the hundreds are moving here. 5% are neutral. What does that mean? 95% are ionized. So 5% neutral means either this language could be written 5% neutral, or this language could be written that 95% are ionized. Okay. So 100 donor atoms were supposed to give me 100 electrons, but they only give me 95 electrons at this particular temperature. Whatever the temperature is, I don't know. So rest 5% of the electrons are there at which position? They are there on the donor energy level only. So donor energy level is having 5% of the electron. So what is the probability of finding an electron at donor energy level? What I am saying? Tell me the probability of finding an electron at donor energy level. What do you think? What will be the probability? That would be equal to 5%, right? 0.05. Because out of 100, 95 have been ionized. That means 95 has reached to the conduction band. Only 5 are left on the donor energy level. So probability of finding an electron on the donor energy level is 0.05. Can I apply this formula now? Which formula? The approximate formula that we write down, e to the power minus E minus EF by KT. This is equal to 0.05. And in place of E, I am putting ED. Because what I am saying is that probability of finding an electron at donor energy level ED, that would be equal to e to the power minus ED minus EF by KT. Is this statement correct or not? Wrong. Why is that so? Because this function is defined for energy state, not for energy level. Till this point we were using energy level and energy state simultaneously. Like sometimes I would call energy level as energy state, sometimes I would call energy state as energy level. But both are the different thing that you know. And here there is a difference. Why is that so? Because the degeneracy factor is 2. That means on the donor energy level, you are having two states. So let's just say if you are, let's just say finding a guy on this floor is having a probability of 0.1 or 0.05. The probability that the guy will be there on this floor, that probability is equal to 0.05. So what is the probability that he will be there in this room? That means he can either be there in this, he can be there either in this room or in this room. So what will be the probability divided by 2? Are we able to understand this point or not? So probability of finding an electron at donor energy level is 0.05, but probability of finding an electron at donor energy state is equal to 0.05 divided by 2. Say yes or no? What I am saying, probability of finding an electron at one of the donor energy state because there are two states, so 0.05 divided by 2, and now this could be equal to, like this was wrong, so this 0.05 divided by 2 could be equal to this particular probability. Why is that so? Because Fermi-Dirac distribution is defined for the energy state, not for energy level. That's why I was focusing again and again on that particular point, that it is defined for the energy state, not for energy level. Okay, so now I can write down f of ED is equals to 0.05 divided by 2, and this will be approximately equals to e to the power minus, because we can apply our approximation, e to the power minus ED minus EF by KT. How I am writing down this thing? From this formula only, 1 upon 1 plus E minus EF by KT. So sir, this thing goes upward, so e to the power minus E minus EF by KT. So minus, in place of E I am putting ED, that is equals to 0.05 divided by 2. So this was the beauty of this question. Although everyone solved this question using the formula, there is a certain formula that is given in our particular book, that is Niemann. You put that formula, you get the answer. But how many formulas will you remember? I will not even tell you that formula. Okay, so it's not practically possible to remember all this formula, and who knows, this question would be coming or something else would be coming, because I have framed another problem here. Now here different formula will be used. So will you mug up that formula as well? No. We will understand the concept, right? That's why here as well in these questions, whatever that we studied previously, whatever the formula that we studied, there also I tried to give you the concept, not the formula, right? So here also we are not going to use the formula, we are going to use our concept. So let's solve it. KT value is 20 millivolt given, so don't do that error. Okay, KT value is 20 milli electron volt that you need to use, because 20 is given here. Usually we use 26, right? But here there is something difference. So let's find out ED minus EF. So take your calculator, zero ln into 0.020, 0.07 electron volt. This is what you are getting, ED minus EF. And what is given? EC minus EF is given. So from here, can you find out the value of what I need to find? EC minus ED I need to find, EC minus ED. So from here I can see that EC minus ED will be 0.25 minus 0.7, that would be equals to 0.18 electron volt. There you go. Okay, easy question, but you should know the meaning of a degeneracy factor. If you know the meaning of degeneracy factor, then you can think in this manner, that on donor energy level there is a probability that 5% of the electrons could be there, that means 0.05 probability, right? And on this level if there is 5% probability, that means
on one of the states the probability will be 5% divided by 2. All good? Let's go to this question. This is from Niemann only, but we are not going to apply any formula. We are going to solve with respect to pure concept. Think about it as much as you can think. Whatever you can think about it, you will be able to get it. Silicon semiconductor doped with Nd. Nd is equals to 10 to the power 16 centimeter cube. 300 Kelvin. Now donor energy level is lying 0.05 electron volt below the conduction band. So this is my conduction band and this is my donor energy level. They are talking about that donor energy level. So conduction band and this is your donor energy level. The difference is 0.045 electron volt. The effective density of states is given. Degeneracy factor is also given. The degeneracy factor of a donor energy level is 2. What does that mean? That means on this donor energy level, you are having 2 rooms. Find the fraction of electrons still occupying that donor state. So what you did, you had 10 to the power 16 centimeter cube inverse, these many donor atoms you were having. So you thought that I should be getting 10 to the power 16 electrons. Basically here Ni value is not given, so you would say that number of electrons will be approximately equals to Nd. It should be approximately equals to Nd, right? Or should I write down Nd plus? I should write down Nd plus because out of these 10 to the power 16 electron, some electrons have reached here and some electrons have stayed back to Ed only. Let us say these were 100 electrons. So out of 100 electrons, it might happen that 99 electrons has reached here, but 1 electron is there in the donor energy level only. So I am writing N equals to Nd plus. That means whatever that has been ionized. Are you able to understand this point? Whatever N equals to Nd plus means the number of electrons that has reached to the conduction band. So what is N here? Number of electrons present in the conduction band. What is N? Number of electrons present in the conduction band. So this is number of electrons present in the conduction band. So at least one equation I can write down. N equals to Nc, right? N equals to Nc e to the power minus Ec minus Ef by Kt. This is one equation I have written. Okay. Now just think about it. What will be the probability of finding the electron on donor energy level? So should I write down donor energy level or donor energy state? Donor energy state, right? If I am saying that, what I am saying, on donor energy level there are Nd electrons. What I am saying, let on donor energy level there are Nd electrons left. Nd electrons left. Behind the electrons still occupying electrons left. What does that mean? That means these are unionized because they did not get ionized. Or you can, if you want to use the language of this particular question, then you can write down neutral. Okay, or I am writing down unionized atoms. So one thing you know here is that N plus Nd, number of electrons that are present in the conduction band and number of unionized electrons, those will be combined equals to capital Nd. Do you agree to this point or not? Right? All good? Number of electrons present in the conduction band, number of unionized electrons in the donor energy level, both combined will be equals to the total electrons that we were supposed to get. Right? Now what I will do is that I need to find some relation of Nd. Basically, I have find out the number of electrons present in the conduction band. Now I need to find out the number of electrons present in the donor energy level. What is my target? My target is finding out the electrons present in donor energy level. Donor energy level. This is my target.
that is equals to Nd. So I need to find out the value of Nd now. Now, what is the probability of finding an electron in donor energy state? Because I know the formula for probability and for the state, not for the level. What I am saying, probability of finding an electron at donor energy. What should I write down? Donor energy level or donor energy state? Donor energy state, because I know the formula for donor energy state, not for donor energy level. Are you able to understand this point? What I am saying is that I know the formula for donor energy state, not for the donor energy level. Basically, this formula that I write down, f of Ed, is it there for the level or for the state? It is there for the state. So probability of finding an electron on the donor energy state is given by e to the power minus Ed minus Ef by kT. Right. Now on donor energy level you are having two rooms. On donor energy level you are having two rooms. Probability of finding the electron on this room is P1 and probability of finding the electron on this room is P2. So what will be the probability of finding the electron on this level? P1 plus P2. What I am saying, on this floor there are two rooms. Probability of finding a person in this room is 0.04 and probability of finding a person on this room is 0.03. What will be the probability that this guy will be lying on this floor? That means either he will be here or here. Both will be added up. Right? All good? Although there is a condition that they should be mutually exhaustive. But those mathematics we don't need to go. Like don't apply PA plus PB minus PA union B. Those things we don't need to do. That they are mutually exhaustive event. They are exhaustive only. Basically, probability of finding an electron on this energy state is P1 and probability of finding an electron on this energy state will also be P1 only because both are there on Ed only. So what I am putting, probability of finding an electron at donor energy state is f of Ed equals to this. Then what will be the probability of finding an electron at donor energy level? That would be twice of that. What I am saying, probability of finding an electron at donor energy level. What that would be? That would be twice of this. Twice of this 2 into Ed minus Ef by kT. Guys, look, it would have been very easy if I just write down the formula and I tell you to remember that. You remember this formula, okay, and then apply this formula, you will get the answer. You can find the formula anywhere on internet, but these things require understanding, right? So you have to appreciate that I am explaining this much. Otherwise, everything could be written in the textbook and formula is there, you remember it, in the examination question comes, you apply it, and then you will be forgetting it and you will not get the correct answer. But you are learning here what we are doing. What we have done now, we have find out the probability of finding an electron at donor energy level. Why we are doing so? Because now I can comment on that how many electrons will be there on the donor energy level. If I know the probability, then surely I can comment on the number of electrons as well. How? How did you comment on the number of electrons present in the conduction band? How did you comment on that? You said that, sir, probability is f of EC and number of states available are NC. So I multiply with them. Now probability of finding an electron is something this we have find out. Okay, that I am calling as P. Okay, P of Ed. This I am calling as P of Ed. So P of Ed, this we have find out. What I should multiply it with so that I get the number of electrons present on the donor energy level? What I should multiply it with? With Nd only, no? What I am saying is that initially, let's just say I was having 100 donor atoms. Now these 100 donor atoms have two chances that either it can go on this floor or it can go on this floor. This floor was conduction band and this floor was donor energy level. Now I don't know anything about this, but I know that probability of finding an electron here is PED. What I am saying, probability of finding an electron on this donor energy level is PED.
let's just say this probability was 0.4. That means out of these 100, multiply with 0.4, that means out of these 100, 40 would have gone here and 60 would have gone here. Do you agree to this point or not, what I am saying? There are 10 to the power 16 donor energy, 10 to the power 16 donor atoms we are having. So let's do with the real calculation. 10 to the power 16 per centimeter cube, these many donor atoms we are having. It has two chances that it can either go on the conduction band or it can go on the donor energy level. As of now, we are not talking about the conduction band because we know that how many electrons will be there on the conduction band, that we have written down. How many electrons will be there on the donor energy level? That thing we need to find out. So that is equals to ND, small nd, that is equals to small nd. Now, I know the probability of finding an electron here, that is given by PED. So probability of finding an electron on donor energy level is given by PED, that I know. So what I will do, I will multiply it with 10 to the power 16 so that I can get the number of electrons present on the donor energy level. So number of electrons present on the donor energy level will be given by ND. I hope you have got the point. Multiply with PED. Very soon this is coming in the examination, okay, very soon. And believe me, when the answer would come, you would see people applying the formula, blindly applying the formula, not even understanding what does the question mean. Okay, so we are not like that, we will understand it. We are not going to apply any formula. Okay, so this PED value I already know, ND value I already know, 2ND. Basically PED is twice of something, no? So these two I have taken outside, and now I will just simply write down ED minus EF by KT. So this is the value of ND I am having. Equation 1, 2, and this is equation 3. Along with that, what value you have? N value you have. That is NC e to the power minus EC minus EF by KT. Now just let me know what you are supposed to find out. This was your equation 1 only, right? Equation 1 only. What you are supposed to find out? Find the fraction of electrons still occupying the donor state. Fraction of electrons still occupying the donor state. What does that mean? That total electrons were ND. Out of these total electrons, how many electrons are there on the donor energy level? Small nd. So this is something I need to find out. This is my target. So capital ND divided by small nd I need to find out. Okay. So let's do it. Let's do it on a page that I need to add. Small nd divided by capital ND I need to find out. So our target is to finding out this thing, right? So what I can do, this can be written as ND plus N, right? Capital ND is equals to small nd plus N, whatever the electrons that are there in the conduction band plus whatever the electrons that are there in the donor level. Now what I will do, I will divide by ND on both of the sides, on numerator and denominator. So this is what I am left with. So if I get the value of N by ND, my job will be done. So can I get the value of N by ND? Yes. That would be equals to NC by 2 ND, N by ND I am doing. So NC by 2 ND e to the power, here minus EC you are having, minus EC plus EF minus ED plus EF. So ED minus EC you will get, right? ED minus EC you will get. ED minus EC divided by KT. Just you need to divide. I hope you can do this process. It's not that tough, right? So N by ND I need to get, that I am getting NC value 2.8 into 10 to the power 19 and 10 to the power 16. 2.8 into 10 to the power 19. 2 into 10 to the power 16. ED minus EC. EC minus ED value is given, no? EC minus ED value is given. Yeah, EC minus ED value is given 0.045. So here negative value I will put. Divided by 0.0259. So you do this calculation, N by ND value you will get 0.045
divided by 0.0259 plus minus e to the power into 2.8 divided by 2 into 10 to the power 3. 246.35 we are getting. So from here if I find out ND, capital ND, that is equals to 1 plus 246.35. So add 1 and then take the reciprocal. So answer is coming out to be 0.0041, roughly around this much. This is the answer. This is the answer. And if they are asking in the percentage, so what will be the ND by N percent? Like how many percentage of electrons have been still not ionized? So how many electrons, how many percent of the electrons is still not ionized? 0.041. So that means you can call it multiply with 100. So 0.41%. So what does that mean? 99 point 99.59. 99.5%, 99.59% have been ionized and 0.4% are neutral. Did you understand this question or not? Okay, so this question was just the opposite of this particular problem, just the opposite of that, opposite process only we are doing. Although although here you need to think more, right? Here you need to think more what is happening. So all these process, whatever that I told you, just watch this question again, and a very good question for your practice purpose. Okay, so you must have understood a lot of new things here. Well and good. So yeah, these two questions we have done. These two are very good question. Let's move to our next topic. We are going to draw the energy band diagram for semiconductors. Okay, so first we will take the case of uniform, then we will take the case of non-uniform. In uniformly doped semiconductor, we will see two cases. One will be under equilibrium and one will be under external bias, or you can say non-equilibrium. Okay, equilibrium means that there is no external bias, uniformly doped it is. Everywhere it is uniformly doped. So it is, if it is uniformly doped, then have we seen the diagram already? Yes, conduction band, valence band, intrinsic Fermi level, and then something else. What I mean to say is that all the diagram we were seeing with respect to distance only, no? Basically we were drawing energy with respect to x. So there was conduction band there was valence band, and for intrinsic semiconductor, where was your Fermi level? It was somewhere in between, somewhere in the middle. Conduction band and valence band. And what about for n-type? For n-type, what was the scenario? For n-type, all these things are same: conduction band, valence band. But where was my Fermi level? Fermi level was near to my conduction band. Fermi level was near to my conduction band. Also, just for the reference purpose, we will always make the intrinsic Fermi level as well. Although it is not useful here, because your semiconductor is not intrinsic, it has become n-type. But still, for the reference purpose, we will always make the intrinsic Fermi level. Okay, always we will make it. And what about the p-type? Conduction band is there, valence band is there, and where will be your Fermi energy level? It will be near to the valence band. And for your reference purpose, we will always make intrinsic Fermi level as well. So these things I already know. So these I have already studied. More doping means it will be more near to the valence band. More doping means it will be more near to the conduction band. These things also I already know. And with respect to the temperature variation also I know. So this we are drawing energy versus distance. Right? All good, all fine. Now what will happen if I give external bias? So let's write down a few things. We will write it down for the electrons. So you know that electrons will be there in the conduction band, right? This is the conduction band. Electrons will be in the conduction band. What will be the energy of the electrons? That would be equals to EC. If your electrons are there on the EC energy level, that means it is having an energy of EC. And what that would be equals to? That would be equals to the charge on the electron will be negative. Charge on the electron will be negative.
multiply with the applied potential. Do you remember? Energy is equals to QV. So applied potential I am saying is V naught, and what I mean to say is that this is your semiconductor, and what we are doing, we are applying a battery across it, because under external bias, that means we are applying some battery across it. So this battery that we have applied, that is having a potential of V naught. That means electron are getting a potential of V naught across them, and they are having the negative charge. So E is equals to energy is equals to QV. So negative charge, applied potential is V naught. This is any random semiconductor, it could be anything, intrinsic, N type, P type, whatever it is. Okay. So EC is equals to minus QV naught I can tell, because electrons will be there in my conduction band. So minus QV naught, this thing I can tell. Okay. And one more thing I am telling, from now onwards, energy will be written as this kind of E, and your electric field will be written as this kind of E. Okay. This E and this E, both are different. Energy, this kind of E, electric field, this kind of E. So this is your one formula. What will be the formula of electric field? Electric field is given by minus dV naught by dx. I am assuming that this is my x equals to 0 and this is my x equals to L. So direction of electric field is always in the decreasing direction of the potential, right? So from here what do I see? This V naught will be equals to EC by minus Q. So what I can do from equation 1 and 2, minus dy dx, in place of V naught what I can put? EC by minus Q. EC by minus Q. So minus sign will get cancelled out. Q is a constant. So what is the electric field we are getting? Electric field we are getting is, look, basically V naught can be a function of x. What I mean to say is that V naught can be a function of x, right? It will be changing with x, no? At x equals to 0, the potential is V naught. At x equals to L, the potential is 0. So it is changing with respect to x. So this is a function of x. This is a function of x. So V naught is a battery, but Vx is a function of x. So here I should write down Vx. Because this V naught potential, basically if I make the diagram of Vx, how the diagram of Vx will look like? The diagram of Vx. Vx is the potential across my semiconductor. So Vx diagram will look like something like this. That at x equals to 0 it is V naught, and at x equals to L it is 0. So this is how the diagram would look like, right? This is how the diagram would look like. From V naught to 0 it is going, Vx versus x. Okay. So if if your potential is a function of x, then your EC will also be a function of x, right? This is a function of x. So EC is also a function of x divided by Q. Minus sign is already there. So minus to minus will get cancelled out. 1 by Q. Q is a constant. So 1 by Q d by dx EC of x. This is what you are getting, right? So similar thing will be there for the holes as well. It will be there for the electrons as well. So whether it is p type, n type, whatever it is, electric field is proportional to the slope in the conduction band. Electric field is proportional to the slope in the conduction band. Okay. So this thing we have derived. So I am saying that this particular thing will be there for the electron holes for both of them. So electric field will be for both electron and holes. For both electron and holes. So this is a very important relation, very important. Electric field is equals to 1 by E dEcx by dx. Now at your level, in your examination, at your BTech level, always the slope of conduction band, valence band and intrinsic Fermi level will always be same. What I am saying? The slope of conduction band, valence band and intrinsic Fermi level. What I mean to say is that whatever the picture of conduction band you will get, let's just say picture of conduction band is somewhat like this. So the same structure you will get for intrinsic Fermi level and the same structure you will get for valence band as well. Basically EC, EFI and EV will always look the same. Always it will look the same, 100% I am telling. So whatever that is happening for EC, the similar thing will happen for EF as well.
And the similar thing will happen for intrinsic Fermi level as well. Are you able to grasp it or not? So this is the formula that you need to remember. It is very easy to remember. You will not even have to mug it up. Why so? Let's see it. What is the unit of electric field? Volt per centimeter, right? What is the unit of energy? Electron volt. Sir, what do I need? Volt per centimeter I need. So that means I need to divide by centimeter. That means energy should be differentiated with respect to x. Then you will get electron volt divided by centimeter. Now you need to kill this electron. That means you need to kill the charge. So divided by 1 by q. Electric field is having a unit of, sir, volt per centimeter. Voltage divided by the distance. Volt per centimeter. Volt per centimeter I need. I have electron volt, that is energy, per centimeter. That means I need to differentiate it. Sir, electron I need to cancel out. Volt per centimeter I need. So divided by q. So E equals to 1 by q d by dx. There you go. So here I am writing down one statement. What is that? Arey yaar. Just a second, guys. I need to put the charger. Yeah. So here I am writing down one statement. What is that? Your electric field is proportional to d EC by dx. Or you can say it is proportional to d EV by dx. Or you can say it is proportional to d EFI by dx. Again, a very important conclusion. Let's remove it off. Let's write it down here. Very, very important conclusion. How will you say it in the statement? How will I say it? In the direction of electric field, what I am saying, in the direction of electric field, the slope of conduction band will increase. In the direction of electric field, here positive sign is there, no? E is equals to minus dV by dx. The potential is decreasing in this direction. The potential is decreasing in this direction. That means what is the direction of electric field? This is the direction of electric field. Is this the same? Yes. Here there is positive, here there is negative. That means this is the direction of electric field. Right? Because there was a negative sign here. But now if I say this is the direction of electric field, then what will be the slope in the conduction band? What do you think? This will be the slope, no? Because in the direction of electric field, the slope of conduction band will increase. Or I should not say slope will increase, I will say slope will be positive. In the direction of electric field, the slope of conduction band will be positive. Just write it down somewhere. Here you can write down. In the direction of electric field, the slope of the conduction band will be positive. Here in the direction of electric field, this was the direction of electric field. So in the direction of electric field, the slope of voltage was negative. In the direction of electric field, the slope of voltage was negative. That's why the relation was E is equals to minus dV by dx. But here there is a positive sign. So in in the direction of electric field, the slope of conduction band will be positive. Say yes or no. Write it down somewhere. All good? All fine? Next, one more statement is there. So this this statement we kind of prove it, right? We proved it. We proved this statement here. But next proof I am not going to give. So in n-type semiconductor, the current will be in n-type semiconductor, the current will be proportional to d by dx of EFN. And in p-type semiconductor, the current will be proportional to d by dx of EFP. What does that mean? In the direction of current, the Fermi energy level will have the positive slope. Sir, where is the proof? We will see it when we study PN junction. In PN junction, we will see the proof. Okay. As of now, you don't need to see the proof. As of now, what you will say? Sir, in the direction of electric field, the conduction band, valence band and intrinsic Fermi energy level will have the positive slope. What I am saying, in the direction of electric field, conduction band, valence band and intrinsic Fermi level will have the positive slope. And in the direction of current, the Fermi energy level of n-type and p-type semiconductor will have the positive slope. You don't need to mug it up. Very easily you will be able to understand when we see the examples. Okay. So for every possible circuit we are going to draw the energy band diagram.
Like whatever the energy band diagram that we are going to discuss in this video, those only can be coming in your examination. Nothing apart from that would come, and that is my 100% guarantee. So whatever that we are discussing, those only will come. Okay, so just have the patience and keep on looking at it with the like a lot of method. By using a lot of method, I will tell you the energy band diagrams. So previously there was no battery involved. Now what I'm doing is that I'm involving the battery. Okay, so this is your intrinsic, this is your N type, and this is your P type. In intrinsic, previously what was the scenario? This was the scenario, right? When there was no battery involved. Now what is happening? Battery is being involved. If battery is being involved, so what will happen? Here positive potential will go, and here zero potential will go, or you can say negative potential will go. Let's talk about the electrons. Let's talk about the electrons. Here there are electrons, here there are electrons. What is the energy of electrons? Q into V naught, right? Minus Q into V naught. So positive charge that is coming, and electrons are having the negative charge. So positive charge multiply with the negative charge. Positive potential multiply with the negative charge. What will happen? Energy will go down. Are you able to understand this point? What I am saying, positive potential multiply with negative charge. What will happen? So energy on this end, energy at x equals to 0 is going down. Energy at x equals to L. Energy at x equals to L. Here there are electrons as well. Here there are electrons as well. So electrons are negatively charged, and potential is also negative. So negative potential multiply with the negative potential, total will be positive. So energy here is going up and energy here is going down. So this was your conduction band. Now what is happening? This energy is going down and this energy is going up. So this will become your conduction band. And what did I tell you? In the direction of electric field, the conduction band will have the positive slope. In the direction of electric field, what is the direction of electric field? This is the direction of electric field, right? Because positive charge is coming here, negative charge is coming here, so this is the direction of electric field. So in the direction of electric field, conduction band is having positive slope. So by two method we are understanding it. One is, sir, here positive potential is coming, here positive potential is coming, this is about the energy. So positive potential is coming, multiply with the negative charge, energy is equals to minus Q into V naught. Positive potential multiply with the negative charge, sir, what is happening? Energy is decreasing. Negative potential multiply with the negative charge, energy is increasing. So conduction band at this end, at x equals to 0, it will have lesser value, and at x equals to L, it will have more value. So this is what I am drawing. I am drawing the graph of energy versus x. Energy versus x. So this is your energy is shown by capital E versus x. So this is your x equals to 0. This is your x equals to 0. At x equals to 0, the energy has decreased, and at x equals to L, the energy has increased. Right? This was your conduction band. Now, although I know that whatever the slope is there in the conduction band, the same slope will be there in the valence band, and same slope will be there in the intrinsic Fermi level. But still, let's understand more things. How will I understand? Let's remove it off. Now I need to see the slope in the valence band. What I am saying, I need to see the slope in the valence band. Okay. So when I say valence band, what should come in your mind? Sir, when I say valence band, in my mind, holes should come. So in my mind, holes are coming. When I say valence band, holes are coming. Here also holes are there. Here positive potential is reaching, and here negative potential is reaching, right? Positive potential, negative potential. What will be the energy of holes? That would be, sir, positive charge multiply with the positive potential. At this particular end, what will be the energy of holes? Sir, positive charge multiply with the positive potential. That means here the energy is more. For the holes, at this end, at x equals to 0, the energy is more, and here the energy is less. For holes I am saying, because holes are having the positive charge. So positive charge multiply with the positive potential, energy is more. Positive charge multiply with the negative potential, energy is less. So sir, here energy more, here energy less. This is how I should make the diagram. No, the energy of holes increases in the downward direction. So if there is more energy, that means this point here there is more energy, so this point will be downward, and here there is less energy, that means this point will be upward. So this will be the slope in the valence band. That's why I said that the slope in the conduction band and valence band will always be same. Although you don't need to remember all these points to solve the question. To solve the question, what you need to do? In the direction of electric field, the slope in the conduction band, valence band and intrinsic Fermi level will be positive. That we have already seen here. But if you are understanding that what is actually happening, this is what I am telling. What is actually happening? There are electrons as well, there are holes as well. For the holes, what will be the scenario? Holes are having the positive charge, multiply with the positive potential. Energy will increase. In case of holes, getting more energy means going downward, because energy of holes increases in the downward direction and energy of electrons increases in the upward direction. Do you understand this point or not? Right? So this particular point is having more hole energy and this particular point is having lesser hole energy. So this will be the slope, this will be the scenario for the valence band, and then I will make the intrinsic Fermi level somewhere in between. This will be your EFI. Okay, so you can simply see, if this question was coming in your examination hall, what you would have done? You would not think, sir, electrons, holes, positive potential, negative potential, nothing. Make the electric field, in the direction of electric field, the slope of conduction band will be positive. Whatever the slope is there in the conduction band, same in the valence band, same in the intrinsic Fermi level. In some rough notebook, somewhere in your rough work, you can write down all the things that I told. Positive charge, positive potential, negative potential, both applied, energy increases, energy decreases. So here there is less energy for electrons, here there is more energy for electrons, here there is more energy for holes, here there is less energy for holes. Okay, well and good. Although no one will ever ask you the energy of holes. Why so? Because holes are not a particle. In the examination, it will never come that, sir, at this point, energy of holes is more. This thing will never come actually. Why so? Because holes are not a practical particle, no? Or it might be asked, like in theory examination, anything it could be asked. They will make the diagram and they will ask you at this particular point, they will give this energy level as EV1 and this as EV2. So which is representing more energy of holes, EV1 or EV2? So EV1 is greater than EV2, right? For in case of holes. So these things they can ask. In the theory examination, anything could be asked. So every concept should be clear to you. Although I cannot write down all the things, that positive charge will be multiplied with the positive potential, so energy increases. So all these things you need to write down on your own. Notes will be made like this only. Okay. Only thing I can tell is that this is the direction of electric field. In the direction of electric field, the slope of conduction band, valence band and intrinsic Fermi level will be positive. Okay. Let's go to n-type. Here as well, you can make the diagram very easily. How you can make the diagram? So first I will make the diagram how I would have done in the examination. How I would have done? Sir, positive, negative. What is the direction of electric field? Sir, this is the direction of electric field. Previously, I have proved that, sir, in the direction of electric field, all these slopes will be positive. In the direction of electric field, all these slopes will be positive. That means conduction band energy will be increasing like this, sir, like this, and somewhere, sir, right in between, right in the middle, there will be intrinsic Fermi level, sir. Arey wah. Now, sir, second thing, what do I know? Sir, this will have some EFN as well, right? It will have Fermi level for n-type. That will be here. Now you know that, sir, what will be the direction of current? This will be the direction of current. This will be the direction of current in n-type. This will be the direction of current in the n-type. So direction of current is this. What is the direction of current? In the semiconductor, what is the direction of current? This is the direction of current. So this shows the direction of current. In the semiconductor, this is the direction of current. So in the direction of current, the slope of Fermi energy level will be positive. That means in the direction of current, the slope of Fermi level will increase. In the direction of current, the slope of Fermi level will increase. There you go. This will be your EFN. So this diagram you will get. EC, EV, EFN, EFI. If I ask you one more question,
or let's not do it here. Okay, I will frame different question. Otherwise, like diagram will be very complex. You will not be able to understand, sir, from where these things come into action. So let's not do anything here. I will simply ask another question in some other problem. So as of now, you are able to understand what is happening, right? Voltage, then electric field direction. In the direction of electric field, conduction band, valence band, and intrinsic Fermi level will have the same slope, or it will be increasing. And in the direction of current, the slope of Fermi energy level will also be positive, or you can say the Fermi energy level energy will also be increasing. All good? All fine? Okay then. And if I ask you, sir, this gap and this gap, will that be same? Yes. Basically, all these lines are parallel. All these lines are parallel. Why so? Why so? Because you know that the gap between conduction band and the Fermi energy level shows, what does it show? Shows the level of doping. Like if the gap is lesser, if I am saying that gap is lesser here and gap is more here, this is your EC, this is your EFN. So if I say there is lesser gap here and more gap here, what does that mean? That means at x equals to 0, this is your x equals to 0, right? And this is your x equals to L. So that means that at x equals to 0, there is more doping, at x equals to L, there is lesser doping. But is that the scenario here? No, because it is uniform doping. We are studying the case of uniform doping. That means both of these lines has to be parallel in case of uniform doping. That's why whatever the slope is there in the conduction band, the same slope is there in the Fermi energy level as well. But in case of non-uniform doping, you will get this kind of diagram. There at one particular level, you will be having more doping. At other x equals to L, you will be having lesser doping. That means one will be near to the conduction band, other will be further from the conduction band. Near to the conduction band means more doping. Farther from the conduction band means lesser doping, right? So although till this point everything is going very smooth, you can do the same for p-type semiconductor as well. What you will see, sir, positive will go here, negative here, sir. This is the direction of electric field, sir. No Jadda here, okay? No Gutka, no Ajay Devgan, only Elaichi, so that my throat doesn't pain much. As a teacher, all these things comes into action, like throat pain, regular cough, you can see, headache. So when you speak too much, like when I explain, like I get so much of energized, right? You would have seen, मैं बहुत ज़्यादा एनर्जी लगा देता हूँ एक बार एक्सप्लेन करने में, तो उससे दिक्कतें हो जाती है, ठीक है? तो गुटखा वगैरह नहीं खाता हूँ मैं, राजस्थान से, उसका मतलब ये नहीं कि बोलो जुबा केसरी, ठीक है? जुबा केसरी वगैरह नहीं है, ऑल दो हम बेचते हैं यार, गुटखा बेचते हैं, ठीक है? हर मारवाड़ी गुटखा बेचता है भाई, बहुत बिकता है यहाँ पे, या तो गुटखा नहीं चबा रहा हूँ मैं, इलायची चबा रहा हूँ ताकि आपको प्रॉब्लम ना हो, मैं ज़्यादा खांसू ना. तो इन द डायरेक्शन ऑफ इलेक्ट्रिक फील्ड, this will be your conduction band. A same diagram would come, no? So what I am doing, I can simply copy it, but I will just have to remove EFN. What I will have to remove? I will just have to remove this one, because here EFP would come. So here EFP would come and it would be near to valence band. Why so? Why this is the slope? Because what is the direction of current here? The direction of current is this only. This is the direction of current. This is your IN, right? Sorry, IP. In the direction of current, the slope of Fermi level will be positive, or you can say in the direction of current, EFP energy will increase. In that manner, it will increase. Increase for the electrons, decrease for the holes, right? If hole is at higher energy, like this is your energy versus X graph, and this energy I am telling for holes. So this is higher energy or this is higher energy? This is higher energy, right? This hole is having higher energy because it is lower, right? So energy increases for electrons, decreases for holes. So yeah, these are the diagrams. I hope you are able to understand very easily. In the direction of electric field, the slope of conduction band, valence band and Fermi energy level is increasing. In the direction of current, the slope of this Fermi energy level is increasing. Okay. So electric field is associated with this, this and this, and current is associated with this. Okay. Well and good. So as of now all the four are having the same slope. Yes. As of now all these four are having the same slope. Why so? Because valence band and Fermi energy level, this gap should always be constant. Why so? Because there is uniform doping. If there is uniform doping, that means the gap between the valence band and the Fermi energy level should be constant. If there was more doping, that means the Fermi energy level will be near to the valence band, and if there is lesser doping, then Fermi energy level will be farther from the valence band, right? Okay. Let's see our opposite potential I have applied now. Very simple thing. Positive potential will go here, negative potential will go here. So where will be the electric field now? Electric field will be there in this direction. Here also in this direction electric field. Here also in this direction electric field. What will be the direction of current? This will be the direction of current. This will be the direction of current, and this will be the direction of current. Why this is the direction of current? You are understanding, right? Holes will move in the opposite direction to the applied electric field. Holes will move in the same direction to the applied electric field. Then from where the current would come? Although all these concepts are very initial that we studied in the first lecture. So direction of current should be clear. Always the current will be flowing out of the positive terminal of the battery. Always the current will be flowing out of the positive terminal of the battery. That's why I am very easily able to make the direction of current. Direction of current, direction of current, direction of current, direction of current, direction of current. Although here direction of current is not useful because here EC, EV and EFI only is there, right? EC, EV and EFI only is there, no? So here direction of current is not much useful because EC, EV and EFI will always have the same slope that I already know. So let's make the diagram very quickly, because now this is the direction of electric field. This is the direction of electric field. This is the direction of electric field. This is the direction of electron current. This is the direction of hole current. Somewhere in between EFI, EFI, EFI. So all these will have the same slope with respect to, it is coming because of the electric field, right? It is coming because of the electric field. Now coming to this diagram, current, and I know that since this is n type, so your intrinsic Fermi level will be, your Fermi level for n type will be somewhere near to the conduction band. So it will be here, and since this is the direction of current, so in the direction of current, the Fermi level will have the positive slope. Fermi level will have the positive slope, and in the direction of current, the Fermi level will have the positive slope. So this is the direction of current. In the direction of current, you should look. This is the direction of current. So in the direction of current, positive slope. So EF, it will be near to the valence band, and these gaps will always be same. Why these gaps are same? Because it is uniform doping, right? In case of uniform doping, the conduction band and Fermi energy level of n-type semiconductor will have the same gap because doping is uniform. Okay. Now, energy band diagram for non-uniformly doped semiconductor. So now the doping is non-uniform. So if there is doping, that means there is no meaning of intrinsic semiconductor. So now we are going to take only doped semiconductor. That means we are only going to take extrinsic semiconductor. So now this is the first case under equilibrium. That means there is no external bias. So this is your scenario, right? There is no external bias. So what will happen here? The electron will start diffusing here, right? Because of this diffusion, because of this electron are starting to diffuse here. Electrons are diffusing here. Because of this diffusion, what is happening? There is this diffusion current coming into action. Let me use a different color of pen. So because of this diffusion current is coming into the action. This all the process is clear to you, okay? And because of this, what really happened? There was a built-in electric field build-up. There was a built-in electric field build-up. Now, because of this built-in electric field, electrons are being drifted in this opposite direction. So electrons are being drifted in this opposite direction. So electrons are drifting here, and since they are drifting here, then there is a drift current in the opposite direction to the diffusion. So there is a drift current in the opposite direction to the diffusion, and this diffusion and drift current is cancelling out each other. right? And since they are cancelling out each other, so total current is 0 here. So what is the total current? Total current is 0. But total electric field is not 0, no? Right? There is a built-in potential developed. Here there is positive charge and here there is negative charge. So your semiconductor, your n-type semiconductor is feeling a built-in potential. So E built-in is there, and in the direction of electric field, the slope of conduction band will be positive. There you go. Positive. Slope of valence band will also be positive, and slope of intrinsic Fermi level will also be positive. There you go. Conduction band, valence band, intrinsic Fermi level. Did you understand from where the slope came? Because of this built-in electric field. Okay? Because there is an electric field, that means here there is positive potential. If there is here there is positive potential, that means electron energy will decrease, and here electron energy will decrease. Here there is positive potential, that means positive charge multiply with the negative charge, energy will decrease. Positive charge, here there is negative charge multiply with the negative charge, energy will increase. So here less energy, here more energy. So this is the slope. But will there be any slope in the Fermi energy level of n type? Will there be any slope here? No, zero slope. This is your EFN. Why there is zero slope? Because you know that the slope in EFM is proportional to the current, and this current is 0, and since it is 0, then EFN will be constant, or you can say uniform. Better you should say uniform, because it is with respect to x. So I should say uniform. Are you able to understand this point or not? And this is telling another important thing. What is that? Here the gap between EC and EFN is less, and here the gap is more. If the gap is less, that means more doping, and if gap is more, that means less doping. Are you able to relate everything now with respect to energy band diagram? So this energy band diagram we are drawing with respect to x, right? With respect to x. With respect to x, and this is your energy. So energy with respect to x. So at x equals to 0, you can see that there is more doping. So if only this diagram was given, what I could have said? If there is no slope in the Fermi energy level, that means there is zero current. If there is zero current, what does that mean? There is no external battery applied. Yes, first conclusion. Second conclusion, there is a slope in the conduction band in this direction. What does that mean? That means electric field also be in this direction only. Conduction band energy is increasing in this direction. So in the increasing direction of conduction band energy, there will be electric field, because electric field is positive in the electric field, the direction of electric field will be in the increasing direction of EC. So this will be the direction of electric field, and if this is the direction of electric field, that means here positive charge is developed, here negative charge is developed. That means here there would have been more doping, because positive and then there is electron. So here there would have been more doping, here there would have been lesser doping. Or you can directly see from here as well that at this point there would have been more doping, at this point there would have been lesser doping. So are you able to relate everything or not? What will happen in this p type? What will happen? Electrons will diffuse here. Total current I already know will be 0, right? What will be the direction of built-in potential? Here there will be negative charge, holes will be diffusing here. So this will be the direction of built-in potential. This will be your built-in potential, right? So this is your built-in potential. If this is your built-in potential, then what kind of slope you will be getting? Slope you will be getting like this, because here there will be negative, here there will be positive. So this will be the slope you guys will be getting. Conduction band, valence band, and intrinsic Fermi level. Okay. Now since the current is 0, what does that mean? Wait a second. क्या हो गया ये? Holes are diffusing in this direction. Okay. Yeah. Okay. Nothing. Now different color of band. Since there is zero current here, what does that mean? since there is zero current here, what do I know? EFP divided by DEFP divided by dx. Slope in the Fermi energy level, is proportional to the current. That means EFP will be uniform. There will not be any slope. So if EFP is uniform, what does that mean? That means this is how your EFP will look like. No slope, simple straight line. This is your EFP. And if this is your EFP, you can directly see there, here there is more doping and here there is lesser doping. More doping, lesser doping. So is that the correct? More doping, lesser doping. This was your x equals to 0 and this was your x equals to L. So if I just see this diagram, what I will see? First thing, okay, Fermi energy level is near to the valence band, that means it is p type. Second thing, electric field is in this direction, that means built-in electric field would have been developed in this direction. Just by looking at the slope, you can never tell whether it is built-in electric field or total electric field, because this represent about the total electric field. No, here did I write down built-in electric field? Did I write down external electric field? No, it is total electric field. So the slope in this one will represent the total electric field. So I cannot say that, sir, this will be the direction of built-in electric field. No, as of now I cannot make any current. But what I can see is that, sir, here there is more doping, here there is lesser doping. So I will make the diagram and I will get to know that yes, this is the direction of built-in electric field. Secondly, I can see that, sir, here there is zero slope. In the Fermi energy level, there is zero slope. What does that mean? Sir, there is no external battery. So only electric field that is left is built-in electric field. Are you able to understand this point? So all these two diagrams are clear. Now the most interesting part would come. The most interesting part would come. Now the most interesting part would come. Okay, we are going to connect the battery, but we are going to connect the battery in 3 different ways. Actually in 6 different ways. Okay, so how we are connecting the battery? This is your n-type semiconductor. You agreeing to this? I have connected an external battery. Where will be my built-in electric field? This will be my built-in electric field, because I know that my holes will be diffusing here. So this will be your built-in electric field. And where will be your external electric field? Sir, this will be your external electric field, because you know that actually this is your V external. This is my V external. So here positive, negative. So this is my E external. So E external is in the opposite direction to E built-in. And now I am saying that built-in electric field is more than the E external. Built-in electric field is more than the E external. So when it was under equilibrium, what was happening? This built-in electric field was the reason because of that diffusion current was cancelling out. Basically how we started, sir, electrons will diffuse. Okay, because of that diffusion current is coming into action. Because of that we are getting built-in potential. And this built-in potential or this built-in electric field was the reason why we got drift current. And this drift current and diffusion current are cancelling out each other. So this built-in potential was enough to cancelling out diffusion current. What I am saying, what is the expression of diffusion current? What is the expression of diffusion current? That is Q dp dpx by dx. Does it depend on the electric field? This diffusion current, does it depend on the electric field? No, doesn't depend on the electric field. Doesn't depend on E field, right? So whatever the diffusion current you are getting here, the same amount of diffusion current you will get in this case as well. So diffusion current under equilibrium or diffusion current under bias, under external bias, both will be of the same amount. So this is my diffusion current. So whatever the diffusion current I was getting previously, the same amount of diffusion current I am getting now. A very, very important discussion. Okay, keep your full concentration here. Whatever the diffusion current I was getting here, the same diffusion current I am getting here as well, because it doesn't depend on the E field. So same as equilibrium. Same as equilibrium. Same amount as equilibrium I should write down. Not the direction, because someone will understand it is about the direction. No. Same amount as equilibrium current. Equilibrium. Okay. But what is happening with the built-in electric field? This is the direction of built-in electric field, and external electric field is in the opposite direction.
and I know that who is winning? Built-in electric field is winning. So total electric field will be this E built-in minus E external. So this will be your total electric field in this direction. That will be E built-in minus E external. And because of this electric field, what will happen? Electrons will drift in this direction. Electrons will drift in this direction. And because electrons are drifting in this direction, there will be some drift current that will be flowing in this direction, I drift. But this drift will be lesser than this particular drift. Why so? Because this drift was coming because of EBI, because of the built-in electric field. But this drift is coming because of the built-in electric field minus some external electric field. That means this field is low. What I am saying is that surely your EBI is lesser than EBI minus E external. There is no doubt about that. That means this field is lesser than the equilibrium electric field. This field less than equilibrium. That means this drift current will also be less than equilibrium. So this current is more and this current is less. That means what will be the effective direction of the current? So what I am saying here is that I diffusion is more than the I drift. So effectively diffusion current will flow in this direction. Effectively your diffusion current will be flowing in this direction. Are you able to understand this point or not? And eventually we expected that from the positive terminal of the battery current should go out. Yes, from the positive terminal of the battery only current is going out. A very, very important discussion, a great discussion. Nowhere in any textbook, in any lecture you are going to find this discussion. Just you need to think purely. So how did we think? Again let me start. Previously there was equilibrium condition. Now I am connecting the battery. Since I connected the battery, this time I smartly connected the battery in the opposite direction to the built-in electric field. So now what is happening? Built-in electric field is actually getting lesser. If it is getting lesser, that means the drift current is getting lesser. Because of the electric field you get the drift current. And that is getting lesser, and diffusion current doesn't depend on the electric field. It will just depend on the concentration gradient. And whatever the concentration gradient you are getting here, the same concentration gradient was here as well. So same diffusion current is there. But the drift current has been less. So diffusion current will be winning. So diffusion current, here I should not write diffusion current. Diffusion current is winning. This actually current is, this current I is equals to I diffusion minus I drift. So total value of the current will be flowing in this direction. So this is the direction of current. And what is the direction of electric field? Effective electric field. Like this is the built-in and this is the external. So what is the effective direction? This is the effective direction. So here I will use this pen. So this is the direction of total electric field. The total electric field is equals to E built-in minus E external, because E built-in is more. So this is the direction of total electric field. So this is the direction of total electric field. That means this will be the slope in the conduction band, this will be the slope in the valence band, and intrinsic Fermi level will be somewhere in between. Intrinsic Fermi level will be somewhere in between. Conduction band, valence band, and intrinsic Fermi level will be somewhere in between. Now next, current is there, IN is there. So current is flowing in this direction. That means the Fermi level will have the slope in this direction. Fermi level will have the slope, positive slope in this direction, and this is having a slope in this direction like this. This is your EFN. And by default you can see that here there is more doping and here there is lesser doping. Are we agreeing to this? Yes. More doping, less doping, less doping. So it is coming by default. Here you need to make the increasing slope. So if I make the increasing slope like this, by default it is coming that here there is more doping, here there is lesser doping. Are you able to relate everything now or not? Every single thing is related. If this diagram is given, then you will understand everything. That sir, if there is some current, that means there would be some external bias. Okay, external bias is there, sir. You would know, sir, here there is high doping, here there is lesser doping. Second thing is also proven. Next, sir, I will see the direction of electric field. Total direction of electric field is this. So what I may think? I may think that, sir, since this is the total direction of electric field, so the thought that can be coming in my mind would be, sir, E built in and E external are getting added, right? Two things could be there, either they are subtracted or added. So I thought that, sir, they are being added, and if they are being added, then, sir, I thought that total electric field will be in this direction. But if they are added, then what will be the potential of battery? The potential of the battery would have been like this. Then the current would have been flowing like this. And if the current would have been flowing like this, then the slope would have been like this. But the slope is this. That means the current is actually flowing in this manner. So potential of battery would be somewhat like this. And if potential of battery is somewhat like this, what does that mean? They are actually being subtracted. So looking at the diagram, I can make all the conclusion. Basically, looking at this diagram, I can make this diagram in the examination. Say yes or no. Okay. So how you are understanding the explanation? Like, how do you find the explanation? I hope you are enjoying. Right? Every single thing I am explaining with good amount of patience, and with every single thing I am writing down as well. So I hope it is crystal clear to you. Okay. Well and good. So yeah. Next thing is E built in is equals to E external, and in the next case E built in would be less than E external. Do it on your own. Do it on your own. E built in equals to E external. That means whatever the built in diffusion current, nothing is happening to diffusion current. It would be same. Whatever the case was there, this was the direction of diffusion current. Nothing is happening to diffusion current. Diffusion current is same. But since E built in and E external both are in the opposite direction, and you are saying that E built in is equals to E external, what does that mean? E total will be E built in minus E external, and that would be equals to 0. So there is no electric field. If there is no electric field, no drift. So total current IN will be equals to I diffusion only. So again the total current is flowing in this direction, but there is no electric field now. If there is no electric field, then this will be the scenario. The conduction band. Wait a second. No. What I am saying. Yeah, no issue. Basically, let's make the semiconductor, and this was my battery, right? This was my battery. So total electric field is 0. Total electric field is 0, right? Total electric field is 0, but the current direction is this. This is your current direction. And total electric field, E total is equals to 0. There is no electric field. If there is no electric field, then what will happen? Conduction band, valence band, and intrinsic Fermi level. There you go. Conduction band, valence band, and intrinsic Fermi level. But the current is flowing in this direction. EFN. And you can directly see that here there is more doping, here there is more doping, and here there is lesser doping, here there is lesser doping. So this kind of diagram is also possible. No gutka. Okay. No gutka, only elaichi. So interesting diagram, right? Someone will see it directly. Okay, there is no electric field, but there is current. How it is possible? That means it is the case of non-uniform doping. If there is no electric field, that means our built-in and external would have been cancelling out each other. If they are cancelling out each other, then this will be the scenario. So if I will just make this diagram, and I will ask you to make the conclusion that at x equals to 0 there is high doping, at x equals to L there is low doping, at the built-in electric field and external electric field are opposite in the direction and having the same amplitude. So these kind of points I will write down that which of the following statement is true. Okay, so in that manner question can be framed. So everything should be clear to you, and I hope it is clear only. Right? Now what is the scenario? E external is more. E external is more. Diffusion will say, sir, I will have my same thing. There is no one who can stop me. I will have my same thing, sir. This is my I diffusion. No one will. Here, writing down diffusion would be wrong. This is your I diffusion. Diffusion current will say, sir, I will be the same. There is no one who can stop me. But now, this is your E external, this is your E built in. E external is more this time. That means E external will be winning. So total electric field will be in this direction.
total electric field will be in this direction. That will be E external minus E built in. That means electrons will be drifting in this direction. Electrons will be drifting in this direction. This is drift of electron. If electrons are drifting in this direction, then what will be the current of it? This will be your I drift. Both are being added this time. Both are being added in this direction. So again you see, this was your semiconductor. Again here there was more doping, here there was lesser doping, here also there was more doping, here there was lesser doping, and there was more doping. In that manner I am showing more doping. Okay, so this was your built-in electric field. This is your E external. E external is winning. E external is winning. So this will be the effective direction of electric field. So how the slope of conduction band, valence band, and all these things will look like. So this is the direction of effective electric field. So conduction band, valence band, and somewhere in between EFI. Right. Next, what I need to do? What is the direction of current? So drift and diffusion both are being added. So this is the direction of current. Right. So sir, I will have to make slope like this. But now think about it. How will you make the slope? What I am saying is that someone will say that sir, I can make the slope like this. Someone will say that sir, I can make the slope like this. Positive slope only you need to make, no? And someone will say that sir, I will make the slope like this. Which slope is correct? In the direction of current, the slope will be positive, right? So you will say sir, both of those could be correct, but the slope would be like this only. Why so? Because here there is more doping. At x equals to 0 there is more doping, and here there is less doping. So this is your x equals to 0, right? And this is your x equals to L. So here there is more doping. So this is your EFN. Understood? Right? Write down the total electric field. This is your total electric field, and write down the direction of current and make the slope. Then make sure that more doping means near to the conduction band. That's it. Okay. So all these three cases, whatever the cases that can be asked in your examination, surely it is there in your notes. And next case would be very easy. Here you take E built in greater than E external or equal or lesser, but both are in the same direction. So now this is the direction of your E built in, right? And this is the direction of your E external. Both will be added. If both will be added, so diffusion will say, sir, I don't know, electrons will diffuse here and I will generate my diffusion current in this direction. Diffusion will say, sir, I am independent of the external bias. I don't care about the external bias. I only care about the concentration gradient. So diffusion is saying, sir, I am as it is. But now what is happening? Built-in and external both are being added. Built-in and external both are being added. That means total electric field is becoming very high in this direction. So electrons are drifting very highly in this direction. That means diffusion current will be very high drift current will be very high in this direction. Why so? Because when alone built-in was there, then diffusion and drift was getting cancelled out. When alone built-in was there, diffusion and drift are getting cancelled out. But now built-in plus external is there. So drift will say, I am having much more importance now. So what will be the total current? Your final IN current would be in this direction. This will be your final IN current. Do you agree to this point or not? So this will be the direction of your total IN current, right? Yeah, this is the direction of your total IN current. So in the semiconductor, it will be flowing like this. In the semiconductor, it is flowing like this. And this is the case for everyone, no? Either it is greater, lesser, or whatever it is, they are being added. So what do you see? This is your total electric field. This is my total electric field. Conduction, valence, EFI. And what about the direction of current? This is the direction of current. So slope will be positive in this direction. look, this diagram will not become much of clear. Now it is fine, right? Slope is positive in the direction, but I need to make sure that here there is more doping, here there is lesser doping, but slope is positive only. You can see slope is positive only, slope is positive, slope is positive. Okay, so making sure that slope is positive, along with that here there is more doping and here there is lesser doping. So this is your EFM. Direction of current is this only. So direction of the current is always, current will be flowing out of the battery, current is flowing out of the battery, current is flowing out of the battery, current is always flowing out of the battery, current is always flowing, here there is no current. So current will always flow out of the battery. So for the direction of current you will never have to think. Now we will do the same for the p-type semiconductor, and we will never have to think, sir, this external, internal, nothing we will have to think. Okay, and I will show you how to do it. So what we will do, this is for the p-type semiconductor. Okay, first case is built-in is more than, first thing I know that this is my external battery connected, so I know that this will be the direction of current. In all of the cases this is the direction of current. What about the electric field? For electric field I need to think. So this will be my built-in electric field, this will be my built-in electric field, and this will be my external electric field. Built-in, external, right? Built-in is more, so this will be the total electric field, and if this is the total electric field, so I can make the slopes very quickly. In this case, you tell me what will be the total electric field? 0, because built-in and external cancelling out each other. So total slope will be 0. And here external is more. Since external is more, so total slope will be in this direction. This job is done. Job done. Okay. So this job is done. So I am just telling that quickly how I can make it in the examination without thinking too much. Now next I know that this will be the direction of current in all the cases, because from the positive terminal of battery the current will flow. So direction of total current will be, forget about diffusion, drift, sir, I know that this will be the direction of total current. This will be the direction of total current. So in the direction of current my slope will be positive, right? So my slope should be increasing like this, and I know that, just one correction I will do. Slope should be increasing like this. There should be a positive slope, and I know that here there is more doping, at x equals to 0 there is more doping, and at here there is lesser doping. So this is not flat, it looks like flat. What I should do, okay, you guys just need to understand that this is not flat. Now it doesn't look like flat. Okay, doesn't look like flat. You just need to show that there is some slope. There is some slope. So this is your EFP. It will be near to the valence band. Yes, it is near to the valence band. Second, the direction of current will be like this. The slope will be positive in this manner. Secondly, here there is more doping, here there is lesser doping. Job done. Next, there you go. Very simple. This is the direction of current. This is the direction of current. Yes, in the direction of current, slope will be positive. Yes, it is positive. More doping, lesser doping, lesser doping. Here, this will be interesting. What will be the direction of the flow? This will be the direction of the flow, right? More doping, lesser doping, and current will also be flowing in this direction. Current will always come out of the battery. So that's it. This is how I can make my EFP and EFP. Very simple, right? Very, very simple. Just see the current direction, just see the total electric field, just see the current direction, your job is done. And current will be always flowing out of the positive terminal of the battery. That is 100% sure. So if you just flow out of the current, then you will get to know. Here also you can just see in all the example, current is flowing out, positive slope. Here in this, current is flowing out like this, positive slope. Positive slope here. Just make sure that here there is more doping, here there is lesser doping. Positive slope here there is more doping, lesser doping. Positive slope here, more doping, lesser doping. So make the slope, making sure that more doping, lesser doping is also satisfied. Last, both are in the same direction. Then this will be your built-in electric field and this will be your external electric field, and this will be the direction of total current, because from the positive terminal the current will be flowing out, right? But concept was more important, that how this current is flowing, because a lot of students would get that out, that sir, current can flow out of the negative terminal as well. So diffusion is cancelling out or not. So all these analysis I have explained you, right? Which diffusion is cancelling out, which drift is cancelling out. So everything I have explained. Now just you need to draw the diagram. So this is the total electric field which are being added, okay, and this is the direction of current. अरे भाई ये बनाना बहुत मुश्किल हो जाएगा यार. We need to show the slope as well, and I need to make sure that it is increasing in this direction as well. So how will I make it? I need to show the slope as well, and also I need to show that it is increasing as well. First I make this and then I make this. There is more slope. So guys, will you be able to make it, or shall I pause the video and make? I will pause the video and make it. Yeah, so this diagram is fine. Basically slopes should be positive only, no? So slope are positive only. In the direction of decreasing x, all the slopes are positive. This is also positive, this is also positive, this is also positive. In the direction of decreasing x, not increasing x, right? Basically in this direction slope should be positive. So positive, positive, positive. But this slope I need to make sure in a manner that this is my EFP. I need to make sure it should be in a manner that it would be near here and further away from here. So a bit it was tougher to think, but you just think that I just need to make sure that here there is more gap. So this is how, and slope should also be there. So this is how I thought. Then this slope should be equal to this, and this should be equal to this. Okay. So although concept is clear to you, right? This diagram is made in the examination, in the options diagram would be made. So you will be able to click very easily, right? And if this diagram is made, then you will be able to think that what is actually happening. Here there is more doping, then total electric field is like this, then you will be able to understand what all things are happening. Okay then. So yeah, this is the end of this lecture. So in this lecture we studied about Fermi-Dirac distribution, then we draw the energy band diagram. It was a very fruitful session, because from this particular session the question is surely coming. If they are framing good question on EDC, then from here the problem will surely come. Now almost the syllabus is completed. We need to see some practice problem and one or two concepts we need to see, like what is quasi-Fermi level, that we need to see. And there was one more query, right, which I asked in the first session. What that was, that in the conduction band there are electrons, in valence band there are electrons, conduction band is completely empty. At room temperature, how they are getting enough energy to make a transition from valence band to conduction band, right? Room temperature the energy is 26 milli electron volt, but the band gap is 1.1 electron volt. So how this 26 milli electron volt is enough to make a transition from conduction band, from valence band to conduction band? So that question I will answer, right? Because now we have studied Fermi-Dirac distribution, so I will be able to answer. And along with that, we will understand about Quasi-Fermi level, and then we will solve some questions. So next lecture will be of roughly around 1 or 2 hours maximum, and after that everything will be completed. All good, all fine. So I hope you enjoyed the lecture, and don't forget to put a like. If you are watching it on YouTube, don't forget to put a like. Okay, and do share it with your friends, that let them know that these kind of things are being discussed here. These kind of all the diagrams are being discussed here. Every single thing, whatever that can be asked in the examination, every single diagram is discussed here. Okay, and more problems we are going to see. So yeah, just share it, and okay then. Thank you very much. Happy learning. Yeah, hi everyone. So this will be the final video of basic semiconductor physics. So all the concepts are completed, just some miscellaneous concept we are going to see, and then we will solve the problems. So first this question was there, that let's just consider the case of intrinsic semiconductor. There will be conduction band, there will be valence band, and there will be Fermi energy level as well. We can make that Fermi energy level as well. Okay. So there is conduction band, there is valence band, and there is Fermi energy level as well. Okay. Between conduction band and valence band, there is an energy gap of 1.1 electron volt. In valence band, there are bound electrons. At room temperature, they are getting an energy of 0.0259 electron volt. How this much energy is more than enough to make a transition from the valence band to conduction band? This was the question, right? Because they need to make a transition of 1.1 electron volt. So how this much energy is enough to make a transition from valence band to conduction band? This is the question. So first let's see it with respect to the mathematics. So what is the probability of finding an electron in the conduction band? What I am saying, what is the probability of finding an electron in the conduction band? So that is given by e to the power minus EC minus EFI, since I am considering the intrinsic semiconductor, right? What do you think, what will be the gap of EC minus EFI? By default I will take it is in the middle, because for intrinsic semiconductor it would be in the middle only. So by default I will take this is in the middle. So this will be 0.55. So what I am getting, 0.55 divided by 0.0259. So what we are getting, somewhat some pretty low value you will get. So you can find it out, 0.55 divided by 0.0259 plus minus e to the power. So you are getting somewhat around 6 into 10 to the power minus 10. This is the probability, not a particular number. This is the probability that an electron can be found in the conduction band. Very low, but it is not zero. You cannot say that sir probability is zero. Although for mathematics you will say sir it is nearly zero only, but still I would say there is a finite probability, there is a non-zero probability, that is 6 into 10 to the power minus 10. A very low probability that any electron could be found in this conduction band at 300 Kelvin. This is the probability that we are getting. But what will be the number of electrons in the conduction band? Why so? Because there will be a lot of states, no? This is the probability of finding an electron on this particular energy state only, on this EC state. But there are a lot of states which is having energy nearly to EC only. So what will be the total number of electrons? Total number of electrons will be number of states multiply with f of EC. This we have already seen, right? Total number of states available, effective density of the states multiply with finding the probability of electron at a particular energy state EC. I am assuming that all these are having the energy of EC only. Although they will have some slightly higher energy, but assuming that all of them are having the energy of EC only. So if this is the probability at EC, then at all of them as well the probability will be EC only. So I can multiply NC with f of EC. There are a lot of states, no? So how many states are there? 2.8 into 10 to the power 19. What is f of EC? 6 into 10 to the power minus 10. Roughly what answer you are getting? Into 2.8 you do 1.67 into 10 to the power minus 9. So 1.6 into 10 to the power 10. So these many electrons you are getting. This would be equal to intrinsic carrier concentration only. So in silicon we say that this is our intrinsic carrier concentration, and by the mathematics we have proven it. So what really happened here was, although the probability that electron will make a transition from valence band to conduction band, that probability is very low, 6 into 10 to the power minus 10, but still it is not zero, and there are a lot of states available. There are a lot of states available for the electron to occupy. That means the number of electrons that will reach here, that is somewhat considerable. So 1.5 into 10 to the power 10. So at room's temperature it can conduct the current. So this is with respect to mathematics we have proven. In an interview if they are asking this question, then you can prove it like this. So I will use the Boltzmann statistics. Using the Boltzmann statistics, this is the thing that I can write down, that finding the probability, what will be the probability of finding an electron at conduction band, or I should not say conduction band, at the EC energy state, at the EC energy state. What is EC? EC is the lowest energy of the conduction band. So this is the probability, and now there are a lot of states. Number of states are roughly around 2.8 into 10 to the power 19 centimeter cube inverse. So sir, this will be the intrinsic carrier concentration present in our intrinsic semiconductor. So these number of electrons are present in the conduction band. That means these number of holes will be present in the valence band, right? If these many electrons are present in the conduction band, then these many holes will be present in the valence band because electron hole pair will be generated. But let's understand it with respect to the crystal. So in crystal, what will happen? Like you will be having silicon, and silicon will be having bound electrons. Then again silicon, bound electrons. Now this energy that you are saying, which is 0.0259 electron volt. So this is not a certain number. Like it's not that, sir, there is some electron. This electron will be getting 26 millivolt. So this electron will also get a 26 millivolt. This electron will also get 26 millivolt. This electron volt is also getting 26 millivolt. It's not like that. It is distributive in nature. Have you studied Gaussian distribution, linear distribution in our communication system or in our mathematics? That it is like it is distributed. At some point you can get more energy, and at some point you can get less energy. So basically this 26 milli electron volt packets you are having, some will get more packets, some will get lesser packet. So some electrons may get more energy and some electrons may get lesser energy. And there are silicon atom as well. So basically atom and electron both will be vibrating because of the thermal energy. Some electrons will be vibrating more, some atoms will be vibrating more, and some atoms will be vibrating less. So these atoms will frame a wave-like nature. These atoms will frame a wave-like nature. Basically what I am saying is that, let's just say this atom is going up, this atom is going down, next atom is going up, next atom is going down. So this wave-like nature they have framed, no? Right? And this wave-like nature only is known as phonon. So because of this wave-like nature, if electrons are colliding with this nature, if electrons are colliding with this oscillating atoms, so let's just say there is very high oscillation. Some atoms are having very high oscillation, some atoms are having very lesser oscillation, and electrons are bound to it. If electrons bound to these oscillations, if these bound electrons are colliding with these oscillations, then they can release very high energy, and that energy would be more than enough for them to make a transition from valence band to conduction band. So this is what is written. When an electron is interacting with one of these rare high energy vibrations, then it can gain enough energy in a single event to cross the band gap. So basically electrons are bound, and these atoms are vibrating like this. Some will be vibrating with very high energy, some will be vibrating with lesser energy. So now that energy would be more than enough to break a covalent bond, and electron will be getting enough energy to make a transition from valence band to conduction band. So either you explain by mathematics or you tell them this thing. Okay. So a very good interview question. In some of the other video as well, like some of the educator was also explaining this particular doubt of some student, and he was saying that some trap energy level will be present. Like between the conduction band and valence band, there will be some trap energy level will be present. So these electrons first they will gain 26 millivolt, then they will again gain 26 millivolt. In that manner they will reach to conduction band. He explained that, and in the end he said that don't ask these questions to other educators because they will not be able to explain, like arrogantly, like those people will not know. I am explaining it, but other people will not be able to explain. I am not taking the name of educator, because when I am teaching, I watch the lectures of every educator, every GATE educator, every NPTEL lecture also I watch, and books also I read, just to know that what they are teaching, because I need to teach better than them. That's the bottom line. Okay, this is how you teach, this is how you make your content. So sometimes it is funny that these kind of good questions are answered in this manner, that too arrogantly. Like if you don't know, you can simply say, right? But you answer and then you say that if you ask other teachers, they will not be able to tell. Yeah, they will not be able to tell this explanation. I'm pretty sure he wouldn't even know what is the meaning of trap energy level. Pretty sure. Okay. Yeah. Funny. Sometimes it is funny. And those are actually very famous. Like they have been teaching for 10 to 15 years. They are doing this kind of error. I am teaching for 2 years. Probably I will not teach for 10 years. And if I teach for 10 years, then I will not have any arrogance. Because if I teach only 1 or 2 subjects for 10 years, what kind of arrogance I should have? Why I should have an arrogance for a subject? You are watching this video, no? Like if you teach a particular subject or 2 subjects or 3 subjects for 10 years, you will be master in that. You will be able to teach in good manner. Like you might be a very average guy. Then also you will be able to teach it in a very good manner. Because 10 years you are reading the same thing. Those only 200 hours you need to teach. Those 200 hours only you need to think. दे विल बी सेइंग आई कैन टीच फॉर 1000 आवर्स, आई नो दिस थिंग दैट थिंग। गेट के एग्जाम के सवाल सही से होते नहीं, ठीक है। गेट के एग्जाम में थोड़ा सवाल इधर उधर हो, दिक्कत हो जाती है। चलो लेट्स नॉट वेस्ट द टाइम, ओके। Look, I'm not saying against them. They say against me, that's why I have to say against them. I will never ever start, because when I started this channel, you go to my older videos, you would see how respectfully I used to take the name of educators. Like, he is a very good educator, he has taught this thing, you can study from him. So this is how I used to take their name. But if someone is doing good and you cannot accept it, you always pull their leg, then I'm not there that I will stay silent and just bear everything just for the name of that they are the teachers. I'm also educator, no? Like, no one here is teacher, all are educators, all are doing their work. Teacher is a separate thing. Teacher you can get in your school life. In this coaching life, you will never get the teachers, you will get the educators. Although I try to connect with the students, but again, like, I never ever say anything, any student to get emotionally attached to anything. Like, after the age of 21, you should never get emotionally attached to anything, okay? Not just the educator, to opposite gender as well, to anyone. Never ever try to get emotionally attached, okay? Just few life lesson I am giving. So saying that we think for students, we think that for student, we are there for the students, हम students के लिए अच्छा करना चाहते हैं, हम ऐसे हैं, गुरु भगवान का रूप होता है, ये होता है, वो होता है. And then your language, then see your language. Contradict, कितना contradict? I will tell you one thing, like, in your life, whenever you go, okay, wherever you go, if someone is saying that he is honest, if someone is saying that he is the most genuine person, then he is the biggest fraud, okay? The genuine and the honest person never needs to tell that he is honest or he is genuine. If someone is saying that मैं साहूकार हूँ, मैं सब कुछ, मैं तुम्हारा अच्छा चाहता हूँ, तो उससे खराब कोई नहीं चाहता तुम्हारा, या फिर इधर ही डजंट केयर या फिर वो आपका खराब चाहता है, वो वास्तव में अच्छा तो नहीं चाहता, क्योंकि जो आपका अच्छा चाहता है ना, उसको बोलने की जरूरत नहीं है. कभी आपने देखा आपका बेस्ट फ्रेंड आपको ये कहता है कि मैं तेरा बेस्ट फ्रेंड हूँ? दो लोग बेस्ट फ्रेंड होते हैं, उन्होंने कभी शेयर ही नहीं किया कि वो बेस्ट फ्रेंड है, उन्होंने आपस में कभी शेयर ही नहीं की ये चीज, है ना? Like, two people who are the best friends, they never say that we are the best friend, right? So those who actually care for you, they will never say it. Parents कभी कहते हैं, like, do your father ever say that he cares for you? No, he just shows the care, he never tells this, right? In our field, you will see a lot of educators saying that we care for you. No, if you care, then why were your course prices were 50K? Why don't you provide courses on YouTube if you care so much? I'm not saying that I care for you. If I care for you, then I will provide every single thing, every single subject, everything on YouTube for free. I cannot do that, right? Because I need to earn as well. I care about myself as well. So if I need to care about my student community, then I need to stop caring about myself, which I cannot do as of now. Who knows, at the age of 30, I might be doing this thing, that I am caring only for the students, not for myself. Because at the 30, who knows at what level I am, right? But as of now, I am 24 and I need to care about myself, right? You are also 21, 22. You also need to care about yourself. Why you are studying? You are studying for the money. So let's be just straightforward. Let's not sugarcoat the things. Let's not do the strawberry talks here, right? So strawberry talks are good to listen. It would make my image better in your eyes, that he is a great educator. What a human being he is. But I am that kind of guy who has always been genuine. Okay, again, now I am saying that I am genuine, but you guys would also know if you are following me for other courses as well. Like, if you are just watching EDC, then you would know it. But if you are following me for the other courses, like, whenever I say anything, I am pretty straightforward for that. If I will be doing this thing, like, if I am saying that basic semiconductor physics will come on YouTube, then it will come on YouTube. If I am saying that complete EDC cannot come on YouTube, then it cannot come on YouTube. That's it. I will never start saying that this subject will be completed and in between I am leaving it. No, this will never happen. Okay, so just being straightforward. Let's get started. Let's go to the next one. Since it is the last lecture, that's why I'm here killing the time. Okay, yeah, Quasi-Fermi level. What we need to study about Quasi-Fermi level. So we don't know, sir, what is this Quasi-Fermi level. Let's solve a question. With respect to the question, you will be able to understand what I mean by Quasi-Fermi level. So there is an n-type semiconductor with equilibrium electron concentration as this, and intrinsic carrier concentration as this. Now what you are doing, you are throwing a light, you are doing illumination, whatever you want to do, you are disturbing the equilibrium. So you have disturbed the equilibrium, because of that excess electron hole pair are being generated, which are 10 to the power 13 centimeter cube inverse. So first you need to find out the Fermi level for the first case, then you need to find out the Fermi level for the second case. Like first case, when it was under equilibrium, when equilibrium was there. So what was the scenario? N naught was 10 to the power 15, Ni was 10 to the power 10, and your P naught would be 10 to the power 5, right? Do you agree to this point? N naught into P naught is equal to Ni square, because thermal equilibrium is there. I have applied which law? I have applied the mass action law, right? So what I need to find? First I will find out the position of Fermi energy level in equilibrium. Position of Fermi energy level. So let's find out the position of Fermi energy level. So what do I know? N is equals to Nc e to the power minus Ec minus Ef by kT. Can't apply this formula because I don't know the value of Nc. Then I know that for intrinsic semiconductor, when it was intrinsic, at that time number of states was same, e to the power Ec minus, in place of Ef, what I can put? EFI divided by kT. And when I am doing for N type, I can put EFN here. So from here I can get the answer, right? So N by Ni, what that would be equals to, and this formula also we already know, what we will get, EFN minus EFI would be equals to kT ln N by Ni, right? So kT value I know, it is all happening at room temperature, 10 to the power 15, N naught divided by Ni. So 10 to the power 5 so 0.3 electron volt below. So what do you see here? This is your conduction band. Forget about the valence band. Okay, let's make the valence band as well. And this will be my Fermi energy level. This is my Fermi energy level. This is the conduction band and this is the valence band. What is this gap? 0.3 electron volt, right? Now I can find out this gap. Basically, I can find out the gap using another formula as well. Sorry, not this gap. Really sorry guys. Which gap we have find out? EFN minus EFI we have found out. Sorry. This gap we have find out. This gap is 0.3 electron volt. Now some other formula also I have. Which formula? Sir, here you are using the formula of only electrons, but you can use the formula of holes as well. What will be the number of holes? Number of holes in your N-type semiconductor. What it is? It is an N-type semiconductor. So number of holes in N-type semiconductor. What that would be? Nv e to the power minus Ef minus Ev by kT. And it is going as N-type semiconductor only. So I am putting EFN here, right? And what I will get? Ni is equals to Nv e to the power minus EFI minus Ev by kT. This will be your Ni. Intrinsic carrier concentration. Are you able to understand this point? This formula I am applying only for N-type only. In N-type, will there be holes? Yes, there will be holes. What will be the probability of finding the holes in the valence band? This will be the probability of finding the holes in the valence band. Since you are doing the calculation for N-type, I am putting N here. What will be the number of states in the valence band? Nv. Now, when it was intrinsic, then what was the probability of finding the holes in the valence band? This was the probability of finding the holes in the valence band. What was the density of states? Nv. So Ni was equals to Nv into this thing, right? So if you do this calculation, P naught by Ni, what answer you will be getting? So you will be seeing that it would be equals to EFI minus EFN. Okay, that would be equals to, this is your EFI. No. If you multiply both of them, P divided by N naught you will be getting here. EFI would go upward, EFN would be here. So EFI minus EFN, what you are getting? EFI P naught divided by Ni.
P naught divided by Ni. So let's do Ni divided by P naught. What I am doing? Ni divided by P naught I am doing. Ni divided by P naught. So what will happen? NV will get cancelled out. This will be upward. This will be plus EV and this will also be plus EV. So that will be cancelled out. This will be minus EFI and this will be plus EFN because that would be coming upward. So you can do the calculation. You will get to know that this is something we are getting. And what we are getting? EFN minus EFI is equals to KT ln Ni by P naught. And it is pretty obvious as well, no? Because you can apply the mass action law here. What is this? KT ln. Here, what I can see is that in place of N naught into P naught, what I could have put? I know that there is a mass action law Ni square. So in place of N naught, I could have put that N naught is equals to Ni square by P naught. So in place of N naught, I could have put Ni square by P naught. So if I put this here, what I will get? Ni by P naught. The same formula I am getting here. Basically, if you solve this, the same answer you will get, which is 0.3 electron volt. And it is pretty obvious as well, no? Because we have seen that for N-type semiconductor, if I draw the energy band diagrams, then conduction band, valence band, intrinsic Fermi level, and your Fermi level will be near to your conduction band. Okay, and the gap between intrinsic Fermi level and EFN is 0.3 electron volt. This we have already seen, and it is pretty obvious as well because here there is mass action law valid. So in place of N naught, you can put Ni square by P naught. So in place of N naught, if I put Ni square by P naught, so what I am getting? The same thing I am getting, this same formula I am getting. So answer would also be same. Simply you put the value of Ni, what that would be? 10 to the power 10. What will be the value of P naught? 10 to the power 5. So what you will get here? ln 10 to the power 5. Here also I am getting ln 10 to the power 5. KT value will be 0.026. So here the same answer you will be getting 0.3 electron volt. So there is only one Fermi level which is near to the conduction band, and the gap between the intrinsic Fermi level and the Fermi level of N-type is 0.3 electron volt. Till this is the condition of equilibrium. Till this point everything is fine. Now what we are doing is that we are disturbing the equilibrium. So number of electrons, what will be the number of electrons? 10 to the power 15 plus 10 to the power 13. So now the number of electrons have reached to 10 to the power 13 plus 10 to the power 15. So you can write it down as 101 or 1.01 10 to the power 15. So this will be 100 into 10 to the power 13. That would be 101 into 10 to the power 13 and 1.01 into 10 to the power 15. So there is not a significant change in the number of electrons. But what will be the number of holes? P naught plus delta P 10 to the power 5 plus, previously it was 10 to the power 5, now plus 10 to the power 13. So it will be nearly equals to 10 to the power 13. Now if I apply the formula that EFI, now what is the scenario? Equilibrium is disturbed. Equilibrium is disturbed. This is the scenario of non-equilibrium. Now I am not deriving the formula, I already know. EFN minus EFI. EFN minus EFI is given as KT ln n number of electrons divided by Ni. So number of electrons are n this time divided by Ni. So almost the same answer you will be getting. Value of n is 1.01 10 to the power 15 divided by 10 to the power 13. So previously actually I was getting the answer as 0.299. So I will write down the exact answer 0.299. Okay, here the answer was 0.299 electron volt. So let's write down the exact answer. Just I know that some answer would be changing, like a bit of answer would be changing, because 1.01 Ni value is 10 to the power 10, sorry, 10 to the power 10, right? Ni value is 10 to the power 10. So 1.01 into 10 to the power 5, and then you need to take ln, then 0.0259. ये कम कैसे आ रहा है भाई पहले से? 0.0259 1.01 5 10 to the power 5 01 ln into 0.026.
Yeah, nearly the same only we are getting. In the next page I have written it down, 0.2982, 0.2984. So here it will come out to be 0.2982. Okay, 0.2982, 0.2982, and now it is coming out to be 0.2984. That means there is no significant change. But if you apply the other formula, of EFN minus EFI, what was the other formula? KT ln Ni by P. What do you get? 0.026 ln, what is the value of Ni? 10 to the power 10 divided by what is the value of P? 10 to the power 13. So if you solve it, what you are getting? 10 to the power 3, right? Then you take ln into 0.026, 0.179, but in the negative. What does that mean? That means EI minus EFN, you are getting 0.179. Here you are saying that EFN minus EFI is this value, and now you are saying that it is this value. There is a problem, right? So now you need to define two levels. When there was equilibrium, from this formula and from this formula you are getting the same answer, because mass action law is valid. But here mass action law is not valid. Number of electrons multiply with number of holes, 10 to the power 28. It is not equal to Ni square. Ni square is 10 to the power 20 only. So when this is the scenario, when mass action law is not valid, when you are not under the equilibrium, then you need to define two levels. This is n-type semiconductor only, but in n-type semiconductor as well, I will define two levels, that will be FNQ and FPQ. So actually here I should write FNQ, and here what I will write FPQ. So with respect to the hole concentration and with respect to the electron concentration, I am getting different answers. So these are your imaginary two quasi-Fermi levels. Are you able to understand this point or not? So before equilibrium, this was the scenario. So here I can say that my EFN was equals to EFP. If I am calculating the difference taking the whole concentration into action, if I am calculating the difference taking the whole concentration into action, or if I am calculating the difference taking the electron concentration into action, I was getting the same difference, that was 0.2982. Then mass action law became invalid, non-equilibrium condition. So you get to know that here number of electrons are not getting changed. Then if you are finding the gap taking number of electrons only, you are getting the same gap, 0.2984, just nearly the same gap. But if you are finding the gap using whole concentration, then your answer is 0.179 electron volt. What does that mean? This Fermi level is below intrinsic Fermi level by 0.179 electron volt. So basically what you are seeing is that this EFN is being divided into two parts. This EFN is being divided into two parts. Those two parts are EFNQ and EFPQ. Okay. So this theory has been written. In equilibrium, a semiconductor has only one Fermi level. This describes both electron and holes. But in non-equilibrium, electrons and hole cannot be described by the same Fermi level. Electrons will have their own Fermi level. Holes will have their own Fermi level. Electrons will have their own Fermi level, that is known as electron quasi-Fermi level, and holes will have their own Fermi level, that is known as hole quasi-Fermi level. Okay. So what is the key idea? Key idea is that if you are at the equilibrium, then EFN would be equals to EFP would be equals to EF. So you can simply call it EF. But if there is extra charge carriers present, then EFN and EFP will be split apart. These will be split apart. Okay. And as much gap is there, if this gap is larger, that means there is more unequilibrium. What does that mean? That means you are more towards non-equilibrium. Basically, when this gap was 0, when EFN minus EFP was 0, when this gap was 0, here EFN was equal to EFP. When this gap was 0, that means equilibrium, right? Equilibrium, yeah. When this gap was 0, that means there was equilibrium. When this gap has become 0.2984 plus 0.179
179 electron volt, then the equilibrium is disturbed. So looking at the diagram, if you see that you are getting 2 Fermi level, that means the concept of quasi-Fermi level has come into action. What does that mean? That means there is non-equilibrium condition in your semiconductor. Sir, why this non-equilibrium condition is important? Because we are going to use this concept in PN junction. So where it will be used, that you are not able to understand. But sir, what is the meaning of quasi-Fermi level, that you are able to understand. Where this meaning will be used, that we will see in PN junction. But as of now, what you have understood, that ideally we should have only one Fermi level if equilibrium condition is there. In non-equilibrium condition, we will get 2 Fermi level. If excess carriers are there, if excess carriers are generated, then we will get 2 Fermi level in same semiconductor, in one semiconductor only. Okay, all good. So that's it. This is the meaning of quasi-Fermi level. There is very rare chance that any question can be asked from here, but it will be used in our analysis in PN junction. That's why we are studying it here. All good? All fine? With the example it is clear to you, otherwise it would become very complex to understand, but with the example it is clear. Number of electrons, number of holes, thermal equilibrium, this was the condition, thermal equilibrium disturbed, this is the condition. That means one Fermi level is split into 2 Fermi levels. These are known as quasi-Fermi level, one for electron, one for holes. As much gap is there, as much you are moving towards a non-equilibrium condition. That means the larger the separation between them, the stronger the non-equilibrium condition. Okay, let's see this question. The equilibrium and steady state before and after illumination of a semiconductor are represented by the energy band diagram shown below. These two energy band diagram they have made at 300 Kelvin. Intrinsic carrier concentration they have given, mobility and all these things they have given, electron charge they have given, KT value they have given. Calculate the percentage increment in the conductivity due to illumination. So this is before and this is after. So what was the condition before? What is the condition after? That we need to see. So what we need to find? So first we are solving for the before illumination. Before illumination. So what would be the conductivity? Conductivity would be N Q mu N plus P Q mu P. So our target is to find N and P. What do I know? EFN minus EFI. EFN minus EFI. That would be equals to KT ln N by Ni. This is the formula. EFN minus EFI. KT ln N by Ni. From here in this manner you can derive it, KT ln N by Ni. But this is before equilibrium, so I will write down N naught by Ni. This is at the equilibrium, no? So N naught by Ni I am writing down. So this value is 0.3 electron volt. It is equals to 0.0259 electron volt. N naught by Ni. Ni value is 10 to the power 10. So previous value you will be getting the previous values only. So yeah, 10 to the power 10. You will be getting 10 to the power 15 here. Roughly around 10 to the power 15 you will be getting. So let's check it. Still we will check it. 0.3 divided by 0.0259. Then e to the power 1.07 into 10 to the power 5. And then 10 to the power 10. Yeah. So N naught value you are eventually getting, because Ni value we already know. That is 10 to the power 10. Ni value is 10 to the power 10. That would be 1.07 10 to the power 15 centimeter cube inverse. So this was your N naught value. What will be the value of P naught? P naught will be somewhat around 10 to the power 5. So nearly you can ignore it. 10 to the power 5 will not make much of the conductivity, right? You can ignore it. So sigma will be equals to 1.07 into 10 to the power 15 into 1.6 into 10 power minus 19 into mu n. What is the value of mu n? 1350. So let's see what answer you will be getting. 1.07 into 1.6 into 0.135. 1.07 into 1.6 into 0.1350. So 0.23.
0.23 Siemens per centimeter. Say yes or no. Okay, because everything is going into the centimeter, rest all the things are fine. Now after illumination you can see that this value they did not mention, but this value they have mentioned, EFN minus EFI minus EFPQ they have mentioned, EFI minus EFPQ they have mentioned. So here I have seen the formula, EFPQ minus EFI was KT ln Ni by P. So EFI minus EFPQ would be KT ln P by Ni, right? So what I need to do now after illumination, what they are saying is that your EFI minus EFPQ is given by KT ln P by Ni, 0.026 is equals to 0.3 again ln P by Ni. Same calculation, no? 0.3, 0.025, this gap is 0.3, this gap is 0.3. So from here what do you understand? That P value is coming out to be, after illumination, P value is coming out to be 10 to the power 15 or 1.07, whatever you want to write down, 1.07 into 10 to the power 15 centimeter cube inverse. Now this P value would have been what? This P value would have been P naught plus excess carrier. So what is this P value? 1.07 into 10 to the power 15. What was your P naught value? 10 to the power 5. That means all of these is converted into the excess carrier only, right? So from here you can see that delta P is approximately equals to 1.07 into 10 to the power 15 only. So after the illumination, whatever the number of holes you are getting, you get to know that these number of holes are much higher than the carrier, much higher than thermal equilibrium, or you can say before illumination condition. So these are much higher than the thermal equilibrium number of holes. So these holes are much higher, that means all these holes are generated because of illumination only. So same number of electrons will also be generated. A lot of people will forget this thing. They will forget to write down that number of electrons will also be generated in the same amount, no? So same number of electrons will also be generated. So now what is the condition? That this is the number of electrons. So this is the number of holes. But what is the number of electron now? The thermal equilibrium electron plus the excess electron. So what is the thermal equilibrium electron? Thermal equilibrium electrons were 1.07 into 10 to the power 15 and excess are also 1.07 into 10 to the power 15. So what it would be? 1.07 into 10 to the power 15 plus excess 1.07 into 10 to the power 15. So it would be 2.14 into 10 to the power 15 centimeter cube inverse. So these are the number of electrons and these are the number of holes, right? Although this calculation was, also necessary to find out the delta P. From delta P I can find out the delta N. Now I have the value of delta N, I have the value of P as well. Now my job will be done, because now what will be my sigma? Sigma nu. Here I am putting sigma old. So my sigma nu will be this N, which is 2.14 into 10 to the power 15 and Q mu. What is the value of mu? 1350 plus, what is the value of P? This is the value of P. P Q. What is the value of Q? 1.6 into 10 power minus 19. What is the value of mu? Mu value is 460. 460. So what will be this calculation? This calculation will simply be double of this. That means it will be 0.46 plus, what will be this calculation? This will be 0.23 into 460 divided by 0.23 into 460 divided by 1350. So you can do the calculation on your own. 0.078. This is coming out to be 0.078 Isn't it too much? Yeah, plus 0.046, sorry, 0.46, 0.53, 0.5387. This is your sigma nu. So what is the percentage change? Let's just say I was having 50 rupees. Now I am having 120 rupees. Or you can say now I am having 100 rupees. So how will I find out the percentage change? 100 minus 50 divided by 50. Basically from 50 to 100 you have. That means you have got the 100% growth, no? From 60 to 60 you get. What does that mean? That means 20% of this growth. In 50 you get plus 20%. So how will you find out? 60 minus 50 divided by 50 into 100, right? So 100 minus 50 divided by 50. That means new minus old divided by old. So what they are asking? Percentage increment. Percentage increment. That would be new minus old divided by old. Into 100%. So 134% you are getting. Okay, well and good. Understood? Yeah, so that's it about this question. I hope you are able to understand. So whenever the question is coming on conductivity, always remember that you need to take care of minority excess carrier concentration and majority excess carrier concentration as well, because a lot of time people will be forgetting this. They will forget this delta n, and if you forget this delta n, answer will be messed up, because here it will be twice of that. So this delta n you should not be forgetting. Okay, now we will discuss 6 questions, easy questions these are. This is the first one, this is the second one, third, fourth, fifth, and then this is sixth. So these 6 questions you try on your own. I think you should be able to solve most of the questions on your own. Out of 6, at least 4 you should be able to solve. Out of 6, 4 you should be able to solve. Okay, so let me take a break and then I will come back and we will start solving these questions, and then our basic semiconductor physics will be completed. Okay, yeah, so did you try this question? In this question, what you need to find out? Electron current density you need to find out. So there is a semiconductor. Okay, they are talking about only electrons, so surely it is an n-type semiconductor, but let's not, it is not important whether it is n-type or p-type, whatever it is. And you can see the doping profile. Here there is lesser doping. At x equals to 0 there is lesser doping, and at x equals to L there will be more doping, and you can directly see here as well. 10 to the power 15 q alpha x divided by kt. That means at x equals to 0 you will be getting the value of 10 to the power 15, and then at x equals to infinity you will be getting infinite value. That means it will be increasing. Here there is no negative sign. If it was negative sign, then it would be decreasing, but your coefficient is positive only, so that's why it is increasing. So value is exponentially increasing. So electron concentration, here there is lesser, but here there is more. If here there is more concentration, then what will happen? Electrons will diffuse in this direction, and because of that, this will be the direction of diffusion current. Okay, so this is the direction of your diffusion current. Now you let me know in which direction electric field has been applied. In the direction of electric field, the slope of conduction band will be positive. In the direction of electric field, the slope of conduction band will be positive. So this is the direction of electric field. Now it is external electric field or it is built-in electric field, that we don't know. But one thing I know. What do I know? I know that my electric field is in this direction. That's the only thing I know. I am not pretty sure that whether it is built-in or total. Sorry, this is the total electric field. Whether it is coming because of the external is being added or it is opposed, I don't know anything. But I just know that total electric field is in this direction. Total electric field is in this direction. That I know. Okay. So that electric field value also I know. What is the value of this electric field? So slope, if you are already having, what you are having? you are having the slope of this dEc by dx you are having, that is given by minus 0.1 electron volt per centimeter. Just by looking at the unit you can tell electron volt per centimeter. I just need to take care of electron. So if that is gone, my electric field will be 0.1 volt per centimeter. Direction here I have shown. If this is the direction of electric field, then what will happen? Where the electrons will diffuse, where the electrons will drift in this direction. So where will be the drift current? So this will be the direction of your drift current. So this will be your I drift. So you can see that I diffusion and I drift both are opposing each other, right? Diffusion current and drift current are opposing each other. So you need to find out the diffusion current and you need to find out the drift current. After that you will be able to know that what will be the value of current density at x equals to 0. Okay. So let's find out the current density they are talking about. So let's first find out the diffusion current. What will be the diffusion current? So diffusion current would be Q dnx by dx. So 1.6 into 10 to the power minus 19. So always we should prefer making the diagram. If you make the diagram, your job is done. That's it. Okay. So 1.6 into 10 to the power minus 19. What is the value of dn? 36. Everything is going in centimeter square. And now dnx by dx. So what it would be? So what is your nx? Nx is 10 to the power 15 alpha x by kt. Your nx is 10 to the power 15 e to the power alpha. What is the value of alpha? Alpha is 0.1 x by kt. What will be the value of kt by q? That will be 0.026 volt, no? So directly I am putting here 0.026. This I think I can do, right? What will be the differentiation of this particular thing? 10 to the power 15 will be constant. A to the power 0.1 x divided by 0.026 into 0.1 divided by 0.026. You need to find out that diffusion current at x equals to 0. Okay, so let's see. 1.6 into 36 into 0.1 divided by 0.026. Now 0.1 volt was there and this was also volt only. Volt per centimeter, centimeter. Yeah, everything is going fine. Ampere per centimeter square. So 2 to 1 I am getting. So 10 to the power minus 4 is there. So 0.22, no? 0.22 you can say. Yeah, 2.22. Basically this is what you are getting. 2.21 into 10 to the power minus 2 ampere per centimeter square. When you solve it, this is what you will get. At x equals to 0, because x equals to 0 I have put here. So this is what you are getting. Okay. This is your diffusion current at x equals to 0. What is your drift current? So drift current would be n x q mu e, right? Value of mu is given? No, it is not given. We can find it out. How we will find out? D is equals to uv. So mu into vt, mu n. So mu n will be equals to dn by vt. What is the value of dn? Dn is 36. Vt is 0.026. 36 divided by 0.026, right? 36 divided by 0.026. 1384.61. Okay. What is the unit? Vd is equals to mu e. Vd is centimeter square volt into second, right? So let's solve it. Now you need to find it out at x equals to 0. So nx value at x equals to 0, what that would be? Value of nx at x equals to 0, 10 to the power 15, because if you put x equals to 0 here, e to the power 0 will be 1. So 10 to the power 15. What is the value of Q? 1.6 into 10 power minus 19. What is the value of mu n? That is 36 upon 0.026 into what is the value of E? What is the value of E? Value of E is 0.1. So isn't it the same calculation? 0.1, 0.1, 0.026, 0.026, 36, 36, 10 to the power 15, 10 to the power 15, 1.6 into 10 to the power minus 19, 1.6 into 10 to the power minus 19. So what answer you will be getting? 2.21 into 10 to the power minus 2 ampere per centimeter square. Will you add them up? No. Why so? Because you know that what is your total current? Total current is both are in the opposite direction. So both are having the same magnitude, both are in the opposite direction. What does that mean? 0. What do you understand from that? That means there is no applied battery, because if there was battery, current would have surely flown. If I had connected a battery, current would have surely flown. So there was no battery actually. So what was the value? How would I make the EFN? This is how I would have made the EFN. This would have been your EFN with 0 slope. EFN would be near to, here it would be nearer, and after that it would be further. So this would have been your EFN. Right? Here there is more doping, after that there is lesser doping. Is that clear to you or not? Okay, very simple question. Just to make the diagram, write down the diffusion current, write down the drift current, and your job is done. Okay, well and good. Here, how would I get the electric field? From here I would get the electric field. That is also clear to you. Because what is the formula of electric field? 1 by Q dEc by dx. So from there I get this expression. This question, this is a good question only. So consider a uniformly doped n-type semiconductor. DC voltage as shown, ND value is given, NI value is given. Okay, ND value is given, NI value is given. ND is 10 to the power 16 centimeter cube inverse. NI value is given as 10 to the power 10 centimeter cube inverse. VT value is also given, 26 millivolt. Now you know that what kind of diagram you will be getting. Can you draw the diagram? Yes sir. What is the direction of electric field? Sir, here there is positive potential, here there is zero potential, so I can say negative potential, and it is uniformly doped, so only electric field will be this. This is your total electric field. So this is the electric field. So what kind of diagram you will be getting? So this kind of diagram you will be getting. And surely what will be the direction of current? From the positive. Do you understand the meaning of this 1 volt? This 1 volt means this is the 1 volt battery. If this is grounded, so 0 and this point will be 1 volt. So this is how I can show it, 1 volt. Okay, and then there is semiconductor, and then there is ground. So ground can be attached. So now this is the structure, and this structure we have already seen, right? I hope you know the meaning of this 1 volt. In network analysis, a lot of time we do this thing. In analog electronics as well, we do this thing, right? So conduction band and valence band. And then there, in between there is Fermi energy level. It is an n-type semiconductor, so intrinsic Fermi energy level. So if it is an n-type semiconductor uniformly doped, what does that mean? In this direction there is a current, so here I will get a EFN as well, right? Now what they are saying, this is your x equals to 0. So here whatever the value you are getting, that is known as EC0, and here what you are getting, that is known as EC1. EFI is of no use for us. EFI is of no use. Or let's see if it is of any use or not. Now in EF, what they are saying, EF is equals to EF1 here and EF0 here. You need to find out the value of EF0 minus EC1. What you need to find out? EF0 minus EC1. This you need to find out. EF0 minus EC1. So my target is to find out EF0 minus EC1. Now ND and NI I am having. ND and NI I am having. Then I could see that surely this value I can find out. Because if this is ND, this is NI, then I can surely tell that number of electrons will be 10 to the power 16 only. So I am having the number of electrons, I am having the intrinsic carrier concentration. So this distance I can find out. And one more thing, energy gap is 1.1 electron volt. What does that mean? That means
Shall I make the diagram again? Let's make the diagram again here in a bigger manner. EC naught, EC1, EF1, EF naught, EFI. And I know that what will be the difference between this guy and this guy? Like this total distance. This total distance will be 1.1 electron volt. Electron volt. What will be the distance between these two? Like distance are parallel. Everywhere distance are parallel. So what will be this distance? That I can find out. EF1 minus EFI, or you can say this distance also I can find out. EF naught minus this distance, whatever it is. So basically this distance I am finding out. So what I am doing? EFN minus EFI, that would be equals to KT ln n by Ni. KT is 0.026 ln n by Ni. What is the value of n? 10 to the power 16 divided by 10 to the power 10. So 10 to the power 6 ln into 0.026. So 0.359, or I can write it down as 0.36. So this value is coming out to be 0.36 electron volt. Can you let me know what will be the distance between these two guys? So total is 1.1 electron volt, and by default I will say that, by default what I will say? By default I will say that this intrinsic Fermi level will be right in between, right in the middle. So what will be this distance? This distance is going to be 0.55 electron volt. And if I know this distance, then I can tell this distance as well. What I can tell? This distance I can tell. What is this distance? EC1 minus EFN. What that would be? Total is 1.1. So 1.1 minus 0.05 minus 0.36. So 1.1 minus 0.36 minus 0.55. So 0.19. Are you able to understand this point? So what I have found out? 0.19. And all these are electron volt. So what I have found out? EC1 minus EFN. Because all these points are parallel, no? EC1, EFN is parallel. So I have found out EC1 minus EF1. That is equals to 0.1 electron volt. What is my target? I will look at the target. Target is EF naught minus EC1. Target is EF naught minus EC1. This is the target. So I need the EC1, but I don't need the EF naught, EF1. So basically I need some relation between EF1 and EF naught. Basically in the answer I need EC1, and then in the answer I need EF naught, but I don't need EF1. So if I get a relation between EF1 and EF naught, my job will be done, right? So what I will try to do is that I will try to find out the distance between EF1 and EF naught, right? EF naught minus EC1 you need, no? EF1 minus EC naught, if you can find out the distance between EC naught minus ES1, EC naught minus EF1, just a second. Yeah, so what I was saying that I need to find out the relation between EF naught and EF1. I need to find out the relation between EF naught and EF1. This would be my target. Now what do I know? What do I see here? That my applied electric field is 1 volt per centimeter. Do you agree to this point? 1 volt is applied towards 1 centimeter. So my applied electric field is 1 volt per centimeter. And I know that if this is the applied electric field, then what will be my 1 by q equals to d EC by dx. So slope in my conduction band would be equals to slope in my conduction band dEc by dx. That would be equals to 1 electron volt per centimeter. But sir, you need to find out the relation between EF naught and EF1, no? With the slope, you can find out the relation between EC naught and EC1. What I am saying is that, sir, with the slope, you can find out the relation between EC naught and EC1. But you need to find out the relation between EF naught and EF1. So just let me know one thing. Whatever the difference between EC naught and EC1, whatever the difference between EC naught and EC1 you will get. Basically, what I mean to say is that whatever this slope is, it will have the same slope, no? Are you able to understand this point? What I am saying? Whatever the distance is there between these 2 points, the same distance will be there between these 2 points as well. Are you able to understand this point? When I was reaching here, EC1 minus EF1, I got to know that in the final answer I need EF naught and I don't need EF1. That means EF naught and EF1 is my target. This distance is my target. Now I got to know that what is the information given. With the information given, I can see that I can find out the slope in the conduction band. I am able to find out the slope in the conduction band. What is that slope? That slope is 1 volt per centimeter. What was this? This end was, everything was happening here at x equals to 0. And what was this end? This end was x equals to 1 centimeter. So this particular distance, this much distance is 1 centimeter. This much distance is 1 centimeter. This is your EC1. This is your EC naught. And I have found out that this slope is 1 electron volt per centimeter. So whatever this value is, I don't know whatever this value is, this EC naught will be plus 1 electron volt. Say yes or no. Basically, this EC naught will be equals to EC1 plus EC naught would be equals to EC1 plus 1 electron volt. Say yes or no. Then only you would see that EC naught, if EC naught is equals to EC1 plus 1 electron volt, then only the slope will become 1 electron volt per centimeter, no? Because what is EC naught? EC1 plus 1 electron volt. What will be the slope here? The slope will be EC naught minus EC1 divided by 1 centimeter, because this distance is 1 centimeter, right? So what is the slope? Slope is 1 electron volt per centimeter. This and this get cancelled out. So EC naught is coming out to be 1 electron volt plus EC1. 1 electron volt plus EC1. Basically, the slope here is 1 electron volt per centimeter and the distance is 1 centimeter. What does that mean? That means the distance between these two guys, this would have been 1 electron volt. So what you got to know? That my EC naught minus EC1 is equals to 1 electron volt. Since lines are parallel, because it is uniformly doped and everything is there, since lines are parallel, so EF naught minus EF1 is equals to 1 electron volt. Basically, everyone got the same slope, no? If everyone got the same slope and everyone is there between 1 centimeter distance, so similar thing is happening. That means EF naught minus EF1 will also be 1 electron volt. So what you are having now? Equation 1 and equation 2. From equation 1 and equation 2, what I need to do? EF naught minus EC1. So from 2 minus 1 I need to do. Equation 2 minus equation 1. So what I am getting? EF naught minus EF1. So that would be 1 minus 0.91. That would be 0.81 electron volt. So this will be your final answer. Did you understand this question or not? So whatever the information was given, just use that information. That's it. Okay. Using the information, we got to know this particular thing. We started from here that ND, NI value I am having. So this distance I can find out. This distance I find out. This distance also I know. Then this distance I can find out. So EC1, EF1. This equation I got. Now I know that I don't need EF1 in my final answer, but I need EF naught in my final answer. So I need the relation between EF naught and EF1. EF naught and EF1 can come from the current, because I know that our current is proportional to the slope of Fermi energy level. But there is no relation of the current, like in the current value nothing is given and I don't even know the exact relation. But what do I know? From here I know that EC naught minus EC1, I can do something here, right? Because I know the electric field value. If I know the electric field value, then I can know that this slope will be 1 electron volt per centimeter. 1 electron volt per centimeter. If I know this slope, that means whatever the value is here, this would be EC1 plus 1 electron volt. So similar thing will happen here. Whatever the value is here, this would be EF1 plus 1 electron volt. So EF naught minus EF1 is coming out to be 1 electron volt. Using this expression, I got this answer. Okay. Solve this question. Energy band diagram with respect to X is given. At equilibrium, you need to draw the potential plot. Electric field is equals to 1 by Q dEc by dx, and this electric field is equals to minus dV by dx, minus dVx by dx, and this is also with respect to x. Electric field will also be a function of x only, so that you can understand. But let's draw the. Now only conduction band is made. Why so? Because you know that whatever the structure of conduction band you will see, the same structure you will see in the valence band, same structure you will see in the intrinsic Fermi level as well. That's why they did not draw any other bands. And since it is at equilibrium, then Fermi energy level will have zero slope. So this kind of diagram we did not even see. You did not see, don't care. What you need to do you need to find out any expression or anything like that? No. Only thing is you need to draw the graph. So sir, we used to see the flat band diagrams. These kind of diagrams we used to see. Yes, we will see these kind of diagrams only. But if any other random diagram is coming, we will try to solve. What we need to do, we just need to plot the potential plot. So can we draw the potential plot? Surely we can draw the potential plot. How we will draw? What I can see? Between, I will mark up some points. Between x1 to x2, what is happening? If I need to relate voltage with this particular expression, then what I need to do? If I need to relate voltage and energy, then in between electric field will come. So between x1 to x2, what do you see? The slope is positive. The slope is positive. So this value will be positive. That means electric field will be positive. If electric field is positive, that means dVx by dx will be negative. That means Vx will be decreasing. So till this point, everything was till this point. What was the scenario? Here, this EC was constant. That means electric field was 0. That means Vx was also constant. What I mean to say is that between 0 to x1, EC was constant, right? This EC was constant. That means, sorry, not constant, uniform. If it was uniform, then differentiation was 0. That means electric field was 0. If electric field is 0, that means dVx by dx is 0. That means Vx is uniform. So Vx was uniform. Now your EC is increase. Your EC is increasing, right? Your EC is increasing. That's why dEc by dx will be positive. Here the slope will be positive. No, this is what I am saying. Slope will be positive. Slope is positive. If slope is positive, then what will happen? Electric field will be positive. Then dV by dx will be negative because electric field is equal to minus dV by dx. So dV by dx will be negative. What does that mean? That means Vx will be decreasing, or you can say Vx will be having negative slope as well. Vx will be decreasing, having the negative slope. So this is how it should go between x1 to x2. Say yes or no. Now between x2 to x3, between x2 to x3, what do you see? Slope is negative. Between x2 to x3, the slope is negative, no? dEc by dx, slope is negative, right? If you draw a slope here, negative. We draw a slope here, slope is negative. Positive slope means this is the positive slope. Now here the slope is negative slope. So this slope is negative, that means electric field is negative. If electric field is negative, that means dVx by dx would be positive. So now the slope will be positive. So till x3, the slope will be positive. After x3, what is happening? After x3, the slope is again positive. So this value again positive. That means electric field again positive. That means dVx by dx again negative.
what does that mean? Vx is again decreasing, and then after that it becomes constant. So if EC is becoming constant, that means this value, sorry, EC is becoming uniform, then this value will be 0. Electric field is 0, then Vx is also uniform. So there you go. This is the diagram of your Vx. So it's like a mirror image. If you put a mirror here, then what you will get? Like, do you remember? This was our semiconductor, right? With respect to x, what was our potential plot? Here potential is more, here potential is more, here potential is less, right? So what was our potential plot? This was our potential plot. Here potential is more, here potential is less. So this was our potential plot. And how did I make our conduction band diagram? In the direction of electric field, this will be your conduction band diagram. So this was your potential plot, and this was your conduction band diagram plot. So again, it's like that. If you just take the mirror image, this guy goes here, this guy goes here. So if EC diagram is made, if the energy diagram is made and you need to draw the voltage diagram, just take the mirror image. About x-axis, take the mirror image. Okay. Although taking mirror image, all these things are not a really good method. We should go by these methods. Simply write down the expression. Simply write down the expression and see. dCx by dx is positive. dCx by dx is positive. Since it is positive, so dVx by dx will be negative. That means slope will be negative. Okay. All good. Fine. And here also you can see that slope is going towards 0. dc, what I mean to say is that dEc by dx value is going towards 0. Whatever the value was here, whatever the value of a slope was here, after that the slope is becoming 0. So slowly dEc by dx is going towards 0. That means dVx by dx will also go towards 0 only. You can see that it is going towards 0. You can see that here also it is going towards 0. So one side is, once it has become 0, here also this slope is also becoming 0. Basically what I mean to say is that if the slope in the energy is 0, then the slope in the voltage will also be 0. Okay. This is rising, decaying, rising. So positive slope, dVx by dx, negative slope. Negative slope, positive slope. Positive slope, negative slope. Zero slope, zero slope. Zero slope, zero slope. Right? So what I mean to say is that if EC is having positive slope, then Vx will have negative slope, and vice versa. And vice versa. Okay, there you go. Next, potential plot is given across a n-type semiconductor at thermal equilibrium at T equals to 300 Kelvin is shown. Find the ratio of doping at x equals to 0 and x equals to 6. N-type semiconductor. Under equilibrium, that means there is no external bias. This is your n-type semiconductor. Potential plot is given. Now, where will be higher doping, where will be lesser doping? N-type semiconductor is there. What do you think? If I make higher doping here, then what will happen? Here there will be positive and here there will be negative. So electric field will be built up in this direction. Basically, here there will be positive potential, here there will be negative potential. So potential at x equals to 6 micrometer will be more, and potential at x equals to 0 micrometer will be less. Is it the scenario? No. At 0 micrometer there is more potential, and at 6 micrometer there is lesser potential. That means what is the profile of doping? The profile of doping is like this. Now what will happen? Electrons will diffuse here. So here you will get positive charge and here you will get negative charge. So what will happen? Forget about the direction of electric field. I don't care about the direction of electric field. I just know one thing, that at x equals to 0 there is more potential, and at x equals to 6 there is lesser potential. Right? What is the potential difference? Do you remember this formula? I told you potential difference would be equals to Vt ln ratio of the concentration. Ratio of the concentration. I am just putting n1 by n2. What I need to find? Ratio of the concentration at x equals to 0 divided by ratio of the concentration at x equals to 6. This value will be greater than 1 or less than 1? Greater than 1. Why so? Because concentration at x equals to 0 is more and at x equals to 6 is less. So whatever the answer I will get, I just need to make sure that it is greater than 1. So delta V, what is the potential difference? 30 millivolt. Divided by what will be the value of Vt? Not given. I will take 26 millivolt. Well, let's take 0.0259. ln n1 by n2. Okay, so 0.03 divided by 0.0259 e to the power 3.12. So what it is coming out to be? That is coming out to be 3.12. So if you solve it, n1 by n2 is coming out to be 3.12. Now let's just say this was my answer. This answer came. n1 by n2, this answer came. Okay. And then I know that at 6 there will be more equilibrium. Let's just say in my case at 6 there was more equilibrium and at 0 there was lesser equilibrium. Then what I would have done? I would have just done the reciprocal, because they are asking at x equals to 0 divided by x equals to 6. You know that this answer should be greater than 1, because at x equals to 0 there will be more concentration, at x equals to 6 there will be lesser concentration. You know this formula is also there. Let's just say you applied the formula and you got the answer n1 by n2 as, let's just say 1 upon 3.12. This answer you got. This answer you got. But you know that answer should be greater than 1. That means here whatever that you put, that should be put in the reciprocal. I told you here n1 by n2 you will remember. Sir, what will come upper side, what will come downward side, don't care about that thing. n1 by n2 you will remember. So whatever the answer came, I know that answer should be greater than 1, then I would do the reciprocal. There you go, answer would be 3.12. So in diffusion current, we are very smartly solving the problem, right? Whenever there is a concentration gradient, very smartly we solve the questions. We don't care about the sign. Whether it is current, whatever it is, we never care about the sign. We make the diagram and then we see. Well and good. Okay, so this is the answer. Now this question. The resistivity at a room's temperature is given. At room temperature for intrinsic silicon is given like this. This is the resistivity for intrinsic silicon. Do you remember resistivity? Resistivity is simply the reciprocal of conductivity, right? N-type silicon sample. If it was N-type silicon sample, then this was the resistivity. A bar of silicon having 3 mm long and rectangular cross section area 3 mm long, and cross section area is 5 into 10 to the power 4, sorry, 5 into 10 to the power 3 millimeter square. Okay. Now this is also in millimeter only. Current of 1 microampere is flowing through the bar and the voltage is found to be 50 millivolt. So when you apply a battery of 50 millivolt, here, so in these kind of questions, if you feel like that, sir, a lot of information is given, always make the diagram. Just make the diagram and your job will be done. 50 millivolt battery with the current of 1 microampere. Okay. If the same bar was made of intrinsic silicon, then what would be the voltage across the bar considering the same current flow? Okay, this was N-type. In N-type, this was the scenario. In N-type, what was the scenario? In N-type, the scenario was, if I am applying 50 millivolt, then I am getting 1 microampere current into the resistance, whatever the resistance it provides. What is the formula of resistance? R is equals to rho L by A. Now what you are doing, you are not changing L, you are not changing A. So L and A are constant. You are changing the material. If you are changing the material, then rho will change, no? Only rho will change, right? Here I am talking about intrinsic. For extrinsic, what is the scenario? The current remains the same. Current remains the same. Okay. You need to find out the voltage, and now, sorry, this was for N-type. Really sorry. This scenario was for the N-type. Now you need to find out Ri value. Now you know that length and area you are not changing. That means R is actually proportional to rho here. Although rho is a proportionality constant, that I know.
but actually it is coming out to be proportional to rho only, because L and A you are not changing. When you are moving from N type to intrinsic, you are not changing L and A. Only thing you are changing is that is rho, right? Fine. Okay. So what I will do is that V divided by 50 millivolt, 1 microampere will be cancelled out. Ri value will be equals to rho I divided by rho N. So rho I is 8.33 into 10 to the power minus, rho I is 2 into 10 to the power 3. 2.3 into 10 to the power 3 divided by 8.33 into 10 to the power minus 2. So what is the answer of V you will get? So 2.3 into 50, 2.3 into 50. So milli and 10 to the power 3 will be cancelled out, divided by 8.33 into 10 to the power 2, 1380. This is the answer. Basically, what does that mean? That means if you were having intrinsic semiconductor, to get the same amount of current, you need to use 1380 volt battery. And when you did the doping, after the doping, to get this much current, you just need 50 millivolt. So how much energy is saved? No. Here there was so much power was here in this case so much power would be consumed, but here very less power is consumed. 50 millivolt multiply with 1 microampere, and here 1380 multiply with 1 microampere. So here 1380 microwatt power is used, and here in some nanowatt, here 50 nanowatt power is used. Just by the effect of doping, you are doing this much things, right? Are you able to understand this point? Okay, so that's why doping is useful for us. Very simple question, just you need to click. If you are able to click, then you will be able to solve. This was the gate PIQ question. Total electric field. Find out the total electric field. This valence band is given. It is having this kind of slope. Find out the total electric field. Electric field is equals to 1 by q dEV by dx. So what is the slope here? Delta by L. So what will be the answer? Right? Because the slope was dEV by dx. Here I can see the slope, that is delta by L. Okay, so if this is the slope, this is the answer. There you go. This is our end of basic semiconductor physics. Okay, we have seen more than enough question. Now your job will be you need to solve the PYQs. That's it. Now from this basic semiconductor physics part, 50% of the questions will come from EDC. Let's just say in EDC is coming of 8 marks, then 4 marks of basic semiconductor physics would come. So 50% marks are consumed from here only. Although this is the 40% of the syllabus, like 40% syllabus is completed. In EDC, 40% syllabus is completed, but 50% of the marks will be helpful in the examination. Okay, so it will be coming for 50% of the marks. So a major portion in a very easy manner we have done without remembering much of the formula, right? Formula remembering I wanted to reduce. That's why that was my major target. In EDC, people think that it is based on formula. This thing we need to remember, that thing we need to remember, and most of the times people will be just studying the concept. But there is an equilibrium between concept, formula, and the problem solving approach, and that equilibrium we have built up in this lecture, right? So basically it would be of roughly around 9, 10, 30, 22.5 hours. In 22.5 hours we have completed our basic semiconductor physics, and usually it would take, if you are not making your own note, if you are just studying from the lecture PDF, then it would take roughly around 35 hours to complete. If you are making your own note, then it can increase, it depends on your pace. But if you are studying from the PDF, then in 35 hours you will be able to complete basic semiconductor physics, and you go to any lecture, you would see the content will be of more than 40 hours. Content itself. Okay, and you let me know in these 40 hours, do you find anything new that I did not teach here? Like there will not be a single topic which they are teaching and I am not teaching. But needless derivation will not be there. Okay, needless derivation we are not doing. Neither we are writing down the results directly. Like if I don't do the derivation, then what I can do, I can directly write down the result, that this is the electron concentration. That's it. I could have written down the result. For this, there is a 2-page derivation for this particular formula. But did I directly write down the result? No. Directly writing down the result is also not good, and doing the needless derivation is also not good. What we did, we understood the importance of NC, we understood the importance of probability. Multiply both of them will give us number of electrons. So this is how we reduce the number of hours. This is how we build up our thinking, and this is how we prepare ourselves for the competitive examination. So in 22.5 hours, we have done absolutely brilliant work. Your target would be to share it. What you need to do, only thing I expect from your side is sharing it, so that this content should reach to a lot of people. Okay, EDC this, EDC that, just see this thing now. Okay, so share it to the maximum. Okay, yeah, thank you very much. Notes and everything will be shared on the Telegram group. Yeah, thank you very much. Happy learning. Let's meet again in some other lectures.